G'day viewers, and welcome to Computer Networks. I'm David Weatherall and I'll be your host for these lectures. And in this first segment, we're going to talk about some goals for the course, what you'll learn by going through it, as well as some of the motivation for why you might care to study computer networks in the first place. So this picture here describes our usual view of the network. You're all probably familiar with using clients, computers, that make use of the internet, and you know that they talk to servers over the other side of the network. What's much less visible, what most of us really don't have a good sense of, is what goes on in here, inside the network. And that is exactly the focus of this course. So if we think about networking courses, there are roughly 3 kinds of topics which are covered. At the bottom layer, there are communications courses, and these courses are all about how we use signals to carry information in bits across networks. Building on this layer, there are classic networking courses, such as those that tell you how the internet operates. These courses are mostly about how packets are carried across networks. And at a higher layer still, distributed systems courses tell you about the different kinds of apps or applications which can be built on top of networks and make use of their services. The ground we're going to cover is here. That is to say, we'll provide you with a classic networking course which talks about packets and the internet, but we'll also do a little bit of communications and distributed systems so that you understand how the network builds on communications, how bits are carried across networks, and also the kinds of things that applications can do on the top of networks. Okay, so we really have 2 main goals for you in this course, and I'll go over each of them in turn. Our first goal here is really for you to simply learn how the internet works. And by that I mean for you to gain a deep appreciation of what happens, for instance, when you browse the web, what really goes on underneath. Clicking on a link is a fairly simple action, but actually there's a surprising amount of machinery that exists below it to support that kind of operation. And in the course of understanding how the internet works, we're going to learn about many acronyms that you've probably already heard of. Things like TCP/IP, the DNS, HTTP, NAT, VPNs, 802.11, and so on and so forth. Many other acronyms too. I expect that you've seen a lot of them, and what we'll go over is we'll do much more than tell you what they mean. We'll give you a sense of how they operate and what their purpose is and why they even exist in the first place. So I'm going to go over each of those points a little bit more and give you a little more detail. So first of all, in terms of learning about the internet, why would you care to learn about the internet? Well, there are several reasons. One is simply curiosity. The internet's a very important artifact. You might be curious as to how it works. Since it's an important artifact, it also has a big impact on our world. I'll go over each of these points in a little more detail. That's what this little symbol means, more coming. And a third reason you might care to learn about the internet is simply job prospects. There's a lot of growth these days in engineering and computer science related jobs for which networking is an important component. So having a deep understanding of networking techniques and how the internet works can definitely be good for your job prospects. Okay, so let's talk about curiosity and the internet a little more. The internet really had very humble beginnings. This is what it looked like around 1970 when it first started, and at that time it was known as the ARPANET. And you can see here is the original 4-node network configuration, the topology. Look at that. And over time you can see that it quickly began growing to this other network in the middle, and then to this slightly larger network as it grew. Well, that was a while ago, around 1970. Here's something that's closer to where we are today. This is a visualization of the internet in 2005, around 2005. And by this time, the internet has turned into an everyday institution. It's something that nearly all of us use. We use it at work, at home, and while we're on the go. Now, actually, no one knows what the internet looks like anymore at this scale. This picture really is a visualization that's based on just a data set that's been gathered to give a good approximation of what the internet looks like. And you can see it looks more like a star chart with millions of links in there. So it's really quite an amazingly complicated structure nowadays. Another reason why you might care to learn about the internet is the tremendous impact that it has on our society. So the internet is really an enabler here of societal change. And you can see this in some of the ways that we already use the internet today. The internet provides very easy access to large amounts of knowledge by systems such as Wikipedia. Previously, that knowledge could be very difficult, time-consuming, or expensive to obtain. The internet allows us to undertake electronic commerce with systems such as PayPal, with really very little friction, so that we can buy and sell goods across the internet very easily nowadays. And the internet's even changed the way that we meet people with various systems and the way that people interact through networks. And the internet also provides us ways of communicating without censorship across even international borders. So it's changed the way that people are able to communicate. This is really a huge impact it's having on the world. You know, we might add to this list education, because the internet now, with systems such as Coursera, is really beginning to have a very significant impact on how we educate people. As well as impacting society, the internet is also having a large impact on the economies of the world. Really, you could think of the internet as an engine of economic growth. And these examples I've given you are all examples of business models that didn't exist before the internet. They didn't really make sense without the internet. So Google, as you probably know, runs using a business model of advertising sponsored search. This is something that's become possible because of the internet. For other stores, such as Amazon, Amazon operates with it's an online store, of course, but it also operates using a long tail model where it's able to sell a very large number of goods. It has an inventory which is much larger than you can really fit in any one reasonable physical store for people to wander around. So it's a different model. Online marketplaces such as eBay enable buyers and sellers to come together quickly, even though they're in very different physical locations. And even more recently, there's a great deal of interest in crowdsourcing systems such as Amazon Mechanical Turk, which can allow many people spread in different areas to all contribute to one task in ways which really weren't possible before. So the internet is having a tremendous impact on the way we do business. Okay, so that's a little bit about why you might learn about the internet today. The other main goal of this course is for you to learn the fundamentals of computer networking. And that is to say, to understand the hard problems that computer networks need to solve, and the design strategies which have proven valuable for solving these difficult problems. Now, it may be a little more difficult for you to appreciate why you would care to learn about the fundamentals of computer networks. Why should you bother, as opposed to learning about how the internet works today? Well, there are several reasons. The fundamentals are going to apply to all kinds of computer networks. We might talk about Wi-Fi a lot, just because it's a network technology that many of you see. And we might not talk about satellite networks, for example. But many of the fundamentals we learn about computer networks will also apply to satellite networks. So you're learning a little extra. You'll be able to transfer your knowledge to other kinds of networks. Much of this material is actually intellectually interesting. There are some thorny problems for us to solve, and I'll give you an example of that in a moment. And perhaps the most important reason you might care to learn about the fundamentals is because of change and reinvention. The internet is not static. It's continuing to change and evolve. And understanding the fundamentals gives you long-term knowledge which will help you understand the internet of the future. Knowledge about the fundamentals is knowledge that doesn't get outdated over time. Okay, so let's just talk about some of that in a little more detail. This slide just talks a bit about some of the intellectual interest you can get from the fundamentals. You know, just as an example of a key problem in networking, a key problem is reliability. If you're sending a message across the network to your bank, it's not acceptable for that message to be altered so that the wrong message arrives and you think that was what was sent. That wouldn't be good. Similarly, it's not acceptable if there's some failure in the internet somewhere for that to prevent you from getting to your bank. The failure is not really on the path. Well, you know, all of these things can happen. Messages can get corrupted as they go across the network, so we're going to have to do something about that. Failures happen all of the time in the internet. Actually, the internet is so large that some parts of it must have failed right now. Yet we want the remainder to work seamlessly. Well, how are we going to do this and provide reliability? Actually, if you think about it, it's quite a thorny problem. Every component in the internet can fail, so we want to be prepared for that. Yet any mechanism we add to handle that can also fail because it's just more mechanism. So you can see the catch-22 here. Luckily, some clever solutions have been devised, and we'll learn about them during the course, that provide fairly high kinds of reliability. For instance, we'll learn about codes which can detect incorrect errors, and also routing strategies which can route around the failed components of the internet. And reliability is just my example, the one I chose to talk about here. There are other deep problems that we'll look at in networking during the course. Another example one is about network growth and evolution. Imagine trying to design a system to be able to accommodate applications that you haven't even thought of yet, and to be able to grow and get 1,000 or 1,000,000 times larger than the initial system. This is really hard. Well, there are some useful techniques that we'll come up with here. And by the way, the numbers here, these are section numbers in your text which you can consult. There's no need to go off and do that for this slide here. This is really referencing material that we'll cover throughout the whole course. So don't jump into all of that yet. Just start with the introductory material. Another difficult problem, just to put a last couple on the table, is the allocation of resources such as network bandwidth. That's really what networks are doing, providing bandwidth to the different users. But if you think about the internet, many people are using it. The users are coming and going as some people surf the internet or stop surfing the internet and so forth. And we're going to need to design mechanisms which can handle all of this different churn and still do a good job of giving whoever wants bandwidth the bandwidth that's available in the internet. This poses some difficult problems. Security is also another difficult area. It actually turns out to be very difficult to design an internet which is very open and easy for everyone to use, which is key for innovation and is an important part of the internet, yet at the same time is secure in the sense of being very difficult to abuse, so that malicious parties can't very easily undermine the actions of other parties. So there's a big tension here, and we'll learn about some of the techniques. Okay, but the other reason you might care about to know about the fundamentals is really the reinvention of the internet. Now, if you think about it, you realize that the internet is constantly being reinvented. The internet is growing tremendously over time, and there are also lots of technology trends. Both of these changes are driving upheavals in the way the internet is designed and the way the internet is used. So the upshot here is that today's internet is actually quite different than yesterday's internet in many respects. Tomorrow's internet is going to be different again. Yet for both of them, the fundamentals are going to remain the same, and they will help you understand what's possible in computer networks. That's why we want to tell you about them. Just to go into that in a little more detail, this graph shows you the growth of the internet in terms of the size. And you can see here in the early 90s we start with maybe 1 million hosts, and up here we've gone up to maybe 1 billion hosts. So wow, look at that. That's a factor of 1,000 growth in just the size of the internet, which is really pretty impressive growth if you come up with designs and you want them to be able to work through that evolution. But more than that, we've also seen many upheavals in the internet over this period. And I've listed here just some of the growth and technology drivers which are causing those upheavals. You can see, for instance, when the web emerged, this led actually to the creation of what are called content distribution networks to satisfy the enormous demand for getting the same web pages to many different people. As the content of the network changed and we shifted to digital songs and videos, there was an upheaval in which we shifted to and explored different peer-to-peer methods for sharing files. As the cost per bit of sending information over the internet has fallen, we've switched increasingly to voice over IP calling, so that functions which were traditionally part of the telecommunication network, the telephone network, have been incorporated into the internet. This one's about growth, many internet hosts. This has actually driven a change where we're going to have to update all of the basic internet protocols, and we're in a transition right now to IPv6. But you can see, while this one's about growth, pure growth, many of the others aren't. They're really upheavals caused by technology trends and changes in the way we use the internet. And finally, just to put out there, advances in wireless have led to many more mobile devices, and these devices stress the internet protocols in different ways that we'll see a little bit of during the course. Okay, and finally, just to close this segment, I want to point out one thing which is not an explicit goal of this course, and that's to provide you with IT job skills, such as, for instance, Cisco certification material to help you configure networks. That's not because this is not an important skill, it's because some of this material can change fairly quickly over time as new equipment comes and goes, whereas what we want to give you really is long-term knowledge which will remain relevant in the future and help you understand the internet. Now that's not to say that this is purely an academic course, however, much of the material you learn will really be very practical about how the internet works, and we'll also experiment a little bit with some hands-on tools. So you'll get a good sense of some real-world stuff. Okay, so on with the show. G'day viewers. In this segment we're going to talk about the uses of network, and that's because it's important for us to understand how the network is used if we're going to be able to design effective networks in the first place. Okay, so as you know, we use networks in many different ways in pretty much all the places we go. We use networks at work for different kinds of email and file sharing and printing. At home for different kinds of entertainment, listening to songs, watching movies, reading the news, as well as messaging and shopping over the internet. And we use it when we're on the go too, not just for calls and texts or playing games, but also for accessing different kinds of information services, watching videos, consulting where we are on the map, and so forth. So there are many different uses of networks, and you are familiar with most of them. But our point here is really not to focus on individual uses of networks, but try and understand what these particular uses, like YouTube and so forth, tell us about why it is we build networks, because that's going to help us build more effective networks in the future when we know what networks are trying to accomplish. Well, I can give you several reasons why we build networks, and we're going to now go through them in some of the following slides. One of the first uses that might come to mind is simply for communication between users. This is a traditional usage of computer networks really from the get-go, and really from the telephone onwards. You might think of using voice over IP, sending telephone calls over the network. These days we video conference as well as instant message and connect people via social networks, but it's all about user communication. The point here is that the computer network is enabling remote communication. And a particular aspect of the network we would need to think about to provide remote communication is low latency. If you really want interactive communication between people, you need a fairly low latency network for that communication to be effective. Another important reason that we build computer networks is for resource sharing. That is, to allow many different users to access the same underlying resource. Now, the classic resource which was shared was a printer. Imagine in a company network, instead of giving everyone an individual printer, you put one on the network and everyone accesses it. They're sharing this resource. That's wonderful. Today, maybe you're not sharing a printer so much, but there are other resources which you're still sharing. Maybe it's a 3D printer today, maybe we're all sharing Google Search Index, or even we're sharing machines which are in the cloud being used. The idea here is that by performing this resource sharing, we are providing a more effective, a cost-effective way to access resources than providing dedicated resources per user. Just think of that printer per user versus one printer per work group. In fact, even the network itself, which is providing a resource called bandwidth, even the bandwidth of the links in the network have been shared by different users over time. And this sharing process is called statistical multiplexing, is the name for it. And I'll go over that next. Okay, so statistical multiplexing is a pretty big fancy name, but all it really means is sharing of network bandwidth between different users according to the statistics of their demand. Multiplexing here is just the fancy networking word for sharing. So statistical multiplexing is just sharing bandwidth amongst users, where the statistics mean when they choose to access the network and so forth. The reason that this is useful, that you want to do this, is it turns out that users of the network are mostly idle. Most of the time you're actually not using the network, or your devices are not using the network. And when you do use the network, your traffic tends to be bursty, so it's occurring in just these little spurts of traffic. So this means that we can combine the traffic of different users, and in that way we'll get to something which is using the network really more of the time, most of the time, and we'll use that resource inside the network, such as network bandwidth, more effectively. At least that's the theory, and the key question for us is, how does it help if we statistically multiplex users together? So let's just think about that. And what I'll do is I'll go over a simple example. This is, a little bit artificial, but it's mostly to convey the point. So don't take this quite literally, just take the big point out of it. Let's consider for a moment users in an ISP network. Here's the ISP network here. This network has 100 megabits per second of bandwidth to the rest of the network, the internet. We haven't gone over megabits per second, but just think of that as units of bandwidth. So 100 units of bandwidth. Now each of the users here wants to subscribe to 5 megabits per second. That's how much bandwidth maybe you want at home to ensure that you can watch your videos. But the statistical multiplexing bit of it is that each user is active only 50% of the time. Actually, that's quite high. Many users might not be active that often, but let's just say 50% of the time. At most, that's when they're active. Well, let's think about different ways to design this network. Assume that we dedicate bandwidth to each user. If we do that, then each user is always going to have 5 megabits per second of their own throughout that ISP, so they'll always have it when they need it. How many users can we then support? Well, we can support 100 megabits per second divided by 5 megabits per second per user. That's 20 users. Okay, but if we think about this case where there are 20 users, let's ask, for the sake of argument, what's the probability that all of the bandwidth within the ISP is being used? Now, the kicker here is we're going to assume that all of the users are independent. That's a little bit unrealistic, but it's good for thinking about this. So let's just, assuming that all of the users are independent. This is a probability calculation. Some of you may not be familiar with it. Don't worry about it too much. So there are 20 users. What's the probability that the first user is using their 5 megabits per second? That's a half. What's the probability that the second user is using their 5 megabits per second? That's another half. And so on, up to the 20th user, a half. If you multiply all of these together, you get a half to the 20th power, and that's just a little less than 1 on a million. Wow, so there's only a 1 on a million chance that all of the users are going to be using their bandwidth, so that the ISP bandwidth will be used. So actually, a lot of the time, bandwidth inside this ISP will be wasted. Can we do better by using a little bit of statistical multiplexing? Well, yes, and that's the point of this example. Just imagine now that I'm changing the number of users that same ISP is serving, and it's going to sign up 30 different users. They're all going to act independently. What's going to happen? Well, this picture here, this binomial calculation, shows you what is likely to happen if all of the users are independent. And this graph here is showing you versus the number of users on the x-axis, the probability that a certain number of users will be using the network on the y-axis. Now, it turns out that according to this, there is only a 2% chance that you'll have more than 20 users. So that's this tail here, more than 20. This is 2% chance. It's not very much. Actually, you can see the most likely situation is where we'll have 15 users using the network. That's the highest probability. This makes sense because there are 30 users, and the probability for each of the users using the network is a half. A half of 30 is 15. That's why 15 is the most likely case. You can see the chance of using all 30 users here is very, very low. Boy, this is 2 to the minus 30. This is like 1 in a billion. Now, many of you may not be familiar with the binomial calculations here. If you're interested to learn more, you can look up binomial probabilities on the web and learn a little bit about it. The point here is that by going through calculations like this, which I would need to use a calculator to use, we can see that if you have 30 users, it's quite likely that the number of users within the network will be somewhere between 10 and 20. Well, if we're willing to go with that 2% chance that most of the time it'll be okay, then we reach this conclusion here. We're able to serve more users with the same size network, and those users many of them are likely to be just as happy or almost as happy. This gives us a gain because now we're serving 30 users in a network, which if we divided it up for users individually, we could only fit 20. This is sometimes described as a statistical multiplexing gain here, and the gain here is 1.5. So we're 50% better off by doing this, and we're able to provide network service more cheaply. That's why you would want to do this. Now, of course, the danger here is that depending on your model here, we could get unlucky. Actually, it's possible that more than 20 users would want to use the network. Some of you may realize this. This is quite similar to airline overbooking. Airlines often sell more seats than they have actually inside their plane because they know that not everyone is likely to show up. So if they sell more seats, well, that will make their service more cost effective. But every now and again, someone gets a little bit of an unfortunate surprise and they try and shift people to other flights. Now here, if we get unlucky and more than 20 users want to use the network, maybe the users will have slightly degraded service. And they'll get 4 megabits per second instead of 5. And this might be okay sometimes. So you can see the attraction of this idea that statistical multiplex and this resource sharing is important in the design of networks to make them cost effective, even though my example is a little simplistic. Okay, forging ahead, another reason that we like to use computer networks is for content delivery. Now, particularly with the emergence of the web, you realize that the same content is now delivered to many users. This used to be web page. Nowadays, this is videos. So these are actually really quite large objects, a large amount of content, exactly the same content is delivered to many users. And we find that with computer networks, we can deliver the same information to more users more efficiently than sending a separate copy of that information to each user. And we can do this by using what are called replicas inside the network. Let me show you how. Okay, so here's a content delivery scenario. Let's just imagine that we don't use replicas first. So we have our 4 users here over on the right-hand side, and we have our source. This is where the video is. And we want to send it to all of the users. And as a measure of work, we're going to use network hops, sending the video across each individual hop of the network. Well, first of all, the source sends information to the first user. So 1 hop, 2 hop, 3 hops, and we get it there. Now the source sends the same video to the second user, the third user, you can see where I'm going here, and the fourth user. And the total number of network hops we've used, or work we've done, is 4 by 3. That's 12 network hops in this example. Well, now let's send the content via these replicas. Here's a replica node here. So the source is the same node here. This is where the video starts off. The users are over here on the right, but we've also added this replica node right here. So the way we're now going to send the same video to all of these users is to send it from the source once to the replica that's nearby, and then from the replica, which is deliberately placed close to the users, we'll send a copy to each of the users. And guess what? Now we're going to take 1, 2, 3, 4 here to the individual users, plus 2 hops here and here. That's a total of 6 network hops. So we've done half the work by arranging the design of our content distribution, and yet we've still got the same video to all of the users. So with clever designs, we can provide more efficient content distribution in networks. Another reason for building computer networks is to let not people communicate with one another, but to let computers communicate with computers, to interact with them in different ways. Actually, we do this all of the time when you're buying something on the internet, using e-commerce or making a reservation and so forth. You might think of these as very human-driven operations, but once you give the go ahead, your computer or a remote computer are interacting to perform a transaction. If you want to take the human out of the loop a little bit, consider things like high-frequency trading, where computers are buying and selling many different stocks very quickly over time. These kind of operations are becoming more common where computers are interacting across the network. And then the internet, the network, computer network in this case, is enabling automated information processing across a range of different parties. They're all coming together via the network. And yet another interesting use of computer networks is for connecting computers to the physical world. We can gather sensor data at computers that are scattered around the network and then use the network to send that information to other places. or we can send commands across the internet to cause actuators to affect the real world. So this is really what's going on with uses such as webcams, where you're observing, gathering video about the internet. Mobile phones here are all about sensing, where you might gather data such as location and combine that with data across the internet to provide maps of where you are. Yet another example, in this case for actuation, is something like a door lock, where you can remotely send commands to the door lock on your front door of your house, say to open it up if a friend is visiting and you're not there. This example is a use of computer networks, is an example of a rich emerging usage. It's starting now, and we should expect to see a lot more of it over time. Okay, well, they're the different uses of computer networks, and to round out this segment, I want to talk about the value of connectivity. And there's an interesting notion here, which is that large networks are more valuable, relatively more valuable, than smaller ones. So we have an impetus to combine small networks together into larger ones, and that's really what brings us something like the internet. This argument for the value that's inherent in connectivity was put forth by Bob Metcalfe, shown on the right here. Metcalfe is one of the pioneers of computer networks. He invented something called Ethernet that we'll get to later, one of the most successful local area networks of all time. Metcalfe posed this law around 1980, and he posited that the value of a network, if you have n nodes in it, that's the size of the network, is proportional to n squared. The implication of this statement is that larger networks are a lot more valuable than smaller networks with the same number of nodes, and so we're more likely to want to connect networks together to realize that value. Let me give you a sense of the intuition for where this comes from. You may be wondering what this n squared has to do with anything. But imagine here, in both of these pictures, on the left-hand side and the right-hand side, I have 12 nodes in a network. Now, on the left-hand side, I have a larger network that has more connectivity. It's more valuable. This network here is what's called a mesh. Actually, it's a full mesh. There are 12 nodes here, and each node is connected to all of the other nodes. We think about the number of connections in it. Well, from each node here, there are 12 of them, we can connect to up to 11 other nodes. Here's one connection here. This is like a unidirectional connection from one node to another. If we consider that, then we have 12 times 11. That's 132 different connections on the left-hand side. On the right-hand side, we have two 6-node networks. So inside one of these networks, we have 6 by 5 unidirectional connections. That's 30, plus another 30. That's 60. Oops, that's 60. So you can see that for 12 nodes here, we have a lot more connectivity, potential connections from one node to another node in the larger network on the left-hand side than on the right-hand side. And that's why larger networks are more valuable. Okay. G'day viewers. In this segment we'll talk about the Socket API, the most widely used interface to write applications on the internet today. Okay, so this figure is providing you with some context to remind you where we're at. We have applications attached to hosts which are using the network. The applications using this interface, the network application interface, to talk over the network. And this interface is really defining how applications can use the network. The purpose of using this API, of course, is to let apps talk to other apps. So that's what apps want to do. They just do this via the local host. And this API should allow them to do this while hiding all of the details of what goes on in the network here, in this cloud, which might be an ISP, for instance. How many routers there are and so forth in that cloud really shouldn't matter to the applications. They just want to talk across the network. So before we dive into the details, here's a motivating application, a simple client-server setup. So on the left here we have a client which is sending this request over the network to a server. The client is actually really a client app or a program running on the host, the client host. And when I say server, I also mean the server app that's running on this host here, which is acting as a server. The server app will receive the request and respond with a reply. This reply could be anything. It depends on our application. The reply will go back to the client app that's running on the client host. This might be a web page, for instance. This is a very simple pattern. However, it's a very important pattern because it's the basis of many different applications which are used on the internet today. For instance, If you just consider file transfer, essentially the request is the name of the file. It's sent from the client to the server, and the server app then returns the contents of the file. That's a much longer reply. If we just consider the web browsing case, the request that you're sending is a URL. So you're sending the name of a particular page you would like. And then the response from the server, the reply from the server, is the contents of that web page. And yet another example is simply the simple echo program, where the client is sending a message and the server is echoing it back. This is very useful for test functionality. Well, this is a key application pattern, even though it's fairly simple. Let's see how you would write it. Okay, to write it, we need some concrete API by which the applications running on a host can interact with the network, and that is the Socket API. It's providing us with a fairly simple abstraction that will let us use the network. And as I said before, sockets, that's the API which you use for essentially all internet applications. So this is the one we really want to look at. Sockets were devised long ago. They were part of some of the early Berkeley Unix releases around about 1983. Since then, sockets have become part of all major operating systems, and libraries to access them are present in all major programming languages. Now, all of the details vary a bit from one language to the other and one operating system to the other, but at a high level, they're all different socket APIs, and they all look quite similar. They just differ in a few details. Now, there are two different kinds of network service that the Socket API provides. And the one we're going to look at is called streams. This is a byte stream, and it allows one application to reliably send a stream of bytes to the other application, and vice versa. That's all we'll really use to make our client server example. There is another kind of network service that's called datagrams, where an application can unreliably send a message to another application. We'll look at this much later in the course, and you can ignore it for now. Okay, so here's one more slightly deeper view of sockets. Now, we've said, so here's the app, and it's running on a host. Here is the Socket API is across here. That's the API between the applications and the network. Sockets use a data structure that are called, unsurprisingly, a socket, to let an application attach to the network. So there's one socket that application's using. An application needs at least one socket, maybe more. And here's another socket that the other application here is using. Sockets also have numbers, what's called a port number. This provides a form of addressing. You can see on the left we have port number 1 on the left socket. The right socket is known as port number 2. These port numbers provide a form of addressing, and that's what allows us to multiplex multiple different applications on a single host, because we can distinguish between them. And here, finally, is the API. This table really shows you all of the main API calls that are used for sockets. So let's see what they are. Well, the top one here, this socket call, is what's used to create the socket structure itself, and that helps you create a new communication endpoint that an application can then use to access the network. Okay, what about the rest? Well, there is a send call. That is what an application uses along with its socket structure to send information, actually to send bytes reliably to an application elsewhere across the network. Okay, and you won't be surprised to learn that there's also a receive call. And this is a call which is used by the application at the other side to receive that information that's come across the network from the application that sent it. So it's probably not surprising to you that we have a send and receive call. What's everything else? Well, all of the other calls have to do with setting up and managing connections. When we're talking about streams, they're really analogous to a telephone call. Before you can simply send information across the network, you need to be able to set up a connection, much like making a telephone call to connect and make sure that there's someone at the other side who's waiting to receive your information. So the connect call here is used by one side to establish a connection to another side. These three calls above it, bind, listen, and accept, these are calls that are used on the incoming side to get ready and to accept an incoming call. And finally, the last call in this table is the close call. Well, that's what you use to release a connection and hang up, if you like, when both sides are finished. So let's go into a little bit more detail and see how we would actually use sockets. Now, I'm drawing a time sequence diagram here. We have a vertical line for the client, the first host, on the left-hand side, another vertical line for the server on the right-hand side. Time runs down this page. So let's see what happens over time. Well, actually, the first thing we need is some phase when we connect the two different, the client to the server, they connect. And then the client is going to be able to send a request. And we want the server to respond with a reply. And after all of that, much later on, we can close the connection. Both sides can close the connection and we're done. So let me tidy that up a little bit. And you can see this is the sequence of interactions that happen. And I've numbered them in the order in which they would happen on both sides. So connect, request, reply, and disconnect. And you can also see the direction in which messages are going. I've also dotted the connect and disconnect because these are really control operations, things that we just have to do to support the mean data transfer in the more solid alignment. The data transfer is what we really want the network to do. Well, let's go into this in a little more detail by writing down the different kinds of socket API calls which are used to cause this to happen. So what have I got to do? Well, actually, one of the first calls I need on both sides is a socket call. This is really to set up our socket structures. Then what would we do? Well, the client's going to connect. Oops. Okay, hopefully you can read that. The client connects, and to make that happen on the server side, we need to go through a sequence of calls. We need a bind, accept, listen, and accept in that order. Bind is really, so when we connect, we're going to want to connect to a certain server host on a certain port. Bind is really establishing an address for the communication endpoint. And listen and accept then prepare the socket to accept connections from the other side, and accept is the call which actually results in a connection being made from the other side. Once all of that's done, what are we going to do now? Well, we're going to send our message. That will cause this request to go over. That's what we want to send. We'd better call receive on this side to be able to receive it. After the request has gone across, we're going to want to call send on the server to send back a response. What the response is up to all of the code on the server. It could do anything. It could read a file off the disk, for instance, to get the message to send back. But we're ignoring that because we're just focusing on the use of the network API. On the other side, we'll need a receive call, and then much later on, both sides can call close. So this is the sequence of socket calls which are used both the client and the server to cause this interaction to happen. So let me clean this up. Here we are, and you can see what I've done now is I have numbered the calls in the sequence in which they will happen. Okay, so let's go through this. And you'll note that I've also added a star here. Star indicates blocking calls where the program makes the call and the program is then halted by the operating system until something happens and on the network side. And the network operation completes, and then the program gets the result and can continue. So here's the sequence of operations. On the left-hand side, we call a socket. Okay. On the right-hand side, we call a socket, and then we go through the bind, listen, and accept. Now, interestingly here, accept is labeled number 4, so it looks like we accept the connection before we make it with step 5. That's because accept is a blocking call. Accept tells the network to wait for and accept a connection. So it's just like telling someone maybe to go and sit by the phone and wait for it to ring. Connect, on the other side, is going to be someone making the call, which will cause it to ring. Eventually, when it causes it to ring, later down here, the program on the server side will continue. Once the server side has picked up the phone with this accept call, what would you do next? Well, if you just picked up the phone, here actually what the program is going to do is it's going to call receive, which is another blocking call. This is really the receiving side simply waiting to receive information. Later, sometime you'll call send. This is after the connectors come back. Then we'll call send. And that will cause this request to go over the network. The receive call, someone is waiting for it. They will then receive it. Now they'll work out what to do, and eventually they'll go back and send it. Of course, on the other side, once we called send, your program has sent the information away. It's going to be received by someone on the other side of the network sooner or later. But without waiting for that, you can go ahead and call receive, which now simply tells you on the other side of the network to now stop talking and instead listen and wait for someone on the other end to say something. Eventually you'll receive the message. That's the reply we've all been hoping for. Then you can get that and display your web page or whatever you want to do. And after that, we can then go ahead and close, and we'll close on both sides. So you can see here I've shown the sequence of calls. And note which ones are blocking, because that's sort of affecting the order and the timing of the execution in the program. Okay, so this is really using the socket. All that remains is for me to take these two sides and divide them so that we have separate client and server programs. And here is the client side as we just go through that. And you can see the calls as we go down. We start with the socket. Now there's actually something that you hadn't seen before, something called get_attr_info. This is really just some translation mechanism. You might have wanted to connect to a host called www.example.com on port 80, say. This might be a web server. Well, the network calls, the socket calls, don't take these high-level addresses. They take things like IP address numbers, network addresses. So get_attr_info is translating between high-level names and network addresses. So it's doing some of that bookkeeping. Now, and then we have the sequence of calls in the same order, and we go down here and we really go through just all of the steps that I previously outlined to execute the client program, sending the reply, receiving the message, and doing whatever we want with it. So what about the server? Well, the server goes through the same things. It creates a socket. Here's another get_attr_info to really, for the same name, a reason to translate between names and any addresses that are needed. Then we go through the bind, listen, and accept calls as before. Now, then we have the usual waiting for request, sending back the reply, and eventually closing. Often, however, this portion will be in a loop. That's because the client program might exist to make a single connection and get the information back. But often a server will be a long-running process. It will be running, it will wait for a client to connect, and it will service that request. Then it will wait for the next client to send a request and service it, and so forth. So there'll often be a loop structure in this program. And that's it. Now we have our client and our server pattern. I want to point out, if you're writing this as code, there's lots of detail that I've omitted here, both in terms of all of the parameters in a program in C or Java or Python or anything you like, as well as all sorts of other code to handle error conditions that could arise if everything doesn't go smoothly. But this is the heart of the program, and you can, by using this pattern, begin exploring your own client-server programs. So now we know something about how to write an application and use the network. G'day viewers. In this segment we'll use a program called traceroute to peek inside the network and see some of its internal structure. So this picture gives us the context for where we were before. You can see that using the Network Service API, sockets is what we looked at, applications talk to each other across the network. Now the Network Service API hides all of the details here of what's inside the network. So we can't really see by using it what's inside the network, how many routers we go through, what ISPs, whether it's a short path, a long path, all of this sort of stuff. Now this is actually good because we don't want you, when you're writing an application, to have to know all of those details or write programs that depend on any of those details. The higher level of abstraction is useful for us, but you might be curious to know what's actually going on inside the network. So in this segment, we're going to use a program called traceroute, which will let us peek inside the network. Traceroute is a very widely used command tool. It's maybe the #1 go-to tool of sysadmins to sort of debug the network and find out what's going on inside it. It runs on virtually all operating systems. You can see it's often called traceroute on Linux or Unix systems. And on Windows, it's traceroute with a RT at the end there. Traceroute was developed by someone called Van Jacobson. We'll hear about him a little more, especially when we get to TCP congestion control. He was one of the pioneers of computer networking as the internet grew up. And the traceroute tool we're going to look at, it works by using the network-to-network interface, I'll call it, really the IP protocol, the internet protocol, which describes how different hosts and routers talk to one another. It uses this program in sneaky ways that we'll get to later. For right now, for the purpose of this segment, you don't really need to understand how traceroute works. It's really just a program that will run and reveal a little bit of information about what's inside the network. Okay, so here's how traceroute works. Traceroute probes successive hops in order to find the network path between a host that's doing the probing, that's over here on the left, and a destination host that's on the right-hand side. So this might be some remote web server, and you want to find the path, the network path between your computer and the remote web server. What traceroute does is it sends a packet towards that remote host, only a single hop into the network, and then causes the network to send a message back, a reply back. Then it sends a packet 2 hops into the network and elicits a response from there. Then 3 and elicits a response from there. And so on. And eventually it sends it almost all of the way, elicits a response. And finally, on the last time, the packet will reach the remote host, which will then send a response, and we'll know that it's arrived at the remote host. All of these responses in the middle, as we get a response from routers in the middle of the network, this gives us information about what those routers are, the number of them, and the sequence in which they're organized, until over here, eventually we get a packet back from the remote host, and we know that we've seen the whole path through the network. So that's roughly how traceroute works. Here's a picture where I've just cleaned up some of those. I've cleaned up some of that figure. And as I say, we'll go into more of the details about how traceroute uses IP to do this later on, but for now, just suspend disbelief and imagine you have this tool that you can run. So let's see how it works. I'm actually in Barcelona right now, so let's try and find out what path is used in the network as I send packets from here to the web server at the University of Washington. Let's enter a command and we'll enter a traceroute. Traceroute to www.uw.edu and see what happens. I'll hit return and traceroute is away. What it's doing is it's sending its packets to probe successive hops. You can see the very leftmost number is the hop number. It actually sends out 3 entries for every hop. And the first numbers are the timing. So you can see initially it was very fast, within a millisecond within my house. But as we got further away from my house and further out into the network, the times got larger, up to a couple of 100 milliseconds. Now on the right-hand side, you can see the names or identifications of all of the routers. Both the IP addresses are given, as well as some of the names there. And we can take some hints from the names and work out somewhat about where the packet is going. Some of those names have Telefonica in it, so it looks like it goes through the Telefonica network. And it looks like it goes through the level 3 network. You can see San Jose there, as well as Seattle later on. And eventually it arrives in some computers at Washington. On hop number 17, we see stars back. The network actually wouldn't return any information for what was at hop 17. Something must have been there, but whatever it wasn't telling us, because it's not required to implement traceroute. Okay, so now in this slide I've taken the same information as from our example before and just laid it out a little differently to try and show you the path between my computer and the destination that I was probing. Here I call it www.uw.edu, even though in the traceroute at the end we actually saw that the name of this that name was an alias for this other computer's name, www.1.cac.washington.edu. Now, I'll point out here that the ISP names and places in the middle are just educated guesses based on the information returned from traceroute. It gives the IP address and a translation into a host name from which we're making guesses about the ISPs. So we could see that after 1 hop, we were still inside the home network here. We came back, and this was quick. For the first 3 hops or so, we're inside some network called TDE. Not sure exactly what that is. You could Google it. I think that's some internal Telefonica network. Actually, I'm guessing the end of that was probably we're still in Barcelona from the BCN here. That stage, it looks like we went through a network, the Telefonica network, for 4 hops. It looks like we entered it, or shortly after we entered it, we went to New York City, and the round trip time here had gone up to about 100 milliseconds. That's maybe consistent with Barcelona to New York City. We're no longer just in Barcelona, we've gone further afield. But after 4 hops or so, it looks like we emerge in another network, this time called level 3. Sorry, they're level 3. And it looks like we enter that network in San Jose and then go through the level 3 network for 6 hops. By By this time, the round trip time is rising. You can see here, I think it rose to about 180 milliseconds. This is just an estimate once again, as we went from New York all the way through the network to San Jose. So now we're on the west coast of America. We're getting close to Seattle, but we took 6 hops through level 3. And at that stage, we arrived somewhere in Seattle, and we actually went through a network called the P&W Gigapop. You wouldn't necessarily know what this is. Again, you could maybe Google it. I happen to know that's the Pacific Northwest Gigapop, which is an exchange where different networks come together in Seattle. And this network then routed us onto the UW network. By now, by the way, the round trip time's gone up beyond 200 milliseconds. And within 3 hops within UW, we arrived at the final destination. So you can see that Traceroute gives us a lot of information here. Really, they're hints. They're not always unambiguous. But Traceroute's giving us a lot of information about the paths that your packets take through the network. So you can try this yourself and find out the paths to some destinations throughout the network. G'day viewers. In this segment we'll talk about protocols and layering, and this is the most important idea there is for the structuring of networks. Okay, so networks need some form of modularity to manage all of their complexity. If you think about it, there are many different functions that you know exist in networks, and I've listed some here. Setting up all kinds of connections, finding the path through the network, reliability, all sorts of things to do with how fast you can send information depending on how many users there are and what network you're going through, security, management of the network so that you can easily add new hosts as it changes, and so forth. That's a lot of complexity. All of this, by the way, underlies the simple action of clicking and getting a web page back. So there's a lot of mechanism underneath to make that happen. Well, what we need is some form of modularity which will help us manage that complexity and allow us to reuse a lot of network functionality across many different settings. That is exactly what protocols and layering give us. Protocols and layering are the main structuring methods which are used to divide up the functionality of networks. So the way protocols and layering work is that each instance of a protocol, now you might think of this just as an object being an instance of a class, for example. It talks virtually to its peer protocol instance, which is on a different host elsewhere in the network. But the catch is, to talk virtually to that peer instance, the protocol is only allowed to use the services of a lower layer protocol on the same host. That all sounds a little mysterious maybe, so let me just try and draw a diagram to explain that. Okay, so let's see, here is a protocol instance. I'll write X to mean this is an instance of protocol X. Now, this protocol instance wants to talk to another protocol instance, X, on some other machine. To do that, it will use the rules of protocol X. So it will only exchange messages of protocol X and so forth. But I've dotted this line because there's no direct communication path between here. These are on different machines, these protocols. So how do they talk? They use the services of a lower layer protocol, in this case protocol Y. And protocol Y is similarly going to virtually talk to its peer, an instance of protocol Y on another machine using protocol Y. So X will locally on a machine use only the services of Y. Let me clean this up. So here's maybe a little bit of a clear diagram. What you should take away from this is that, so here's one host, by the way, if I just draw here, node 1, here's another host, node 2. So on this diagram, the layering is happening vertically as each protocol instance talks to the lower layer protocol instance, and the lower layer talks back to the upper layer when things are received from the other side. The protocols are designed horizontally. They're really specifying the form of interconnection between the two different systems. Of course, I still haven't really gotten to the bottom of this picture because we don't know how protocol Y really communicates. We see the virtual communication, but what's going on? Well, this is what's going on. The same thing happens again. The protocol Y communicates using the lower layer protocol. And when you do all of that, you get what's called a protocol stack. So here is a protocol stack. And here it's just listed layer 5 through 4, 3, 2, 1, down to the bottom. What's going to happen at the bottom? Well, at the bottom where it's labeled physical medium, this is really just a wire, or something like a wire, such as a fiber optic cable. This is the medium which carries whatever message as electrical signals from one side to the other, and then layer 1 is going to interpret that as a message. So by acting in this form, we've got a higher layer protocol such as layer 5 being able to virtually communicate with its peer instance here without really knowing what's going on anywhere below layer 4. Well, protocols and layering are everywhere. You've probably heard of many different protocols, even if you didn't realize they were protocols. I'm thinking of things like TCP/IP, 802.11, Ethernet, HTTP, SSL, DNS, and many, many more, some of which we'll come across in this course. They're all protocols. We can even, just to show you how some of these things fit together, let me draw you an example protocol stack. And for this example, we'll choose a web browser on your host, say, and let's just assume that you're wirelessly connected to the internet. Okay, so now let's see, here would be your browser. That's really an application that's using the network. Now the browser, well, if it's a web browser, I happen to know that the web protocol is HTTP. Doesn't matter if you don't know this, we're going to cover all of these protocols by the end. The browser implementation will actually often include an implementation of HTTP. HTTP in turn runs on top of TCP/IP. These are the common internet protocols. And if you're on a wireless host, this TCP/IP will be running on 802.11. And then the wire comes out of here. I'll draw it as a wire, but in this case, the link really is wireless, so there would be no physical wire. But we can still draw it like this to show the connectivity. Here we are. I've cleaned it up once again. So this is the protocol stack that would be used for this particular instance. Okay, well, we're not quite done with protocols yet. There's still more mechanism that I want to tell you about. We said that protocols are layered one on top of the other, but we didn't really talk about how this layering is manifest or implemented. Well, encapsulation is the mechanism that's used to affect protocol layering. So the way it works here is that the lower layer wraps all of the higher layer content. It's going to have to add its own information, control information for delivery throughout the network. To understand how this really works, the analogy that we'll use here is that of sending a letter through the postal system. What you do is you write your letter, good old-fashioned letter, you write it with a pen, then you seal it in an envelope. The envelope is like the lower layer, a header information. It contains all of the addressing and so forth when you pass it to the post office in that form. The post office only then needs to use the lower layer information on the envelope to get the letter to the other side. And at the other side, the envelope is extracted. The letter is extracted when you open the envelope. Actually, there are probably even other lower layer protocols in here. Letters going to the same destination may be all bundled together so that they can be routed, in an airplane or a truck all at once and so forth. So this is what's going on with encapsulation. We can draw some pictures to show you what would happen with our example protocol stack here if we send messages through it. So let's see what happens. Well, at the top, HTTP, we're just going to start with a message. Okay, now, HTTP will pass it down to the lower layer. What will happen at the TCP layer? Well, here is the HTTP message. The TCP layer will add, well, actually, I should draw it like this. It will wrap it and add its own control information at the top. It'll then pass it down to the IP layer. Here that blob is. What will happen? The IP layer will wrap it and add its own header. That will then pass it down, and guess what will happen again? There it is. The 802.11 layer will wrap it and add its own header. Wow, this is a little tricky to draw boxes inside boxes, so I'm going to clean that up for you. And here you are. Look carefully at all of those different boxes. I omitted all of the inside detail just because it was too much for me to draw. But you can see that messages on the wire begin to look more and more like an onion. And that in fact the lower layers are outermost. You might think the higher layers should be outermost, but the lower layers are outermost because of the way it's constructed going down that protocol stack. Here's the same view as I've shown both the sending and the receiving protocol stack. So we go down that protocol stack and you can see, what happened as we expected here. Now, this is the interesting bit. This is what actually you would see if you were to look on the wire of a network and to see a message going by. It would be like this. And this is the beginning. This is the start over here. On the receiving side, you can simply go through the reverse process. The 802.11 layer looks inside it and extracts this bit, this bit here and sends this up to the higher layer and so forth, and we continue. So that's encapsulation. In fact, actually, normally we'll draw encapsulation much more simply. I showed it as really drawing a layer around the higher layer payload to encapsulate it, but often encapsulation will simply proceed by having each layer add its own control information to the front. So TCP there will add a layer in front of HTTP, IP will add a layer in front of TCP, and so forth. And 802.11 will add this layer in front. This is a simple form of layering, just adding a header in front, but this is often what's used in practice for many of the protocols we'll look at. In fact, this is just how we'll think of it. Layering practice can be more complicated than this. For instance, you might have trailers as well as headers. Trailers are information, control information, which is added at the end. And the information that's in the middle may be transformed in reversible ways, such as encryption or compression, such that you might not be able to see it literally, instead of simply leaving it alone. But we can just ignore this for now and think in terms of our simple model here. And actually, there's even more complications. Sometimes you might use, what's called segmentation and reassembly. This is when a long message from a higher layer is divided into many smaller shorter messages at the lower layer, just because the longer message didn't fit through the network as is. But wait, there's more. There's one other thing I've got to tell you about layering, and then we're mostly done with the mechanics of layering, and we can see how what we get out of layering. Okay, well, when a packet comes in down here at the lower layer, we've got to work out what protocol instances are inside it. Your computer is probably running many different protocols that are used by many different applications. Now, if what came in is really part of our web application, we knew from before the protocol stack was this. It was, let's say it was Ethernet, TCP, and HTTP. But how do we know to follow this path through the graph and not, for instance, this other path, Ethernet, IP, UDP, DNS? This other path is a real path. It's something that's used for DNS traffic to translate host names to IP addresses. Well, how are we going to do this? Think about it for a moment and see if you can work out the answer. Okay, you ready? Well, this is what we would do. In fact, what must happen is that each layer includes inside it some control information to identify the higher layer. So as the packet comes in here, we know it's Ethernet here simply because Ethernet, all messages on this network are Ethernet if it's an Ethernet network, say. But the Ethernet header will have a little bit of information that says go this way to IP. In Ethernet, this is actually called the ether type value. Now, then as IP processes, IP will look inside its control information. There'll be a little bit of information. It's actually the IP protocol field, which says go this way to TCP. And inside the TCP header, there'll be a port number, which says go this way, which will happen to be HTTP. This information in each protocol layer is what's called a demultiplexing key, because it helps us undo the multiplexing and go back up the right route. Okay. Well, now let's see how we can gain some advantages from layering, now that we've gone over its mechanics. Layering, the key advantage it gives us is information hiding, and through that, reuse. So imagine we have our browser and server application here, our good old web browser. You could run it on a protocol stack like this. Well, all the browser knows is that it's talking to HTTP here. But let's say you happen to run HTTP on the protocol stack TCP, IP, and Ethernet. Okay, Ethernet is a typical wired enterprise network. You could similarly run the same web browser on a different protocol stack. Let's just say we want to run it on TCP, IP, and 802.11 because this is a wireless host. Wonderful. The web browser doesn't actually either know or care what it's running on at the lower layer, and this is a tremendous advantage because it would be terrible if we had to write our web browser differently depending on all of the details of the protocol stack. By hiding information, we're getting a lot of powerful reuse out of it. There it is cleaned up. Oops, I chose the sides differently. Doesn't matter. And we can also gain further advantages. You can use this information hiding to interconnect different kinds of systems. So imagine over here we have the browser. It happens to be running on an 802.11 network. Well, the server, that happens to be running on an Ethernet network. Doesn't matter with our protocol layering system. This is what we can do. Here, we'll have the 802.11. It must talk to a peer 802.11 box. And similarly an IP layer. So we will use this 802.11 box to terminate the packet, the 802.11 layer, pass it up to the IP layer, which can then pass it across, or keep it within the IP layer is maybe a better thing to say, and pass it down to an Ethernet layer. In the same way that over here we passed an IP packet down to an 802.11 layer. This Ethernet layer is then able to virtually communicate with another Ethernet layer protocol. And everything is okay. We've managed, by using protocols and layering, to interconnect web browsers and servers running on different kinds of networking technology. So this is what protocol layering is all about as a means to connect things. Note that to do that, we needed to have something like a single layer here which provided connectivity all of the way across. And this is what IP does frequently in the internet. It's the basis for being able to connect everything with different kinds of media type below and different kinds of applications and protocols above. Here's that same picture cleaned up a little bit. What I've done also is down here I've drawn a picture just of the message as it would appear on the network. You can see we started with the HTTP message and we added these headers. Now I've shown in pink here, this portion is the portion which is not touched as it's carried across the network. I've left the IP piece unshaded a bit because the IP processing happens in here, so the IP control information front may be altered. And similarly, we can see as we go across actually, this 802.11 will be taken off and this Ethernet portion here will be added as we go on the other side. But all of the information in the middle that we cared about, the TCP and HTTP, will be passed unaltered. And this is what is providing us with virtual communication between the browser here and the server here. So that's protocols and layering. Just to round out our notion of protocols and layering, I'll tell you that there are some disadvantages to layering. It's not all roses. Here are two disadvantages. The first disadvantage is that layering, adding more modularity, adds a little bit of overhead. If we knew, for instance, that our protocol stack went HTTP, TCP, IP, and Ethernet, maybe we could devise a custom header which had all of the necessary functions in one, and it would be shorter. So we definitely lose a little bit of efficiency. Often this is a minor concern. If you're thinking of large packets, the overhead of layering is small, in some small number of percent. Now, on the other hand, so that was this, adding overhead. A bigger concern probably is that layering hides information. We said that our web browser now doesn't know whether it's running over a wired or a wireless network. Well, you know, that allows us to run the application, it's true, but your application might care whether it's running over a wired or a wireless network, because really they're quite different. On a wireless network, the bandwidth is much more variable and you could be changing locations all of the time. This is something that an application would like to know. So information hiding is a disadvantage of layering. Okay, but the point is, now you know about protocols and layering, the key mechanism that's used to structure computer networks. G'day viewers. In this segment we'll talk about reference models, which give us a way of organizing protocols. Okay, so now we know about protocols and layering, good for us. But what we still don't really know is which particular function should be implemented in which protocol. If you think of a function such as finding a path through the network for routing, should that be implemented in a higher layer protocol or a lower layer protocol? We don't really know yet. So this is the key question. And it's a major question for designing any network. It's probably the largest question. Well, there are actually no definitive answers because in which layer to place a particular function is a matter of experience as people design networks. But we do have something which will help us out. The reference models I'm about to describe provide us with guidance to tell us which layer it is often valuable to place particular functions. So here is one famous reference model. It's called the OSI 7-layer reference model. Now, this is a principled international standard effort. It's all about providing a reference model that will allow systems to be interconnected. Systems made by different people, that is, different manufacturers, to be interconnected in a way such that they'll all work. It's been tremendously influential. It was actually put together by a standards body this is probably all the 1980s. But even though it's hugely influential, it's not really used in practice. Oh well, in fact, I'm not even going to tell you what OSI stands for because you don't really need to know. Okay, I'm just kidding, I'll tell you. Open Systems Interconnection is what it stands for, just in case you're asked. But this standard is really an influential one rather than what's literally used in practice. Let's go through it. You can see that there are these 7 layers here. At the lowest layer is what's called the physical layer. The function of this layer is all about being able to send bits across some physical medium like a wire. So that's going to involve sending signals. The layer above that, the data link layer, is about sending units of information. Here they're called frames, but the point is they're not mere bits. They're now closer to the message we care about. On top of that is the network layer. That's about sending packets across multiple links. It sounds suspiciously like the data link layer, but its scope is broader. Now we might talk about sending packets across multiple networks, as in the internet. On top of this is the transport layer, which provides different kinds of end-to-end delivery services, such as reliable delivery, for instance. On top of this, then, are another couple of layers that are a little different. The session layer manages task dialogues, it says here. What that really means is bringing together many different components that are used in a related way together so that they can be manipulated as one. For instance, an application might use many different connections across the network, all in service of the single application. The presentation layer is about different representations for information, different file and image and video formats, for instance. Because many applications can communicate using different kinds of formats for the same inherent content. And finally above that is the application layer, and that's really what we think of as applications. They provide whatever specific functionality is needed by users. So this is the OSI 7-layer model, and you're going to want to remember all of the different layers of that model. But I'll tell you now what we mostly use in practice, and particularly in the internet, of course, is something called the Internet Reference Model. This is a 4-layer model that's based on experience. In fact, in some ways, it's the opposite of the OSI model. The internet began to be built, and whoever implemented pieces that worked, well, that's what became the internet. The model was really fashioned out of it, abstracted out of it later on, just to try and clarify what was going on. And it really drew on many of the ideas from the OSI model, which had a brilliant model, but no implementation of protocols that anyone really cared to use. So you can see that there are some differences compared to the OSI layer model. We really omit some of the layers, and instead of a network here, it says internet. The internet layer is the key replacement for the network layer, and the internet layer is all about the IP protocol. So if I was to number this, going from the bottom up, we start with the link layer. Its purpose is to send frames, these units of information across links. I'll call this layer 2 and 1. Because really compared to the OSI model, it's often performing both of those functions. On top of this, the internet layer is really a replacement for the network layer 3. You'll often hear network and internet in the same breath in terms of layering. The transport layer is then layer 4. It's providing services on top. And people might talk about layer 7 as the application layer. That's what it was in the OSI model, layer 7. And you can see here we're missing the presentation and session layers, which actually are not normally present in a layered structure. Presentation and session functions are useful notions, but they're often provided by libraries and they might not be explicit in the layered protocol structure that's used in networks. So here we have it. We have the Internet Reference Model. Let's go a little further and look at what we can do with this model. Actually, I mostly want to relate it to the protocols you might have heard of. Now again, just to clarify, a reference model is a framework for describing what protocols perform what kinds of functions. It's not actually the protocols themselves, so we need to put different protocols in different layers, and you might devise new protocols in your career, who knows. So what kind of protocols go where? Well, at the internet layer, guess what? It's the IP protocol. It is the main instance of a protocol at the internet layer that we're going to use in the internet. Transport layer protocols, you might have heard of TCP, and there's something else called UDP, which transfers information without reliability. Oops, my writing's a little off there. These are two protocols which are used here. Now, on top of that are various applications. Applications here are really things that use the services of the network. We might have HTTP, that's used for the web. Other things, RTP is used for real-time. SMTP is used for email transfer, and maybe something even like DNS. And there are plenty of others. I'm just sketching a few examples here. Okay, below IP, we have different kinds of link technologies, which are used to combine different systems. This is, different kinds of physical medium, if you like, that we're going to use to connect different nodes. So we might have, it's 3G cellular, Ethernet, I'll write DSL and cable, just as different kind of physical layers that you plug into, and even 802.11. Okay, let me clean some of this up a bit. Oh, I mostly chose the same protocols, that's good. Now I've drawn it in this fashion to show you that IP here is the narrow waist of the internet, because if we always use IP as a standard reference for the network layer position here, as we do in the internet, then we're able to use a diversity of different technologies below and a diversity of different applications above. And we can change any of those new link layer technologies or any of those new applications and transport protocols, and we would expect to be able to interoperate across all of these systems because we have a common layer in the middle, IP, which is the narrow waist of the internet, is providing connectivity between all of the diversity below and all of the diversity above. So this is really, this narrow waist using IP is at the heart of innovation in the internet. Okay, let's see. Oh, here's the other thing you might be interested in, and this is just where on earth all of these protocols come from. We will see many examples of protocols in this course, and there are many more that are out there which are used in practice that we won't even have time to go over. So who's making all of these protocols? Well, the answer is different standards bodies are making these protocols. And the reason they're making it, what they really care about is interoperability. They're making a standard so that different manufacturers of a device that performs some function, such as playing video over the internet, will be able to operate with one another. This is good for all of them because it increases the size of the market. You don't want to have incompatible technologies that do the same thing. It promotes standards wars. So the focus here on these standards is on interoperability. In fact, the focus is not usually on how to do a good job of implementing this standard at all. That's really left to companies, and whoever can do a better job there has a competitive advantage. So this can lead to strange things being left out of standards, actually, because information that's going to help you do a good job in terms of performance need not be specified. So I can show you some examples of different standards just to tell you about it. There are different bodies here. In the telecommunications area, there is a body called the ITU, the International Telecommunications Union, specifies a lot of telecommunications standards. Examples here are things for like ADSL, your DSL link used at home. The MPEG-4 standard, which is used to compress audio and video and widely used, is actually in the ITU standard. These standards are often called letter standards. You can see the G dot and the H dot. That's actually the official name for that standard. It's not called ADSL, it's called G.992, for instance. There's another body, the IEEE, the Institute for Electrical and Electronic Engineers. And this body produces standards in the communications areas via different working groups. The most famous of its working groups is the IEEE 802 working group, Project 802. And that's produced many standards, of which you probably used and are familiar with. We all know Ethernet and Wi-Fi, or at least you've probably heard those terms. This is actually 802.3 and 802.11 standard. This is why Wi-Fi is sometimes called 802.11. That's the name of the standard for Wi-Fi, whereas Wi-Fi is just the common garden variety name. Then there's a body called the IETF, the Internet Engineering Task Force. This body produces internet standards. And these are sometimes called RFCs, or requests for comments. So there are many different RFC numbers, and they specify standards that you might have known, that you might know about. For instance, here's an RFC for the DNS. There would be other RFCs for things like TCP and IP, for instance. And finally, I'll mention the W3C, the World Wide Web Consortium. That produces web standards, not surprisingly. So things like the HTML5 standard and the CSS standard. This is about the content over the web. Actually, the protocol that's used across the internet, HTTP, is specified as part of an RFC. Okay, so now you know a lot about standards. What I want to do now, just to finish out this unit, is to talk about something else we get from reference models. And that is the structure of the reference models often gives us some names and terminology just to talk about networks. In fact, a lot of the names we use to describe units of data take their names from the layering. If we're talking about units of data at the physical layer, well, typically we're talking about bits is what we're going to call information at the physical layer. If we're talking about the link layer, we'll often be talking about frames of information. The network layer is where packets exist. And the transport layer, a unit of information at the transport layer is actually called a segment. And there's a generic term for applications and everything above that's message. So different layers technically have different names for groups of information. Nonetheless, I want to point out that packet can either be used in a very specific way, meaning the network layer precisely, or we'll often use this just in a general way as a form of convenience to refer to a unit of information that's going over the network. It might more properly be called a frame or a segment, but often just for the sake of convenience, I'll call things a packet. And you'll have to work out from the context whether it's actually a frame or a segment. Layer-based names are also used for devices in the network. Now here I have a device that's called a repeater or a hub. It works like this. You see this picture shows that it performs processing at the physical layer, but it does not touch information at any higher layer. You might also have heard of devices called switches. A switch operates at the link layer, so you can see here that it connects different instances of a link, typically with the same technology, and that's how they can be connected together. Whereas a router operates at the network layer, so it's able to take in and connect instances of different links. So this might be 802.11 and this might be Ethernet. And this is how the router was able to connect different network technologies by connecting at a higher layer, the network layer. And we can go up even higher. Here we are. There's a variety of terms just for things that operate inside the network to provide connectivity and relay messages between devices, yet they look more highly than the network layer. So they might look into the transport layer or even the application layer. These are variously called proxies or middle boxes or gateways. They're actually strange devices in the middle of the network. Not at hosts. Hosts, of course, need to process these layers. I'm really talking about devices in the network here. Now, the reason this is all important, these names are important, and that you understand your layered diagrams, is all of these boxes just look exactly like this. I mean, they're just different kinds of boxes. You might be able to recognize a particular kind of router or switch if you're used to working with them, but if it's something you haven't seen before and it's a box, you don't really know what kind of processing it implements inside it. If you can find out, well, these diagrams and these particular names tell you the kinds of processing that can exist within different kinds of boxes. And finally, to finish out this segment on layers, I want to tell you that layers, and with our reference models, are really a guideline. They're not strict. In fact, you might have multiple protocols operating at the same layer, and there may even be cases when a particular protocol is difficult to assign to a layer. It might not neatly fall into our different kinds of layered framework here. In fact, this is a lot of the complexity and the fun of networks. That you might have protocols that don't neatly fit in here. So don't just assume that because something sits on top of a network layer protocol, it's a transport layer protocol. That's not necessarily the case. Nonetheless, our overall layered framework will prove valuable just for thinking about the functionality and roughly what's going on at every layer. Okay. G'day viewers. In this segment we'll cover a very brief history of the internet. So you can see here I've shown you a rough timeline for the internet, and it goes from, say, let's call it 1970 to today. So we're spanning more than 4 decades here. And over that period of time I've drawn 3 main phases that I'm going to talk about as the internet having gone through: an ARPANET phase, an NSFNet phase, and really the modern internet and web as we know it today. Throughout those phases, the internet has grown enormously. In fact, from every phase to the next, we have about a factor of 1,000 growth, which is just huge. So from the end of the ARPANET, from 1,000 through to 1 billion hosts today. And this is all very rough. We can go into more detail as you'd like. There are many resources you can read to find out a little more about this. Okay, so let me tell you a little bit about each phase. So in the beginning, there was the ARPANET. The ARPANET was a network that was built and sponsored by the US Department of Defense. It was the precursor to the Internet, so it became the Internet. This network was motivated for resource sharing, obtaining access to some early and relatively powerful for those days computers from offices at different locations. It was actually launched with just a modest 4 nodes in 1969, and during the ARPANET phase it grew up to be hundreds of hosts. And in fact, during this phase, one of the first killer apps in the Internet emerged. It was email. This was not what the network was intended for. It was intended for resource sharing, but email, which was written just a handful of years after the ARPANET was born, became very popular as people used it to exchange messages. During this time, there were several key influences. So I've shown here some key influences leading up to the creation of the Internet. And one of the key influences here is what is called packet switching. Packet switching is something that was pioneered by Donald Davies in the UK and Len Kleinrock in the United States, amongst others. And packet switching was really interesting. It's really just the notion of packets and sending through networks is what we would think of today. It's interesting because it's quite different than the circuit switching, which was used as part of the telephone network at that time. The whole notion was to organize information in small units of packets through which they were sent through the network. And this could be much more efficient for connecting computers together than using telephone circuits, which are maybe good for people, because computer traffic is very bursty. So we might sometimes have many packets, but often there'd be no packets. So dedicating a whole circuit would be wasteful. Whereas if we use packets, we'll get the advantages of statistical multiplexing that we talked about in terms of getting better use out of the links. So this was one key influence. Another key influence was that of decentralized control. From the early efforts of Paul Barrett, who produced various designs that emphasized decentralized control. In those days, the telephone network was organized very hierarchically, so that if you took out a high-layer node, you would really paralyze a lot of the network. Being able to create networks where control was fully decentralized, so that if you blew up a portion, the rest of the network could continue to function, was obviously something that was very appealing to the military at the time. And so this is often why you hear of the Internet, the ARPANET has been created to withstand a nuclear war in which a portion of it was lost. But really this is just one of the influences leading up to it. As the ARPANET took off, in the very early Internet, another key influence became paramount, and that was internetworking. Internetworking here was pioneered by Vint Cerf and Bob Kahn, shown here in their pictures. Internetworking is all about connecting different networks together into a single larger network. Cerf and Kahn pioneered it fairly early on in the ARPANET, starting in like 74. And this later became the TCP and IP protocols. So really the key idea of internetworking is that we have different network technologies. One way you could build a big network is by getting everyone to use the same technology, mandating it. But Cerf and Kahn realized that this was infeasible already. There were packet radio networks, satellite networks, and the ARPANET. They're all different kinds of technologies there. Cerf and Kahn instead proposed to use a higher layer of interconnection, to a level of indirection, if you will, to combine all of these different networks together. And they solved the problems which were required to be able to internetwork these technologies. For this achievement, they're popularly known as the fathers of the Internet, and they've received many awards for this. Okay, so here's an early geographical map and a network topology map for the ARPANET. It comes from around 1978. You can see by now the ARPANET has grown up a fair bit, although by today's standards it's still a very small network. There are all of these different circles. These are different kinds of nodes. They were known as IMPs. This was the name for the early router. I think that's IMP is an Internet Message Processor. And the links between things, well, here's a link here. They ran at 56 kilobits per second. So you can see we've got a network here which is growing up. As it grew up, and now we've passed on to, I guess, thousands of different nodes, as it grew up, the NSF commissioned a network which played a key role, and this was called NSFNet. The ARPANET really connected people who were doing business with the US Department of Defense. And there were many other players who didn't have a contract with the US Department of Defense who wanted to be able to connect using this interesting newfangled technology. And so the NSF built a network which would allow all different kinds of educational institutions, universities, to connect to this network. Initially, this network connected supercomputers at different sites together, but eventually it connected many different sites and it became the backbone for all internet traffic, effectively replacing the ARPANET. It's during this period, this was a tremendous growing up period, this period of a decade or more. It's during this period that the classic internet protocols as we know today emerged. All of TCP/IP, the DNS and the Sockets API emerged around 83, quite a year, I guess. And internet routing in the form of BGP, that's a protocol we'll get to later in the course, took a little longer to emerge in the modern form that we recognize, but it was around by 93. During this period also, there was tremendous growth in interest in computing and networking technologies. The personal computer was really coming into its own, and personal computers appeared, and then became personal computers, first really on campuses, educational institutions for research. As they became effective, they made their way into businesses and eventually in the form of personal computers into homes. So it's not just personal computers, computing, but networking technology. Ethernet, the most popular form of local area networking, emerged in this period too, and it took off like wildfire, allowing all of these early computers to be connected. And so the result is that by about 93, we had maybe 1 million hosts that were all connected together as part of the internet. It's growing up. Here's the architecture of this early internet when the NSF-Net was in use. And you can see this picture here is really, it's meant to just be very simple and hierarchical. The NSF-Net here is the backbone. What that means is if the two customers in different places want to communicate with one another, a local customer network might be a university network, would send packets up to its regional network, which would send packets to the NSF backbone network, which would send packets down, which would carry packets, I guess, across the country and deliver them to the right regional network, which would carry packets to the right customer network, and we would achieve connectivity. Now, the early NSF network backbone, you can see here just the speeds it used. It started off with 56 kilobit per second links. Fairly quickly it upgraded to 1.5 megabit per second links, and then to 45 megabit per second links. So the network was really growing quite fast in terms of speed as well as in terms of size. Well, after a decade or so of all of this growth in the popular technologies in computing and networking, we arrive at the birth of the modern internet, which contains the internet and the web as we know it today, is really a continuation of what was started here. And this was around the early 90s. There are two major changes I want to point out to you compared to the earlier structure. Now, the first is that after around 95, connectivity was no longer provided by the single NSF-Net backbone. Instead, connectivity is provided by large ISPs. There are several different large ISPs, handfuls of them, and they're providing connectivity to people across the wide area, and they're also competing with each other as business. So there are now multiple players at that top level. And the way we're making sure that packets get everywhere is that all of these different players, these large players, interconnect at IXPs, Internet Exchange Points, so that they're able to exchange traffic and get it anywhere on the internet. And later, large content providers also come along and connect into these IXPs, so that they can distribute content all over the internet. So that's one change, the way we route across the internet and the architecture of the internet. And another big change is really the web. The web, which was pioneered by this man over here, Sir Tim Berners-Lee, emerged, it burst onto the scene really because it took off so rapidly. It emerged around 93. And it really took off in terms of traffic, and it caused a lot of interest in the internet. Everyone wanted to get on it. The growth led to the formation of what are called content distribution networks to be able to efficiently distribute all of this content. Naming became much more of a concern, and this led to the establishment of the body called ICANN, the Internet Corporation for Assigned Numbers in Names, later on, around 98. The content has continued to evolve ever since. Most bits now actually are video that's going over the internet, just because videos are so large. And most of the traffic is soon to be going over wireless networks, and probably from mobile devices. Not quite yet, but it's skewing rapidly in this direction. And really the new kinds of content are driving the internet. That's where we are today. And I'll skip all of the later, Facebook and everything, because I'm sure you're more familiar with the evolution of these particular companies in the internet ecosystem. Really, it's the web and the continuation of the web that they're providing. And finally, I just want to show you the modern internet architecture. So this picture here is to contrast with your previous picture of the NSF network backbone. You can see here I have the IXPs as the point of interconnection and different transit providers. Here's a transit provider. This is like a big ISP. Connect to different IXPs, and content providers also connect to the IXPs. So what you might have now is that you might have the case that content is going from here through an IXP to a transit provider and then down to a particular customer. Or we might be sending traffic from this customer here. If this customer wants to get traffic to the other customer, we might go up through the transit network, and then we might go through to the transit ISP, then we might go to an IXP and be routed to another transit provider, who we would then send traffic down, and let's say now we're going to this customer. So you can see they all fit together in a rather different architecture with no single backbone up at the top. That's the defining characteristic of today's internet architecture. Okay. G'day viewers. In this segment I'm going to tell you how the rest of the lectures in this course are organised. But first, congratulations are in order. You've now learned about the key concepts of protocols and layering which you use to structure networks. So that means that you can read diagrams like this and understand, for instance, that here are two hosts that are using wireless connectivity to talk to one another. And you've also seen how the internet protocols are organised in frameworks such as this internet reference model. This model in particular, I want to point out the narrow waist of the internet, which is IP, and how it allows a diversity of different link technologies to flower, as well as a diversity of different applications to be used on top of the network. Well, in the rest of the course, we're going to use this reference model that's shown below. So you'll see that we mostly follow an internet reference model. We actually do a little more, so if we go through this model, we start at the physical layer, which is all about sending bits using signals. We're going to do a bit more of this layer than you would usually see in the internet. And then we move on to the usual link layer to send frames across links, the network layer to send packets across multiple networks, the transport layer for different kinds of end-to-end delivery, including reliability, and the application layer for all manner of programs which make use of the network. So as well as doing a little more on the physical layer than you would get in your typical internet reference model, we're also going to talk about some of the alternatives to IP. So I won't always be very internet specific. Sometimes I'll show you other ways of doing things, which may or may not be popular in practice. The idea is here to give you a good sense of how networks, not only how the internet is used, but how networks can be designed, as might be valuable to know in the future. Our progression of lectures is going to work through these layers really from the bottom up. So we'll start here at the physical layer, and you'll learn about wires and fiber and wireless. Then we'll move on to the link layer, where you'll learn about protocols such as Ethernet and 802.11, which are used to connect all manner of hosts. At the network layer, we'll learn about IP is really the main example, as well as technologies like NAT and routing in the internet with protocols such as BGP. Then we'll look at the transport layer, the TCP and UDP protocols mostly, and then all manner of protocols which make use of the network applications such as HTTP, DNS, and CDNs. After that, we'll follow up with a little more detail on some subjects which span multiple layers. And I'm thinking in particular of quality of service and security. All of these topics cover more than one layer. They don't neatly fit into any of them. And all the way through, this will be an upper division college level course. So there's definitely a lot of material. This is the sort of course that you can be proud of accomplishing. For the textbook, The textbook is Computer Networks, the 5th edition. Either the US or the International edition is just fine. And throughout all of the lectures, I'll note the section numbers that the lecture corresponds to in the text. Now, this text is optional but recommended. So this means you don't have to buy it if you don't want to. That's just fine. We've done our best to make all of the lectures and the homework self-contained so that you can go through them by yourself and you can learn a great deal about networking. But you may occasionally need to look things up on the web if you want a little more detail, because it's unusual for these college level courses to run with no textbook at all. For those of you who do have the textbook, read it on the indicated sections, browse through them and look at them to gain more explanations for a greater level of depth and detail on the concepts we cover. This is very helpful if you want to do well, in particular on the homeworks and the exams. I'll also point out extra topics that you might be interested in and you can read about in the text, but we just don't have time to cover in this course. And you can also use it, there's a lot of reference material in it. Okay, well I think we're good to go. G'day viewers, in this segment I'm going to introduce the physical layer. So here's where we are in the course. This figure shows a layered protocol diagram, and you can see out of all of the different layers we're going to start down the bottom with the physical layer, and then through the rest of the course we're going to work our way up to the application layer. Now, the physical layer is all about how we use signals to represent bits so that we can convey bits across a physical channel or a simple link from one end to the other. So you can see here, if we just consider a wire as an example of a physical layer, we've got here bits going in on the left, binary digits, that's the message we want to send, and bits coming out on the right. That's wonderful, that's what we wanted to get out, the same bits. But of course, if you were to look in the middle of the link here, if you were just to cut the link, you wouldn't see these bits anywhere. What's carried across a physical channel, like a wire or a wireless or fiber optic, is an analog signal. So we're going to need some way to represent digital bits with those analog signals. That's really the heart of the physical layer. So to understand how this whole process works, we're going to go through several topics. First of all, I'm just going to talk about the different kinds of media and their properties. So this is where we'll learn just a little bit about different kinds of wires, wireless medium, fiber optics, and so forth. Then I'll talk about how signals propagate over these different medium. This will introduce us to concepts such as bandwidth, attenuation of signals, and so forth. And equipped with all of this learning, then we'll build on top of that and really get to the heart of the physical layer, and that is how to represent bits using signals, the kinds of signals which will go over these physical channels. These schemes are sometimes called modulation schemes, how to encode bits. So this is what we'll look at. And finally, in the physical layer, we'll talk about some fundamental limits which constrain how well any real physical channel can do. And this will give you some sense of the bounds that are possible. So those are all of the topics we're going to cover. Now, by the time we've covered them, you'll understand how the physical layer works, and we'll also have we'll help to have realized a simple abstraction for a link or physical channel. And that abstraction actually is all that the higher layers are going to need most of the time when they use links. That's really following our layered protocol model. We're learning about the internals inside a layer, but the layer is going to expose an abstraction to the higher layers, in this case the link layer and beyond, to use. So this simple model is really all, in some sense, that the higher layers need to know about links. And here is some of the key bits of that model written down here. So I have, here's my simple link, or physical channel. This is a wire. I'm sending the message across it. You can see it's going over here. And there are just a couple of key parameters here. There is the rate, that's R. The rate might sometimes be called by different names, the bandwidth, the capacity, the speed. It's really the rate in bits per second at which a message can be sent onto this channel. And the other parameter is the delay. It's the delay D in seconds. And that delay is the amount of time it takes for the signal to cross the physical channel. So it's related to the length of the signal. Now, there are other properties of physical channels that are important and will sometimes rear their head, and we should understand. One good example is whether a channel is broadcast. Wireless links tend to be broadcast, for instance. On a broadcast channel, when a message is sent by a receiver, it is received simultaneously by all, when a message is sent by a sender, it is received simultaneously by all receivers that are within range of that sender. Other kinds of media, like wires, for instance, are typically not broadcast. They just go from one sender to one receiver. And we may also sometimes care about whether a link has a very high or a very low error rate. Media such as fiber have very low error rates, so when you send a message across it, if it's engineered well, nearly all of the time you'll get the message intact at the other side. Other kinds of media such as wireless channels have high error rates, so wireless messages will quite often be garbled. And we're going to have to, of course, eventually we'll get to mechanisms to deal with that and fix that, so you're not going to send bogus bits onwards. Well, actually, given that simple model, we can already start to do some useful things. So for instance, we can already compute the message latency, and that is really the latency or the delay to send a message across a link. Let's think about what this delay is. Now, it actually turns out that it's really composed of two different components, two separate components. First of all, there's something that we call the transmission delay here. And this is really the time to put this message, made that's m bits long, onto the link, sending it out at a certain rate. So that delay, that component is really m divided by r. That's all it is. The second component is what's called the propagation delay. Once bits get onto the wire, they have to go from the beginning, where they just entered the wire, to the other side. Now, it takes a finite amount of time for signals to propagate down the wire that's related to the length. In fact, the propagation delay is given by the length divided by the speed at which signals propagate in the media. And for most wires and fiber optic media, 2/3 of the speed of light is a good example. For wireless, maybe the speed of light, close to the speed of light, is a better example. But basically, it's the light divided by the speed at which signals propagate in that medium. And we'll refer to that as Ds, because we'll often be given the delay in seconds rather than as a length measurement in feet. So if we combine these two things, we have that the latency to send a message over a link is m divided by r plus d. Well, let's see a little bit of an example of that. Oh, sorry, before we have an example, this is just a cleaned up slide with a little more detail that you can go over in your own time. Well, before we go over an example, I'll briefly just talk about some of the metric units that we'll use here and elsewhere in the course. You can see this table just lists some of the common prefixes. We'll use kilo, mega and giga for 1,000, million and billion, and milli, micro, nano for thousandth, millionth and billionth. These are all standard terminologies, standard notation rather. And in addition, we'll generally stick with powers of 10 to describe rates. So that means that 1 megabit per second will be 1 billion bits per second. But we'll occasionally use powers of 2 when we're talking about quantities of only storage. So for instance, 1 kilobyte a second is going to be 2 to the 10, or that's 1,024 bytes. This is just sort of following standard practice. Storage quantities are often expressed as powers of 2, whereas rates tend to be powers of 10. And you'll also see we'll tend to use a capital B for bytes and a lowercase b for bits. Okay, so on with a couple of examples. Well, I've got two different cases for us to compute the message latency. First of all, here, let's consider dial-up sending over a telephone modem. This is an old style use of sending bits of information over the telephone network. So the rate there was 56 kilobits per second is a fast modem, 56,000 bits per second. And we'll just talk about a delay of 5 milliseconds. So that's we're sending from your computer to another computer fairly close by, maybe in the same city. So what's the latency going to be? It's going to be equal to m divided by r plus d. Well, first of all, I'll do the plus d because that's easy. We've got 5 milliseconds plus m divided by r. I've got 1250 bytes. I'm going to multiply by 8 to get that to bits, and I'm going to divide by 56 times 10 to the 3 bits per second. And what's that equal to? Well, if you do the math, you should find that it's equal to about 184 milliseconds. Wow, well that's kind of interesting. And it's interesting because the delay here is not a dominant term. In fact, it's this last part here which contributes greatly to the message latency. That's where nearly all of the latency is coming from. So simply the time to get a message on a wire can be a key factor in the latency. Let's see another example, a different scenario. Now I'm talking about sending information across the country, and you've got broadband access via cable or DSL at home. So let's say across country, we'll call that 50 milliseconds. And the rate, you've got 10 megabits per second is what you've got from your provider. So let's compute our latency again. So I've got 50 milliseconds plus m divided by r. So that's 1250 times 8 divided by 10 times 10 to the 6 bits per second. Well, that's 50 plus, this is 10 to the 4 divided by 10 to the 7. That's going to be 10 to the minus 3, which is actually a millisecond. So this is 51 milliseconds. Okay, well, interesting. So in this example, nearly all of the delay is coming from the propagation delay to send the message across the country. The transmission delay component is almost nothing because we have a reasonable speed. So here you can see I've just cleaned this up a little more, and the point that I want you to take away is that either a long link or a very slow link, both of these can contribute to the latency of sending messages across the link. Now, and also often in practice, one of the delay components is going to dominate. So if we have reasonable rates, we'll generally tend to worry more about the propagation delay. For instance, if we're talking about sending messages across the country at a reasonable rate, you won't even need to compute the transmission delay because it'll be too small to add significantly to the message latency. Okay, well, so we've done message latency. Great. This model turned out to be kind of useful. But wait, there's more. I'd now like to tell you about something called the bandwidth delay product. It is a kind of an interesting realization to think that messages actually take up space on the wire. So it's as if some messages, a volume of bits, is actually stored inside a wire when you're using it to send a message. You've sent it from the sender, yet they haven't reached the receiver. This quantity, the amount of data in flight, is called the bandwidth delay product. And the formula for computing it is this. It's to simply take the rate at which you're sending bits into the wire or other media and multiply it by d, the propagation delay before those bits get to the other side. That gives us the volume. You might measure this in bits or in other units for convenience, like in terms of fractions of messages or packets, just depending how you set the units for your calculation. And what you should find is that the bandwidth delay product will be very small for things like local area networks, where we're like a Wi-Fi, but it can be large if we're talking about networks where both the rate is high and the delay is high. These are sometimes called long fat pipes. Imagine a gigabit per second link which goes across country, for instance. Well, let's do an example to get the hang of it. Here we're going to look at sending data across Australia, it looks like from Perth to Sydney. So I'll assume here that the rate is 40 megabits per second. So you've got a good maybe fiber connection from your ISP and you're at home. And the delay for signals to propagate across the network, across that link, is 50 milliseconds for across country. So let's see, the bandwidth delay product now is equal to 40 times 10 to the 6 times 50 milliseconds. So that's 50 times 10 to the minus 3. Putting that together, we have 2000 times 10 to the 10 to the 3. And that's in bits, so if I convert that to bytes, we'll have 250 kilobytes, the 10 to the 3 being a kilo. So 250 kilobytes. Wow, well, here's just a cleaned up version of that. The point I want you to take away is that that's actually quite a lot of data that happens to be stored inside the network. Pretty good picture. Actually, it's like a small novel if you just consider all of the text. And all of that is just hanging out in the network. Okay, so now we put our model to use and you have some introduction to the physical layer. We'll go into the physical layer topics in the subsequent lectures. G'day viewers. In this segment we'll talk about different kinds of media, wires and so forth. This is material at the bottom of the physical layer. Okay, so there are three kinds of media which are very common that we'll talk about. Wires, fiber optic cables, and also wireless is a kind of medium for propagating signals. The issue with all of these kinds of media is that they propagate signals. These signals carry bits of information. In this segment, we're just going to talk about these basic types of media and get a little bit of a feel for them. Then we'll move on to understand how signals which carry the information are propagated across these media. So the first kind of media we have is just wires, twisted pair wire. That's your garden variety wire. It's quite common. This is the kind of wire which runs to your house for your telephone, assuming you still have a wired telephone. You will also probably seen it in enterprises. This cable shown here, the category 5 UTP, stands for unshielded twisted pair. That is a common Ethernet cable. You can see in here that there are 4 pairs of twisted pairs. The twisted pairs, each one is literally 2 wires twisted around. The signal is carried as a voltage differential across those wires, and they're twisted just to help reduce the interfering RF signal that's radiated. At least they reduce the radiation of that signal, and by reducing that, we reduce the interference between adjacent pairs of wire. Another kind of wire here is shown in the picture in the middle. It's a coaxial cable. It's also fairly common. It used to be used to carry video signals, still is, for a cable to your home. These kind of wires generally have better performance than twisted pairs, meaning that they're able to carry faster amounts of data, higher data rates, longer distances because of their physical properties. You can see here it's built, instead of just twisting a couple of pairs of wire, it has a metal core in the middle, and that you can see here, and also an outer conductor around here, around the edge, instead of the 2 wires. And it's put together in a nice way. Both the twisted pair and the coaxial cable, you'll see them around. They're the most common kinds of wire, and they're designed for communications. There are many other kinds of wire we might use too. One interesting kind that you could just have a look at is household electrical power lines. These are starting to be used, for instance, to carry information around your home just by reusing the existing infrastructure. We can do that nowadays. You can read a little about it in the text if you'd like. A different kind of media is fiber or fiber optic cables. A picture shown here just of the operation of a fiber. The fiber is here in the pink. Now, a fiber is really just a very long, thin, pure strand of glass. The way it operates is when you shine light in from a light source, that could just be a laser or an LED, a light operating diode. The fiber is so thin that the light bounces around. It doesn't come out of the fiber, it bounces around until it gets to the other end. And then it goes out, and you can detect it with some kind of instrument, a photodetector. Fiber, compared to wire, is able to transfer enormous amounts of bandwidth, very high data rates, over very long distances. This is because fiber, because of its physical properties, allows very wide ranges of frequencies through. And it also attenuates signals very little, because very pure light just tends to zap right through it. So signals can go for a long way before they're attenuated. There are, just like different kinds of wire, there are different kinds of fiber. The 2 most common varieties are what is called multimode and single mode. Multimode is the cheaper version, so it's good for shorter links, maybe links that are less fast. Single mode is the more pure, higher quality version. In a single mode fiber, light can only go straight down the middle because it's so thin. And single mode fibers can be used to carry signals up to 100 kilometers or so. Just like the wires, there's a lot of construction here. This portion in the middle, this is actually the fiber. The rest is just all the padding and packaging that goes with it, the cladding and the jacket. And then over here, there is a bundle with 3 different fibers in that one cable. And the third kind of media that we'll look at is wireless. Wireless is fundamentally different than wires and fiber optic in one important respect. And that is that the sender is radiating a signal in many directions. It's radiating across a region. So the signal, rather than being confined to a wire or to a fiber optic cable, radiates in many different directions. This has an advantage that it can reach potentially many different receivers at the same time to everyone in the vicinity, but it also causes a sizable complication for using wireless systems. That nearby signals, which have been transmitted on the same frequency, can interfere with one another at the receiver. This picture shows the setup. Here we have a laptop in the middle, so this is the receiver. And you can see that there are two transmitters. I've shown one is a little closer, so there's a fairly strong signal that arrives at this laptop. The other one is further away, but its signal still propagates and reaches the laptop. So this laptop receiver will receive two signals at the same time, two signals superimposed on one another, so it will be somewhat jumbled. Now, because these signals interfere, we need to be careful and coordinate the way the wireless spectrum is used. Guess how we do that? Well, here's one answer. Look at this chart. This is quite amazing. This is the United States frequency allocation chart. I don't expect you to be able to read all of that. The key issue here is that this chart shows how regulation is used to manage the different parts of the spectrum. Different frequencies are used for TV stations, radio stations, police communications, aircraft, as well as computer networking. So the government regulates who's allowed to use what frequency. You can't just use any frequency you like. In fact, just these small circled regions are the ones which are used for Wi-Fi computer networking. There are also some other 3G frequencies, but only very small portions of the spectrum are actually used for data communications. Even within these circles, it's just a small portion. The portions of the spectrum that are used for Wi-Fi are actually fairly interesting in terms of a story. They are the frequencies that we like for data communications tend to be in the microwave band, from hundreds of megahertz up to several gigahertz. Now, that's where you'll find Wi-Fi as well as 3G, cellular network communications. Wi-Fi is actually transmitted in what's called the ISM band. You can see here this figure just shows different frequencies, and frequency goes up to the right, so this is frequency, and some portions of the frequency were reserved as part of these ISM bands. They're shown here. Wi-Fi actually uses portions of these bands. In, I think, 1985, the FCC decided to allow anyone to use these bands without a license. So you don't have to buy an expensive license, as TV stations and mobile network providers or cellular network providers do. That's why these bands became unlicensed. These were actually the junk bands, garbage bands, just left over with a lot of interference and so forth. They were considered undesirable. But in these circles, people began to use them for computer networking. That was part of the intention. Now, this means that, within this area, many different computers may be using the Wi-Fi, so they will all have to coordinate themselves, since the government's not doing it for us by exclusively allocating us a frequency. But these bands have been a major success, as you know, by the prevalence of Wi-Fi today. There's been a huge amount of innovation in different kinds of computer networking technologies using just this tiny niche of the spectrum. We'll learn more in the next lecture about how signals propagate through different kinds of media. G'day viewers. In this segment we'll talk about how signals propagate over wires and other kinds of media. This will take us one step closer to understanding how to send information across wires. Okay, here's the context. I think you've all heard me talk about this before many times. So on the left and right we have computers, which are really just sending bits. That's what we want, at least, from our links. But across the link they're sent as analog signals. We know that. We've talked about different kinds of media. Now, this means that we're going to need to represent bits as signals. To do a good job of that, we need to understand what happens to these signals as they propagate across media. That is our focus in this segment. Well, one of the first things we need to know is that signals in time can also be represented in a frequency space. Here's our signal over time. on the bottom left, you can see I'm just tracing over it here. Here's this signal. This is how we're used to thinking of a signal as going up and down and changing over time. Now, it turns out that that signal can be represented equivalently, so you can map back and forth, to a representation that describes the amplitude and also phase of different frequency components that are at harmonics. This first frequency component is a fundamental wave that oscillates maybe over the time period of the whole signal here. This second one labeled 2, the second harmonic, means to add a component which oscillates twice as fast and with a higher amplitude. Then we're going to add another component which oscillates 3 times as fast with a smaller amplitude, and so forth. If we sum up all of these different oscillating frequencies, then, believe it or not, we'll get this equivalent signal on the left. This equation here, I'm just going to write OK to forget. I want to show you this equation. This equation sort of tells you how all of the different components of the frequency harmonics can be summed up to provide the original signal. But you don't need to remember the details of that. The important point for you is to remember that this mapping exists. This is actually a tool called Fourier analysis, which is widely used in electrical engineering. So any of you who are studying that subject, you can expect to get a lot more depth about our frequency space representations. The key issue for us is what happens to different frequencies as you send a signal across a media, like a wire. As you lower the bandwidth, there's a pronounced effect. As you lower the bandwidth, this means that fewer and fewer frequencies can get through, only the lower frequencies which oscillate less quickly. So you can see here in this box lost, I've taken the signal from before and I've scrubbed out all of the frequency components over 8 times the fundamental. This means that the components that I have left can only make transitions less rapidly. The effect is that our signal, which used to be this beautiful square signal that I'm drawing over here, has become more rounded. It's become this signal that we have left here. Why? Well, because when we threw away those higher frequency components, we lost a lot of the sharp corners. As you degrade further, as we lose more bandwidth, you can see that the signal here on the left becomes even more rounded. It's barely recognizable. And as you go down further, well, I can't even really make out that signal, whether it was a 1 or a 0. By the way, here's a question for you. Out of these 3 different channels which provide different amounts of bandwidth and effects on the signal, A, B, and C, which one do you think is good for data communications? Think for a moment. The answer is probably likely to be B is best. Why? Well, because we can usually make out whether the signal is a 0 or a 1. It's high here. 0, 0, 1, 1, 0. If those are the original values which were sent and we can recover them at the other end, then we've done a good job of using that bandwidth. We actually didn't need the higher fidelity signal. In a sense, we were wasting bandwidth. Now, of course, if you had an analog application like listening to a stereo, you want the higher fidelity signal or it will sound terrible. Okay, so this last bit that we learned, that fewer frequencies degrade the signal by making it transition less rapidly and getting more rounded, is key to understanding what happens to signals as they pass over a wire. In fact, I can now tell you that there are roughly 4 rough effects here that happen as the signal propagates across a wire. First of all, it's delayed because it takes a little while for the signal to propagate, as we heard before, so a fraction of time will pass. Next, the signal is attenuated. Over a wire, a signal might go from meters through to kilometers. And the electrical signal that's going to come out the other side will be smaller in magnitude than what you put in, because some of it will be lost, some of the energy will be lost. The signal will also be attenuated or more rounded because not all frequencies will be passed through. A wire tends to pass frequencies well up until a cutoff frequency. And after that frequency, the signals are fairly highly attenuated. They're mostly lost, as in our example. And finally, some noise is going to be added to the signal. Just thermal noise in the receiver, that's the sort of thing that you can't get around. And if the signal is very small, this noise will end up causing errors. I'm going to show you pictures of these effects in just a little while. We'll make them up. Before I do that, I just want to point out the information in the box here. Interestingly, the EE and the CS community have different ideas of what bandwidth actually is. In terms of the EE community, bandwidth is literally the width of the frequency band. So on a frequency diagram, some of the diagrams from before, we saw a range of frequencies. The width of frequencies a wire passes is its bandwidth. So it's measured in hertz. In the CS community, bandwidth is regarded as the information carrying capacity of a link. It's given in bits a second, megabits per second. We might talk of that as bandwidth. This is really, these two quantities are really related, because if you have more EE bandwidth, you'll be able to get a link which sends information more quickly. It will have more CS bandwidth, so they're certainly related, but they're not quite the same thing. So you need to be careful who you're talking to understand what they mean. Okay, so let's see those effects. Imagine that the signal on the left is sent. What's going to happen to it? Well, one of the first effects is that it will be delayed, but we're not going to picture that because I can't draw a time delay. Then it will be attenuated. What will that look like? Well, a smaller version of the signal will come out the other side. Now the bandwidth will be limited because we go through a wire and the high frequencies won't be passed. What will that do? That will make it more curved, so we'll get something that might look more like this. And then finally, we show here that noise is going to be added. What will that look like? Well, instead of being smooth, the signal may go something like this. It's still rounded, but it has all of these jaggies on maybe, because there's a little bit of noise. You can see here the amount of noise is small, so I can still see the signal very clearly. If the signal had been greatly attenuated, then the noise would be a larger component of it. Okay, so what about fiber? Well, I don't have much to add about the transmission mechanisms over fiber. Rather, the important differences in sending signals over fiber compared to wires have to do with the physical characteristics of fiber. This graph here, this figure, shows you the attenuation that's on the vertical axis against frequency, or wavelength, as I'll get to in a minute, on the horizontal axis. And you can see here two properties of fiber which make it very interesting to carry signals. First is the low attenuation. Attenuation there is given in decibels per kilometer, but basically the attenuation is very low. And this means that you can send signals a long way through fiber before they're greatly attenuated, many miles, up to 100 miles maybe. And that's quite different than wires. Now the other characteristic here is you'll look at the bands in which the attenuation is lowest, and there are these colored bands here at different frequencies which are used to transmit signals over fiber. Actually, I keep saying frequency, but by convention the horizontal axis is given in wavelength here. Wavelength is inversely related to frequency. So the wavelength is equal to the speed of light divided by the frequency. So that way you can relate the two of them. Now, in these bands, first of all, you see these bands, if you do the computations, you'll find that they run at very high frequencies. So we're not able to send signals literally. We need to use a carrier signal at higher frequencies to send information. And I'll get to that in a sec to give you the intuition. And moreover, the width of these bands, if you compute it in terms of hertz, it's very large. We're talking about many gigahertz of bandwidth that's available to transmit signals over fiber in windows of low attenuation. That great bandwidth translates into being able to send information at very high rates, many gigabits per second. This is where the high capacity of fiber comes from. Okay, and wireless. What about sending signals across wireless links? Well, the principal difference compared to wires, or at least one key difference I want to point out to you, is that we need to send signals over wireless links using a carrier rather than directly. Here's a good old baseband signal, the signal we actually want to send that encodes the ones and the zeros. That signal can't be sent directly out an antenna for physical reasons. You need a very large antenna and a lot of power and so forth. So instead, higher frequencies, carrier frequencies, are the frequencies which propagate over wireless channels, and we need to use a carrier frequency to send information. What does that look like? Well, it's not as complicated as it sounds. The carrier is simply a signal which goes up and down rapidly at a certain frequency, the carrier frequency. And what we can do is change characteristics of it. Here I'm going to change its amplitude. And you can see what I'm trying to do there is change the amplitude to convey just that shape of the signal we wanted to send. So by looking at the envelope of the signal, I'll be able to work out what kind of information it is we're sending. And fiber also carries information, uses a carrier signal to carry information because we're sending at higher frequencies than at baseband. Okay, here is the second characteristic of wireless for us to look at, and that is that wireless signals are attenuated rapidly as they travel away from the source of the transmission. So here I have a diagram which shows you the signal strength on the vertical axis against distance. Spatial distance, we'll just consider a line on the horizontal axis. And I have 2 points of transmission, Tx for transmission here at A and B. Now for each of them, we transmit with a certain power level and the signal falls off rapidly as we go away, and this attenuation is proportional to 1 on the distance squared. The signals are going to be attenuated at least this rapidly as you move away from the source. You might wonder where that 1 on distance squared comes from. Well, it's physics. If you think about the formula for the surface area of a sphere, as a signal expands over a volume of space, that sphere has a surface area of 4 pi r squared. So the area of the sphere is increasing as the radius squared. That translates into the energy per unit area, if it's the same energy, decreasing at least 1 on the distance squared. And it's at least that because other mechanisms can cause the wireless signal energy to be lost. Now, don't worry about that. You don't need to really understand that. That's just if you're curious. The point I want you to take away is that wireless signals attenuate quickly, at least most rapidly from the source. The signal energy goes down very quickly. And a third characteristic of wireless which is important to us, and this is unlike wires too, where in wires the signal travels directly down that wire, and whatever we put on the wire we sort of get out the other end. Well, in wireless many people can be transmitting in different locations, and if they transmit, here we have our 3 transmitters at A, B and C. If they transmit on the same frequency, their signals will attenuate. Here's their signal attenuating, but they can overlap spatially. And this leads to a phenomenon called interference at the receiver. Let's just imagine for a moment that we have the receiver at another location, right here. I'll call this D if you like. What does D see? Oops, D, good grief, I'm just trying to write D sees. What does D see? Well, at this particular location, we can see that there are signals from all 3 transmitters are present at different amounts of attenuation. So actually, D will see a strong signal from C, and that's this up here, high here, and down here we have weaker signals. I'll just say a weak signal from A and B. Now D will see all of those signals together. It would be nice if they were all separated, but that's not the way it works. You see the superimposition of all of these signals. Actually, this means that D may have a lot of trouble disentangling them. In fact, it may be able to cleanly separate out to receive none of these signals individually because they're all messing up one another. And finally, the last characteristic, actually maybe not quite the last characteristic, but we're almost getting there, that I'll tell you about for wireless is what's called spatial reuse. And that has to do with this phenomenon of interference. So we talked before, this is the same diagram as the previous slide, and I said that, if we were at point D, we would see all of these signals overlapping. But if you look at the decay of these signals, you should be able to see, over at least about, let's say, this band and this band. Here, I should be able to send, within these regions, I can receive the signal B without the signal from A interfering. If I simply look at a point here, I get a fairly strong signal for B, and I get no signal that I've shown here for A. A signal continues to propagate and attenuate, but below about this level here I just haven't drawn it on the graph because we consider it too weak to be picked up. Similarly over here, you can see that within this region here, anywhere within the region that I'm showing here, A signal can be received and the signal from B is not strong enough to really be noticed and hence interfere with that in a noticeable way. This means that we can reuse frequencies at these two transmitter locations, A and B. However, if you consider C, is C, a signal being transmitted, well, if we try and receive it at a point in the middle here, actually we get strong signals from both B and C and they interfere as I've described in the previous slide. So that means for these two signals, C and B, no reuse. You can't cleanly reuse the same frequency at these two transmitters because they're closer together and their signals will interfere. So the notion of spatial reuse is that if the transmitters are far enough apart spatially, we'll be able to reuse and transmit information on the same frequency. Okay, well, you can see how wireless is getting kind of complicated. I'm going to stop telling you about wireless effects in just a moment. I really want to make two points and then one more effect. There's always one more to show you about wireless. And this is really to give you a sense of the complexity. So wireless is by far the most complicated medium in which signals propagate compared to the case of wires and fiber, really for two reasons. They're all the same basic electromagnetic effects, but two reasons here are getting us. One is that wireless propagation is very complicated because it depends on the environment. We're no longer just going down a wire, we're propagating in a complicated environment. So there are buildings that can get in the way and shadow signals, trees, signals can bounce off all sorts of things including the ground. The signals can be divided and recombined in interesting ways. And this makes wireless propagation a very complicated phenomenon because of the environment. And the other reason that wireless propagation is complicated is that many of the key effects depend significantly on the frequencies. Signals at different frequencies propagate in different ways. To use an analogy, light is a very high frequency, so it propagates in a very directional way, like shining a torch. Sound is a very much lower frequency phenomenon, and it does things like it goes around corners. You can hear people even when they're in another room. So a different frequency there can be related to very different physical effects. For us, some of the physical effects which will be most important will be those that happen in the microwave band. That's what's used for 802.11 and 3G cellular and so forth. And in a particular effect that I'm going to tell you about is multipath, and we should care about multipath. Other than that and the other effects I've told you about, I'll leave it at the wireless propagation is complicated, but we won't really have to worry about any more than the effects I've already told you about. Multipath is important for us to understand because it has a big effect on communication systems. Multipath occurs because in the microwave band, signals bounce off objects. This means that they can take multiple paths between a sender and a receiver. On the left, here I have a transmitter, and on the right, I have receivers, TX and RX. Now let's just look at one receiver up at the top here. The signal from the transmitter is going to be sent out in all directions. Some of it might go directly to the receiver. Another bit of it might go in a different direction, but bounce off. A filing cabinet is the classic thing, and also arrive at the receiver. The receiver will then see two different signals that arrived over multiple paths. These signals will be superimposed, so they will add. Let's just say that we had one signal like this and another signal which was also going up and down just as fast. When we add them, we get this strong signal. It's not faded. Now, suppose that just because of the position of the reflector, the path, the same thing's going to happen down at this other receiver. It's going to get a direct one via this reflector. But now say that the path from this other reflector has a different length. It will. And in this case, the phase of the signals is going to be a little different. So I'll receive one signal, just like this as before. And the other signal, oh gosh, how can I draw this? I'm going to offset. It's the same thing, it's just shifted. The result when you add these things together is that these signals mostly cancel. and you get a faded signal here. This is called multipath fading. The effect is very difficult to deal with because it can change over very small distances. As I move just, maybe even a few centimeters, my signal might go from fine to mostly gone. This effect is also frequency dependent. The result is that in wireless channels, often in data communications, often your signal is really quite messed up. It's missing portions of it because some frequencies were lost. We then need to handle it with fairly sophisticated communication methods. If you're interested in learning more, you can look in your text. In particular, there's a method that you'll hear about quite a lot called OFDM that's used. We're not going to have time to go into OFDM in this course. G'day viewers. In this segment we'll talk about modulation, or how to represent bits as signals. Okay, so here is the setup. You must know this setup quite well by now. We have a computer on the left sending bits to a computer on the right across a link. But of course across the link we can't send bits, literally, we send analog signals. So we need to work out some way to represent these bits with signals. I've said that many times. You must be wondering how exactly we do it. That's called modulation, and that's the topic of this lecture. Let's dive right in. Here is a simple modulation scheme. It's the one that you would think of first, I think, if you were just trying to come up with one on your own. We will simply use a high voltage to represent a 1 and a low voltage to represent a 0. This is a modulation scheme called NRZ, for non-return to zero. The name's for archaic reasons, don't worry about it. We can work through an example. You see I have a sequence of bits here, and I'm going to draw the waveform underneath. So for a 0, we have a low voltage down here. Then I'm going to go up to a high voltage for a 1, down to a 0, up for a 1, 1, 1, 1, 0, 1, 0, 0, 0, 0, 0, 1, 0. Oops, looks like I've got a little bit of noise on there. Must be just the way a waveform would look. Let me clean it up so you can see it a little more. There it is. That's one kind of simple modulation. Now there are many other schemes which are variations on this, which can be used in practice. For instance, we could use more than two signal levels to represent bits. If I just look at if we group the bits that we sent, 2 bits at a time, we could send more different levels. If I go over those bits, I think the sequence was 0, 2, 3, 3, 1 from the bits before. If I use 4 signal levels, it would look something like this. This will be 0, this will be, level 1, 2, 3, and 4 to represent a 0 through 3. So I'll start low, then I will go up 2 levels, then I will go to the top level, and down to the not quite the lowest level. There we are, that would be using 4 levels. The schemes which are used in practice are very much driven by engineering considerations for how you get this to work. I'm going to talk about one of those considerations, which is called clock recovery. So for clock recovery, here's an example of the problem. Imagine that we have this NRZ signal here. Here it is, a 1, and then a 0, a 0, a 0, a 0, lots of zeros, big long run of zeros. If you are the receiver, you see this signal, but you don't see the bits, of course. Your job is to work out what the bits are. So it's clearly a 1, and then how many zeros is it? After a while it gets very difficult for the receiver to accurately work out the transition points between 1, 0 and the next. We could imagine that you'd have a very accurate clock, but that turns out to be expensive. Instead, what you would really like are frequent transitions in the signal itself so that you could help work out the timing of the signal at the receiver. Now, there are several different ways that you might go about this. In your text, you can look at, there is an example of something called Manchester coding. That is a coding where there is a transition built into every signal, either a 0 or 1. They all include a transition, a waveform which has a transition. Another approach is something called scrambling. You could exclusive OR your data with a pseudo-random signal, which makes it highly likely that you'll get transitions. You can look at these designs for fun. Instead, what I'm going to do is tell you just about one form of modulation that's used to help with clock recovery, and that's called 4B5B. Now, the idea here is that we're going to map every 4 data bits into 5 code bits, which are then sent as a signal. And we'll do this in a way where we won't have long runs of zeros. So here are some examples taken from the table. Here's an input of 4 bits, 0, 0, 0, 0. And if we want to send those 4 data bits, we're instead going to send the 5 code bits, 1, 1, 1, 1, 0. At the receiver, we'll map back from code bits to data bits, so we'll know what we were talking about. There are 16 entries here in the table. They're not shown, they're omitted, but just to save space. But you could imagine there's a whole table full. And if we follow this mapping, you'll find that there are at most 3 zeros you can get in a row. So we won't have long runs of zeros anymore. Great. Of course, if you've been thinking ahead, you realize that you can have fairly long runs of ones. We haven't done anything to prevent long runs of ones. So to prevent that being a problem, we can use a kind of coding where we invert the signal level on a 1 and keep it at the same voltage level for a 0. This form of coding is called NRZ-I, where the I stands for invert. We invert on 1. And it's also shown in your text. I'll give you an example. And here in our example, I've reproduced the table of 4B5B for reference, or just some of it. You can see the message bits I want to send. They start with 1, 1, 1, 1. Okay, let's look that up in our table. You can see over here on the left, that should go to 1, 1, 1, 0, 1. I'll write that in, 1, 1, 1, 0, 1. Next, we have 4 zeros. That goes to 1, 1, 1, 1, 0, 1, 1, 1, 1, 0. And finally, we have 0, 0, 0, 1, which in our table goes to 0, 1, 0, 0, 1. 0, 1, 0, 0, 1. So those are the bits we actually want to send using an NRZ-I signal. How do I send that signal? Since this signal inverts on a 1 and stays the same as a 0, I'll show that transition in the middle of a bit time here. So if I just arbitrarily start at the bottom for a 1, then the 1 will contain an inversion. And then for the next bit, there's a 1, it's another inversion of the signal level. 1, an inversion. 0, I stay the same. 1, invert, invert, keep on inverting, stay the same for 0, 0, invert on the 1, 0, 0, 0, invert on the 1. And that is the waveform that I would send. I would then be able to see the transitions, get enough transitions at the receiver to find the bit boundaries, and then go back from my code words to my data bits, and everything would be good. I would have sent bits of information across a link. Oh, here's that example for you, just cleaned up a little bit so you can see it better. Now, what I've told you about so far turns out to be what's called baseband modulation, how you would literally send a signal over a wire. That's great, you can do that. When we talk about wireless or fiber though, we want to send information not by putting a signal directly in the medium, but by encoding it on a carrier signal which is operating at a higher frequency. The reason for this is that only higher frequencies are going to pass well through the media, or we might want to divide up the medium in terms of frequency bands to permit multiple people to use it. So we need to work out how to send information on higher frequencies. It might sound a little tricky, modulating a carrier. It's not so bad. Let's see. Here we can work through an example. So first of all, let me show you, this is just the carrier. The carrier is just a signal which is oscillating here at some desired frequency. This could be around 2.4 gigahertz for ADA to 11, for instance. Now to modulate it, we can change it in several ways. We can change the amplitude, that's how far up and down it is. Maybe I should draw here, the amplitude is how far up and down it is. The frequency is how fast it wiggles. We can have it wiggle quickly or a little bit more slowly. And the phase is where it is in its cycle. We could change the phase from up down to maybe down up, would be different phases. Let's see an example. So here is passband modulation, an example of it. At the beginning I show you the baseband modulation signal. It's just our old NRZ signal. I'm tracing over it just so you can see that it just simply goes from zeros to ones and back as it encodes bits. Now, our first passband modulation is going to modulate the amplitude of a carrier. So you can see here, the carrier is not shown directly, just the modulation is. And you can imagine there's a carrier going up and down just as before, but its amplitude has been changed. Its amplitude is 0 for some of the initial bits here, and then its amplitude is 1 when it's oscillating up and down with that amplitude, with that magnitude. Alternatively, here is another kind of number 2, a different kind of passband modulation, frequency shift keying. You can see now that I oscillate rapidly for a 1, this is a 1, and I oscillate more slowly for a 0. And finally, we have phase shift keying. This signal looks a little more difficult to see, but in essence, I'm using a waveform which starts by going up and then down. Although this would occur more rapidly, there would be many cycles in each bit time. That will represent a 1, and a signal that starts by going down and then later up, so it's out of phase with the other signal, will represent a 0. With these schemes, I can now represent information on carrier signals which are in frequencies of our choice. Real wireless modulation schemes are considerably more complex than I've shown you in these examples. In fact, you can take a whole communications course to understand some of this in detail. Nonetheless, what we've covered gives you the basics of how we send information, bits of information with signals across either wired or wireless links. We'll move on next to error recovery. G'day viewers. In this segment we'll talk about some of the fundamental limits for how quickly information can be sent over a physical channel or link. So when we build communication links, often we'll like them to have high performance to run as quickly as possible. So it's useful to know just how fast it's possible to build a link. In this segment I'm going to talk about two different results, the Nyquist limit and the Shannon capacity. As you can see, these are fairly early results. They've been known for a long time. They give us limits on what it's possible to achieve. So the real systems which are built are going to operate within these limits. These different results are expressed in terms of the key properties of channels which we might care about. The properties that are used are the bandwidth, B. That's important because the amount of bandwidth limits how quickly the signal can make transitions up and down and hence convey information. And the signal strength, S, and the noise strength, N. These are as measured at the receiver, how strong a signal they receive at the receiver. As you might imagine, the relative strength of the signal compared to the noise limits how many different signaling levels we can distinguish. More signaling levels will let us send more information. Let's see the results. So the first result I have for you is the Nyquist limit. This is for a noiseless case where we're just ignoring noise. The Nyquist limit tells us that the maximum symbol rate is 2B. A symbol is simply a waveform which is used to convey information. It might represent 1 bit, more than 1 bit if you have multiple signal levels, or even less than 1 bit in some cases. So a symbol is a waveform that stands for bits. Nyquist tells us that if we have a bandwidth of B, we can signal symbols at a rate of up to 2B. Here I've shown just a simple waveform, say that's the highest frequency we can send. That can encode 2 different bits per transition there, an up and a down, a 1 and a 0 I've shown here. Now if we also have different amplitude levels, if we have V different signal levels, that would be log to the base 2 of V different bits. For instance, if you have 4 signal levels, that will allow you to convey 2 bits with each level. 8 signal levels, 3 bits, and so on. Putting these two terms together, Nyquist tells us that the maximum rate we can send information across a noiseless channel is 2B multiplied by log to the base 2 of V bits per second, where V is the number of signal levels. Let's move on to the other result which we'll care about, really the end result here. This result is due to Claude Shannon. Shannon was a giant of early computing. In 1948, he put together a treatise called The Mathematical Theory of Communication. This was a landmark paper that put forth many of the key concepts and helped found a field called information theory. It told us really what information was, all sorts of things. Shannon, as well as making fundamental contributions to communications, also made contributions to digital computing and security. He was quite an amazing guy. He also had fairly wide-ranging interests. This picture shows an electromechanical mouse he built. The mouse, there are magnets underneath. The mouse runs on this maze. You can reconfigure the maze and the mouse will learn how to solve it. And this was a long time ago, so it was quite amazing. Shannon's capacity tells us the maximum information carrying rate of a channel, and it does that by considering the noise. Now, the number of different levels we can distinguish, signaling levels at the receiver, is going to depend on the relative strength of the signal that we receive. That signal is actually S plus N, the signal plus the noise at the receiver. The strength of that signal compared to the noise. If it's large, if that ratio is large, we'll be able to distinguish many different levels. In the picture here, you can distinguish maybe 4 different levels. So if I receive something here, maybe I can know that it's most likely that a 1 was sent. Because if I sent a 1, the noise would only have moved it up and down by a bit, and so 1 is probably what was sent. On the other hand, if I receive something here, it's probably the case that I sent a 0. Keep in mind that this noise is a random process. The arrow here is only a depiction of how big it is on average. So at any given time the noise could be larger, and we may have some errors that are caused when our assumption is wrong. We'll have to deal with them later. The signal to noise ratio, or S divided by N, is typically expressed on a log scale because it can take on a wide range of values. So if, for instance, we have a signal to noise ratio of 1,000, that's often written using our little formula here. We express it on a log scale by taking log to the base 10 of the ratio and multiplying by 10. That's often written as 30 dB. Log of 1,000 is 3, multiplied by 10, you get 30. There are many other common SNR values in decibels that you might come across. So, as you might imagine, 100 goes to 20 dB, 10 goes to 10 dB, 2 is a common value, and that goes to 3 dB, and so forth. Okay, armed with this understanding of the signal-to-noise ratio, we can talk about the Shannon capacity. This is a limit for the information carrying capacity of a channel. The limit, the capacity, is given by the bandwidth, our factor from before, multiplied by log to the base 2 of 1 plus S on N, where S on N is the signal-to-noise ratio. This bit in parentheses, you might recognize this as what we receive, S plus N divided by N. That's really S on N plus 1. This bit, log to the base 2, is converting to bits. And then we'll multiply them by the bandwidth. The Shannon capacity is really quite fundamental for a channel. Shannon showed that it is possible to transfer information reliably over a channel up to that rate, but no higher. This was quite revolutionary at the time, when there always seemed to be errors on channels, and the only way you could get rid of them was by sending a stronger signal. Shannon really told us that in theory there exist codes so that you will be able to send information reliably across channels up to a certain rate. Even for whatever signal-to-noise ratio you're sending in. So just to sort of wrap up on this segment, I'm going to give you a little perspective on wired versus wireless links. We've now seen pretty much everything we need for the physical layer. Error coding is a big subject that I'll get onto next, but we've seen how to modulate signals and send information across links. Yay, we're well on our way. There is a big difference, however, between wires and fiber and wireless. I would characterize it this way. With wires and fiber, you can often engineer the parameters. You can fix the bandwidth you're using by the quality of the wire and the signal-to-noise ratio. You might send a certain value in and say the cable can be no longer than 100 feet. This means that you can fix the data rate. On the other hand, wireless is quite different. You might be able to fix the bandwidth you're using as part of the design of the system, but the signal-to-noise ratio will vary greatly. It says here up to a factor of 60 dB. If you do the math, that is 1,000,000. That's a lot. That might be the difference between signal strength in being close to an access point, an 802.11 access point, and receiving information quickly, and being far away on the very edge of reception, but still being able to use it. Given this wide variation, the signal-to-noise ratio is going to vary a lot. We can't design the system for the worst case, or it will always run at a rather slow rate. Instead, the name of the game in wireless is adapting the data rate to the conditions you find. So just recapping, for wires and fiber, we engineer the system to give us a certain data rate that we expect and spec. For wireless, we need to adapt to the SNR. And finally, just to put some of these things together, I can now give you an example. Let's talk about a link that many of you know about, maybe you're using right now, DSL or Digital Subscriber Line. This is a widely used technology for providing broadband internet to homes. There are many different variants of it, and they run at tens of megabits per second. DSL reuses the twisted pair telephone line that goes to the home. So here's the local telephone exchange, and there might be two different lines that go to the home. Now, it turns out that the telephone is only using the bottom 4 kilohertz of this wire, but the wire has a bandwidth of up to 2 megahertz. We can reuse the higher portion of that bandwidth, which is currently unused, to carry data. That's exactly what DSL does. Because it's been refitted to the existing telephone wire rather than designed from scratch, it has some of the characteristics of wireless too. As you might imagine, this close house, if I'm close to the exchange, I might get a high SNR, compared to if I'm a long way away, the signal might be weaker and I might get a low SNR, because the signal's attenuated by the time it's got there. When I've got a low SNR, I might get a rather small data rate, compared to the other house, which could get a fast data rate over DSL. This is why when you want to buy DSL, sometimes your provider will tell you that you're a long way away from the exchange and they can only sell you a plan that goes this fast. Or that you're lucky, you're close to the exchange and they can sell you a plan which runs at the maximum rate. Here are a few more details for DSL. DSL, because it is sending at frequencies above the voice band, uses a form of passband modulation. I'm not going to go into all of the details, that's sort of a whole course. It does use a technique called OFDM, which turns up many times in communication systems. You can read a bit about this in your text if you're interested, just for fun. DSL divides the frequency band to provide separate bands for upstream and downstream communication. You can see here that it uses 4 kilohertz for voice, that's not much, and then it divides it into different portions for the upstream and downstream. DSL, or actually the picture here shows the frequency plan for ADSL2, which is a fairly garden variety version of DSL. It allocates more bandwidth to the downstream version than the upstream version. That more bandwidth is going to translate into a higher number of bits per second. The A in ADSL stands for asymmetric. This asymmetry is deliberate to allow you to download information from the internet faster than you can send it. The modulation that's used inside these bands varies both the amplitude and phase of the different carrier signals. It's called QAM. You don't need to remember that though. If you're now all of the different signals in here, they can send information at different rates. If you have a good portion of this band and you're fairly close to the exchange, you've got a good quality signal, you might get a high SNR and you might be able to send it up to 15 bits per second. Sorry, up to 15 bits per symbol. So that's a lot of different amplitude and phase levels, 2 to the 15 at least, to convey that number of bits. On the other hand, you might have a different band, part of the frequency, which might be bad, not working very well. This one's nice and solid, let's say, and the other one's not working very well. This particular part of the band might give you a low SNR, in which case you'll only use it to send 1 bit per symbol. So this is how you can get different rates over DSL. Okay, well, we've now seen a lot about the physical layer, and shortly we'll move on to the next topic of error coding. G'day viewers. In this segment I'll give you an overview of the topics that we're going to cover in the link layer. Okay, we're moving on. We've now done what we need to on the physical layer. We know how to send bits over a wire, and we're moving up. Through the link layer is our topic next. Our picture here has changed. This picture shows you the scope of the link layer. Now that we have a bit stream, the scope of the link layer is focused on how to send messages across one or more connected links. These messages are called frames at the link layer, and so you could also think of them as packets, although frames is the right word, but they're going to have a limited size, and they're going to build on the abilities of the physical layer. So we'll no longer be talking about signals, just bits. Here's a layering diagram. Let's just recall how layering fits in with this. The network layer shown at the top here is sending a packet down to the link layer. What happens at the link layer? You're meant to remember this, by the way. I'm going to draw it in, but I hope you remember this. The link layer will take the packet. That packet is a payload there, and then it will encapsulate it and add a header. Actually, as part of encapsulating it, often you will add a header, but in some cases, particularly at the link layer, you may also add a trailer. That unit will then be passed down to the physical layer where it will go across the wire, come up the other side. You'll have the same structure. And the packet in here, I'll just put H and T. The packet will be unwrapped and passed up. And because of that, we're virtually communicating messages from one link layer protocol instance to its peer protocol instance on the other side, via the services of the physical layer. This packet in here is going through unchanged. And here I've just cleaned it up a little bit so you can see the picture. You might also be wondering where all these different layers are implemented. So I'm going to draw a diagram that just shows you the typical implementation of layers. On a computer, you might have applications, programs which run at user level, supported by the operating system. And underneath the operating system is the hardware itself. The applications, here we are implemented typically at user level. They're just programs which run on computers. Within the operating system, we'll then typically have the transport and network layers, and we'll also have some of the link layer. The link layer typically straddles the operating system and hardware. Some of it's implemented in the operating system in the lower part of drivers. Often there's some hardware support for the link layer on a NIC, a network interface card, which is inserted in your machine. And then the physical layer, well, that's hardware at the bottom. Here's a slightly more cleaned up version of that picture, or close to that picture. It doesn't show the transport layer there because that's not involved in this particular picture. But don't worry about that. So in our exploration of the link layer, we're going to cover several topics. This week, we'll talk about framing, which involves how to delimit messages, the beginning and end of messages. And we'll also talk about error handling, how to detect and correct errors. Because of noise at the physical layer, they'll occur, and we want to be able to deal with them. Later on in the following week, we'll talk about yet more topics in the link layer as we work out how to retransmit and handle packet loss, how to deal with multiple people using the same channel as in 8211, and how to even build small networks by combining different links with switches. G'day viewers. In this segment we'll talk about framing messages which are sent across the link layer. So the need for framing arises because the physical layer delivers a stream of bits. We've worked hard with modulation to turn signals into a stream of bits, but of course a stream of bits is not really what we want. We would like to be able to send a sequence of messages called frames across the link layer, so we need some way to delimit the start and end of those messages. That's what framing is all about. In this segment we'll look at different methods which can be used for framing. First of all, we'll look at a byte count method. This is really a motivational method just to get our hand around some of the different issues. Then we'll look at byte stuffing, Byte stuffing is a method which is used in practice. And finally, we'll look at bit stuffing, just to show you an alternative. That's actually an older method. Now, I do want to point out that that all of these methods impose a framing structure on top of any bit stream. You could use them in systems you design. In many real low-layer links, however, the physical layer and the link layer are implemented together. And the physical layer often helps the link layer framing by providing signaling about the boundaries. For instance, by using physical layer symbols that can't otherwise occur to indicate the start of frames. So we're not looking at those methods. Okay, so our first method, byte counts. What would you do if you wanted to impose a framing structure on a bit stream? Here's a brilliant idea. We'll just start the beginning of each frame with a length field. That length field will tell us how long the frame is. That way we'll know where it ends and where the next frame begins. It's a simple method, it's fairly efficient, and hopefully it's good enough. What could possibly go wrong? Well, here we can see an example of byte counts. I'll just show you here. The first byte here is 5, so that says this frame is 5 bytes long. 1, 2, 3, 4, 5. So if we hop beyond that, we'll get to the start of the next frame. And so on. You can see, oops, almost missed that. We're hopping down. And we'll hop past. Great, there's our simple scheme. There is a problem with this scheme though, as you might guess. And the problem is this. If we ever lose synchronization because of an error or for whatever reason, aside crashing and restarting, then it is very difficult for us to find the start of frames once again. We really have no way to resynchronize and we could be lost forever. Here's an example. First of all, we've got a nice byte where we're in sync. It says 5, we go to here. This byte is an error. It should have been a 5 or something. If we interpret it now as a 7, we're going to overshoot and interpret something else as the beginning of another frame. After that, we will happily invent fictitious frames. Here, 1 byte, okay, the next one must be here, 2 bytes, the next one must be here, 4 bytes, 1, 2, 3, 4, we must be, here. 7 bytes, we're somewhere else. But we've lost synchronization, we can no longer work out when frames start and end. Byte stuffing is a better idea that allows us to resynchronize. The idea with byte stuffing is that we will use a special character called the flag byte to indicate the start and end of frames. Here it is here. We put down a special character that we can look for to know where frames start and end. Of course, to do this, we're going to have to do something with flag bytes which might occur in the middle of a payload as real data. We'll have to escape or stuff these flag bytes with an escape character it's like quoting material to indicate that it's not really the real flag. There's a small complication here too. If we introduce a special character like an escape code, we'll also have to escape the escape code because there might be escapes in the real data. Here's an example of byte stuffing. The rules here are every time you see a flag in the data, replace it with the sequence escape flag, an escape flag. And every time you see escape, replace it with escape. That's it. So we can fill out this example together. On the other side, you'll have A, then there's a flag. We better escape that. ESC flag. B. Similarly, if we have an escape inside the data, ESC, ESC, B. You could have an escape flag, but if that's actually the data and we want to stuff it, you will have to escape the escape. Then you will see a flag character as a literal and you will escape the flag. And similarly, let me escape the 2 escapes. So, and the receiver is going to apply the same rules in the other direction. Whenever it sees an escape in the data, it's going to take it out and replace it with the following character. If we use this scheme, it has the virtue that any unescaped flag is now the start or end of a frame. So we can use this method to quickly resynchronize if there's ever any error to find the start of frames. All we have to do is look for that unescaped flag, which doesn't exist here. You can see all of the flags are actually escaped, so they're not real. Okay, there's also another kind of stuffing. You can do stuffing at the bit level. Here's how that would work. So we will call our flag sequence 6 consecutive ones. The rule we'll use at the transmitter is if you ever send 5 ones in the data, send a 0 just in case the 6th thing was going to be a 1. On receive, you're going to do the opposite. If you ever get a 0 after getting 5 ones, throw it away because it was added by the sender. This is quite a simple scheme. Actually, this scheme came before byte stuffing. If you do an analysis, you would expect that this scheme actually has slightly less overhead. Nonetheless, it's more complicated than byte stuffing because we might have to deal with messages with, for instance, 193 bits. And we would rather deal with whole octet or byte numbers. So byte stuffing is what's used in practice. Oh, we have an example here we can go through. So let's just quickly do a little bit of bit stuffing. 0, here's the data, I'm going to copy it down. 1, 1, that's 2 ones in a row, then a 0. Oh, no problem. Here we've got 1, 2, 3, 4 ones in a row. Now 5 ones, problem. You have to insert a 0. Now we continue. The next one I'll count as 1, 1, 2, 1, 3 ones, 4 ones, 5 ones, 0. Now we're up to here. 2 ones, 3, 4, 5 ones, 0. Then 1, 1, 0, 0, 1, 0. No problem. Here are the characters I've inserted by stuffing. This slide just cleans it up a little bit. And I've already told you how it compares in terms of maybe being slightly more efficient, but being more complicated and not worth it in practice. Now that we've seen how framing works, I can give you an example of a real protocol. PPP is what the protocol is called. It stands for the point-to-point protocol. It's fairly widely used in the internet to carry IP packets to frame them over any kind of bit stream, byte stream transport. For instance, PPP is used to carry IP packets over SONET optical links. You might not know what SONET optical links are, don't worry too much. These turn out to be the big fat pipes that run at many gigabits a second, which are used by ISPs in the middle of the backbone. Here's a little more on how PPP works. First we have the protocol stack here. You can see the IP layer here is going to produce packets and hand it down to the PPP layer, which is acting as the link layer and providing framing. The link layer is then going to run over the SONET layer, that's the physical layer here. And once we've got a little bit of a physical layer, eventually it'll go out that optical fiber. On the right hand side it shows us some of the encapsulation and just some of the real world wrinkles that you run into here. The IP packet is encapsulated inside a PPP frame, that's pretty much what we expect. But the PPP frame might actually be split across 2 SONET payloads. It's a sort of real world complication that networking protocols are full of. If we focus on the PPP bit, since that's our focus for this video, then we find that PPP frames the packets it gets from the IP layer using byte stuffing that in a way that's quite similar to what we've described. Here's a picture of the frame. The payload is what comes down from the IP layer, and you can see to that the PPP layer adds some of its headers and control information and also some trailers. And then the outer layer is the framing with our flags. In fact, the flag character here is 0x7e, and we'll also have to escape this character if it occurs inside the IP packet that's inside the payload, and we'll do that using 0x7d as the escape character. There's one slight twist here though that's a little interesting. It's in the details, but I think it's interesting, so I'm going to tell you. Here's the rule for byte stuffing. To stuff or unstuff a byte, you add or remove the escape character, just as we've seen, and you also XOR the byte which follows the escape character with 0x20. Now if you expand all of those bits and look at that hexadecimal notation, you'll find what that does is toggle the 5th bit. So for instance, if I have 0x7e in the data, so 7e, if I stuff that, I will get 0x7d, the escape character, and then I'm going to XOR 7e with 0x20. That will flip the 5th bit, and I'll actually get 5e. I've just changed the value of 1 bit. Similarly, if you stuff 0x7d, then what you'll get is 0x7d, the escape character, and then I XOR 0x7d with 0x20, and I will get 5d. And at the receiver, I'll do the reverse. I'll simply XOR whatever comes after the escape character with 0x20, and that will turn it back into the 7E that we wanted. The virtue of using this scheme is that we've completely removed occurrences of the flag character 0x7E from the contents of the frame. So now we can just search the byte stream for 0x7E, and when you see it, you've got the starter frame. It can't occur inside the frame because we've modified it in some way by using this convention. Okay, well now you know about real link layers and how framing is done. G'day viewers. In this segment I'll give you an introduction to the error codes we're going to see to detect and correct errors. Our topic is how to handle the different errors that occur at the physical layer. The problem in essence is that some bits in our messages at the link layer are going to be received in error because of noise at the physical layer. This is unacceptable in that we can't send a message across a network and have a different message arrive at the other side and think that was the real message. You wouldn't be very happy if this happened every time you sent messages across the internet, for example. So we will need some way to handle these errors. There are a few alternatives that we'll look at. It's possible to detect some of these errors using codes. We'll look at this later. It's also possible to correct some of these errors using codes. You'll receive a message and not only realize that something's not quite right with it, but be able to take a good guess about what message was actually sent. And finally, it's possible to, after you've detected maybe that there's a problem, retransmit a message which was in error and has otherwise been lost. We'll look at this option later, and first of all just talk about error codes. These kinds of error codes are a reliability function, and we'll also see as we go through this course that reliability is a concern that cuts across all of the layers. Every layer will generally do its part to improve the reliability of the system. At the link layer, we're mostly concerned with bit errors that might occur and what to do about them. At higher layers, we might be concerned with recovery actions and so forth. Okay, so the problem here is that noise can flip some of the received bits. You can see the signal I sent in above, just one of our good old-fashioned NRZ coded 0-1 signals. I'm going to draw a slightly noisy version of it. It's a 0, the signal's kind of wandering, and then a 1, and then a 1. A few zeros, and a 1. But you can still make it out. On the other hand, if the line has been long and the signal is very attenuated relative to the noise, we might have something that's much more messed up. What is this? Well, this looks like 0, 1, 1, 0. I don't know what this is. This could be a 0 or it could be a 1. Maybe that's a 0, 0. I don't know what this one is either. Let me make that even a little more messy, just so it's clear that there's a lack of clarity there. In this case, we may end up making decoding errors and think that we got a 1 here when we received a 0, or vice versa. These are the errors that we would like to handle. Observe that in our case, in this scenario, the receiver maybe doesn't even know there are errors. It's just got the bits, it's decoded them. Some of them might be bad, it doesn't know that yet. How are we going to deal with these errors? To handle them, what we will need to do is add structure to the message by adding some redundancy. Only by adding some kind of redundancy and structure will we be able to recognize that the message doesn't look quite right, that something is wrong with it. With error detection codes, we add a little bit of structure in the form of check bits. We add these check bits to the message, and these check bits will then let us detect an error at the receiver, when an error has occurred. On the other hand, we could pursue error correction codes. In these schemes, we'll add check bits also, but usually more check bits, so that not at the other side we can look at the structure of the message, see that something's wrong, and take a good guess as to what the message was, and thereby correcting some of the errors. The key issue for us is how we're actually going to do this. It sounds kind of hard. This is actually a very interesting topic, don't you think? How are we going to structure these messages with codes so that we can solve this problem? Not only that, but for a good code, we would like the code to be able to detect lots of different kinds of errors, not just single bit errors, but maybe situations when 2-bit errors occur in a packet, and so forth. We'd also like to do this with few check bits. Every time we send a check bit, we're using the channel for something other than the real data we care about, so we're adding more overhead, so don't use too many of them. We'd also like to do this with a scheme that involves only modest computation at the sender and receiver, if we can. We're generally willing to use a bit of computation, will really help, but this is computation that has to go on, at line rate at the sender and receiver, so it's adding complexity to the system. To warm up to some of these codes, we'll start with a motivating example. So here's a simple code that we could use to handle errors. Got a brilliant idea? You ready for it? Here it is. Send 2 copies. It's just an error if they're different. I hope no one's patented that. Okay, so here's our example. Here is the message, 010, and we're simply going to send another copy. We'll send it again, back to back, 010. Great. Actually, let's not rush out and patent it before we think about how good this code is. First, we could ask, well, how many errors will it detect or correct? The number of errors it can correct is 0. It can't correct anything. Suppose, for instance, that we had received a 1 on the very end instead of a 0. Well, now you can see these two things don't match, so we know something's wrong, but you don't know which bit is in error, that this one was flipped rather than this one. You just know there's a problem with some of them. How many errors can it detect? Well, I don't know. I guess it could detect up to 3 errors if there were errors in different bit positions. But here's the key issue. The key issue is not how many errors it could detect in the, for very errored messages, but rather the minimum number of errors which are required, which are able to make the code fail. Suppose that I also flip this same bit in the same position. They match. Our check will say there's no errors. But all I've done is added 2 errors. With 2 errors, this code can fail. So it's not a very good code, really. Not only that, I guess, but to get that level of protection, I spent 50% of my link on overhead for error correction, error detection. And I didn't really get a lot of error detection out of it. 2 lousy bit errors, and the scheme could fail and tell me I've got a message that's right, when in fact it's wrong. So we want to be able to do better than this. We want to be able to handle more errors with less overhead. We're going to look at some real codes which are used to do this, that can detect and correct errors in stronger ways than that motivating example. These codes are basically going to be different kinds of applied mathematics. In general, you won't go out and invent a new code. You'll look one up and you'll use some well-known existing codes which have been checked and debugged, which have been optimized by mathematicians, essentially. These different codes, though, they won't be able to handle all errors. All of the codes are built to handle some level of errors, not an arbitrary level of errors. It can't be done. And it's also the case that these codes focus on accidental kinds of errors, rather than malicious errors, as might occur when an adversary is trying to trick you. It is possible to come up with error detection schemes which work for malicious traffic. These are called secure hashes. This is a cryptography subject, and we'll probably mention them briefly when we get to security at the end of the course. But right now I'm just focused on regular error detection and correction codes for errors in the physical layer. To use error codes, just diving into the next level of detail, here's the overall structure. We're going to send code words. A code word is going to consist of the D data bits. That's actually the message bits that we want to send. And then to that we're going to add these check bits we talked about, R different check bits. There is a vast literature on error codes, and the kinds of codes I'm going to talk to you about, just so you know, they're called systematic block codes. Block codes mean they operate on a block of bits at a time. Systematic means you append the check bits rather than rewrite all of the data bits. Those terms will help you if you're trying to read other literature and see where these schemes fit in. The way the codes will be used at the sender is that the sender will be given the data bits D from the higher layer, and it will then compute the check bits. The check bits here are strictly a function of the data, so they're computed by a little routine as a function of the data. We'll then append them and you send them into the network towards the receiver, and you're away. The sender has done its job. On the other side, the receiver will receive from the network this package of D plus R bits. There could be errors in this bit, in these bits. Let's just say there's an error in the data here. Maybe I'll do an X in the data here. What the receiver will do is it will take the data bits and it will recompute the check bits from that data. R there is a function of the D data bits, and it will see if they match the R' bits that it received. They should match. If they were both computed from the same data, they should match if everything's okay. If they don't match, then it's an error. In the case where I put an X here, we will get an error because our R should be, hopefully, we've got a good code different from our R'. Observe that one thing that's difficult about the codes here is that the error could also be in the check bits. Suppose actually my data was fine and the error is in my check bits. This procedure will still tell me there's an error. There is. Not an error I really care about because my data bits are okay, but I have no way of knowing that, simply that there's an error somewhere in the D plus R bits. And that's because the bits that go over the physical layer don't distinguish check bits from data bits. The check bits are not magical, they're sent over the channel, and so they're subject to errors just as much as the data bits. This is what makes error codes very tricky and interesting to look at. Here's a little more intuition as we think about how to design some of our codes. Okay, we have D data bits and R check bits. In this picture, I'm trying to draw just the space of some of these different designs. If we look at all of the code words, how many code words are there? Well, a code word is D plus R check bits. So there are 2 to the D plus R different possible code words that could be sent and received. Actually, that could be received on the other side. There are 2 to the D plus R possible incoming sequences of D plus R bits. But actually the code words, the really correct code words that get sent, how many of them are there? Well, we know that they're D plus R bits long, but there are only actually 2 to the D different bits because the R bits are computed as a function of the data. So there are only 2 to the D possibilities. Well, that means if I randomly pick a code word from this space, anywhere from this space, it's quite unlikely to be correct. In fact, the chances of it being correct would be something like 1 over 2 to the R. That's what you get when you take 2 to the D and you divide it by 2 to the D plus R. 1 over 2 to the R gets fairly small as R gets large. If you have a 16 check bits, for instance, you've got a 1 in 65,000 chance of accidentally picking a code word. What we would like to do when we design code words is make it so that errors essentially make it likely that we will pull a random sequence of bits out of this space that will not be a valid code word. Then we'll be able to work out that something's gone wrong and try and correct it. Much of the early work in this space was done by Richard Hamming. He was a pioneer of some of the early codes. There's actually a very nice paper he wrote in the 1950s. This one, Error Detecting and Correcting Codes. You could look for this this paper on the web and read it. It's really very readable and it develops in a very elegant way something called Hamming codes, which we'll look at. Hamming did all sorts of work on codes and other things. He was one of the great early pioneers. You could also find on the web a talk he gave on You and Your Research, which is part motivational and advice that's often quoted. Okay, so here are some of the concepts that Hamming came up with, which we need to know to work with error codes. He came up with the concept of the Hamming distance. The distance by itself is the number of bit flips you need to change. It says D1 to D2. This should really be full code words. D plus R1 to D plus R2. Whoops. Now, let me give you an example of a code. Suppose when we have a data bit of 1, I'm going to send 1, 1, 1. Triple repetition code. Just send the same data 3 times. Seems good. Got to be better than sending it twice. For a 0, I'm going to send, you guessed it, 0, 0, 0. What is the distance? So this is the complete code set here. That we just 0 and 1 are the only messages. So 1, 1, 1 and 0, 0, 0 are the only code words, valid code words, which could be sent. Of course, any sequence of 3 bits could be received. What's the distance between these 2 code words? The distance is the number of bit flips to turn one of these into the other. So it's 3. We need 3 bit flips. Now the Hamming distance of a code is the minimum distance between any pair of code words that are in the code. In this code there's only one pair of code words. The code word for 1 and the code word for 0. The distance is 3, so the Hamming distance of this whole code is also 3. Seems fairly simple so far, but we'll use it in just a moment. Okay, so one of Hamming's results was that if you want to do error detection, if you have a code whose distance is d plus 1, then it is able to detect up to d errors always. That many errors, if they occur, you are guaranteed to be able to detect it. Let's see an example. For the code I just looked at, we have d plus 1 is equal to 3. Therefore, you guessed it, d is equal to 2. So that says with my triple repetition code, I should be able to detect up to 2 errors. Here were the 2 code symbols that are valid that we could send, the 2 code words. Let's just write down what you can get if you make 2-bit errors. Well, I could get 001. Yeah, that's an error because that's none of those things. We haven't changed one into the other. I could get 010. I could get 100. I could get 011. I could get 101 or 110. That's all I can get by flipping 2-bit flips from any one of these things. And none of these are valid code words, so I'll always be able to detect it. Of course, if I make 3-bit flips, I can change one of these valid code words into another valid code word, and I won't be able to detect that. But with only 2-bit flips, I will. Here is another of Hamming's result, and this is for error correction. The result here is that if I have a code of distance 2d plus 1, then up to d errors can be corrected by mapping them to the closest code word. If we assume that that there are few enough errors, then that can be done. Let's give an example again. Here we have the Hamming distance is 3 for the code, so that was 2d plus 1 is equal to 3. D is equal to, you guessed it, 1. This means we should be able to detect up to we should be able to correct up to 1 error unambiguously with our triple repetition code. Let me write down just an example error. 010. That's the sort of thing you could get as an error. What should we map it to? I think we would map that to 000. Now, if there's only been 1 error, it had to be this, not 111. What if we got 110? Well, we could correct that if we knew that there was only up to 1 error to 111. That's the code word to which it is unambiguously closest. So that's what must have been sent if only up to 1 error had occurred. If more than 1 error can occur in this scheme, all bets are off. If 2 errors had occurred, then this code word, the second received sequence could have actually been all zeros. But this is why with Hamming's bound, this error correction code is only good for circumstances in which there can be up to a single error. G'day viewers. In this segment, we're going to talk about specific schemes that can be used to detect errors in packets. We talked previously about errors occurring in packets because of noise at the physical layer. In this segment, we're going to go over some specific schemes which can be used to find those errors when they do occur, to detect them. And we will look at 3 schemes in particular: parity, really mostly for motivation, followed by checksums and CRCs, with the latter 2 are used fairly widely in practice. I'd point out also that detection by itself won't fix errors, but it will allow us to fix errors by combining detection with a mechanism such as retransmission. And we'll look at retransmission later. Well, let's start with our first simple error detection scheme, parity, or the parity bit. Parity works as follows. You take D data bits and then you add 1 check bit, the parity bit, and that check bit is going to be the sum of all of the other D bits. That sum will have to be done modulo 2 because we've only got 1 bit left over to put on. And by the way, this is equivalent to XORing all of the bits together. Here's an example. Let's just say I have 1, 0, 0, 1, 1, 0, 0 as a 7 bits of data to send. If I then want to add parity to it, an 8th parity bit, the parity bit for the case of even parity will be the sum of all of the data bits modulo 2. I've got 3 of those. Modulo 2, I get left back a 1 instead of a 0, so we get a 1. This is the parity bit. Great. That's essentially parity. And you can check the computation at the receiver. You would go through and add them all up again. Except for the parity bit, you could see if they're equal, or you could just add everything together, including the parity bit, and you should get 0 out by design. How well does this parity code work? Well, if you recall our concepts of error codes, we can sort of begin to think about it. First of all, we can ask, what's the distance of this code? How many bit flips do I need to make? What's the minimum number to turn any one code word into another code word? Well, in this case, if I flip any one bit, the parity sum will be wrong, but if I flip another bit, then I can get to a place where the parity sum would be right, even though the data has changed. So the distance of this code is 2. Given a distance of 2, how many errors are we able to correct? Well, the answer to that is 0. You don't correct anything. If the parity is off, you get to see if there's been one error, but we don't have enough distance here to be able to correct anything. What about detecting errors? How many errors are we guaranteed to detect? If the distance is 2, we're guaranteed to detect up to 1 error. So that's all that parity is good for in terms of any guarantees. Now, for errors, so it's not that strong. For errors larger than a single bit, what happens is going to depend on the structure of the computation. For parity, if you think about it, actually it has this nice property that it will catch all odd numbers of errors, where an error is changing a 0 to a 1 or vice versa. The first error will be caught by parity, the second error will cancel out that parity bit, won't be caught. That was why it's distance 2. But the third error will bring us back to the situation where there's a problem with the parity check bit once again. So we've detected all odd numbers of errors, but not all even numbers of errors. Here's a stronger alternative, and one that's used in practice much more widely today. The idea here is, in a checksum, is to sum up data, much as we did with parity, but instead of using a single bit, we're going to sum up the data in terms of n-bit words and use an n-bit checksum, or n check bits. For example, TCP, IP, and UDP, they all use a 16-bit checksum. This checksum is going to provide stronger protection than parity. We'll find out later it's really not that strong, but it is stronger than parity. I'll give you one specific example, and that is the internet checksum. This is the particular kind of checksum that's used in TCP, IP, UDP, and other internet protocols. Here's the definition of the checksum. The checksum field is a 16-bit ones complement of the ones complement sum of all 16-bit words. Oh my goodness, that sounds very confusing. It's not that confusing once you get used to it. Essentially what it's saying here is that you sum up all of the data 16 bits at a time, and then you negate it, so you come up with the negative sum. The catch here is that all of this arithmetic is done with ones complement addition, and it's done that way to give a better distribution of data over the 16 error bits. Ones complement notation is a way of describing binary numbers such that the ones complement, or flipping all of the bits of a number, gives its negative form. So for instance, if I have 001, the ones complement version, the ones complement or bit flip of that is 110. So this is 1, and this other bit one is -1 in ones complement. Ones comp. The computers we use perform addition where all of the binary numbers, the integers, are represented in 2's complement form. To get 2's complement, you do 1's complement and you add 1. So for instance, this -1, 110, if I add 1, I would get 111. This is actually -1 in 2's complement. The hitch with using 1's complement addition on a 2's complement or regular computer is that when you add up numbers in 1's complement form, if any of the bits overflow into the carry field, you need to take them back and add them to the low order bits. That's probably a lot more than you wanted to know or bargained for hearing about ones complement addition. It's really not that bad though, so let's have a look. Here's an example we're going to work through. We're going to calculate an internet checksum. The first thing you do when you want to send data is you arrange the data of the packet to be sent in 16-bit words to sum up. That's these four values that I've shown here. So the packet, if you like, read 0001, F203, F4, F5, F6, F7. And I've just laid it out in these 16-bit words to sum. Now we're going to add these together. We'll actually put a 0 in the checksum position here, just so we can have the same algorithm on the receive side. And we're going to add all of these things together. What do we get? Uh-oh, this is making me work hard. Okay, let's see, when we add up these numbers, we get 10, we get 16, so that's actually, is that right? Okay, so 16 is, we get a 0 here, and we carry the 1. Here, we'll end up with F, and we'll carry the 1. Now we have 11, 12, 13. 13 in hexadecimal is a D. And here we have 3 Fs, which are all added up. F stands for 15 in hexadecimal. What we're going to get is 20, we're going to 2, and what's left over will be a D. Now, so we've got that sum. Of course, this left bit here is overflowed from the 16-bit position. So what we're going to do is take that back and add any carryover back. So we'll just take those high order bits, D, D, F, 0. We'll add the 2. The 2's moved down here. When we do that, we get D, D, F, 2. Okay, now our final step is to negate by complementing this value, and then we'll get the checksum. So we want to negate all of those bits. Okay, let's negate D. If you remember, if I do the binary representation of D, D is actually 8, 9, 10, 11, 12, 0, 1. That should be 13. When I bit flip that, flip, I'll get 0, 0, 1, 0, or 2. So when I negate that, I'll get 2, 2. Bit flipping F is all 1, so when I flip all of that, I'll just get a 0. And when I flip 2, I'll get a D. So 220D will be the internet checksum. And we will then take that value, replace it where we used all zeros, and then send those 5, including the checksum 16-bit words, out into the network. Okay, it's all cleaned up here, and thankfully I ended up with the right answer. Now let's look at the receiving side. What's going to happen? Actually, exactly the same algorithm happens. We just want to make sure that we get 0 out when we've negated everything at the final end. Let's work through it. It should be the same steps. Here, we arrange the message in 16-bit words. The checksum is there, it's the last word. It's non-zero because it was calculated on the other side. Now we add it. So what do we get? Well, before we have 16 plus D, so that will be D. We carry the 1. 1 FF, that will be, we'll end up with an F. And we're going to carry a 1 here. 10, 11, 12, oh, guess what? It's, what is it there? 13, 14, 15, so we have an F. And we're left here with FF, FF, 2. So when we add that together to D, we'll get to F. Okay, now of course we've carried over, so we've got to take this high thing and add it back. So we'll just do this sum, F, 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 D plus 2. What do we get? We get F, 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 F. Oh, this is looking good. When we complement that, we get 0, 0, 0, 0. That's correct. The checksum passes. No error was detected in this packet. And it's cleaned up here. You can see I've highlighted it as good. I already knew I got the right answer because it came out as zeros. So that's how checksums work. What we need to ask, though, is whether they're any good. How well does this checksum work at detecting errors? We could begin by asking, what's the distance of this code? Actually, the distance is not so impressive. This is a sum. So if we want to get the same sum, you can imagine just having errors in 2 bits of the data. In one place, we'll add a certain value, like maybe 16 to a 16-bit word. In another place, we'll subtract a certain value, like 16, the corresponding value from a word. Or maybe we'll add the 64-bit position, and so forth. But the point is, we could make 2 corresponding errors and fool this sum. So the distance is only 2. Well, rats. This means that, as before, the number of errors we can correct is 0. This is just error detection, not correction, so we're not trying to correct anything. But the maximum number of errors that we are guaranteed to detect is actually 1. 2 bits can fool this checksum. Well, has this gotten any better? It has gotten better. So if we think about larger errors, what's detected here is going to depend on the structure of the code. We will actually find all burst errors up to 16. So it's a 16-bit checksum. A burst error is just a sequence of errors in a row, or a window of errors where in that window errors occur. Maybe some bits in the middle are not flipped, but over that window, a small window in space, the error occurs. It's a burst error. So it's an advantage here that if those errors occur in bursts of 16 or less, and there's just one in the packet, we're going to detect it. Because if you think about it, those 16 bits can only be affecting one 16-bit word or 2 adjacent ones in different places, so they can't cancel out. If there are much larger errors, in fact, if we just make up random data, then we will detect random data to random with probability 1 in 2 to the 16. If we just make up data, random data, then since there are 16 bits, there are 2 to the 16 different possible checksum values. So there's only a 1 in a 2 to the 16 chance that the checksum will actually match the data. So this is much stronger than parity. So we have got quite a lot by going from checksums to parity. It's really much stronger. But it's not as strong as we would like things to be in practice. For the same number of bits, we can do even better with codes which are called CRCs, or cyclic redundancy codes. The way a cyclic redundancy code works is you take n bits of data and then you generate k check bits so that when you add them together, the n plus k bits are evenly divisible by what's called the generator, C. I can show you an example here with numbers. So let's just say we're working with decimal digits. The number I want to send is 302, and I'm going to send a 1-digit check. So I'm going to send a message 302 something. We just want to work out what that something is. We want to choose a something so that the whole number, including the end, is evenly divisible by our generator here, which is just going to be the number 3. Well, one thing I can do is I can just start with 302. Let's just add a 0 at the end. And let's just look for the remainder when you divide it by 3. That's equal to what? Well, the 3,000 falls away, 320, that goes 18, so we're left with 2. The remainder is 2. And you can see, since 3 minus 2 is 1, I'm just 1 short of being evenly divisible. So all I need to do is put a 1 here, 3021, and send that. That is evenly divisible by 3. And so I've computed that my check digit there should be a 1. The catch for CRCs is that we need to do all of this based on the mathematics of finite fields. The binary sequences here represent polynomials. So in fact, this binary sequence here represents this polynomial. You can see there's a 0 there for x to the 0 or 1. There's 1x to the 1, no x to the 2's, 1x to the 3, 1x to the 4, no x to the 5's, no x to the 6th, and 1x to the 7. Boy, this could be complicated. What this really means, if we're going to do a complication ourselves, which is a little horrible and grungy, but we'll try and work through it just so you can really get to the bottom of it, is that if we're going to do these CRCs ourselves, we need to work with binary values, and our arithmetic will be done modulo 2. So the send procedure for a CRC is as follows. You take the data bits, and really we're mimicking here what we did with our decimal digit example. You take the data bits, you extend them with k zeros, then you do a division by this generator value. Once you do that, you look at the remainder to see what it is. Keep that, ignore the quotient from the division. And using this remainder, you adjust the check digits by the remainder so that they will be evenly divisible. The receive procedure is to simply divide the whole thing, including the CRC bits at the end, the check bits at the end, and once you've divided it, check that the remainder is 0. If that's the case, there'll be no errors in the packet. Okay, let's try and work through this. Here's an example. We have a sequence of data bits here. You can see I've written them over here. And we're going to divide by our generator, which is 1011. That's the divisor here. The first step, and I have 4 check bits. The first step is to add 4 zeros to the end, since I have 4 check bits. Now, I'm going to do a long division. Wow, this might take a little while. Let's go with our divisor and write it out. So we're going to take away 1, 0, 1, 1. Oh, sorry, good grief. No, it's a 1, 0, 0, 1, 1. When we take that away, what do we get? 1 minus 1, that's a 0, that's gone. 1 minus 0 is 1, 0, 0, 0. 1 minus 1 is 0, 0 minus 1. It sounds like minus 1, which is actually 1 in modulo 2 addition. Okay, now I could write up the top just that the quotient goes here. For instance, I got a 1 here when I divided, but we're not going to keep this anyhow, so I'm going to ignore it. I'm going to keep going on now, taking things away. So now we're down here and we're going to take values away. I'll move down what we've got here. There's a 1. So again, I want to take away 1, 0, 0, 1, 1. Boy, we're in luck. That's the same thing here. So this is all going to go to zeros, all zeros. And now what we're left with is down here. I'm going to copy down these digits. Now I'll continue subtracting 1, 0, 0, 1, 1 from this, and I'll get 0, 1, 1, 0, 1, and I've got another 3 0, 0, zeros here. Do it again, 1, 0, 0, 1, 1. When I subtract that, I get 1, 0, 0, 1, 0, 0. One more subtraction, 1, 0, 0, 1, 1. Cancel, 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 cancel. I'm left with here 1, 0. And that's the final remainder. What I would like to do then is take that remainder and use it to modify the bits that are transmitted. I would like to send 0 minus that. I would like to add 0 minus that value, so that it'll be evenly divisible. What will end up happening is that we'll basically, because this is all modulo 2, end up putting this value 0, 0, 1, 0 from the bottom, 0, so these were zeros, up here. And then the checksum bits that we'll send out, sorry, the CRC bits that we will send out will be 0, 0, 1, 0. That's a little messy. Let me clean that up. And you can see, yeah, here it is. And at the bottom, there is the transmitted frame. You can see it's the data bits, and we computed our CRC to be 0010. Great. Here, there's also a little more information like the quotient, which gets thrown away. And I've shown some other steps here, which were omitted in the middle, just so you can work through that and check it all if you would like. At the receiver, you do the division and you should get 0. We'll skip that in the interest of time. As with checksums, let's think about CRCs for the moment and just ask what kind of protection we get from them. The kind of protection is going to depend on exactly what generator we used. Now, unlike the other schemes, we're not really going to be able to work this out for ourselves. CRCs are based on these mathematics of finite fields. People have calculated over the years good properties of different generators, and in fact, there is a standard CRC which you'll see almost everywhere, even though better ones exist these days. There's a standard CRC. It's defined to be this number. That's actually a polynomial if you write it out. But this CRC is used on Ethernet, Wi-Fi, all sorts of places. This CRC, I'm just going to tell you the properties since we can't really work them out from first principles ourselves. The Hamming distance of this CRC is 4. This means it will detect all errors up to and including triple bit errors. So any 3 errors, 1, 2 or 3 errors, you're covered. 4 errors, there must be some way to get around it. It will also detect, like parity, any odd number of errors. In addition, it will detect all bursts up to k bits in error, where k here, for a 32-bit CRC, that would be 32 bits. And it's also stronger than checksums in that it's not vulnerable to systematic errors. Checksums, because it's simply a sum, if you were to do something like insert a lot of zeros inside a packet, it wouldn't alter the sum, you wouldn't pick it up. With a CRC, if you move data around or add zeros or splice things together, it will pick it up. And finally, to wrap up, let's talk about error detection in practice. CRCs, the strongest form we saw, are very widely used on all sorts of different link layers. They're used in Ethernet and 802.11, as I mentioned. They're also used over your DSL link, cable links, and so forth. They're an industry standard. Checksums you'll also find are fairly widely used in the Internet by all of the Internet protocols, TCP, IP, UDP, and so forth. Compared with CRCs, though, while they're simpler to compute, they're weaker. And I would hazard to guess that if the Internet were being designed today, stronger forms of checksumming would be used. Finally, there's parity, which says there's a good motivating example for us to work through, but it's little used in practice because we can usually afford more sophisticated schemes for error detection. G'day viewers. In this segment we'll talk about codes which can be used to correct errors in messages received across links. So the context for this segment is the same as the previous two, which is that we know that messages can be received with errors caused by noise in the physical layer. What we would like to do in this segment is devise code so that we can look at the structure of the message, the bits we receive, and from those bits work out not only that an error has occurred, but guess what the message was which was actually sent. So this goes a step beyond codes for simply detecting that an error has occurred. And we will go through the example of Hamming codes. They're one of the simplest, realistic error correcting codes. And then I'll mention other codes which are used in practice. Finally, we'll talk about why you might use detection rather than correction. Since it seems as if you could come up with codes for error correction, then you would want to use them rather than detection because they're stronger. But it's not quite that simple. Okay, well, to get the ball rolling here, let me remind you why error correction is hard. Now, if we had reliable check bits that you could send to go with the data bits, everything would be much easier. You could send that reliable information and use them to describe the structure of the message and narrow down where the error was in the data. But of course, there can be problems in all of the check bits. In fact, the error could be in the check bits as well as the data bits. The data might even be correct. That would be all we would care about. If the error was in the check bits, that would maybe throw us off. We would think there was an error, even though we actually wouldn't necessarily care about it. Going a little further, just suppose for the moment that we could construct a Hamming code with a distance of 3. That means that we would need at least 3 single-bit errors to transform a valid code word to any other valid code word. If we then have a single-bit error, that will be closest to a single unique valid code word. So if we can assume, and here's one of the key assumptions, if we can assume that the errors we will see in practice will only be either 0 or 1 bit, then we can correct errors by mapping whatever bits we receive to the closest valid code word. This argument also generalizes to work for correcting D errors if you have a Hamming distance of 2D plus 1. Here's a diagram that helps us visualize this intuition. You can see here in this code, the pink circles represent a valid code word, so the data bits and the check bits match. Whereas the gray circles here, they represent an error code word where you've got a bunch of bits in, but the data and the check bits don't match. This code has a Hamming distance of 3 because we need to go at least 3 hops, which is changing 3 bits to get from any valid code word to any other one. Here's another one. Now let's look around A. This circle, this is the code words which are within a single bit error of A. What we will do for correction is when we get in a code word such as this one here, we will say this is closest to A, so therefore I'm going to correct that by saying A would be sent. You can see that must be the case if we got either 0 or 1 error, because there's no other way that we could have got from a valid code word to be so close to A. This slide just cleans it up a little bit so you can see it a little more clearly. Okay, so Hamming codes give us a way of constructing this code with a Hamming distance of 3, and also an easy decoding method which will allow us to do the correction and move to the closest valid code word. In a Hamming code, they're a parameterized family, so if you pick a k for a number of check bits, then you can work out n how many data bits go with that using the expression 2 to the k minus 1. If I have k for 3, for example, then I will end up being able to send up to 4 data bits. The way a Hamming code is constructed is you take all these bits in the code word together and you lay them out, putting check bits in any position p that is a power of 2, starting your numbering from 1. The check bit in the position p is then a parity sum over all of the positions which have a p term in their binary values when you write them out. Okay, that's all a big mouthful. Let's work through an example to see how it goes. Okay, now here we have some data. The data is 0100. We're going to use 3 check bits, so we have 7 bits altogether. They're shown at the bottom here. Let me just write in the parity bits or check bits and the data bits. Parity will be in positions that are powers of 2, so that's 1, 2, and 4. These are going to be the check bits. The data then will go elsewhere, so if I write the data in left to right, I've got a 0, 1, 0, 1. Now let's compute some of these parity sums. Check position 1 covers the check bit in position 1 is going to cover all other positions which have a 1 in their binary expression. That's going to be 1, 3, 5, and 7. That's P1. We can ignore the 1 itself because there's nothing in it yet. We're going to add it the 3, the 5, and the 7. 0 plus 1 is equal to 0. We'll put a 0 in here. Check bit 2 is going to cover positions with 2 bit turned on in the binary expression. That'll be 2 and 3 and 6 and 7. The parity sum here, 2 and 3 is 0, 6 and 7 is 0, 1, that's equal to 1. So we'll put a 1 here. Parity bit 3 is going to cover positions where there is a 4 in the binary expression. So that is 4, 5, 6, and 7. So if we add those together, 1 and 0 and 1, we get a 1. So I'll write a 1 here. This then is how we constructed a code word for that particular data in the Hamming code with 4 data bits and 3 check bits. And that will then get sent out the wire. Okay, here's a cleaned up version of that. And I think we have our parity sums right. Do we or not? 1, 0, 1. Oops, no, I didn't. I flipped back. 1 plus 0 plus 1, that is a 0. So parity bit 3 in the 4th position here should have been 0. Okay, now we have that right. Moving ahead, the Hamming code gives us a way to decode these codes. What we do is we proceed by recomputing all of these check bits using the same parity sums, now including the check bit parity value itself, because there's a value in there. We then take those check bits and arrange them as a binary number and look at the value. This value is called the syndrome. This value will tell us the position of an error. If it's 0, there's no error. If it's another number like 3, for instance, then the bit in position 3 is wrong and we should flip it to correct the value. Wow, it's pretty cool that this works out. This was all worked out by Richard Hamming, and you can read about it in his paper that I mentioned in a previous segment. So we better try and work through an example. Okay, here is the code word just that we had from before with all of the parity sums computed. Let's recompute the parity bits. Parity bit 1, we're going to add positions 1, 3, 5, 7, and that's equal to 0. Parity bit 2, we're going to add 2 and 3, and 6 and 7, that's a 0. Parity bit 4, we're going to add positions 4, 5, 6, and 7. That's a 0, plus a 1, plus a 0, plus a 1. And guess what? That's a 0. Our syndrome is 0, 0, 0, so there's no error. Yay? Then our data is what we get if we take everything but the check bits. We see it is 0 in position 3, 1 in position 5, 0, 1 in 6 and 7. Here's a cleaned up version. On the other hand, we might actually have had an error during transmission and we want to correct it. That's the whole point. So let's check to see that this method actually works. Parity sum 1, we add up positions 1, that's a 0, 3, 5, and 7. We get a 0. Parity bit 2, we add up positions 2 and 3, and 6 and 7. That is a 1. Parity bit 4, we add up positions 4, 5, 6, 7. That is also a 1. Okay, what's our syndrome then? The lowest order digit is parity bit 1 in position binary at the least significant bit. That's a 0. Ahead of that we have a 1 and a 1, or 6, the binary representation of 6. This means that there is an error in position 6, which we can see is right. So we're going to flip that. The data that we get then is a 0, a 0, a 1, sorry, a 0 and a 1, a 0 and a 1. That's what, and that's what the real data should be. Yes, and we can see here that it's correct after we've flipped the bits. Now, the bad news here is that the error codes for correction which are used in practice are generally much more complicated than the Hamming codes. Hamming codes are useful, but they're fairly simple. Some codes which are widely used in practice are convolutional codes. They tend to take a stream of data and they output a mix of bits at all positions. This mixing process makes the output bits less fragile. They're decoded with what's called a Viterbi algorithm, which has the advantage that it can use the confidence information from the bit values from the physical layer. So we can know if some signal was really high and it really looked like a 1, or if it was close to 50-50 and maybe it was a 1. This turns out to be useful. There's another kind of error code which is becoming widely used in practice, and that is the low density parity check code. Low density parity check codes are based on the mathematics of sparse matrices, and they're decoded iteratively using what's called a belief propagation algorithm. This is the same algorithm which is used in machine learning, also comes up in communications. They're state-of-the-art codes today, and they're increasingly being widely used. An interesting side note is they were invented by Robert Gallagher, one of the pioneers of network more on the theory side, as part of his PhD thesis in 1963. And then they were promptly forgotten for more than 30 years, put aside until they were computationally more viable, because they do involve a fair amount of computation. And now those codes are all of the rage. I can also talk briefly about error detection versus correction. Let's consider a hypothetical example. What would it be better to use, error detection or error correction for a particular example? It's going to turn out that which one we will want to use is going to depend on the kinds of errors, the patterns of errors we're going to correct. But suppose you have messages which are 1,000 bits long, and you have an average bit error rate, or BER, of 1 in 10,000. That means on average, 1 bit will be an error out of 10,000 bits over a long-term average. What should we use, detection or correction? What do you think? How would we even go about working this out? Really, we would like to use the scheme which has least overhead. That will be our measure of goodness. But it turns out that we can't work it out yet. We actually need to know more about what kinds of errors would actually occur. So I'm going to posit two different models. The first model for our errors is the random. 1 in 1,000 bits are errored at random. Well, this means, sorry, 1 in 10,000 bits are errored at random. This means that any message is likely to have 0 or at most 1 errors. Most of them have 0. Now, to do error correction, to handle about 1,000 bits, if you go through some of the Hamming expressions from before, you'll find that you need about 10 check bits to be able to correct a single error. So the overhead here per message is how we'll work it, would be simply 10 check bits, 10 bits. On the other hand, that's for error correction. On the other hand, suppose we used error detection. In this case, we would need only, let's say, 1 check bit to detect that there's an error, because we could use a simple parity bit if we're going to have 0 or 1 bits wrong. But then, of course, if there was an error, and this will happen maybe 1/10 of the time, if messages are 1,000 bits and we're going to have an error every 10,000 bits or so, then 1/10 of the time we're going to have to retransmit that message, and we'll have to send 1,000 bits to retransmit it. And this is a rough approximation, but this is going to get us close enough. The overhead then will roughly be 1 check bit plus 1,000 bits, 1/10 of the time, that's 100, just call it 101 check bits. Wow, well that's a lot of overhead, so we would be paying a lot of overhead to detect those errors. For the random error case, where errors occur, it seems to be better to use error correction. On the other hand, here's a different model. Let's assume that errors come in bursts of 100. Well, in this case, rather than having 1 in every 10 packets likely to contain an error, we're likely to have not 1 in every 10, but 1 in every 1,000 packets have an error. Or maybe 2 out of every 1,000 if those 100 bits are spread across 2 packets. So errors are going to be rarer in terms of packets or frames, but when they occur, boy, it's a big error. If we use error correction, you've got to send the correction on every frame just in case it's in error. How many bits would we need? I don't know how many bits you'd need to correct an error that's that large, 100 bursts of 100 bits. Let's just say you need at least 100 bits of error correcting code to be able to correct 100-bit errors, probably a lot more. What about for error detection? Well, we would like to be able to detect something that's gone wrong, even when there are 100 bits in error. How many bits to do that will we need? I'm not sure. Maybe something like 32, because then we would have the probability of 1 on 2 to the 32 that something's gone wrong. That's quite small. That's basically 1 on 4 billion of missing an error if there's a nice random error. So 32 might do it there. Plus, of course, if you actually do get an error, you'll need to retransmit it. So we'll need to send 1,000 bits again, but we'll only need to resend these bits 2/1000ths of the time. So we're going to need, our overhead here will be 32 plus 1,000 divided by 2,000. So 1,000 divided by 1,000 times 2. So that's 2. That's about 34 bits. You can see that the overhead here is mostly error detection code, not the retransmissions. So in fact, for this case, error detection turns out to be better. To summarize that point, error correction is most useful when the errors are expected. It's the normal case. As an interesting aside, they're also useful when there's no time to do a retransmission because you need information delivered quickly. Error detection, on the other hand, is usually more efficient when errors aren't the expected case, so sending along error correcting code information would just send more bits which are wasted, or when errors are large when they do occur, because in that case you would need an awful lot of error correcting code bits to be able to deal with them. And finally, let me tell you a little bit about error correction in practice. We find that error correction is heavily used in the physical layer, usually with advanced codes like the low-density parity check code. That's becoming common. Older convolutional codes are in fact widely used in practice, but LDPC is going to be the code of the future for all sorts of uses, Wi-Fi, digital television, fourth generation cellular, and so forth. And that's because errors are expected, the normal case in the physical layer, and we'd like to throw some machinery at correcting them. On the other hand, error detection is widely used with retransmission techniques above the physical layer, so in the link layer and above, in the transport layer too. This kind of mechanism is really about dealing with residual errors once the physical layer has got a lot of them down. We'll also see much later on perhaps that correction is also used in the application layer. When it's used in this context, it's often called forward error correction. This usage also has a different kind of error model. Usually at the application level, if you're correcting errors, you know when you've lost bits. Maybe you would lose a whole frame and stripe your information across multiple frames and want to correct it. This error model is called an erasure model. But previously we didn't know if there was an error, which bits they were in. Now, here you know that there's an error in a bit and you don't know what it is. This is actually very close to the setup that's used for codes that you might have heard of, like Reed-Solomon codes, which are used widely in CDs, DVDs and so forth. So that if you were to lose some information on the disk due to a scratch or something, you could use an error correcting code to work out what the information was. So that's error correction. Now you know something about how to detect and correct errors in messages that are sent across the network. G'day viewers. In this segment I'll give an overview of the link layer to remind you where we are in the course. Okay, so here's our layered protocol stack, and if you recall, we've already done the physical layer, we've talked about that. Now what I'm going to do is finish off the link layer, which builds on top of the physical layer to be able to send frames, individual units of information, across a link between computers. Now we've already covered some of the different techniques and problems and solutions that you find in the link layer. In particular, I've already talked about framing, which is the ability to delimit the start and end of messages so we can send complete units of information called frames across a link. And we've also talked about error detection and correction, which allow us to handle some kinds of errors as information is sent across links. When you put these topics together, we've actually seen quite a lot of the link layer. For instance, they allow us to construct a DSL link. That's something that many of you might be using right now to access the internet from home, and we can understand the techniques which make a DSL link work. What we're going to do now is go beyond that and cover these three topics to round out the link layer. These are actually three pretty exciting topics. The first topic is that of retransmissions, which allows us to handle links where loss is quite common. This is the case for many kinds of wireless links, such as 802.11. Without a mechanism such as retransmission, many frames would be lost as they're sent across the link, and the network as a whole would become inefficient. So we're going to want to retransmit information to get it safely across that link. The second topic we'll cover in this unit is multiple access. In the links we've looked at so far, there are two ends, and one end just sends frames and they arrive at the other end. But sometimes you can have multiple parties, all of whom want to access the one link. Just think of an 802.11 network where many different clients, maybe more than two, maybe 10, want to talk to the same EP. That's a single wireless link, and we need some multiple access scheme to coordinate the way in which these different users will use the link. We'll talk about classic Ethernet schemes, and also 802.11 will appear again. And in the third topic, to round out the link layer, I'll talk about something called switching. Switching allows us to use boxes called switches, unsurprisingly, to combine individual links together into something that really looks like a much larger happy link that connects a host to all of the other hosts on the switch network. It's used to build something called modern Ethernet. Actually, by the time we've seen all of these units, we'll know quite a lot about how to build networks. For instance, we'll know a lot about how 802.11 networks work, and we'll also know a lot about how modern switched Ethernets work. These are the garden variety wired networks that you find if you go to any enterprise or campus and so forth and ask to look at the network. Okay, so let's get on with it. G'day viewers. In this segment we'll talk about retransmissions as a strategy for handling errors. Okay, so just as a bit of context, we have two general strategies which we'll use to correct errors in networks. The first strategy is to detect that an error has occurred, say with an error detecting code, and then retransmit the information across the network. We've already seen the error detecting code, so now we're going to focus on the retransmission half of this strategy. The overall strategy goes by the name of ARQ, somewhat archaic name, it just stands for Automatic Repeat Request, but we can just think of it as retransmissions. The second strategy is to correct errors with an error correcting code. Send enough information as part of the message that the structure can be checked and any errors that occur along the way can be corrected. We've already looked at how this strategy works as part of our exploration of the link layer. And I'll give you just a little bit of context on reliability in general before we jump into retransmissions. An important question for us to consider is where in the stack we should put reliability functions. Well, we have a whole stack here. Should our reliability functions for dealing with errors go at the physical layer, the link layer, the network layer, the transport layer, or the application layer? What do you reckon? 5 different choices. The answer is essentially that reliability functionality should go everywhere in the stack. Reliability is one of those key issues for networks. Networks have to be able to deliver information reliably. And to support that, each layer will do its part. The key issue here really is how each different layer should contribute to the overall reliability. What we will find is that at the low layers of the protocol stack, like the physical layer, error handling functionality will mostly be there to mask errors, as we saw with an error correcting code. This is often as a performance optimization. Looking at retransmissions at the link layer is again about masking errors. If the retransmissions occur as in Wi-Fi, the higher layers, like TCP, will never know that there's been a loss. They won't have to worry about it. The error will be masked, and this will generally improve performance. On the other hand, all the protections we like at the low layers won't stop things going wrong at the higher layers. Maybe a sending application can't connect to the right receiving application, can't find the right path through the network, or a message is received which is unexpected on the other side. No amount of scrubbing the bits as they go over to detect and correct any transmission errors will handle these scenarios. So the higher layers of the protocols will also need their own functionality to handle reliability. This functionality is mostly then concerned with correctness and usually recovery actions rather than performance and masking errors. Okay, so that's reliability in general. Let's go on to ARQ. ARQ is used in Wi-Fi, and we'll also see it in TCP. It's used where errors are expected or they're common enough and they need to be corrected. In Wi-Fi, it's because it's wireless and there's a lot of loss, so packets might be lost. In TCP, it's because packets might be lost in the network due to congestion. We'll cover TCP later. Now we're really just talking about the link layer, but much the same mechanism is used. The rules for ARQ are fairly simple. At the receiver, all you have to do is automatically acknowledge correct frames. And what an acknowledgement means is that you'll send a short packet from the receiver back to the sender. This short packet is called an ACK, short for an acknowledgement. The rules at the sender is simply that you automatically resend the frame if you have not received the ACK after a certain time period. This is called a timeout. So a timeout essentially means that the sender hears no ACK within a certain time bound. If that's the case, the sender will automatically resend. Here we can see how ARQ works. Let's just go through some examples. This is the normal operation case. And this is when no packet loss, no frame loss occurs. And this is a new kind of diagram for us. This is a time sequence diagram. The sender and receiver are both shown as vertical lines. In this diagram, time runs down the page. So I'll trace over the action on the diagram. Two things really happen here. The sender sends a frame to the receiver. There we go. The arrow slopes downwards because sending takes some time, so time passes to send this message across the network. But at any rate, the receiver receives the frame and it sends its own message, an ACK, back to the sender to say, yep, got a good packet there. This ACK is received before the timeout period passes, so the sender doesn't need to resend. Everything's good. The frame has been transferred across the network and no retransmissions are needed. Here's the loss and retransmission case. The frame is sent, something happens, doesn't make it to the receiver correctly. After a certain amount of time passes, the sender says, hey, what's going on here? Something must have gone wrong. And it automatically resends the message to the receiver. This time the message gets through, the receiver sends an ACK back, and I guess that is before another timeout passes. That being the case, both sides are happy. This could go on if the more frames were lost, the sender would repeat again and again and again. Now there are a couple of things we might note about this diagram. First, you might actually wonder how it is that a frame can be lost inside a link. What happens? Does the signal just get tired and stop propagating? No, the signal continues to propagate. Two things could happen. The frame could make it to the other side, but an error could be detected because some of the bits were corrupted. When this happens, it's normal for the receiver to throw the message away and not take any action because it's uncertain what the correct message is. So this could look like a message disappearing, even though it really reached the receiver. However, it's also possible that the receiver will not even see the message. This could happen if the transmission error is severe enough that, say, the framing was affected. In this case, the receiver might not even find the start of frame, so it might not even detect that there is a frame there. This would look like a frame has been lost inside the network. A second thing to note is you can see why ARQ in the simple form here is normally done by having the sender automatically resend a message. It's difficult for us to have the receiver send a message to the sender saying, hey, could you send that again? Here the receiver doesn't even know that it's missing a message. It didn't hear something, so it's in no position to request it again. Even if it did, the ACK is just another frame. It could get lost, so the sender might not hear the message to resend. So this is ARQ. ARQ looks fairly simple as a mechanism. Once you get it, you just automatically resend. But a funny thing about network protocols is that there can be some quite subtle interactions. And that's also the case with ARQ. We'll find this a lot for network protocols. With ARQ, there are two non-trivial issues that I'm going to talk about. The first is this timeout. What should the value of the timeout be? We've got to pick something. How long should it be? And the second is actually a more serious issue about how to avoid accepting duplicate frames as new frames. If the sender sends three different frames across the network, 1, 2, 3, maybe with some retransmissions, we would like the receiver to receive the same set of frames in the same order, 1, 2, 3. It's no good if the sender sends 3 frames from a higher layer, passes them over the network, and the receiver thinks that 4 frames have in fact been sent across the network. This could really muck with messages if they were transformed in some way as they went across the network. We don't want that to happen. In fact, what we want to happen for ARQ, which we also usually want for many protocols, is we want performance in the common case, right? So performance is linked to the common case, but we want correctness always. No matter whether our performance is good or bad, we want this protocol to be correct. So let's look at these two issues. Timeouts. Okay, well, the value of the timeout is one of these not too big and not too small kind of issues. We don't want it to be too big because if it is too big, we'll sit around twiddling our thumbs for a long time. The link will go idle and we'll be wasting network resources. If it's too small, the ACK will be on its way, but we'll panic a little early and we'll go ahead and resend a packet or a frame. This is also a waste because we could have sent a new frame. Now, coming up with a value for this timeout is fairly easy on a LAN in the case of most links. And that's because for a LAN like a Wi-Fi, there's usually a clear worst case. In the case of Wi-Fi, for instance, you know about how big the network can be, so you can work out the maximum propagation delay. Wi-Fi also has rules that a receiver needs to send an ACK within a certain time period. So we can usually bound pretty well when an ACK will come back. And that's the case for most links. However, timeouts are actually much harder when we're talking about sending across the internet as a whole, and timeouts in the case of ARQ being used at the TCP level. And this is because there's a lot of variation in the amount of time it can take to use a path across the internet. You could be sending next door or to the other side of the world. There can also be variation due to other traffic effects on the internet, so it's very hard to predict. We'll revisit this topic later. For now, we'll mostly ignore timeouts and pick a value that's about right, just to make the performance good. Okay, duplicates is a more thorny issue. Let's see what happens if an ACK is lost. Okay, here's our frame being sent. The ACK comes back, the ACK is lost. What's going to happen? The sender will not see anything, and so after the timeout period, the sender will send the frame again. The receiver will see it and send an ACK. Great, looks good. Except, what happens at the receiver here? We get another frame. The receiver has no real way of knowing what this frame is. Is this a new frame? As far as the receiver knows, it might well be. If that's the case, the sender will think it's sending one frame, the receiver will get 2 frames, our network has gone astray. Here's that diagram cleaned up. Similarly, what's going to happen if the timeout is early? Here's our frame being sent, our ACK coming back, but just a little late. The timeout goes off here. So we will send the frame again, and the receiver will receive it and send an ACK. Again, what's going on here? As far as the receiver is concerned, we've got another frame here, a second frame. This is probably the next frame. It's a new frame, but it's not because of the spurious timeout. And that diagram's cleaned up. Okay, we need to fix this problem to ensure that the retransmission mechanism is correct. To do this, it turns out that it's required that both frames and acknowledgements carry sequence numbers. These sequence numbers, we're going to check them as part of our protocol at the receiver to make sure that we've got the right frame and the protocol is operating correctly. Now it turns out that in the protocol I'm showing you, where the sender's only sending a single frame at a time and resending it until it gets through, we only need a flag, a single bit, to indicate 2 different states or 2 numbers to distinguish the current frame that's been sent from the next one. That's going to be sufficient. The name of the protocol in this case is called stop and wait. Let's see it in action. So our 2 states with a single bit, we're just going to call them 0 and 1. We're going to alternate packets and number them 0 and 1, 0 and 1. So here's how it would work. This is a frame, F for frame. We'll call this one 0. So I'm going to get an ACK for that. I'll call that A0. Okay, the sender will now advance to the next frame. It will send F of 1 and will ACK A of 1. You can see here at the receiver, first of all, we get frame 0. And now down here, we can see this is frame 1. We have some way to distinguish these two. So here's this cleaned up, and you can see I've added the timeout just to show it's the normal case. Let's look at some of the problematic cases from before. Here's the ACK loss case. So what's going to happen when we have ACK loss? Well, after the timeout, the sender will resend. Now, since it's a resend, it is sending frame 0. The receiver will ACK 0. Here, the receiver received frame 0. Now it is receiving frame 0 again. So the receiver is clear that this is a resend. Yes, got that one right, always comforting. Okay, the other case, a spurious timeout. The timeout goes off a little early. We'll send frame 0. We're going to ACK frame 0. The receiver, here it got number 0, and here it can see it is a resend. Wonderful. You'll also note over here, the sender is going to get another ACK for frame 0. Oh, okay, that's fine. I guess that's what it expects since it's sent 2. The sender here does not actually know whether here, this first ACK, it probably thinks this ACK could be in response to the second time it's sent it. It's just got a very short timeout. For all it knows, the first frame was lost and the second frame got through and produced this ACK. It can't really disambiguate these cases. And it doesn't matter. Our protocol is correct in either case, even though the sender and receiver don't necessarily know what's going on. That's all of the subtlety in the design of the system. So here's a cleaned up version of that figure. And now you've seen stop and wait, ARQ, and all of the rules, and this is basically the protocol. This is how it works, and you've seen the different cases. Before we finish, I do want to tell you about one limitation of stop and wait. Stop and wait allows only one frame to be outstanding from the sender at a time. That is, the sender tries to deliver its frame, resending it until it's there before it moves on to the next frame. That is effective for a LAN, and it's used in Wi-Fi, but it's not effective for networks that have a high bandwidth delay product. That's what BD is. Let me just write that. Bandwidth delay. And the reason for this is because with a high bandwidth delay product, many packets could fit on the network at one time, but with stop and wait, we'll only send one. Let's see an example. Here we have a picture of a network where the rate is 1 megabit per second and the delay is 50 megabits per second. That means that the round trip time, or the time taken to send a frame across and receive a reply, is going to be 2D or 100 milliseconds. How many frames could we then send a second? We could send 10 frames a second. And if you imagine a frame is roughly 10,000 bits, that's about 100 kilobits per second. That's not so great considering we've got a megabit per second link, 10 times as fast. What would happen if we raised the bandwidth to 10 megabits per second, the rate of the link? Well, actually, you wouldn't be able to send any faster. With stop and wait, you can only send up to 10 packets a second over this link. So the maximum throughput you can achieve is 100 kilobits per second, no matter how fast the rate is. Wow, that's not so good. The generalization of stop and wait, which handles this problem, is called the sliding window algorithm. The sliding window algorithm allows up to W frames to be outstanding. What we want to do is set W, the number of frames outstanding, to be roughly twice the delay expressed in packets. Twice the delay is also called the RTT, where RTT stands for round trip time. That's a useful thing to know. And if that's the case, as you can see from the figure here, we'll have multiple packets in the network going across and the X coming back, and this traffic will keep the network busy. This is what we will use when we get to the transport layer in TCP, because the bandwidth delay product is higher than it is for most links, like a Wi-Fi. And when we get there, we'll see various options for handling the way we number frames, acts, and so forth. But there's no need to go into all of that now. We'll look at that later. And for now, you know how ARQ and retransmissions work with stop and wait. G'day viewers. In this segment we'll talk about multiplexing schemes which allow the bandwidth of a link to be shared. Okay, so recall that multiplexing is just the fancy network word for sharing. The classic scenario is sharing the bandwidth of a link amongst the different users. I'm going to talk about two different methods which are used to do that: time division multiplexing and frequency division multiplexing. Here we go. Okay, so in time division multiplexing, this is simply sharing over time. Different users take turns on a fixed schedule at different times. So you can see here we have traffic coming in from 3 users on the left. And a portion of the traffic is taken from each of those users in turn. So this diagram is showing the evolution over time of how the users are sharing one link or a channel. You can see one user here in the pink, user 2, gets to send some information at the beginning. Then the user has to wait and gets to send no information while users 3 and 1 send, and later user 2 will get to send again, gap, and then later user 2 will get to send again. And this is our regular schedule that we follow. There may be a very small gap between these transmission times called the guard time, just to allow for a transition from one source to another. Conversely, in frequency division multiplexing, the users share the channel by transmitting simultaneously on different frequency bands. So this picture shows the way the channel is divided in frequency. Each of these users has about the same amount of bandwidth to send. The middle user their bandwidth profile is shown in pink, And you can see that for all of these users, they have about the same bandwidth requirement. To share, according to frequency division multiplexing, we just shift the frequency band on which the user is transmitting to a different portion of the overall channel. The width of the frequency band describes the amount of, or limits the amount of the data rate with which the user can send. Moving this band around in absolute frequency space does nothing to the data rate. It keeps it the same. As we add all of these different transmissions together onto the same wire, you can see here that we have 3 channels in 3 different frequency bands, which correspond to the original transmissions. So now we're sharing the channel in frequency space. That might be a little strange to get your head around, so let me just draw the time evolution of how we're sharing the channel. With TDM, if we just consider one user, what's happening is that user gets to send at a high burst, they get the whole channel, like user 2 gets to send all of its bits at the whole channel rate. Then they get no bits per second for a while other people send. When it's their turn again, they get to send at the very high rate, then no bits per second. High rate, no bits per second. High rate, and so forth. So their evolution of their bit rate over time looks something like this. On the other hand, with frequency division multiplexing, all users are sending in parallel at their lower bitrate on the channel by simply dividing the channel into different frequency bands. So the same user will have a bitrate like this. It's continuous but at a slower rate. Time division multiplexing and frequency division multiplexing are simply alternative ways to divide the resources of a link. Neither one is inherently better, neither one provides for more capacity. They do have some trade-offs. You can see here in time division multiplexing, it's a little more complicated in the sense that we require synchronization of where to send. This is just one user, so the other users have to fit into these time gaps in the middle. On the other hand, with time division multiplexing, when you get to send, you're sending the information at a faster rate. So if the information arrives from an upstream link just at the beginning time, just here, well, the delay will be lower because it will go out at a faster transmission speed. So there are maybe a few minor trade-offs, but there's no inherent difference in the capacity we're getting. Here's that cleaned up version of that diagram. So time division and multiplexing and frequency division multiplexing are typically used in telecommunications to statically divide the bandwidth or the resources of a link. They're well suited for cases where traffic is continuous and there is a relatively fixed number of users. So classic scenarios for using these techniques would be with, for example, television or radio stations. These stations might always transmit. You could allocate them a different frequency band. They can all send in parallel on their different frequencies, and the spectrum is used effectively. This is good. With cellular systems, such as the GSM is a second generation cellular system, one of the most popular cellular systems still deployed today as we transition to 3G cellular systems. Calls in GSM are allocated on different frequency bands, so we're using frequency division multiplexing to divide the spectrum. Within each different frequency band, time division multiplexing is used to give many different calls a slice of that band at different times. So these methods can be combined. However, there's a problem for the kinds of traffic we would like to handle, network traffic. And the issue is this: unlike a radio station or a TV station which is constantly putting out a signal, network traffic tends to be very bursty. It's described as an on-off source. If you just think for a moment about your own network usage, at home you might be looking at a web page, surfing the web, so you're demanding that the network send lots of packets to download the page. Then you'll read the page. While you're doing this, of course, you won't be using the network at all, perhaps. You will be imposing no load on the network, so there'll be a short pause. Then you might do something and there's a burst of activity again, and so forth. In short, the load in data communications networks of a particular user usually varies greatly over time. If I just make up, here are different users, user 1 and user 2. These are completely hypothetical as examples. Here's a profile for user 1, maybe this is the different rate at which they send traffic over time. Sometimes they're very busy, sometimes they're not so busy, they're not doing much. And user 2. we could see they might look like this. Okay, that's just an example. What does it mean? Well, it means that methods such as time division multiplexing and frequency division multiplexing, which are geared towards continuous traffic for a fixed number of users, are not very effective. To serve these users well in the network, we would need to allocate a bandwidth level here, R, which corresponds to the amount of bandwidth they need when they actually need the network. If we have to pick one level, we want to pick this level. If we picked a much lower level, then they wouldn't have enough bandwidth when they actually wanted to use the network. But of course, the difficulty with this level is we're wasting all of the bandwidth. I'm shading in the portion here, which is not being used at any given time. That's a waste. This is good bandwidth. We'd like to get something out of it. Instead, well, there's an alternative that we would like to get to when we multiplex network traffic. And that is, we would like to multiplex network traffic according to the demands which every user is placing on the network. And we can do this with what is called multiple access schemes. We would really like for these users to share a link such that whenever they want to send packets, they get to send packets, and all of their packets are mixed up on the link according to their demands. If we did this, we would get the gains of statistical multiplexing. Remember from early on in the course, we talked about sharing based on statistics as being a way to pack more users into a given amount of bandwidth. You can see that here in that I have the two users, they both need bandwidth R, but if I combine their signals, I might get a load line like this green line, which I'm drawing over. Well, the amount of bandwidth we need to support that is going to be some level I've called here R dash. The crucial insight is that R dash is likely to be somewhat less than 2R. So by using less than the bandwidth we would need if we handled these users individually with TDM, we should be able to serve them, both of them, as effectively. This is what we want to happen. We don't know how to do this yet. TDM and FDM don't do this. Instead, multiple access protocols share this link at by dividing the bandwidth finely over time. We're going to look at these multiple access protocols in the next videos. We're going to look at two families of multiple access protocols. One is this class of randomized multiple access protocols, where nodes randomize their attempts to access the median. Essentially, they're going to try and access it whenever they've got something to send. This is good for low load situations, and I'll tell you now, this is what's used for Wi-Fi 802.11. We'll also look at an alternative, just so you can see some of the pros and cons. This alternative is called a contention-free multiple access protocol. In this family of protocols, nodes take turns in a well-defined order to access the median. So it shows you just a different way you can do things. It's better where you need much more control over the quality of service you'll get. Okay, well, let's see these two different kinds of multiple access protocols. G'day viewers. In this segment we'll talk about randomized multiple access control protocols. Okay, so that's a mouthful of a phrase, randomized multiple access control. But the topic is a fundamental one and also an important one in computer networking. The issue is simply this. We have multiple nodes, a set of nodes, who want to share a link. How do they do it? When they have traffic to send, who gets to send when? This is a scenario that comes up in Wi-Fi, for example, when you might have multiple laptops, and they would all like to talk to the one access point. How do they decide who gets to send when? We've looked previously at multiplexing schemes called TDM and FDM, which divide up the link in terms of either time or frequency. They're well suited for continuous traffic, but not very well suited for computer networking where the traffic is bursty. So in this segment we're going to start looking at alternatives. To do that we'll use the simple model that's shown here, where we have the multiple computers just all attached to a single wire. So if we wire them together they can all talk over that wire, and we have the multiple access problem of deciding who gets to use the wire when. Now, like many networking issues, protocols, this actually turns out to be quite a subtle issue in many ways. The designs you come up with can have strange effects, strange side effects. One of the key things which makes this hard is that it is a distributed system. All of the different nodes there get to see what they can see locally attached to the wire, so they can send and receive messages to other nodes, but they have no overall view of what's going on in the system. So there's no one in charge, there's no special party. If there's someone in charge, like you or I, and we can look at this network and see what's where, we can organize things fairly easily. But we're now trying to solve a multiple access control protocol without that central view. That's what's difficult. Okay, so the schemes we'll explore are a family of randomized multiple access control protocols. What does this mean? It simply means that they use randomization to handle some of the difficulties like collisions when multiple nodes try and send at once. Randomization, or randomized multiple access control protocols, are the basis for classic Ethernet. This is one of the most successful networking technologies of all time that we'll learn about. And before we dive into it, I'll remind you of the central problem here, which is that we want sharing while the data traffic is bursty. In this figure, for instance, these nodes, the middle one looks like it's asleep. The one on the right is maybe occasionally sending a bit of traffic, but not much. The one on the left is very busy. If we use TDM or FDM to divide the link up into 3 different parts, the one on the left would only get 1/3 of it, the other ones aren't really using their share. What we would like to do is statistically multiplex these demands so that the one on the left could use most of the wire while the middle one's asleep and the right one's not using it much. So let's see how that works. Well, our story for randomized multiple access control protocols actually begins in the Hawaiian Islands in the late 1960s. In this setting, a new kind of way of multiplexing a link was developed. Rather than use TDM or FDM, this new protocol was devised by a guy called Norm Abramson. The setting here was that we have all of these different islands, Hawaiian Islands. They have a wireless link. The islands want to send to one another. They're distributed. How do they decide who gets to send when? And let's not use simple TDM and FDM. Here's the protocol. Like many things, it's a very simple idea. It works like this, the Aloha protocol. When a node has traffic to send, guess what? It just tries to send. If you send successfully, you're going to end up getting an acknowledgement back of some form. I won't go into all of the details here. And then that means everything's okay, it was received. If you don't get an ACK, that means there's been some collision. Maybe 2 nodes have tried to send at once. So all you do is you wait a random amount of time and try again. That's it. A very simple protocol. What could possibly go wrong? Here's how it works. Just as a bit of a diagram, you can see we have 5 different users here, and they're all sending packets over time. If we follow the protocol, they'll all just send when they have traffic to send. Now, if more than one of them sends at the same time, the signals will superimpose. We won't be able to receive it correctly. There's a collision and it's lost. So you can see here, several packets are involved in a collision over this time window. Some portion of the packets were being transmitted at the same time, and also over here. However, even though some of these frames are lost, many of the other frames get through. Okay, so is this a good idea or a bad idea? You can think about that for a minute, and I'll tell you the answer. Actually, it's a pretty good idea on the whole, or at least a reasonable one. It's a dead simple scheme. It's fully decentralized. There's no central point of control here that can fail or is required for the system. And it works quite well under circumstances of low load where the link is not busy most of the time. Now, for many networks, low load is actually a common case. We might have many computers, but often they're really not doing anything much with the network, or at least they used to before we have all of these background processes. Under low load, well, if the network's mostly not being used and someone has a packet to send, they can just go for it. It works. So it's relatively effective under low load. Of course, the problem is when you really want to use it and multiple people want to send, which was basically our problem, it's not efficient then. You'll get collisions. You can actually do some sort of randomized analyses of this, and if you dived into all of the details, you'd find that the most efficiency you could get in terms of the fraction of the link that's successfully used to transfer packets tops out at about 18%. So we've wasted more than 3/4, more than 4/5 of this link, its capacity. That's not so good. you can actually come up with some improvements here. If you slot time so all packets begin on regular boundaries, it turns out that you can double the efficiency from 18 to 36%. And the reason for that is now collisions are all or none. You no longer have a packet or a frame that's mostly mated, and then at the very end someone just clips the end of it and the whole thing is ruined. But rather than look at that, we're going to look at other kinds of improvements to turn this into a much more effective protocol. And the place that I want to get to is so that you understand the design of something called Classic Ethernet. Ethernet was invented by Bob Metcalfe in in 73, the early 70s here. It became really the most popular LAN, local area network technology of all time. So in the 80s and 90s it was very common to see Ethernets deployed in buildings. And it worked like this. Essentially all of the different computers here were wired to the one cable which snaked around the building and connected all of these together. It was, usually a 10 megabit per second cable, somewhere near the beginning. All the nodes really have to do is solve the multiple access control problem, and then they can all talk to one another. So to do that, we're going to improve on Aloha in several ways. Let's look at those improvements. The first way that Ethernet improves upon Aloha is with a technique called CSMA, for Carrier Sense Multiple Access. This simply means that a node should listen to the medium to see if it's busy before it sends its frame. It sounds like rather an obvious technique, but it's not quite so obvious in the sense that it's easy to engineer with wires, and so Ethernet does it in a wired context, but it's actually more involved in the case of wireless, as we'll get to in a subsequent lecture. Okay, so our technique is now simply to listen before we send packets. And the question I have for you is whether this is in fact going to eliminate collisions completely. Let's think about it for a minute. If every node listens before it sends, will this eliminate collisions? Why or why not? Well, actually, it doesn't eliminate collisions completely. Now, many people, when posed with that question, will say, well, it's still possible if two nodes send instantaneously to have a collision, if they send at the same instant. However, even if they send at slightly different times, a collision is possible. And the reason for this, the intuition, is that it takes time for these frames to propagate along the medium. So, for instance, here's what could happen. Well, actually, it's possible for both of these nodes. Here's one on the left. We have our 3 nodes in a network. This node to listen. Let's see, is there anything here? No, and start sending a frame. At the same instant in time, this node can listen. Is there anything here? No, and start sending a frame. Now, this can happen because it takes a finite amount of time for the frames to propagate from one end to the other and cause a collision. In fact, that time to propagate is d, our delay. Here's a picture of that. Once again, just the 2 nodes, both sit as idle, both send. There will be a collision, it just hasn't happened yet. So it turns out that what we're really saying here is to remember the bandwidth delay product, which is a measure of how much information can fit on the network. CSMA, Carrier Sense Multiple Access, is a good defense against collisions only when this bandwidth delay product is small. And by small, I mean less than 1 packet. Much less than 1 packet. If that's the case, well, if there's much more than 1 packet, you can see in this picture the kind of thing that can happen. Someone can send, their packet can be on the medium, a collision will happen much later. If it's much larger than 1 packet, you're still sending, and your packet time is sufficiently long that the interval during which a collision can happen is small relative to a packet time. So collisions are less likely or less damaging because they only occur during a smaller window of time. The second improvement that Ethernet uses on top of Aloha is to use collision detection. Not only do we listen before we send or talk, but if someone else is talking or using the medium at the same time, then we stop sending. We detect that there's been a collision and we abort our own collision. In Ethernet, the way you abort a collision is you send a jam signal just to say to everyone, whoa, stop, there was a problem. And then you can cease transmitting your frame. Now again, this sounds like a fairly easy technique. It works well enough with wires. It's a little harder in the wireless context. So here in our picture, both nodes have detected a collision and they're both going to issue a jam signal. It's actually a little more complicated than I've been making out. When there is a collision, you would like all nodes that are involved in the collision to realize that a collision has occurred. Otherwise, a node could send its frame, think that everything is fine, and not realize that the frame never got there because of a collision. If there is one and all nodes know, then they can take action in the future, such as retransmitting their frame. So this leads us to think about how every node is going to realize that a collision has happened. And again, a key factor here is the propagation delay of the medium. There is a window of time during which a node can detect a collision. You would hope that if you send and someone else is sending, you know right away, but because of the propagation delay, it can take a finite amount of time. Here's a scenario. This node starts sending. Its signal propagates down to the other end of the wire. Now that takes about d seconds. Well, just before the signal gets here, this other node decides to send a packet, just an epsilon before. It starts sending and immediately it's going to detect a collision, but its signal is going to take, you guessed it, another d seconds to return to the other end. And it's only when it returns to the other end that this node here will see that there's another signal on the wire and detect a collision. That's then taken up to 2d seconds to detect a collision. In Ethernet, or with CSMA-CD, the technique that's used to detect collisions, we ensure that all nodes know that a collision has occurred by imposing a minimum frame time. We require nodes to send frames so that the minimum frame takes at least 2d seconds to send. That way, you'll still be sending the frame for the time interval during which you could detect a collision. So if there was going to be one, you'll know that a collision occurred. The node can't finish before the collision is what it says here, which is a good way to put it. If you do the math for an Ethernet, depending on the bit rate and the maximum length and hence the D, the amount of time things can propagate, you can work out that the minimum frame for an Ethernet is 64 bytes. This means that actually if you wanted to send a packet with a one character in it or a short message like OK, the minimum message size that you're going to send is 64 bytes regardless. If you try to send something smaller, it will be padded out. And finally, there's a third issue in Ethernet as we move away from Aloha, and that's the issue of persistence. This is a good illustration, actually, that these protocols, that are simply random access protocols where you just send, conceptually they sound very simple, but there can be very complicated interactions between different nodes when everyone independently follows all of these rules. Persistence is one illustration of that. So the persistence issue is simply the question of what one node should do if it senses that another node is using the medium. Obviously it's going to wait and not send right away, or that would cause a collision. But how long should it wait? That's the question. So what do we do now? Okay, well I have a brilliant idea. The node here on the left should simply wait until the other node is finished and then go for it. That's the simplest solution I can come up with. I like simple. Generally we like simple designs. They're better. Sounds good. What could possibly go wrong? Well, as you might have guessed, something can go wrong. Here's the problem that you get if you use that scheme where you node that senses the medium busy, waits for that sender and then sends immediately. Actually, that is a good design if you are the only node that is waiting on the medium for someone else to finish, because then you go right away. But what if there are 2 or 3 or 4 different nodes, all of whom wanted to send and they're waiting for another node to finish? If they send immediately, they will all collide. In fact, we've really created a problem here with this rule of wait till someone finishes and then go for it, in that the node that's sending is almost acting as a perfect synchronizer for the other nodes. It's lining up all of their transmissions so that a collision is guaranteed if there's more than one of them. This is not good. It's also more of a problem with more load, because the more load, the more likely it is that more than one node will be waiting to send, so that you will get collisions. And the more collisions there are, the more nodes will have to resend their frames to try and get them through. So we'd like to do something about this. Well, if we shouldn't send right away, how quickly should a node send? The difficulty here is that it depends on the number of queued senders. If there is only one sender that's queued up and waiting to send, it should send right away. If there are two senders, you would like each of them to send with probability about a half, so that on average only one of them would go right away and the other one would wait. That would be good. On the other hand, if there are 10 senders, you would like each of them to send with probability about 1 in 10. We would expect that way that only one of them is likely to go. That way we'll make sure the network's used. But there's unlikely to be a collision, which will waste that bandwidth. In general, if there are n queued senders, then you'd want each to send with a probability of 1 on n. That's what we would like to happen. But since this is a distributed system and the load is changing dynamically over time, this node, or any of these nodes here, does not know what n is. What is n? If you knew what it was, you'd be able to send with probability 1 on n. But at any given time, a node doesn't know what n is. Well, there's a clever heuristic which is used in Ethernet to solve this problem. It's called binary exponential backoff, and it's a technique that's probably useful in a lot of other contexts where you're trying to adapt to a certain level of load. Binary exponential backoff cleverly estimates the 1 in n probability. And it does this by starting and optimistically assuming, after a collision, that, well, since there were a collision, at least 2 people were involved, but it will assume there was only 2 of you. And so every node that's going through this process will say, okay, I will wait only 0 or 1 frame times. That's 2 options. So I'm going to send right away with a roughly probability a half is roughly what it corresponds to. Not exactly, but roughly. If you collide again, you say, well, whoops, maybe there were actually more than 2 of us. I'm going to try again. This time, I will send my retransmission chosen randomly over a 4-slot time. So that's like sending with probability 1 on a quarter for every time slot, roughly. If you collide again, you say, wow, well, maybe there are actually more than 4 of us. I'm going to double the number of slots I'm going to wait for. That's 8 slots now. I'll send with probability 1 on 8, roughly. And so on. So what binary exponential backoff is doing is it's doubling the interval for which you're waiting over with each successive collision. Now, as you know, this exponential growth and doubling gets quickly very rapidly. So even if you needed to wait for, if 100 nodes were contending all at once, binary exponential backoff will get you there relatively quickly. All you would need to go through is, 6 or so different collisions, 6 or 7 different collisions, and you'll get up there fairly quickly. So in practice, binary exponential backoff is very efficient. It's able to adapt over a large different operating range. And this is a property we very much like to see in our network protocols. You'll often hear the word scalability in networking. We would like to design network protocols which work when the number of nodes in the network is very small, but they also work well when the number of nodes in the network is very large. That way, as our network grows, there should be no problem. Binary exponential backoff works well when there are very few nodes, because it optimistically starts by assuming that there's no one much around and you can send rapidly. But it also works well if there are a large number of nodes, because by doubling this backoff, it very quickly gets to about the right operating point. Okay, so when you put all of these improvements together, we have Classic Ethernet. Recall Classic Ethernet was this hugely popular LAN technology for connecting computers. This shared cable snaked around the building, you connected the computers to it, they could all talk. There are some details here just to relate to our physical layer talk. It was a 10 megabit per second cable, it's a coaxial cable. The signals were sent here using baseband signaling. Now, the key for Ethernet is this multiple access control problem. And the solution that Ethernet uses is one persistent CSMA CD with BEB. Wow, that's a mouthful. But we've seen everything that you need to understand this. So Ethernet uses carrier sense multiple access. That's this bit where you listen before you talk. And it further uses collision detection so that if 2 people start sending at once, they realize there's a collision and stop, so that we don't lose too much efficiency. The stations, the nodes using the Ethernet are persistent. They're what's called one persistent, meaning that if someone else is sending, they wait for a moment and then they send right away. They try and send right away. Well, we know that can cause collisions if people queue up, so Ethernet also includes binary exponential backoff. to adapt the persistence so that everything works. And there we have this technology. I'll tell you just a little bit more about it. And to do that, what we'll do is we'll look at the structure of frames that are sent across the network. It's often very helpful for protocols to look at the format of their messages, because we can see the different functions that are included, the different information that's in these messages, and that helps us understand the different functions of the protocol. One thing that you'll immediately see if you look at an Ethernet frame that we haven't talked about before is it has addresses on it, a source and a destination address. We didn't need this when we were talking about a link where a sender is connected to a receiver, because whatever was sent, it just went down to the other end. For our multiple access scenario, we do need this because there might be several laptops around an AP. If there is a frame in the air, who's it for and who did it come from? Ethernet includes this kind of addressing. The destination address actually goes first here. That's the first thing that is sent out, because remember here to the left this is what is transmitted first. So this means the destination address comes first. Everyone can look at it and see if the packet, the frame I should say, is destined for them. There is a whole frame format here. We can see some of our framing concepts. What we learned before really is useful. The frame begins with a preamble here to identify it. That's actually a bit of a signal from the physical layer to help with our framing problem. The frame ends here with what's called a checksum. This is used in a generic way. The checksum is actually this CRC32, or a 32 bits cyclic redundancy check. So that's a check that's used for error detection. If you remember all of that, that will allow us to work out if something's gone wrong. Now interestingly here, there are no acknowledgements or retransmissions. Ethernet, because it's sent over a wire, is usually fairly reliable. The CRC is just there in case something goes wrong to weed out errors, but mostly there won't be any errors. If there are errors, this means since they're not handled by Ethernet, other than collisions, that is something that might be thought of as an error that is repaired by Ethernet. But anything else that's caught by the CRC, well, that will just have to be handled by the higher layers. And we'll see some of that much later. Okay, and before we wrap up on Ethernet, there's one important thing that I want to remind you about. And that is we've just looked at classic Ethernet. Now, it turns out that modern Ethernet, the kind of Ethernet that you'll see in any building today, does not use this multiple access control protocol. It's really based on switches. That's these boxes here. So there is a twisted pair, for instance, cable that connects every different computer to a different port on the switch. And the connectivity is happening inside this switch. This is called switched Ethernet or modern Ethernet. The difficulty is that everyone will call both of these things, they're all just Ethernet, which can be very confusing. But again, we've studied classic Ethernet, which is how the Ethernet evolved and is all about multiple access control. Ethernet, as you'll find it in buildings today, is this switched form of Ethernet that we'll look at a little later. G'day viewers. In this segment we'll talk about wireless multiple access protocols. And yes, this is it. This is Wi-Fi, what we've been waiting for. So let's find out how it works. Okay, so our setting here is the same as the setting that we looked at in the previous lecture. We have multiple nodes, they just want to share a link. How do they do it? In this setting, however, the nodes are wireless. Or the link is wireless and the nodes are using that wireless link. So we have 4 different laptops here. They're talking to an AP. They just need to decide when to send. Now, to understand the way the protocols work in this setting, what we're going to do is build on the schemes we used in our simple wired model. So all of that carrier sense multiple access stuff, that was more useful than just for classic Ethernet. We'll use it as a foundation to understand how 802.11 works today. Well, the first thing that you might ask is why wouldn't we just use some of the protocols we've seen before that were used for classic Ethernet? And the reason for this is that the wireless case is more complicated than the wired case. I say surprise here because this always seems to be the case for wireless. The way signals propagate across a wireless medium is much more complicated than sending signals down a wire. And that seems to have all sorts of implications for how you design the rest of the protocols for a wireless system. In our case, just thinking about multiple access, there are a couple of issues here. One issue is that nodes can have different coverage areas. When you send down a wire, if everyone's attached to the same wire, you expect that everyone on the wire can hear all of the messages. That's not the case with wireless. The nodes might be a fair distance apart, and so they might not be able to hear one another clearly. This will mean that our schemes such as carrier sense don't work very well. The second complication is that nodes can't easily hear one another while sending. There can be enormous differences in the power level between a signal that's sent and received. The received one can be so much weaker that it's difficult to hear both signals at the same time, so it's difficult to detect collisions. So we'll have to come up with alternatives to that. The bottom line here, you can see in the figure at the bottom, is just to remind you that wireless 802.11 does not operate according to CSMA CD. We have to improve it. So let's see how we do that. Well, first we've got to go into these two issues. The first issue is the different coverage areas. Here's what's going on. In the figure here we have 4 different nodes, A, B, C, and D, and they're just spread out over space. Now the wireless signal is broadcast, and as it's broadcast it propagates over an area, it's attenuated, it can be received by receivers as long as the signal to noise ratio is high enough, and that's just within a region. So here it looks like A can send to a neighbor B that's adjacent to it, but A's signal can't be received by C. It's too far away, the signal's grown too weak, it can no longer be received. Similarly for B, C, and D, and this leads to different coverage areas. You can see the radio range here is indicated as just enough to get from one node to the next, but not a lot further. B, by the way, when it sends, its signal will be received by A, but also by C, because that's also within radio range. Different coverage areas lead to problems. And one of the classic problems here is something called hidden terminals. When you think it's okay to send because you can't hear someone, yet interference still results. So in this figure we have a hidden terminal situation when A and C are hidden terminals when sending to B. Let's see what happens. Now A and C, when they want to send, they cannot hear one another's transmissions. This means if they use something like carrier sense, they would listen and they would hear no one and say, okay, the medium is not in use, it's fine to send. However, if they both send at the same time, both of their signals receive at B, received at B, or arrive at B simultaneously. Those signals are mixed, superimposed on one another. The result is a jumble, 2 people speaking at once, so B cannot separate these messages and receive them. It's a collision. And we would like to avoid this because we've just wasted some of the resource of the link. We could have used it to deliver a real frame. Instead we got a collision, and neither of the frames gets through. The second problem that arises because of different coverage regions is something that's called the exposed terminal problem. Now, exposed terminals are a situation when you think you have interference because senders can hear one another, but actually there is no interference at the receivers, so you would really like to send multiple packets at the same time. Here, B is sending to A, so B is sending to A there, and C is sending to D. And in this situation, they are exposed terminals. They're exposed terminals because B and C can hear one another. When they're sending, it looks like their signals will collide here. However, C's signal doesn't propagate all of the way to A. There's no problem here. So A will be able to receive B's signal cleanly. Similarly, B's signal doesn't propagate to D, so D will be able to receive C's signal cleanly. When this situation occurs, we would like to take advantage of it and have B and C send at the same time because we'll get more performance out of the network. We can send 2 frames concurrently and get them both through the network. The second problem, the second complication for wireless had to do with the inability to detect collisions. And that's really because with wires we can engineer the relative strengths of the transmission and reception signals so we can work out if both are going on at the same time. With wireless, there can be a tremendous difference between the power levels of the sent signal and the received signal, which might be 1,000,000 times weaker. This makes it very difficult to process them both at the same time. So essentially when you're sending, you're shouting and you're deaf. You can't hear if someone else is talking. With wires, we're able to detect collisions, and because of that we can abort the transmission, and this greatly lowers the cost of collisions. So you can see here the wired collision takes only a very short amount of time. It happens, everyone sees it's happening, they stop sending, then we can recover. With wireless, these two nodes are sending, but neither node can hear one another, so the collision goes on for a long time. This wastes more of the link, it's more inefficient, so that's why it's a problem. So now we need to solve these problems. We know that wireless is more complicated than wired. What can we do about it? I'll tell you about a possible solution, which is quite influential, and that solution is something called MACA. I think it stands for Multiple Access with Collision Avoidance. You don't need to remember that. MACA is actually not quite what's used in 802.11. 802.11 uses a refinement of MACA. But going over MACA will give you a sense of just how these issues can be handled if you're designing protocols, and it'll help us understand what 802.11 uses. The idea in MACA is that since we have these problematic scenarios, instead of simply sending the frames directly and maybe encountering them, we're going to use a short handshake between the sender and receiver to find out what's going on, make sure it's okay. Here are the rules for MACA with that short handshake. Okay, step one here. The sender simply sends a small frame called a request to send. That's very short, like about an acknowledgement frame. It's not a big data packet. It sends that request to send to the receiver. The request to send also includes a frame length, so it tells you how big a frame the sender wants to send to the receiver next. The receiver, when it gets this, replies with a clear to send. That's simply another short packet saying, okay, yep, you know, coast is clear, I'm expecting your frame, go ahead. Fine, we've just sort of added a bit of preamble. And then, after all of this, the sender simply transmits the frame. That's it. The interesting part, however, is that nodes that heard the CTS stay silent while the sender transmits the frame. They can do this because the RTS and CTS include information about how long the frame is, so the nodes that hear the CTS know how long to be silent. And this is the key addition of MACA that's going to solve some of the problems. We'll see how in a minute. It's true that the RTS and CTS are just sort of like short frames, and as we send them we could run into some of these same problems. But the RTS and CTS are much shorter relative to packets. They might be 100 or 1,000 times smaller. And in this case, the collisions, since they're a lot shorter, are just less likely, so we run into fewer problems. So let's see how MACA solves some of these problems. First of all, hidden terminals. Let's suppose that A wants to send to B, and C is a hidden terminal that might interfere. Okay, first of all, A sends the RTS, here it is, to B. That should be received. Now, I've shown that. Next step, B is going to reply with a CTS to A to say, okay, go ahead. B sends the CTS to A. Great. Of course, that transmission, since we're in radio range, will also be heard by C. Right? Now, C at this stage will say, oh boy, I didn't hear a request to send. You know, so maybe, since you didn't hear that, you didn't know anything was going on. But luckily, C did hear a clear to send. So C knows that something is about to go down, even though it didn't hear the request to send. Here's that picture cleaned up. So you can see C's now in a state of alert. It knows that someone's going to use the wireless. Now, A simply sends to B. C, because it heard this clear to send, defers or just waits for this time period to pass so that the transmission from A to B would be successful. Great, we solved hidden terminals. What about exposed terminals? Now, B will send to A and C will send to D, and we want them to both be able to send in parallel. Step 1, B sends a request to send to A, C sends a request to send to D. Now, of course, B's request to send will also propagate to C, and C's request to send will also propagate to B. Neither of those nodes will probably hear the request to send because they're transmitting at the same time, so they can't also receive. Next step, we've got the request to send there. We'll also send a clear to send. A gets the request to send intended for it, and it's going to reply to B with a clear to send saying, yep, go ahead. Similarly, D is going to send its clear to send to C and say, yep, go ahead. Now, observe that the clear to send from B doesn't make it to D. B only hears one clear to send. Everything's good. Similarly for C. So they both get just one clear to send, and this tells them both that they can both go ahead. Here's what happens. Here's just the diagram cleaned up. According to the protocol, they've sent their request to send, they've heard their clear to send, and there haven't been any problems with either of these messages, so everything's good. So now we simply send. B sends to A, C sends to D. At the same time, because we're in radio range, the signals from C propagate to B, the signals from B propagate to C. So the situation around B and C is a mess with superimposed signals. This doesn't matter though, because what really matters is what goes on at the receiver to receive the signal. Both A and D have clean reception scenarios because the other signals don't propagate far enough to interfere at the receiver. Right? So it's interference at the receiver which is the problem. So here we have no interference. And that's what we want. So we've solved the exposed terminal problem. Now that we know how MACA works, we can move on to 802.11 or Wi-Fi. We've really seen most of the machinery we need to understand how multiple access works in 802.11. So 802.11, of course, is this incredibly popular LAN technology that we use today. It's been around since the 1990s, getting more and more popular. 20 years on, it's near ubiquitous. It's really the Ethernet of wireless. It's everywhere. In Wi-Fi, the way it's commonly used, these clients, different laptops or other devices, phones and so forth, get their connectivity to the internet from an access point. So they're all wirelessly talking to this access point. The access point is typically wired to provide connectivity to the greater internet. The key bit we're looking at here is this multi-access problem of how these different laptops get to talk to the AP. The multi-access problem is at the heart of Wi-Fi. I'll also point out for you just that it's a little difficult even talking about Wi-Fi because many different flavors of Wi-Fi have been developed over time. So if you really wanted to know any details, we have to be clear what kind of Wi-Fi we're talking about. But generally, I'd say all of these different flavors of Wi-Fi have gotten faster over time and added many more features. We'll see just a little bit on some of this. What I'm going to do now is just talk about the physical layer and the link layer of wireless. The physical layer, I'll tell you a little bit about it just so you know. This will relate to some of the lectures we saw on physical layer characteristics, so you should be able to understand some of these parameters. Okay, so Wi-Fi is sending using either a 20 or a 40 megahertz channel of bandwidth on these ISM bands. The bands that the government opened up for unlicensed usage in about 1985. They let anyone sort of make equipment that would use it with some constraints, but no expensive license like a TV station. This led to huge innovation, mostly in the form of Wi-Fi, which has taken off. So that was really a very valuable thing to do. Of the different flavors of Wi-Fi, 802.11b and G and also N, they're all different flavors of Wi-Fi that work differently at the physical layer. They're the same at the link and higher layers mostly. These flavors of Wi-Fi operate on the ISM bands around 2.4 gigahertz, and the 802.11a and N flavors work around 5 gigahertz. So N is capable of working in either one. Now they use a kind of frequency division modulation scheme, frequency division multiplexing scheme to modulate information over those bands. They divide this band 20 megahertz up into many fine channels which are used in parallel. It's actually a form of FDM called OFDM. It's more detailed than we're going to have time to go into. You can read a little bit in your book about it if you'd like. This is for 802.11 G and A and N. 802.11b is mostly the legacy form of 802.11. Now, it's slower, it has some different physical layer details. We're not going to worry about it. When we're sending wirelessly here, the different symbols use different amplitudes and different phases to convey information. Depending on your SNR, you might be able to distinguish more amplitudes and different phases. So you will have many different kinds of symbols, and you can get different bit rates that range from 6 to 54 megabits per second, just depending on your SNR and how many amplitude and phase levels you're using. In addition to this, many other bits are transferred across the physical layer to provide error correction. In wireless, errors are common just because the medium is very noisy because of interference. So we need to use error correction in the form of error correcting codes to be able to even receive packets and sort of clean them up. You might, well, I'm just going to point out briefly, you might well have heard of faster kinds of 802.11 than 54 megabits per second. Various tricks are used, including for some of the fastest kinds of 802.11 using multiple antennas at the same time. This is pretty cool. It's well beyond what we can cover in this class. But if you're interested, you could look at a little article here I recommended. 802.11 with multiple antennas for dummies would give you a sense of what's going on. Let's talk about the link layer, because that's where the multiple access control problem comes up. In 802.11, multiple access is done with a scheme called CSMA-CA. It's a carrier sense multiple access scheme with CA stands for collision avoidance. So it's not quite MACA, but it's a variant of it. And it optionally includes RTS-CTS as part of that, the RTS-CTS we've seen. Although it tends not to be used very much in practice because it's often not necessary for typical Wi-Fi configurations. With Wi-Fi, unlike Ethernet, the frames are acknowledged and retransmitted with ARQ. With Ethernet, we just had a CRC32. If an error was detected, you threw it away. That happened rarely. With Wi-Fi, because wireless is more prone to errors, many packets would be lost if we did this. So the packets are acknowledged, and if they don't get through, they're retransmitted, just to up the likelihood of them getting through. Now I said, just moving on to the third bullet here, that a good thing to do with protocols is to look at the format of their messages to see what's going on. If you do this for Wi-Fi, you'll see pretty funky things with the addressing. Most data frames are going to have 3 addresses on it. It's kind of weird. You'd usually think of a source and a destination. What's going on here is that 802.11 heavily involves the AP. So we actually have 3 addresses identifying a source and a destination and an AP that's potentially in between them. Although, often the AP is really the destination as well. Errors here, as well as the AXN transmissions, we have a 32-bit CRC just to sort of detect residual problems. And there are many, many more features you could read about for Wi-Fi that I'm not going to go into, but I'll just mention by way of example that these features include encrypting the contents of the frame so you can't read what's there, and other functionalities such as power save functionality, so devices can tell the AP that they're going to sleep so they can save on their battery. Okay, finally, let's look at this 802.11 CSMA-CA scheme for multiple access to see how it works. It's somewhat simplified compared to MACA. So multiple access control is a subject which hasn't really been definitively solved for wireless. And there are different variations around and they sort of work okay, but none of them are quite ideal. And so this is just what 802.11 does as a reasonable trade-off. Instead of using RTS-CTS most of the time, you can optionally do that as well. What 802.11 does is it avoids collisions by inserting small random gaps instead of an RTS-CTS. If we have these small random gaps, that's why you don't need RTS-CTS always. So in this scenario, we have a timeline here. Time is just going from left to right across the page. And we have timelines for 3 different senders, A, B, and C. A is going first. A is just sending a data frame. And there's also going to be an ACK after that, because that's how this wireless works, unlike Ethernet. This data is going to D, some other node that's not shown here. Now let's suppose that B and C both want to send while A is sending. Well, you can see here B is ready to send its packet, but it uses CSMA, it senses the medium and it hears A. A must be talking to the AP or something. Similarly, C was sending. Not sending. C became ready to send while A was sending. It heard A. So both B and C are waiting to send. Eventually A is finished. Its data frame and ACK frame is done. What happens? If we just sent right away, as is the case with Ethernet, we would run into a collision. We would waste a lot of the medium. It would be a problem. Instead, both B and C insert small random gaps. Here's a small random gap. C inserts this random gap, waits. After this much time has gone by without anyone else using the medium, C sends its packet here. There's the data frame, followed by the ACK. B happened to choose randomly a slightly larger delay, even though it was ready first. Everyone picks a random one and its roll of the dice was bigger. It waited this long, and then it stopped here simply because it heard that C was sending, so it suspended its timer. After C was done, it continued counting down its timer up for this small random interval. When it expired, here B got to send its frame. And in this fashion, by inserting these small random gaps, just to sort of test and allow someone else to use the medium and see who's waiting to send, B and C, even though they both wanted to send, have ordered themselves and they both got to send their frame. These back-offs are sort of wasted time, idle time on the air. And this is the cost of using wireless. But these back-offs are small relative to the data frames in duration. So we do okay in wireless. And finally, just to wrap up 802.11, let me just talk a little bit about some of the future trends for 802.11. 802.11 is a key technology, so I thought it might be interesting just to do this. Now, I don't really know what's going to happen with 802.11, of course, so this is just a guess. Firstly, it's likely that 802.11, well, it's already ubiquitous. It's likely to become more ubiquitous. Really, all devices these days seem to have an 802.11 NIC for wireless connectivity. What's likely to happen here, though, is that we'll have greater diversity. You can have very fast computers, high-end computers, and very low-end computers, your wristwatch or whatever, can all have Wi-Fi and all want to use the same AP. So now the nodes are not generally equal in capability like a laptop. Some are more powerful, some are less powerful. That will affect the protocols in small and subtle ways. We can also expect a lot of innovation. Everyone wants to be able to send more information across Wi-Fi. It always seems to be getting faster. This is likely to continue, and maybe more so than simply getting faster, Wi-Fi is likely to get more power efficient, so that the nodes that can use it, if they're battery operated, don't deplete their batteries so quickly. This kind of innovation is very much driven by physical layer technologies. As these technologies advance, Wi-Fi just sort of gets better, even without the MAC layer changing very much. And finally, I'd point out right now that Wi-Fi is a bit of a hassle to use. It's quite manual in terms of identifying what access point you can use, for which you have credentials, typing things into web pages and so forth. It's also a little limited in that transmissions go through an AP even when you have two devices in the same room most of the time. It's often easier to use something like the cloud, Dropbox or something, to exchange files than Wi-Fi, even when your devices are in the same room. That's just wrong in some sense. So we're likely to see more seamless integration of Wi-Fi into the massive connectivity that devices have. Then people would have to be less involved in setting up and configuring Wi-Fi. This is likely to happen over time. Okay, so now you know about Wi-Fi. G'day viewers. In this segment we'll talk about contention-free multiple access, an alternative design to the method of multiple access used in Wi-Fi and classic Ethernet. So in Wi-Fi and classic Ethernet, the multiple access problem is solved with randomization. What we'll talk about in this video is a completely different technique which is based on taking of turns. So in this picture here, the four nodes might take turns from left to right, 1, 2, 3, 4, to send to the access point. Before we get into the design of turn-taking multiple access protocols, one issue we need to talk about a little bit is why we would bother. Why aren't random multiple access protocols good enough? If they were, after all, there's no need to worry about these different turn-taking protocols. Well, it turns out that CSMA, the carrier sense multiple access method we looked at for Wi-Fi and Ethernet, is good under low load. It's very effective there. And the reason is that it grants immediate access, so there's no delay. And under conditions of low load, few collisions are expected, so the overhead is very low. But the issue, and the reason we're talking about turn-taking multiple access, is this bullet here. Randomized schemes are not so good under high load. The issue is that under high load you expect collisions, and this leads to a high level of overhead. It's also the case that the access time varies. A node, when it tries to send, might get lucky, try and send and get its packet off right away, its frame off right away, or it might get unlucky. It might suffer repeated collisions, and so it might take a long time for its frame to be sent. We would like to do better under conditions of high load. With turn-taking multiple access protocols, the protocols define an order in which the nodes send. The order is really an opportunity to send. It's a chance to send. So if you have a frame, when your turn comes around, you get to send it. If you don't, you just pass and the next node gets its turn to send a frame. All we really need to do to come up with these protocols is to devise some ordering. I'll talk about one on the next slide, a method called token ring. But you can imagine other methods. For instance, the nodes could use their addresses to impose an ordering from lowest to highest or vice versa in terms of who gets to send next. So with token ring, the physical topology is used to provide the ordering. The nodes are wired together in a circle, in a ring. And then a special frame called the token is put on and sent around the ring. You can see the token here. And it's going around the ring anti-clockwise. As the token passes the nodes, it gives each node who has the token an opportunity to send. They grab the token, then they, instead of sending it on, first of all they send their frame, and after their frame has been sent, they then pass the token on to the next node, further along. So the sending order here is going to go 1, the token will go on to node 2, to node 3, 4, 5, 6, 7, 8, 9, and then we're back and so forth. That's our order, and that's token ring in a nutshell. This kind of turn-taking protocol, token ring, as well as other turn-taking protocols, do have advantages. In this scheme, there is a fixed overhead with no collisions. The collisions are gone as a source of overhead, and in particular, we won't have an increasing number of collisions or a large number of collisions as the load gets high, just the fixed overhead. Because of this, the turn-taking protocols are more efficient under high load. We also get a regular opportunity to send. This leads to more predictable levels of service. You know that you'll get to send a packet every, say, 100 milliseconds or so. And the concept is easily extended to different qualities of service. As you might imagine, we could just allow one node to send, say, 2 frames every time it got an opportunity to send, instead of 1. That way, we get to send twice as much traffic as another node, if it was a high priority node, for instance. There are some disadvantages though, and the principal disadvantage is this, complexity. There's more to this protocol, defining the ordering and imposing it, and that means that there's more to go wrong. What could go wrong? Well, just as an example, what would happen if the token was lost? Now this really shouldn't happen, the token's just a frame going around the ring, but unexpected things can happen occasionally. Let's just suppose that the token is corrupted by bit errors, and it's too corrupted for any error correcting code that's used down there to deal with, or even an error detecting code to recognize that the token's in error and allow it to be repaired. If that were the case, the token might suddenly appear to disappear, and then the whole protocol would lock up. And if you can't send until you've got the token and there is no token, boy, you just never get to send. That would be no good. So we'll obviously need to guard against that. How? Well, token ring protocols in practice have every node have extra machinery to guard against these kind of failures. Nodes might run a timer, for instance, and if they haven't seen a token for a long time, they might decide there's been an error, and the nodes would collectively mint a new token. They'd work out who would do it, they would have to coordinate so they didn't have to have multiple tokens, and so forth. You can see that even though losing a token is a rare case, it can add considerable complexity to the protocol. There's also somewhat higher overhead at low load. The overhead of token ring is fixed, just passing that token around, but it's non-zero. And at low load, CSMA or randomized schemes have almost no overhead whatsoever. G'day viewers. In this segment we're going to talk about switches, which are a very widely used technology to connect computers together into small networks inside buildings. Okay, so we've talked about multiple access schemes a lot. Now they are very widely used for wireless networks. 802.11 was the popular example. But when we're using wires, rather than have the host run a multiple access control protocol, the method which is used today, which is vastly more popular, is to connect all of the hosts to a switch device in the middle. You can see in this figure at the bottom here, I have 4 different boxes which are all wired to one switch. The switch will provide connectivity between all of these different devices. This architecture is the basis of switched Ethernet or modern Ethernet, and it's used ubiquitously to tie together computer equipment in all manner of buildings. Let's just drill down in a little more detail. So the scenario is like this. Inside your building, your home, your office, the campus, you have different hosts, and these hosts are connected via a twisted wire cable, a twisted pair cable typically, to a box called a switch. This switch has many ports, so you can connect many different hosts to it. Somehow this switch is going to provide connectivity between all of the hosts so that when they send frames, because we're still operating in the link layer, when they send frames, the frames will go from one host to the right other host. Typically the wiring is done so that the switch will be in some kind of central location and all of the wires in your building will be run to a wiring closet in a convenient location. So the big question for us is what's going on inside this box to provide all of the connectivity? That's a pretty interesting question. If you remember back to our diagrams on protocol layers, I said something like this, that all of these different kinds of boxes, there are many boxes that have cables attached to them. They're distinguished by the functionality of what goes inside. And we can draw different kinds of protocol diagrams to describe the processing that goes inside. In a hub box or a repeater box, the devices operate at the physical layer. So they're really just connecting bits around, moving bits around. In a switch device that we're looking at now, the functionality inside the box runs at a link layer. So it's connecting frames from one port to another port. And in a device called a router, the functionality inside the box works at the network layer. So it looks at the details of IP packets, in the case of the internet, to work out which way to send them. We'll get to routers later on, so we're not going to look at IP packets and routers now. Instead, we're just looking at switches, operating at the link layer, sending around Ethernet frames. Well, to understand that, we'll go over both hubs and switches, because this will show us the difference between the two. We'll start with hubs. These are a physical layer device. In a hub, here's a inside view for what could be going on inside this box. We have all of the different lines coming in. These lines come from some host. They attach to the ports. Inside the box, if this is a hub, as a physical layer device, you could simply imagine that all of the ports are wired together. This will provide physical layer connectivity, and that's all we need. So for instance, if a frame comes in on this port from some host and it's all wired together, that same frame will go out on all of the other lines. Functionally, this is equivalent to the setting on the right, where if one host sends onto the wire, the frame will be delivered to all of the other hosts. It's just another way of wiring it. It's generally more convenient than winding one long wire through all of the different offices, because now we can run twisted pair to a central wiring closet. It's also more reliable, because if we lose one particular wire here, well, some host is out of luck, but chances are that the rest of the hosts are still able to communicate. However, if we break this wire here, you generally do more damage. You might have broken your LAN in half. It just doesn't work anymore. The signals get messed up too. Inside a switch, something very different is going on, even though it looks like the same box. Switches operate at the link layer. So as the frame comes in now, the switch will look at the link layer information, that's the source and destination Ethernet addresses, to be able to forward this frame out the right output port. This means, for instance, that if let's just say I just number these hosts, 1, 2, 3, 4. If I send a frame in here, it might be destined to the host on port 4. I would then send it through the switch fabric and out port 4. At the same time, the host on port 2 might be sending a frame to the host on port 3 using a different path through the switch fabric. The switch fabric here is shown as a grid. You could just imagine this as almost a street map and traffic lights. Depending on the addresses that are on the frame, different kinds of traffic lights or switches here are being turned on or off to connect different input ports to different output ports. And so that is how we can use different parts of this switch fabric to connect different input hosts to different output hosts at the same time. Here's just a cleanup of that figure where 1 is sending to 4 and 2 is sending to 3 at the same time. I'll note a couple of other things. First of all, I just sort of draw a line between a host and the port here to represent a link. Typically, for all switches you get today, this is a full duplex link. So even though I draw one line, really you might think of this as having two halves. Inside the cable there's usually a wire going one way and a wire going another way to make it full duplex. And this port really has an input and an output port structure. Yes, so they're full duplex. Also, what that means is that I can use, because I can do this sending in parallel, there's no multiple access control protocol for a switch. The host just send the frame into the switch when they're ready, and the switch will deal with making all of the right connections to send information at the same time. This is quite different than a hub, for instance. With a hub, when one host sent, the message was received on the wire at all of the other hosts. This means that two hosts couldn't send at the same time. Those hosts need to use a multiple access control protocol to coordinate their actions. With a switch, there is no MAC protocol. The lines are full duplex, they send into the switch works it out. This new method of working, however, does pose some problems. There is a lot going on inside a switch. In particular, you might wonder what happens if two different inputs are sent to the same output. So let's say that the first host here is sending a packet through the fabric to the same host on the output side. Well, what happens if all of the other hosts are also sending there? It's just a very popular destination. So we're all sending through the switch fabric to this one output. This can't happen at the same time if the lines are the same speed. Only one frame could be going in or out of a given port, maybe in and out if we can use it bidirectionally at the same time. The other frames which are coming in from other ports, which are destined for this one port over here, will need to be stored somewhere temporarily. For this reason, a switch has buffering, either on the input side of the switch or the output side, or both. You can see I've shown the buffering here as the pink here. So this is a little bit of storage memory to temporarily store frames until they can be sent on an output port, the right output port. The issue here, however, is that this buffering is fine if there are very short-term mismatches. Two hosts sent to one given output, and well, it took 2 frame times to send it out, so a frame had to be buffered for 1 frame time. But it's not going to work. Even buffering won't solve the problem if these hosts are sending to if multiple hosts are sending to one output in a sustained manner. If that's the case, the frames will build up inside the buffers. Eventually the buffers will be full and we will have loss. Now this is an example of some kind of contention or congestion happening inside the network. Because of this loss, as you send packets or frames across a network, they can almost disappear inside the network. They can be thrown away because the network could not support the traffic patterns. We're going to look at this issue much more later on when we get to TCP/IP, because the same sort of issue happens as you send packets across the network. They can be lost due to a lack of buffering inside switches. For now, we're not going to worry about it too much, and we're going to say if the switch is well engineered, this can happen, but we hope it won't happen very often. So switches and also hubs have some significant advantages over just connecting all of the hosts to a single shared wire, as was the case with classic Ethernet. Hubs and then switches became possible really due to Moore's law as electronics sped up greatly and also became a lot cheaper. And nowadays they're prevalent. They're what you find everywhere. They're not just possible because of technology, but they have definite advantages. It's more convenient generally to run wires to one central location rather than to sneak it through the offices. Imagine what you have to do to change it if you want to add another host and you've just got this one wire. They're also more reliable, as we said before, in that if the wire fails, you might lose a host, but you probably have connectivity for all of the other hosts in the network. This is different than a classic Ethernet. If there's a break in the Ethernet, actually it doesn't work for all hosts for electrical reasons. You may wonder if the switch itself is a problem for reliability. It is, after all, a single point of failure. You blow up the switch, you lose connectivity to all hosts. That's true, but if you lose connectivity to all hosts, you know exactly what to do. Go find the switch, take it out and put another one there. So it can be repaired fairly easily. It's not hard to find where the problem is. The other key advantage for switches is this. Switches offer scalable performance. This is a real win. With our single shared cable, maybe you have a 100 megabit per second cable, you attach 10 hosts to it. Each host, its fair share is maybe 10 megabits per second of bandwidth. With a switch, because we can send frames in parallel, you might provide 100 megabits of bandwidth per port. So every host then is able to send and receive it up to 100 megabits per second. Performance is much more scalable for these switches. Okay, so I'd like to go into one particular issue for making switches work. You might have wondered as I talked through there how switches, if they deal with Ethernet frames, find the right output port to which to send a frame. This would be easy if frames carried port addresses, send me out output port number 7, but they don't. The addresses which are on these frames are Ethernet addresses. They indicate a host, either the source host or the destination host. Now, that destination host might be plugged into any port on the Ethernet switch. We could imagine having someone manually configure a big table. This would be a terrible job to have. We don't want, that's exactly what we want computers to do. So let's try and solve it with an algorithm. And we also want an algorithm which will allow hosts to move around. You might move your computer to another office and connect it to a different switch, and that should be okay too. So we need to find some way when frames come in and we just have a source and destination address to work out what output port to send that frame to. The algorithm we use to solve this problem with switches is called backwards learning. It works as follows. So the switch needs to build up its own table that maps between addresses and ports, so it knows which port to use. It does so as follows. Step 1, first thing we do is we build up this table. An insight to allow us to fill in this table without having any human configure it is to note that Ethernet frames carry both source and destination addresses. So if you see a frame on a port, you can look at the source address and say, oh, I see a certain source address, so this port is where this address lives. If I ever see a frame which is destined to this same address, now I know what port to send it on. So you look at the source address of the frames to find out what port they're on. That's the backward bit in backward learning. Usually you might think you just look at the destination to work out where to send the frame, but by looking at the source, we can also work out where people live. The second step is what you do to forward these frames. You just got a frame on an input port destined for a particular destination. What do? You look up your table. If you know the port where it lives, because you've learned it earlier somehow, then you just send it to that port and you're done. What if you don't know? What do? In that case, you broadcast it by sending it out all ports. You just say, I don't know, it's attached to some port, I'll send the message out all ports. That way it's going to get to the right port destination. It'll also get to a lot of other ports and they'll just have to ignore it. Let's see how that works in action. So the very first time the network's used after it's powered up, A is going to send to D. No one knows anything at this stage. So A's frame comes in, it just says, hey, I'm a frame from A, I'm trying to reach D is the destination address. This switch It's clueless, it's just been turned on. It says, I don't know, there's nothing in my table. So therefore, I'm going to forward this frame, I'm going to broadcast this frame, I'm going to send it out all ports. Well, phew, it reached D, that's very good. It also reached B and C. Oh well, not a very efficient use of bandwidth. We also learned something here. We learned that A is on port 1, right? That's a valuable bit of information. Okay, so this is what happened. Now, step 2. Let's assume, because most communication involves requests and then replies, sometime later D is going to send a frame back to A. What will happen? Here's D, it sends its frame in destined for A. At this stage, the switch can look up its table here and say, yep, I'm just going to send it directly out that port. Wonderful. We did not have to broadcast it out the other ports. Here we are, cleaned it up, I just changed the color so you can see them. Oh, I should have said we also learned something. We also learned that D is on port 4 by looking at the source address as the frame came in. This is the normal situation now. Everyone sent a little bit of traffic and we've learned, because, if they're using the network, they're going to send some traffic, hosts, then we learn what port they're on. Now we're fine. Let's imagine now that A happens to send another frame to D. The frame will go into the switch. It'll come in port 1. The switch will know, yep, D, port 4. It will just send it there. Now we're sending frames between the port 1 and port 4, between A and D, fine, without broadcasting and sending extra traffic to other hosts. That just happens once, and this mechanism is fully automatic. We've learned how to get from one port to another with no configuration from a human and in a way which is fairly efficient. So that's pretty cool. There's something actually that's even cooler about this. This same mechanism works if you run it independently in the different switch. They're shown here as B1 and B2. Even if you have some hubs in there here too, by the way, there's a hub in here, H1. Assuming there are no loops in the topology, this is a crucial assumption. We're going to want loops in the topology, or at least we're going to want to allow them. So in the next segment, we'll handle the case where there are loops in the topology. For now, we'll assume there are no loops. Then the mechanism I've shown you will solve the problem. Let's see what would happen when A sends to D and then later D is going to send to A. Okay, A sends to D, here the frame comes in. With beginning of the world, everyone's just woken up. This switch, B1, has no clue. This switch says, okay, I will broadcast it out all of my ports, because I don't know. I'll also remember that if I ever want to get to A, I use this port, port 1. Okay, so this frame is going to go to host B and C. It will also go over this link and enter switch B2 through this input port. B2 actually doesn't know that it's come from another switch. As far as B2 is concerned, A could be directly connected here. It really doesn't know. It can't see the overall topology. But B2 runs exactly the same algorithm. It gets something in from A, destined to D. It's clueless also. It learns, hey, A is here. D, no idea. Well, we'll just send it out all of the ports. That's what we do. We broadcast if we don't know. It'll go to G. It'll go to D. Yes, that's what we wanted. It'll also go out here to the hub. The hub, by definition, wires everything together, so it will go out the other ports. It'll reach E and F. Wow. So A's frame went everywhere. But at least it got to D. Here's that again, and now let's look at what happens next. Now D is going to send to A. Here's D's frame, comes in on port 1 on this switch. It wants to get to A. Well, switch B2 actually remembered that the way you get to A is you send out this port. So it'll simply send it out that port. There's no need to broadcast. It'll come in this port. Switch B1, as far as switch B1 is concerned, this could have come in directly from D. D could be plugged here, it doesn't know. Switch B1 looks at the destination, that's A, it looks at its table and says, yep, that just goes out port 1 here, no worries, done. No broadcast, we now have an efficient way for D to send to A. And of course, you know where I'm going here. You can work through yourself the case of how A sends back to D, and you'll see that we're using the switch very efficiently. So this algorithm extends naturally to topologies with multiple switches and hubs. That's pretty cool. Now you know a lot about how switches work. This is how a modern switched Ethernet works. We've just not handled one condition, and that's that there might be loops in the topology. I'll get to that in the next segment. G'day viewers. In this segment, we'll talk about the spanning tree algorithm, which will complete our understanding of how LAN switches work. Okay, so in the previous lecture, I talked about switches, modern switched Ethernet, how hosts were connected to them, and how they forwarded frames, so thus providing connectivity between all of the hosts. But a major assumption we made was that the topology and the way these switches were connected could not contain loops. Now I'd like to talk about how we can allow these switches to be connected in ways that do contain loops and still have the overall system work. There are a couple of reasons you might want to have a loop in the topology. You might simply want some redundancy in your network. You can see here on the diagram on the right, I've added a redundant link in the middle between the two switches in the middle. You might do this simply because one of them might fail and you'd like to provide a little bit of redundancy ahead of time, so there is that if there is a failure, there are still links in the network so it can work. You might also make a simple mistake. Networks evolve over time. I think components are always being added and removed, and it would be very easy for someone to plug a cable into the wrong port and inadvertently create a loop. This could happen, and we wouldn't want a simple mistake to take the whole network offline and have it not work. So we would really like for these LAN switches to just work, to provide very much a plug-and-play environment. LAN switches, in fact, are some of the earliest sort of plug-and-play computer networking that just works. I guess Ethernet does too, but LAN switches are really an extension of that. We also want to do this. One of the constraints for the design of LAN switches, Ethernet switches, was that the switches should work with no change to the hosts. So we don't want to have to go and upgrade all the software in millions of hosts just to be able to connect switches with loops. But if we don't do something compared to what we've seen so far, we have a major problem with loops. Let's look at that for a minute. What can happen? So suppose that the network is started and we have our network here. I've labeled the hosts A through F. What's going to happen? I think I'm just going to override on this diagram and draw a series of frames being sent. A sends to F. Well, at the beginning of time, no one knows where anything is, so they're just going to broadcast frames. A's frame goes into C. C gets it. C will broadcast, so it will send it out the other ports. That's what we've got to do initially. Okay, so it went to B and it went to D. It actually went to D twice because we have a loop in our topology. D, well now let's just look at the first of these frames it gets. Consider the right one first. D will get that frame in and then it will send it out everywhere else to F, to E. It will also send it back to C on the other port to C. Oh boy, you can see that things are going to go a bit south here. D will look at the second frame that it gets. This is from D on a different port. Now it doesn't know this is the same frame. You might think we could just look at the contents, but you don't know whether this is a second message from A or not. We really have no way of telling. D will then send this frame out to E and F, and of course up the other link back to C. Wow, E and F are now not so happy. They've now received 2 copies of this, and they didn't want, well, at least E didn't want any of them. But we're not done yet. We now have these 2 frames that have gone to C. Let's look at the one on the left. It went to C. What does C do with it? It broadcasts it because it still doesn't know where F is, hasn't seen any frame from F. Goes out to A and B and down to D on the other link. And similarly, for the frame from D to C, the second one, it will come up, go out to A, B, and down to the other link, back to D. Now, this diagram is getting very messy. If you follow some of the logic through, I could write all this down. I think I'll do that on the next slide. You'll see that we have something nasty going on. I'm just going to draw a big massive circle here. Some packets are spinning around here left to right. There's another series of packets spinning around here in another direction. And traffic has been forwarded out to all of these nodes, A, B, E, and F, as we go around this loop. So we have a storm here in the network. One packet was sent in by A. It never ends. Traffic keeps going around the network and fresh copies of packets have been delivered to all hosts on the edge. This is really nasty. Wow, so here is just the beginning of that logic spelled out for you a little more in terms of who sends where so you can follow it through. and it just goes on and on. It never ends. So a forwarding loop here has caused something pretty nasty to happen. The solution that we'll come up with to prevent this problem, and we would really like to nip this problem in the bud because you can see that one packet can cause devastation here with the loop. The solution we'll use is for switches to collectively find and agree on something called a spanning tree. A spanning tree of the topology. A spanning tree is simply a subset of links of the topology, which is a tree, so it has a root and branches out from the root, but it has no loops in that topology. The subset of links in this topology is a spanning tree if it's a tree, and it spans the topology. It reaches all switches, so it will allow us to deliver frames to all hosts on the network. Once we find this spanning tree, this is the first step, the thing we want to do, then we simply use it as before. Switches simply forward frames along the spanning tree. So they just pretend that the topology was only the spanning tree. If we know which way to go, great, it'll get there. If we don't, we're going to broadcast. And if we broadcast on the spanning tree, frames will tend to go up the spanning tree to the root and then down all branches, so they'll get everywhere, but they won't loop. This sounds pretty messy with spanning trees, so let's just look at some examples to get a sense of what a spanning tree is, and then I'll talk about the algorithm to find one. Here on the left, we have the topology. This is the links which were physically installed in the network. Now I want to talk about some spanning trees. Usually there are many different possible spanning trees for a network. Let's just see some of them. Let's just pick a node here arbitrarily, top left one, as the root of a spanning tree. How are we going to create a spanning tree? Well, from this root, let's create some branches. Let's say I go down here and here. And, I'm just going to say there are only 2 branches in the tree. So from here I'll go up to here, and from here I'll go over to here. This then is one spanning tree. It reaches all switches in the network. I can cross out the links we haven't used. Okay, fair enough. Here's another spanning tree just to show you that multiple ones are possible. I'll select a different node as the root. From here I'm going to just arbitrarily pick one branch down, and from here I'll divide. I'll just say I'll use this other branch here that's going to reach these switches, and a different branch here will reach these switches. In this spanning tree I don't use these 3 links of the topology. These are all different possible spanning trees. Of course, in our automated solution we're only going to want to choose a single spanning tree and have everyone agree which spanning tree we'll use. Here's that same diagram cleaned up. You can see, it looks like in this example here, sorry, I chose a slightly different spanning tree. This is just yet another possibility. Instead of going here, I went over here. Okay, well that just shows you yet another spanning tree. But conceptually, the point is exactly as I'm saying. Okay, so now we need an algorithm to find the spanning tree. We've seen there are a few. I can't even agree amongst my slides on which spanning tree is which one. But we want all of the switches to find a single spanning tree. Then they can use it. How are they going to do this? It's a little complicated or subtle, again, because this is a distributed game. If someone like you or I could just see the network, we could draw a spanning tree and say, here, use this. But the switches can't do that. They're distributed. Firstly, every switch runs the same algorithm. There's no special distinguished switch which is in charge. This is actually helpful because then there's no switch that can fail and throw your network into chaos. All switches can handle what's going on in the network. These switches are going to start with no information because we don't want to have configuration or make assumptions. Now, switches can only see what's going on with themselves. They can send and receive messages, but they don't know what's happening elsewhere in the network, just what they hear and what they send. In fact, all of the switches are not only doing this, but they're operating in parallel because they have no way to otherwise coordinate their actions with other switches. As they operate in parallel and send messages, we want these switches to continually search for the best solution. If we do this, we will end up, if we can solve this problem, I haven't told you how to yet, we will end up with a highly robust solution. It will work for any topology with no configuration because we assume that we start with no information and have no special switches or position in the network. It will also adapt to link and switch failures. And the reason that we will try and do that is that we'll have the switches continually search for the best solution. And we'll have them throw out information about nodes that's not repeated over time. So if there's really old information about a switch that you haven't heard from for half a day, you'll eventually forget that and find the best solution in the network that you believe exists now. And that way, if some component fails, you'll converge to another spanning tree which uses the nodes that are in the network and cut over maybe from a failed link to another redundant link. I'm getting a little bit ahead of myself. Let's work through some examples to see this spanning tree algorithm, because if you haven't seen algorithms like this, there's a lot to it. Don't worry, we'll work through an example. Oh, and I'll just tell you that the spanning tree algorithm that I'm going to go through was pioneered by Radia Perlman. She's shown here, you can see her picture. She did much of the early work on different kinds of spanning tree and early routing protocols in the internet. She worked on different kinds of routing in the internet, the spanning tree algorithm we're going to look at, and also different kinds of link state routing, in particular link state routing that we'll look at when we get to IP networks. Nowadays she works on network security. But what we need to go through now is the spanning tree algorithm. Here is an outline for that algorithm. These are the steps that will happen. First of all, to come up with a particular spanning tree, we need to elect a root. The root could be any node, that's possible. They just need to agree on who it is. So we're going to let the switch with the lowest address be the root. So switches can use their addresses to look and send messages and agree on who's the root. When we have the root, we are going to grow the tree from the root using the shortest distance from the root as a way to decide what branches are on the tree. If we have ties, because from one particular switch you could get to the root by two different paths of equal length, we will again use the lowest address as a tiebreaker to decide which branches are on the spanning tree. And when we have the spanning tree, we'll then simply turn off any of the links, the ports, which don't forward onto the spanning tree, and we can then use the spanning tree to forward using a learning algorithm. Now, actually, one thing that's slightly complicated is that steps 1 and 2 happen in parallel. There's no phase 1 and then phase 2. This kind of logic is interleaved. Whereas once things have stabilized, then we proceed with turning the ports off and using the tree for forwarding. Okay, now in a little more detail, I've said what these nodes want to do. Find the lowest node, grow a tree out from that node. But they do that by sending messages. So here's a few more details on the messages they send. Initially, each switch is going to believe that it's the root of the tree in its messages. And every switch is then going to follow this same behavior. Every switch will send periodic updates to its neighbors. These updates will contain its address, the address of the root, and the distance in hops to the root. So an example is shown below here. Here's switch C. It's sending out a message. It might say to its neighbor, "Hi, I'm switch C. You know, I've heard that there's this great root of the network called A, and it's 2 hops away from me." We will abbreviate that message as CA2 when I write down what happens, or the state of a switch. Now, all different switches are going to get messages from their neighbors, and they're going to process them. When they hear different messages, switches are going to update their configuration, and they will favor ports which reach better routes, lower cost routes with shorter distances, again using lowest addresses as a tiebreaker. And it's quite amazing really that if all switches follow this simple process, this rule, this 1-2 punch rule, and update, the network as a whole will converge to a single shared spanning tree. Wow! Okay, let's see how that could happen. This is kind of tricky stuff. We do need to work through an example to see what's going on. Okay, so in the beginning, I've labeled all of the nodes here of the simple topology with their state. Everyone thinks they're the root, and they're distant 0 from the root. Now, in every round, all nodes send out messages to their neighbor with their state, and then they receive the messages from their neighbors and update their own state. Let's look at the kinds of messages that are sent out. I'm just going to pick one node, node C here. So node C, this is its state. It will send this message out, all of its links, to nodes A, B, and D. D twice. They'll all get these messages. And similarly, every other node will send that information to its neighbors. Having got that information, they'll then update. Node A, for instance, will hear from node C, but A will say, well, my state's better, I'm a better route. Node B will get messages in from node C and node F saying that they both think they're the route. And node B will sort of say, well, rubbish, I'm a better route than either of you, so I'm sticking with my state. Some people will change though. Let's imagine node E. Node E will send out and it will get messages back from D and A. Well, guess what? A is lower than E. D is lower than E too, so E will actually hear two better messages. The best one is A. So E will be forced to update its state. It will say, oh, okay, well, I'm still E, but I've heard this is route A, and I am distance 1 from it, since I got a message from A saying it was 0 hops away. Similarly, there are going to be some other updates. C is going to update to say C, A1. C now thinks A is the route and it's next to it. D will also update. D will actually think the best thing it hears here is from C. It thinks it's next to C1. Now I can also see here that F will update to be F. It will hear from B as its best option and it's 1 hop away. So that is the new state of nodes. Let's go to round 2 now. Round 2, I've replaced the diagram, I've updated the state of nodes. All of the nodes send these messages out to their neighbor. So C sends the message CA1 out to neighbors A, B, and D twice, for instance. What's going to happen? Well, A still sticks with its configuration. It's the route. No one can beat it. B, as it gets this message from C, let's see here, unfortunately, B learns that it is not the best option. B will update its state to be B, A, 2. It's 2 hops from A. A is a better route than B. And it's going to reach the route through C. C is going to keep its state. It won't change. D will actually update too. D will hear from both E and C that there is a route A. In fact, D could get to the route A via 2 different routes. It could either send via C to A or E to A. D is going to decide that it will send via C to reach A because C is a lower address than E. And D's state is going to update from DC1 to DA2. And I think everyone else is about where they were. Okay, so here it's cleaned up. Third iteration. Everyone sends out their state again. We process the received messages. What happens? Well, this is a lot of work. How long can this go on? We'll see. Okay, A and B, and actually C and D remain where they are. Now you notice here for D, I've said that D is going to reach the route via C on the left-hand side. There were 2 possibilities. Actually, both of these ports will have addresses, so D will be able to choose the lowest port. That's just a quirk there. E, yep, E stays the same. F, however, is going to update. F is going to hear that there is a better route because B sent this message out saying, oh, I'm B and, there's this route A, I'm 2 hops from it. D actually will also send a message out. And F will update its state to be F, A, 3. Okay. Well, I think we've finished now. Let's see. Yep, so this steady state has been reached. Every node will now continue to send out its message, but nothing will change. When nothing changes after a while, everyone knows that we're done. And you can see here I have grayed out and we can turn off these links. They're not, in fact, used for forwarding. The algorithm will continue to run and it will time out information so that, for instance, if node A fails, then eventually other nodes, switches here, will discard the messages from A and forget about it because it really doesn't seem to be there anymore. B will become the new route, and that new spanning tree for B will be computed and then used. We can see how the spanning tree is used. Forwarding proceeds just as usual according to the backwards algorithm, the backwards learning algorithm. So let's see that the network's just been turned on. D wants to send to F. What's going to happen? Okay, well, now since no one knows where anyone is, everyone will broadcast and forward out all ports. We're only going to use ports on the spanning tree though. That was our restriction. So D sends to C, C sends to A and B, A sends down to E, B sends down to F. Got it, we've reached F. Now, when F sends back to D, we're going to proceed along the reverse path because now this switch F knows that you get to D through here, and A knows that D is down here, and C knows that D is down here. We're more efficient sending back from F to D in that we did not broadcast over our spanning tree, so we didn't reach all switches on the network. Nonetheless, you might have noticed that we didn't really use the best route. There was a link here between D and F, but our spanning tree didn't include it, so we didn't get to use it. This should give you a hint that we can do better than the spanning tree. And we'll see how when we get to the network layer and think more about routing, we can come up with better algorithms. Nonetheless, the spanning tree algorithm works well in that no hosts were changed, yet we've solved this problem. It's completely plug and play and we can handle any topology. This slide cleans things up, just shows you some of the transmissions in different colors. I don't know why. I think I see one error here. There are two errors here. I'm just going to cross one off. There should only be one. A will only send to E once. I've written down just the transitions here so that you can see them. So the forwarding, so that you can see it. And if you're sort of wondering how you would remember all of this, here's a poem, an algorithm that Radia put together. She came up with the spanning tree when she was at DEC, and while it initially seemed like a very difficult task, it proved to be easier than she thought when she worked out how to think about it. She did that in the early part of a week, and it gave her enough time to write a poem in the rest of the week. So there you have it. You can see this algorithm. And now you know how LAN switches work. G'day viewers. In this segment I'm going to give you an overview of some aspects of the network layer, and we'll go into more detail in these aspects in the following lectures. Okay, so first of all let's look at where we are in the course. Well, we're starting the network layer. That's where we're at. And yes, this is IP. This is the unit in which we'll learn how the Internet Protocol works. As you can see from this reference model, we've gone through the physical and link layers, so you know how to send information and bits across a link instead of signals, and you know how to send frames of information across connected links. That's great. Now we're going to move on to the network layer. The network layer builds on the link layer, and its job is to have routers send packets of information across multiple connected networks. So let's see how that works. Well, actually, before we do that, one of the first questions I'd like to talk with you about is why we even need a network layer in the first place. Now, we've already seen with switches and links that we can build small-scale networks. So here's a small-scale network, and if we follow all of the ideas we've seen so far, we would be able to send frames from one computer to another computer that's connected somewhere to those switches. This is pretty good. If we can do this already, we should ask what it is that we're going to get out of a network layer, since a network layer would seem to be doing much the same thing in sending packets across all of the hosts and routers that are connected together across many networks. Well, I'm glad you asked. There were actually three shortcomings of the switch approach we looked at that I remarked on very briefly at the end of that unit, and I'm going to remind you of them now. The first shortcoming was that the method we looked at didn't really scale up to large networks. Now, as your network gets larger, it goes from tens to hundreds to thousands, up to millions of different hosts. Think for a moment about how the switching approach would scale. A couple of things happen. One, there is a blow up of the routing table. So that's this situation here. Every different switch in this diagram is keeping a table which maps for every different destination which way to go. That table is going to have millions of entries with our switching approach as the network gets bigger. That's a lot. Everyone needs to maintain this table. A second issue is this broadcast. That's here. As you remember, to reach new destinations that they haven't heard of before, switches broadcast. This means that the first time you send to a new destination, it could get sent across the entire network. Imagine sending a packet to a new destination and having it go through to millions of other hosts on the network, just because you weren't sure which way to go. So this design doesn't scale as well as we would like. A second shortcoming is that the switch approach we've seen doesn't work across more than one kind of link layer. It's a link layer approach, so it's designed for a particular link layer. Now, we've already seen different kinds of links. We've seen Ethernet inside wired enterprises, 802.11 inside, many houses, and 3G for cellular mobile connectivity. They're different kinds of links from our point of view. We would like to be able to network them all together and send packets from, say, an 802.11 host through to a host on a wired Ethernet. But the switching approach we've seen so far doesn't really take this into account. It isn't equipped to join these different kinds of link layer technologies together. And a third reason is that switches don't give us much control over the routes which are taken through the network. The spanning tree algorithm we looked at is pretty impressive, really, in that you can just plug your network together however you like, and the network will be able to find a spanning tree and get packets from any host to any other host. But it didn't guarantee that the paths which were taken were necessarily very good ones. So traffic in a spanning tree network might follow this path. Say from one switch to another, we might go along this path I've outlined, when in fact there was a direct link which would have gotten you straight there. That's not what you would necessarily want, because usually the most precious resource in a network is the network bandwidth on all of the links. We would like to use it well, and to do that we want to have good control over the paths that packets take through the network. So when we look at a network layer approach, we're going to see ways in which we can improve on all of these shortcomings. We'll look at ways to scale the network. Essentially, instead of sending to an individual destination, we'll be able to do all of the routing and forwarding through the network, all of the work at routers, in terms of blocks of IP addresses called prefixes. This is applying hierarchy so that all of these different routers will have smaller tables. They won't necessarily need to have millions of entries for millions of hosts. We'll also see in the network layer support for heterogeneity. IP uses an approach called internetworking, in which different link layer technologies are put together. And we'll study IP really as the big case example here, in which there's a lot of experience in what you have to do to make an effective network. And finally, eventually, we'll look at different ways of having better control over how you use bandwidth. Rather than the spanning tree, we'll look at lowest cost or shortest cost routing, which is a different framework for deciding which way to go. And eventually we'll even look at quality of service, although that will come later in the course. Quality of service is really also about different ways in which you would make good use of the bandwidth you have. Okay, so this slide here gives you a topic list of what we're going to go through in this unit. It's fairly detailed, and I don't expect you to understand all of the terms here right now. You can use it as a roadmap for the units that will, or the different topics in lectures that we're going to go through in the different segments. First of all, I'm going to tell you about different network service models. As well as a traditional packet model of datagrams, there's also a virtual circuit model, so there are different possibilities for networks. Then we're actually going to spend quite a while going through different segments on IP. IP is the big example from which we can learn a lot about how to build networks, as well as understanding how the internet works. So we'll go through many different aspects of IP. And we'll cover all of these things, and you'll get to know what all of these ARP and DHCP and MTU and ICMP acronyms mean. So don't worry about it now, we'll go into it. This that we're going to look at, IP, is really IP version 4. That is the version of IP which essentially most of us probably use today with our computers. There's a new version of IP in the internet that's now being deployed, it's the future, and that is IPv6. So to finish up on IP, we'll look at IPv6 to find out what's different and what's going on with its deployment. Many of you have probably heard of IPv6 as something that's coming to the internet. And finally, in this unit, we'll look at NAT. NAT is a strange kind of forwarding technology. It's called a middle box. It is something that many of you probably have in your houses. If you have it inside an EP that you hook to the internet, usually has net technology inside it. We're going to understand exactly what it is, since it's something that many of you probably encounter day to day. And we'll see how it does fit, or rather how it doesn't fit, with the standard IP model. And then eventually there's this item down here that's grayed out for now, routing algorithms, which we'll get to in the next unit. There's actually a lot of detail in there. Routing is a big and important topic, but we're going to put that off for a while. Before we go ahead though, I want you to be able to be aware of one important distinction, and that's the distinction between routing and forwarding. They're two different things. It's a little confusing because routers in the internet do both of them. They're responsible for both routing and forwarding, so that's why I'm pointing it out. Now, routing is the process of deciding which way your traffic should go in the network. This is a process in which all of the routers participate. So routing involves talking to all of your neighbors and saying, hey, who's where, and do you know who's over here, and generally working out what is the best way, the best links you should use to send to reach all different destinations. So it's a network-wide process where everyone agrees on things. It's global, and because of that, it's relatively expensive. Forwarding, on the other hand, is the process of deciding what to do when you get a packet. Someone tosses you a packet, what do you do with it? You forward it by throwing it out the link on which it needs to go and doing a few other things. So forwarding, of course, uses the information that comes out of routing. After routing, you're sort of left with a table which tells you which way to go to get to different destinations. Forwarding is the act of using this table. This means that it's a process that happens purely at one node. It's a local process. And because of that, it's fast. Actually, it has to be fast because a router might have to process millions of packets a second. So we've got to be able to forward quickly. Now, our plan, looking ahead, is to treat these two topics differently. Actually, the first one we're going to do is forwarding and understand what routers do with packets. Now, logically, you might think that routing comes first. It's difficult to know how to forward a packet until you know which way they need to go. But we think that it will actually prove easier for you to understand the internet if we go through the forwarding model first, and then we deal with routing later. So I'm going to ask you just to suspend disbelief for now, and just imagine that routers somehow magically know which way to send packets. What we're going to look at in the upcoming segments is how they actually send those packets on their way, because there's quite a lot involved in that. Okay, now that we've got this distinction in mind, let's go for it and find out how the internet and IP work. G'day viewers. In this segment I'm going to talk about the different kinds of network service models. So our topic is really the kind of service which the network layer provides to the transport layer. Like all good layers, the network layer is going to provide some kind of service interface to the higher layer, the transport layer in this case. And so what we would like to talk about is just what kind of network service is going to be presented by the network layer, and how that service is implemented at routers. We're just going to talk about these topics at a high level, and in future segments when we dive into IP, you'll see how one of these models is realized in detail. So it turns out that there are actually two quite different kinds of service models that the network provides to the transport layer, both of which have been talked about a lot and experimented with in practice. One kind of model is what's called the datagram model, datagrams or connectionless service. The analogy here is the post office. So datagrams are just like sending letters through the postal system. They're self-contained units. You send them, you write your letter, you seal it up, you hand it to the post office. They're all treated individually. The post office delivers them by looking at the address and sends them on their way. This is very much like IP. IP is based on a datagram service. And that's really the way you might have expected the internet to look because of that. But there is another model here too. This other model is called the virtual circuit model, or a connection-oriented model. And the analogy here is one of the telephone system. You need to make some kind of connection, just like dialing someone, before you can use the network. But once you've made this connection, you can then sort of send data down the pipe and it will arrive out the other side. So this is quite a different kind of model. Both of these models have their pros and cons, and I think it's useful for us to know about both of them before we dive into the details of IP too much. So I'll also say that both of these different models are implemented with a technique that's called store and forward packet switching. Well, that's a bit of a mouthful. It really doesn't mean anything too complicated. It essentially means that the way routers are going to work is that they will receive a complete packet unit and they will store that packet temporarily while they work out what to do with it and send it out on the right link so that it's going to arrive at the destination. They won't necessarily need to store it for very long. In fact, they might only need to store it if, there's contention for that destination. Other people are trying to use the link at the same time. One thing that's important about this model, that's one reason why it's used widely for all data communications networks, is that it uses statistical multiplexing to share the link bandwidth over time. In the description I gave you of having packets come in on links and simply sending them out links, what we're doing is we're sharing the bandwidth of all of the output links at a fine grain over time by sending different packets, maybe coming from different hosts and going to different hosts over that link. And we're using a bit of buffering inside the router to queue things up if you can't get on right away. So this is statistical multiplexing at work. It's quite different than dividing that link according to fixed time periods or fixed frequency periods like radio stations using the link. And it gives us many of the advantages of networks in terms of using the capacity well. As an aside, I'm going to dive into the store and forward model a little more, just to give you a better sense of what can go on inside these routers. So here's a fairly general model for all switching elements, switches, routers, funny devices that have a lot of input and output connections inside the network. They're all going to look something like this. They have inputs here. I've drawn the inputs on one side, so these will be plugged into ports, twisted pair wires coming in maybe, and they'll have outputs on the other side. Really, the input and output might be combined in a port, but it's more convenient for me to draw this from left to right. Inside the box, it's just another box. You can't, tell what the functionality is inside until you have some description of what layer it's doing the processing at and so forth. Inside the box is usually a switching fabric. That's what's providing the connectivity between different input ports and output ports. And what I want to highlight here is there's also necessarily some buffering. That's these pink things here that's both the input and the output. Why is the buffering? Well, there's buffering because maybe at the very same moment a packet came from this first input up top and it was destined for this output up top. And also a packet came from another link and it was destined for this output, and yet another link and it was destined for this same output. All three of those inputs can't go to the one output at the same time. So if the packets enter the switch, they need to be stored somewhere, either on the input buffering side or the output buffering side. But we do need buffering. And that buffering is just for temporarily holding the packets to help with our multiplexing of the output link. That model I just gave you is a little detailed in some ways, and it will often suffice to think of a much simpler conceptual view of what's going on inside a router. So here's another picture of a router. I've really drawn here just one output port, and in the simplified model here, we imagine that there is output buffering for each output port. So there's just one unit of buffering, and that unit is provided at the output port. That buffer, that big long buffer, is then filled up with packets. You can see I'm drawing them in here. As the packets come in from the input side and they're waiting to go out that output link. Exactly how that buffer is managed depends on how the router or switch is implemented. There are all sorts of different possibilities. But a typical one is to use a policy that's called FIFO, first in, first out. That just means that whatever packet gets in the buffer first is going to go out the output link first. And the rest of them will just have to queue up behind it. If this buffer gets full, by the way, there's no space and another packet comes, that packet will be discarded, or there'll be some discard policy. A packet will be discarded. So you can see here an important implication of these switching elements with buffering, and that's that packets may be discarded under load. This is actually what we refer to as congestion, and we're going to study it in a lot of detail later on. Okay, so now you know about some of the internals of routers. I'm going to tell you about the two different models we talked about in a little more detail. So first of all, the datagram model. Here's a network, and packets are going to go through this network between different hosts. In the datagram model, each packet contains a destination address. So every packet contains a full destination address. That's what the router uses to be able to deliver the packets onwards. Now the path through the network to get from one host to another might be this path here initially. The way that will work is all of the routers here, A, C, and E. As a packet comes in, router A will look at the destination address, and if it sees it's, well, let's say it's really H2, but let's just say it's F over in this direction. A will look up in its table, see what it is, F, and it will learn that the way to forward it is along this path to here, in this direction. The packet will then arrive at C, which will go through the same process. But now realize, because every packet is handled individually, and a different process is responsible for maintaining the routes, it's possible that the routes can change while someone's using the network. At a later time, A might change its mind, and packets might follow a different route through the network. Thus, the host at the other end might receive its packets fine, but there might be strange delays or misorderings because the packets could actually have gone along different routes some of the time. We can just look at that in a little more detail just to sort of complete our thoughts about the datagram model. These pictures here show you the forwarding table that's used at each of those routers. So here, over here, maybe is C's table. Here's C's table, and you can see that it has a table where for every different destination, it has a next hop to output the packet to. That next hop is really going to correspond to which output line it should send it on to send it to there. I've shown you tables here for A, C, and E, and A's table actually changes over time. Let's just imagine that we're trying to send a packet from A to F. And when the packet arrived at A, what A would do is it would look up in its table, it would see that it was going towards F, and the next hop for that is C. So it would then send it over the network, it would arrive at C. C would similarly see the packet's trying to go to F, look it up, see that it's meant to send it to E, and so on. It would get through the network. At some later time, A's table might change. You can see here that for some reason, routes towards the destination E and F have changed. They're now forwarded onwards to the next hop of B rather than C. Why? Well, we don't know why, but that doesn't really matter. We don't have control over it. We don't know when it could happen, but it could happen. The datagram model will still be fine. These packets, when they arrive, we will look up a destination like F. If another packet came, this time we would send it to B. No, B will have to look at its table and work out what to do, and maybe now we're following that other path through the network. So this is datagrams. The most popular datagram model by far is IP, the Internet Protocol, example of a datagram model. IP is the network layer of the Internet. It's what you have to use to be on the Internet, so it's used everywhere. It almost defines the Internet. The addresses I've shown you here, just shaded, these are the 32-bit addresses in IPv4. They're on each and every packet. Often packets might be up to around 1.5 kilobytes long, so you can see the picture here shows the header, which is going to occupy some number of bytes, not that many. If you've got 1.5 kilobyte packet, the overhead's not too much. There are various fields there, and the bottom one that says payload, or TCP segment, that's all of the data of the packet beyond the header. Don't worry about all of these details on the header here, all of these different fields. They're the fun bits of IP that we get to go into in all of the segments which are coming up. But for right now, I just want you to know that IP is the most famous example of a datagram model that's out there, and we're going to look at it in detail to understand how it works. Second model. The second model I talked about for providing a network service to the transport layer was the virtual circuit model. Virtual circuit model is unlike a datagram model. Datagram model letters, everything packet is independent, self-contained, fully addressed. Not the case in a virtual circuit model. In a virtual circuit model, just like the telephone, we go through 3 phases. The first phase here is a connection establishment phase. You've got to set up some connection or circuit from the person who wants to send to the person who wants to receive the information. Setting up the connection really means finding a path through the network, choosing that path, and setting information about the circuit that we're about to use in all of the routers that are along that path. So they'll know what to do when they see packets from this virtual circuit. Once it's set up, then there's a data transfer phase. This is the useful bit in some sense, the bit we want. We send packets along this virtual circuit, and all of the routers along the path forward them on to their destination. And then finally, when we're done, particularly if we're nice, there is a circuit teardown phase in which everything's cleaned up. The state about this circuit is deleted from all of the routers along the path in the middle of the network so they can forget about it and move on to new circuits. So this model is called a virtual circuit because it's fairly similar conceptually to a telephone circuit, but unlike imagining a physical wire or a certain level of resources that are reserved for a telephone call, it's virtual in the sense that there's usually no bandwidth associated with this circuit. The bandwidth across the links is still shared with statistical multiplexing. So how much bandwidth you get from this circuit is just going to depend on how much traffic you send and all of the other traffic in the network that was competing for it. Well, let's look in a little more detail. Here's our picture of our network again. Now, unlike packets in a datagram model, packets in a virtual circuit model don't necessarily, well, they don't contain a full address. All they need is a short label which says what circuit they're on. Hi, I'm on circuit number 7, so that the router will then know what to do with it. Because during the connection establishment phase, it's worked out what circuit number 7 means and where it should go. So these labels don't have any kind of global meaning. They just have to be unique to the link, to the router, where they're going to arrive on a certain link, so the router will know what to do. But they don't have to have any other unique meaning. In this network, we might have two different circuits going at the same time. Now, both of these circuits might be going along some of the same links. So here's one and here's another. Both of these circuits could be used at the same time. Maybe if host 3 and host 1, maybe if they're both sending to host 2. Well, let's just, because we're going to want to be able to send multiple circuits on the one link, otherwise we haven't got much of a network. Okay, let's look at just a little more detail. We looked at the forwarding tables inside a datagram network. Let's look at the forwarding tables inside a virtual circuit network. And the reason to do this is for you to see how they're different than the forwarding tables inside a datagram network. So now all we really need is a table which tells us the incoming circuits and what to do with them. By convention, the table tells you the incoming circuit, it tells you what link they're coming from. So something arriving at A could be coming from either host 1 or host 3, and what circuit number they have on the link they're coming in. These both happen to be labeled circuit number 1 on their respective input links. And then the output table tells us what to do. So you can see that the circuit that comes from host 1 with identifier 1 is forwarded out the link going towards C, where it is known to C as circuit number 5. What that means is that we're going to change the label or the circuit number inside the packet as it goes through the network. This packet is going on the link from A to C. It's identified by 5. When it arrives at C, it comes from A with 5, that's right, and what happens? We look it up in the table. We're meant to send it on to E with the circuit identifier of 1. So we're going to change that 5 to a 1, send the packet out the link to E. When it gets to E, what happens? It's coming from C with a 1, it goes out to F with a 1, and so on. I'll just go back now and consider traffic from host 3 going to F and eventually on to host 2, let's say. The reason to do this is because this circuit traveled down some of the same links. So we've got to be able to separate these two different circuits on this link. This example will show us how we do that. Now, the traffic from host 3 comes in with circuit identifier 1 to A. A has different input lines for host 1 and host 3, so it knows which one is which. When it gets circuit identifier 1 in from host 3, its instructions in its table here, and this is just one example, you could construct many different tables, but its instructions here is to send this packet onwards to C with circuit identifier 2. So it would change the 1 to a 2, send it on to C. At C, this comes in on link A with circuit identifier 2. Note that both of these circuits at C came in from on link A. So we really needed them to have different circuit identifiers so we'd be able to distinguish them. We have, one's known by 5 and the other's known by 2. So we couldn't have called them both 1 going out C from A's table, because that would have resulted in confusion at C. C wouldn't have been able to separate these two circuits, but they have different numbers, so it can. Now we send it onwards to E with a circuit number of 2. E, when it receives it from C with a circuit number of 2, sends it on to F with a circuit number of 2, and so forth. They still have different numbers, so we've distinguished these circuits. Okay, so that's virtual circuits. Here's a cleaned up version, and hopefully I've got everything right there. You can check that I got all the numbers right and work through it yourself. Okay, we all hear about datagrams a lot because that's what IP is all about. But I'm also here to report to you that virtual circuits are alive and well. Some of you might have heard of a technology called MPLS, multi-protocol label switching. This is a virtual circuit-like technology which is widely used inside ISPs. The way it works is that ISPs set up circuits inside their backbone from different ingress points to different egress points. So across their network they set up all of these circuits. By doing this, they can carefully control the path through the network and, separate traffic in different circuits and handle them differently. It allows them better control over their network. This means, by the way, that when the packet comes in to the network, then the ISP network, since it's now using circuit switching, is going to need to add this MPLS header to the packets. So you can see a packet, here's an IP packet, came in, and what happened inside the ISP network is we added this MPLS header. That header, what's the most important part in it? The label we talked about. The label is this circuit identifier, which is going to tell routers inside the ISP which way to go. So this packet will then follow all of the labels to follow the circuit. It will eventually get to the other side of the ISP, and when it does, all of this MPLS header and the PPP link layer header are going to be stripped off, and will then be left with the IP packet, and we can then send that onwards to internet-style routers that understand IP as datagrams. I'm not going to go into more detail about MPLS. You can look at it in your book. If you want to know more about how ISPs work in detail, it is worth finding out about, although it's a bit of an advanced topic for our course. And finally, we're able to, now that we've seen these two different alternative service models, to draw a bit of a comparison between them. So just on a bunch of different issues, you find that datagrams and circuits behave a different way. This is actually a good way to check your understanding of datagrams and virtual circuits. So let's go through them. First issue, a setup phase. Well, for datagrams, a setup is not needed. You just make your datagram packet, throw it into the network whenever you like. On the other hand, for virtual circuits, a connection setup is required. Router state. What do routers need to remember? Well, with datagrams, they just need their table of how to get to different destinations. With virtual circuits, they actually need to remember more. For every different circuit or connection through the router, they need to remember what to do about it. So you might have a lot of different circuits ongoing at the same time. Addressing. Datagrams carry the full address, an IPv4 address, say, of 32 bits, whereas a packet might carry a short label, 20 bits or less, for 20 bits for the case of MPLS. Routing. Routing essentially happens on, you have to do the work for every packet, so it's on a per packet basis for datagrams. The routing for virtual circuits is really done when it's set up, and after that we're just sending packets down the circuit, however it is. So there's a chance to amortize work here across a whole circuit full of packets. Failures, on the other hand, well, in datagrams, failures are actually easier to mask because we're not storing any information in the network about a circuit and how to handle it. With virtual circuits we are, so if the router that holds that state blows up, we're kind of stuck, we've lost something and we have to scramble to do a lot of work to repair it. So in theory, datagrams should be easier to mask failures in than the virtual circuits. Quality of service is the other way around. With datagrams, every packet is handled independently. So it's hard to add quality of service because quality of service is usually not something that applies to an individual packet. Usually it applies to a group of packets, like all of the packets in a video conference, for it to be useful, for example. With virtual circuits, it's easier to add because we do have this identifier for all of the packets in a circuit. We might have one circuit for the whole video conference, for example. Okay, so now you know about these two different models, datagrams and virtual circuits, and we're going to dive into the datagram model in lots more detail as we go through IP. G'day viewers. In this segment we're going to talk about internetworking, or how to combine multiple networks together into one larger network. So internetworking, or connecting all of these different networks into a single larger network, is difficult because the networks we might want to connect might be very different in terms of how they operate internally. They can just be different in many ways. I'll go into some in a moment. And what we would really like to do with internetworking is to paper over these differences so that we're able to connect from hosts on one network to hosts on another network as though it was a single network. That sounds kind of hard. It is hard. It doesn't always work. What we'll do to learn about internetworking is we're going to essentially look at IP. IP is a case example, if you like, a case study, but it's the most extensive case study around, and it has a lot of experience with how to combine different networks together, because IP, of course, is the protocol that grew up into the internet that connects all of the different kinds of networks today. So how might networks differ? If we're going to interconnect them, we need to understand some of their differences. Basically, they can differ in a lot of ways, and we're not going to be able to resolve all of those ways. I talked about, in an earlier segment, for instance, different kinds of network service models. Suppose you have a network service model using datagrams in one network and one using virtual circuits in another network. Imagine combining these. It's a little like combining the post office and the telephone network. It's not clear that would work very well. Different networks might have different kinds of addressing, since they'll normally be designed by different people. So they might have different kinds of addresses. So it's not clear that we can even write the different kinds of addresses in the right place in other networks. And there may be many different features in these different networks. They can range from large to small. A fairly large one, for instance, might be quality of service. Imagine if one of the networks has multiple different kinds of qualities of service. Maybe it has regular packets and packets that are priority packets, which should be afforded ahead of regular packets. And another network doesn't, it just has basic service. How are we going to combine these networks and still honor the quality of service arrangements of the one network that uses quality of service? It's not clear. Smaller examples of a difference might be that different networks can typically handle packets of different sizes. Is this going to be the case? Yes, it's the case all of the time for technological reasons. Different kinds of link layer technologies can handle packets of different maximum sizes. This seems like a small mundane detail, but even this detail actually turns out to require a lot of work from the architecture to deal with, let alone larger things like networks that have different kinds of quality of service or security. The job of internetworking is to hide all of these differences across networks with a common protocol. If you think that sounds kind of tricky, you're right, it is. Just to give you an example and sort of get into the flavor of how we might connect these things, I'll talk about connecting datagram and virtual circuit networks as an example. So suppose that you have a source sending to a destination. The source is on a datagram network. The destination is also on a datagram network. And here in the middle, I put a virtual circuit network. Oops. Just to make things a little tricky and bring up some of these issues. So let's imagine what's going to happen when you want to send from this source to this destination. We have the packet here on the left. So first of all, you'd need to be able to write the destination address in this packet, even though the formats might be different because one's on 82.11 and the other's on Ethernet. Suppose we could do that and we send this packet into the network. In the datagram network, it will be forwarded using the destination address all the way through a router at a time until it reaches the virtual circuit network. At that point, something needs to happen. This individual datagram needs to be mapped to the right circuit and it then needs some other identifying information that it didn't have, the circuit identifier, slapped on it, so that it can then go down this circuit, and that circuit will take it all the way maybe across the network, if in our case it's going across. At the other side, we're back on a datagram network, so we can forget about whatever virtual circuit it came from. I've described the transition here as a bit of a bump in the road, because suddenly you have to do a lot of potentially unusual things. For instance, this circuit needs to be set up. If it wasn't set up ahead of time, then we would need to hold the packet and wait while setting up a circuit. That's a bit of a daunting proposition because packets can arrive fairly fast, and so in MPLS, for example, the circuits are already set up ahead of time. Even so, we'll have to have some sort of special table to look up how destination addresses, well actually it's more than destination addresses, it's how packets from a certain source to a certain destination should be mapped to circuits, virtual circuits that go across the ISP network. So we'll have to do that at the ingress, and at the egress we'll have to take off the virtual circuit information and so forth so that it can go into the datagram network. So you can see that this adds some amount of complexity. Well, internetworking is a topic that's been around for a fair time. In fact, it was pioneered by Vint Cerf and Bob Kahn. You can see their pictures here. These two are widely credited as being the fathers of the internet. They began working on internetworking in 1974. Internetworking is what really led to both TCP and IP. The early internetworking protocols kind of combined some of these functions, and it was only later that it was divided into TCP, transport layer functionality, and IP, the network layer functionality for datagrams that we're looking at now. Their work tackled all of the problems of interconnecting these networks, and really in some ways their key insight was that of internetworking, that they would find some way to connect all of these networks. Instead of, for example, mandating that a single link layer technology, a lower layer network technology be used. If you only had that single lower layer network technology, it would be fairly easy to grow larger networks because we wouldn't have to deal with all of these differences, like some networks use virtual circuits but others use datagrams. However, if you've been around the block more than once, you'll realize that mandating a single network technology is something that would never have worked. There are many different reasons, technical and non-technical, for using different networking technologies. And so it's very much to our advantage if we can have some way to combine them. That's what we do with internetworking and IP. This slide here is actually one from one of our early lectures. And I put it up just to remind you of what sort of happened with IP. IP has been this layer to which we want to put all different networks together. And so the different link layers and transport layers all essentially conform to IP. And IP, because connecting these networks is so valuable, has become the narrow waist of the internet, as it's called. It's shown to be narrow here because there's somewhat of an explosion of link layer technologies and different applications. Both the link layers go below and the transports and applications go above. And IP is the glue that's really holding all of this together. So these days, if you come up with any application or networking technology, there's great pressure for it to conform to IP. There was less pressure, I guess, in the early days as IP essentially emerged, as all of the different networks sort of worked out what they would have to do to be able to connect together. A result of a lot of that pressure is that IP really is forced to become something of a lowest common denominator service. If you think about it, just imagine for a moment this hypothetical case. Suppose that you have two networks and one of them has good support for quality of service, priorities or different priority levels, and the other has nothing. What's going to happen if you internetwork them and combine them together? You can combine them, sure. Let's say you could send a packet, a normal priority packet, from one network through to the other network, and it will just go through. But it's going to be difficult for you to preserve this quality of service feature, since inside the network that doesn't support quality of service, you have no easy way to distinguish between the high quality and the low quality of service packets. As a result, IP tends to be pushed to be the kind of lowest common denominator. It asks very little of the lower layer services, essentially the ability to deliver packets to where they're sent. That's it. And as a result, because it asks very little of the lower link layers, it's only able to provide it gives very little extra to the higher layer services. Essentially, it's a glorified way to deliver packets through the network. If applications want more than that, well, they're going to have to build transport layers and application processing of their own to provide higher level services which do more for us. But this approach, nonetheless, of having the lowest common denominator service proves to be very useful because it does allow this glue to essentially combine everything together into one internet. Well, here is the picture of the IPv4 header and a payload following it. Often the best way to find out what's going on with a protocol is to look at the format of its messages because they tell you the information that's been exchanged. This picture here shows us what is going on inside the IP, inside all IP packets, and it really focuses on the IP header because that's where the action is. This last bit here, payload, this is just the data that the packet is carrying. So if the higher layer is TCP, this would be a TCP segment. Now these diagrams, you might not have really seen them much before. This diagram shows us the order in which information is put in a packet. You might imagine that it's difficult for us to draw a packet as a very, very long yet thin line that goes from left to right. Our page isn't wide enough. So instead, it's common to see diagrams drawn in this format. You read it from left to right across one layer and then the next layer going down. So left to right, top to bottom is the way we read all of these bytes. This really corresponds to the one long line. So you can see here what this means is we begin at the top left with it says the version field. And this diagram is 32 bits wide. So every time we go across, that's another 32 bits. Well, let's look at a little bit of what's in the IP protocol. Most of our looking we're actually going to do in the subsequent segments. So first of all, the IP header here includes various fields which meet pretty straightforward needs. They're interesting to look at, just so you can know all the details, but I'm not really going to spend any other time than this slide to go into them in detail. They're things which it's fairly obvious that we'll need in some ways. There are length fields. There is a total length field here which tells you how long the overall datagram is, and this one, IHL, the Internet Header Length, tells us how long the header is, so down to here before the data starts. There's also a checksum here, just provides a little bit of way to check the reliability of the different header. There's a version number. This version number, since this is IP version 4, that should carry 4, and a 4 there really tells us that the rest of the format is what we expect for IPv4. One that might be a little interesting to you is there's a protocol field. This tells us the higher layer protocol that's inside IP, like for instance TCP, if the payload is carrying a TCP segment. If you remember way back from protocol layering, this protocol field here is the demultiplexing key, which allows us to pass the contents of the packet to the right higher layer. Okay, so there are all of the sort of the scaffolding fields, which really hold everything together. Here are some other fields, and what I'm going to do now is just give you a quick tour to mention what fields are in there. We're actually going to go through how many of these fields are used in lots of detail in the following segments. So in this segment, I'm really just going to point them out to you, and then we'll go through them later. A very important part of the Internet header are these fields, the addresses. There's a source address and a destination address. Since the network layer of the Internet uses datagrams, every packet that's a datagram needs to include a full address on it so that the routers will know where to send it. This layer of addressing is a new layer of addressing which is not the link layer addressing like an Ethernet address. It's a layer of addressing above it. This is a new network layer address. And in IPv4, 32-bit addresses are used. What we'll go through in some of the next segments are how routers forward packets based on these addresses. And then there's a bit of other information in the header. You can see here that there are several fields which are actually used to handle the relatively simple sounding problem of networks which transit packets of different sizes. So, actually Ethernet and 802.11, for instance, can carry packets of different sizes. The largest packet on 802.11 is too big to fit through an Ethernet. So IP includes machinery that uses these different fields to handle this problem, including breaking packets, large packets into multiple smaller packets, and then reassembling them on the other side. So we'll look at some of this machinery later. And there's really very little that's left in the header. There are a couple of fields here, which we'll come to eventually, a fair bit later, some number of units further on. One is a differentiated services field. This has to do with quality of service. So IP is sort of being retrofit to provide some different kinds of quality of service. And we'll talk about that near the end of the course almost. Something we'll get to sooner is there is a time to live field. This field is used in conjunction with the error reporting protocol called ICMP. It's actually used for traceroute. We looked at traceroute and that uses this field quite heavily. So in a few segments you'll learn how that works. Okay, so we've now looked at the IP header and we've heard about some of the different fields. What it's time to do in the next segments is to go into some of the functions that are behind those fields in detail. G'day viewers, in this segment I'm going to talk about IP addresses and IP prefixes. So I've talked a fair bit about packets, and we know packets carry addresses and so forth, but I haven't really gone over any of the details so far of those addresses inside packets. That's what we're going to do now in this video as we take a deep dive and look at IP addresses. And as well as IP addresses, I'll also tell you about an important concept called IP prefixes, which are really blocks of addresses. And just a quick note here, what I'm going to cover is for IPv4, the version of IP which is mostly deployed in the current internet. It's going to change when we get to IP version 6 later on. So IP addresses. IPv4 uses 32-bit addresses. When we get to IPv6 later on, we'll see that IPv6 uses 128-bit addresses, a much larger address space. The reason for that is that the 32-bit address space is near exhausted. But for now, we'll just concentrate on those 32-bit IPv4 addresses. These addresses are written in what's called a dotted quad notation. They're 4 8-bit numbers separated by dots. Because, of course, the 4 8 bits, that's where the 32 bits comes from. You can see here I have binary representations where all of the bits are spelled out in the groups of A's, B's, C's and D's, each 8 bits long. And on the other side are the decimal numbers that they correspond to. So we might be able to write out a number in binary, but we're not going to want to work with it in that format. It would be tedious. Instead, we'll convert the 8 groups of bits into the decimal equivalent and write them in this dotted quad notation as 4 decimal numbers. They're going to range from 0 to 255 since they're 8 bits, each number separated by dots. So let's do an example. Here's the example here. Now, we have this big long binary string, wow, and we want to write it in our dotted quad notation. So what's it going to be? I'm going to start at the end, and this last number, all zeros and a 1 bit, well, that's the equivalent of the decimal number 1, so there's a 1 at the end. I just know that because the 1 is in the 2 to the 0 position. Above that, all zeros, well, that's also the decimal number 0, that's not too hard. Okay, now we have to do a little bit of work for the one above it. We have a 1 bit on in the 2 to the 0 position, that's a 1. In the 2 to the 1 position, that's a 2. The 2 to the 2 position, a 4. The 2 to the 3, 8. And the 2 to the 4, 16. So if I add up all of those numbers, 16 plus 8 plus 4 plus 2 plus 1, I will get 31. So this is the binary representation of 31. And going on over here, this has the 2 to the 2 bit and the 2 to the 16 bit. Set, so when you add them up you get 18. So that's the binary representation of 18. You might be a little rusty or unfamiliar with all of this, and it can take a little while to get started, but you can usually work through binary addresses. It just takes a little getting used to. That's an IP address. I also want to tell you about this concept called an IP prefix. IP addresses are allocated in blocks called prefixes, and that's what routing in the internet is going to use. That's why we're going to talk about prefixes. Well, what is a prefix? Well, it's really just this block of IP addresses, but it's a block that's structured in a specific way. All addresses in an L-bit prefix are going to have the same top L bits. So you can see here, here's L, here's my prefix length of L. L can range, well, I guess from 0 up to 32. Although commonly it will have values such as 16 or anywhere from 8 to 24. Now if I have the prefix length of L bits, that means that the top L bits in this number are going to have some fixed value And the last bits here I can just write X's here because they can take on any of the different possible binary patterns. So this means that since the top the L bits are fixed and there are 32 bits overall, we have 32 minus L bits at the end that can vary. So there are 2 to the 32 minus L addresses in an L bit prefix. For instance, a 24-bit prefix is going to have 8 bits left over, so there are 2 to the 8 or 256 addresses in a /24 in a 24-bit prefix. These addresses, by the way, are also going to be aligned on a 2 to the power of 32 minus L boundary. So prefixes with 2 to the 16 addresses in will start on a multiple of 2 to the 16 rather than any arbitrary binary position. This is just like talking about numbers that are powers of 10 aligned on multiples of 10. Sorry, numbers that are multiples of 10. 10, 20, 30, 40 and so forth. And they start on multiples of 10 rather than 22, 32, 42 and so forth. Okay. We also want a way to write IP prefixes. How are we going to do that? We need a notation. Well, we're going to use this IP address /length notation. The address will be the lowest address in the prefix written in our familiar dotted quad notation, and the length at the end, the /length, will be just the length of the prefix in bits. So for instance, 128.13.0.0/16 means it has a 16-bit length prefix, so that means the last 32 minus 16 or 16 bits will be free. So the addresses will range from the bottom address, which was given as part of the prefix, to the same address when I turn on all of the bottom 16 bits. So you can see when I do that, I get to 128.13.255.255. This means that a /24, and that this is how you pronounce something like this, or a /16 for instance. As I said previously, a /24 will have the last 8 bits free, so it'll have 2 to the 8 or 256 addresses. Similarly, a /32 really means one address. Let's do an example to see how all of that works. So here is a number written out in binary, except I've X'd out the last bits because they can take any value. How will we write that in our notation? Well, we have the last 8 bits are free, so the first 24 bits are fixed. So that means this is a /24 prefix. Okay, and to come up with the value, well, I'll set for the lowest address, I'll set all of the X's to 0. So we have .0, above that is 0, and above that, well, I have to do my binary to decimal conversions, but luckily I'm using the same examples as before. So you might recognize that as a 31 and an 18. So this prefix is 183100/24. Let's do another one. Okay, this other prefix that I talked about above, 128.13.0.0/16. Well, we said that the first 16 bits are fixed, the last 16 bits are free, so I'm going to write X's for them. We sort of fill them in as zeros just to write the lowest address in the prefix. Above that, I have 13. I want to write that as binary. Well, let's see. 13 in terms of powers of 2 is 8 plus 4 plus 1. So I'll turn those bits on and I'll turn the other bits off. 1 on the 8-bit, 1 on the 4-bit, and 1 on the 1-bit, and everything else is 0. So this was 13. And I also want 128 for the top bit. It sounds a little harder, it's a bigger number, but 128 is actually a power of 2. That is 2 to the 7. So the top bit's going to go on, and all of the other bits are going to go off. And there we have it. There's the binary representation of that prefix. There's a little more terminology that goes with prefixes too that we need to know. We can talk about either more specific or less specific prefixes. More specific means that the length of the prefix is longer. That is narrowing the range of addresses because we're pinning down more of the bits at top. So a more specific prefix will have a smaller number of IP addresses. Similarly, a less specific prefix has a shorter prefix. It allows more of the bits to be free, so it will have a larger number of IP addresses. And I'm spelling this out because it's a little counterintuitive at first. But you can see on this diagram, as I go to less specific, the prefixes get shorter, but the number of addresses that can be within the prefix gets larger. Similarly, as I go to more specific, The length of the prefix gets longer, it's been more specific, but the number of addresses inside that prefix gets smaller. So that's IP prefixes. Now you know about IP prefixes. There's a little more I can tell you about IP addresses though, and I'm going to start with classful addressing, which was used historically. So we use IP prefixes today. Originally, IP addresses came in fixed size blocks. So the prefix length, if you like, was fixed and pinned down as part of the address. In particular, Class A addresses that are shown here had the first 8 bits were used for the network portion, the last 24 bits were free, and Class A addresses were identified by a leading 0, and then you could set the remaining 7 bits of the network mask to whatever value for the different Class A addresses. So you can see actually that a Class A address corresponds to a /8 since only the top 8 bits are fixed. So there are a lot of addresses in a Class A address to the 24, that's large. Similarly, if you do a little bit of work, you'll see that the Class B and Class C addresses here are equivalent to our /16 and our /24 prefixes. Although, of course, the top bits are constrained in these patterns, 10 and 110, so we can identify the Class A, B, or C addresses just from looking at the top portion of the bits. Now, addresses still have these top bits that identify whether they belong to a Class A or Class B or Class C networks, but the classes themselves are ignored. If you like, the prefix notion that we use today is a generalization of these classes which is used instead. Now, instead of only being able to have /8, 16, and 24, we can have prefix lengths in between and so forth. And that's why the top bits of the address, they're left in there for compatibility, but they're ignored otherwise. There's also one important distinction for addresses that will come up as we use them in the internet is between public and private addresses. So far I've been talking about public IP addresses. So for instance 1831, here I'll use .0.1 is a public IP address. Public IP addresses are any address which is a valid destination address and can be used on the global internet. So you can send packets to that address and from that address. Well, before you can use a public IP address, you've got to get one from somewhere. You can't make it up. So they need to be allocated to you. And I'll talk about that in a minute. The problem with this allocation is they're mostly exhausted. We've almost run out of them. That's why we need IPv6. On the other hand, and this is the distinction I want to draw, there are also a small number of what are called private IP addresses. Private IP addresses are addresses that you can use freely without anyone giving them to you in your own private network. And that might be a small home network or a small company network. You can just assign these addresses to computers. You might have seen some of these addresses already. Anything in Net10 or often home networks, for instance, use 192.168.0.0/16 as their prefix. So these are private addresses, but of course, pretty much any network, even a private network you make, you're going to want to connect it to the public internet so you can talk to all of the computers out there. To do that, you will need to get a public IP address, you'll get that from your ISP, and you'll need to use a technology called NAT to translate, network address translation, to translate between these private addresses, which are only valid within a private network, and public addresses, which can be used on the public internet. We'll get to NAT in a later segment, and I'll explain how it works. For now, you should mostly think in terms of public IP addresses. When we're talking about addresses on the open internet, that's what we mean. Well, to complete the picture, let me finally tell you where these addresses come from. The allocation of public IP addresses follows a hierarchical process. In the beginning, on the left-hand side of this diagram, all addresses belong to a body called IANA. That's the Internet Assigned Numbers Authority, something like that. And what IANA does, it owns all of the address space just de facto. It delegates different portions of the address space to all of these regional bodies. These are called RIRs, Regional Internet Registries, and they have different names. There's ARIN is the name of the Internet Registry, the RIR that serves the US and Canada, North America, other places, maybe Antarctica, something like that. There's APNIC for the Asia Pacific. Actually, maybe they serve Antarctica. RIPE, LACNIC for Latin America, AFRINIC, and so forth. These are all regional bodies. What these bodies then do is the regional bodies then delegate IP addresses to companies in their regions. The companies apply for these IP addresses and they get them. And then finally, once your company has an IP address, it assigns those addresses to computers in its network, either its customers or in the case of an ISP, who then assign them to their computers. Or in a small enterprise, you would assign them directly to your computers. This is done with a protocol called DHCP these days, and we'll get to DHCP again in a later segment. Okay, but now you know a lot about IP addresses. G'day viewers. In this segment we'll talk about how routers forward packets. So as we get into our topic, I do want to remind you of the distinction between routing and forwarding. Forwarding is the process of handling a packet when it arrives, sending it on its merry way. Routing is the process of computing all of the paths through the network so that you'll be prepared later on to forward packets because you'll know which way to send them when they arrive. Now, we're just looking at forwarding right now, and really I would also flag that we're going to be looking at how IP does forwarding. So this is really learning about IP rather than the more general topic. As for routing, we'll get to that much later. So for now, just suspend disbelief and imagine that routers have all worked out the paths through the network, and we're just looking at how routers actually handle packets when they arrive. Before we get into the meat of that topic, let me just recap where we were at in the network layer. We really had several goals for our network layer to go beyond what we could do in the link layer with simple switch networks. We wanted to be able to scale to large networks. That's what we're getting to in this video right now, seeing how we use the hierarchical structure of addresses to scale. We also wanted to do other things, support diverse technologies. I've talked about internetworking, I'll talk a little more about that later. And we also want to use the bandwidth of the different links in the network well. This is covered by different routing formulations, and we'll get to that much later. So, let's look at how we scale to large addresses with IP forwarding. Well, without much ado, I'll simply tell you that we use IP prefixes to our advantage to achieve scaling. And here's how it works. The key observation here is that all of the IP addresses on one network belong to the same prefix. That means that in our forwarding table, what we can do is simply put down one entry for the entire prefix. And that way, if we encounter any packets that are destined to IP addresses within that prefix, we'll all send them to the same place, whichever way we should go for the prefix. Here's an example of that, and you can see here is a forwarding table for a particular router here, this router here. And the forwarding table only has a couple of entries, but they're prefix entries. So the first prefix here, it's a /18, and the second prefix is a /22. There are different next hops, so there are different things you do with addresses in each of these prefixes. But both of these prefixes could cover a relatively large number of addresses, many different destination addresses that different nodes were sending packets to. So even though there might be a large number of IP addresses represented here, and you can work that out from the prefix lengths, we'll get to that in just a minute actually, you can see that the forwarding table is quite small. It scales well. Now, it's not quite as simple as I'm making out for IP forwarding, and the reason is this, that prefixes in the table can overlap. If you just imagine a very basic notion historically with classful addresses, the blocks didn't overlap. But with prefixes, you can have prefixes of different lengths and they can overlap one another. To resolve this, we use a forwarding rule called the longest matching prefix rule, which I'll tell you about. And this rule is able to combine the hierarchy that we get from using prefixes with a little bit more flexibility, even though the longest matching prefix rule is a little more complicated than a straightforward table lookup. The rule is simply this. For each packet that you're trying to forward, you look at its destination and you find the longest prefix entry in the table that contains the destination address. That is going to be the most specific entry. This is why it's called the longest matching prefix, of course. So we might find in our forwarding table that that the destination address fits within several different prefixes we have. We want the most specific of those. And then we'll simply forward the packet according to the rules for the next top router for that most specific prefix. That sounds pretty simple. Let's work through an example just to see how these prefixes can overlap and what it means. So here's the same table from before, with the address ranges, and I'm going to show them on this figure. Here, IP addresses go up from all 0 at the bottom to 255.255.255.255 at the top. So let's put some of the addresses on here and show where the ranges are. Okay, so this first prefix here, the bottom address is 192.24.0.0. That's down here. That's the lowest address, and so I just drew that in here. The next prefix in the table, its bottom address is 192.24.12.0. So it's higher, and I've drawn that here. We don't have the top addresses yet. Let's try and calculate them. Okay, so for the /22 prefix, that fixes the top 22 bits, leaves the bottom 10 bits free. So we will calculate the top address by taking 192.24.12.0 and turning on the bottom 10 bits. Well, if I do that, I'm going to turn on the bottom 8 bits for sure. That gives me the 255 up here. And I'm also going to turn on the bottom 2 bits of the next one. That's equivalent to adding 3, so we go from 12 to 15, and I end up with 192.24.15.255. So you can see for the /22 prefix, I've colored that with the pink diagram, and I've made it longer because it's a more specific prefix. What about the top of the other one? So for this other prefix, 192.24.0.18, well, this will have 2 to the 14 addresses in it. The last 14 bits are going to be free. So I've got to turn on the last 14 bits. So what will I get when I do that? Well, I started from all zeros and I turn on the last 8, I get 255. Then I've got to turn on another 6. So it's going to be 0, 0 and then all ones, and then 6 ones. If you convert that from binary to decimal, you should get 63. So the top address will be 192.24.63.255. This is the grey block where we forward to D. This is a much bigger block. And the other pink block is within it. And I've drawn this to be not as wide because it's a less specific address. Well, anyhow, this is a representation of our forwarding table. Let's try and use it for forwarding now. So I have several addresses here. Number 1, number 2, and number 3. Let's see where they go. The first one, number 1, 192.24.6.0. Well, where is this on our address range? Well, it's somewhere in here because it's below 12.0. So this is number 1. So guess what I want to do to forward number 1? It's in this grey region here, so I'm going to forward it to D. Okay, what about let's do the last one. What about number 3? 192.24.54.0. Where is that? Well, it's above .15.0 and it's below 63.0, so it's going to be in here somewhere. Number 3. So number 3 is also going to go to D. Okay, the middle one, well, you can probably guess what's going on here. It has a .14.32, so that's actually somewhere between the lower and higher address of B, so it's going to be in here. Number 2. Number 3 was in here somewhere. So this one will go to B. So you can see how we use the forwarding table to do this. And this is the longest matching prefix algorithm. Okay, so there's one other thing I can tell you about routing and forwarding, and how we scale it using a little bit of hierarchy and so forth. There's actually a distinction in the internet between hosts and routers. So in the internet in particular, routers do the routing. So hosts don't do the routing. Hosts just send packets to routers. That might sound a little obvious, but that's actually a little bit of a choice. In particular, what I'm trying to say here is we place the responsibility of knowing which way to send packets for all IP addresses on routers. They need to do the routing, so they'll be able to forward to all different destinations. Hosts, on the other hand, are on a local network, so they might be able to reach hosts on their own prefix, but they send any remote traffic that's off the prefix to the nearest router. So hosts really don't need to participate in routing, they just need to know the nearest router. And you can see here, the host is saying, okay, if it's a local, I'll send it on my network, but if it's not, just send it to the router, because the router will have to work out which way to go, and it might be different ways for all sorts of different IP addresses. The reason that I'm bringing this up now is that this distinction between hosts and routers fits very naturally into our longest matching prefix rule. In particular, we can formulate a forwarding table for hosts which has this kind of behavior. And we just use it by using a default route to 0.0.0.0/0. That might sound a little odd, but a forwarding table for a host will look something like this. It will have the network prefix that the host is on, so a host will need to learn that. And if you're sending to a destination in that address, it's to a local host, so you just send direct to that next host because it's on the local network. Then we have this funny entry here, 0.0.0.0/0. Well, what is this? Let's think about it. It's a 0 length prefix. That means that the remaining 32 bits, that's everything, can be free. So this is really an address meaning everything, all IP addresses, is encoded simply using our prefix notation. And the next hop for that is just send to the router. So that way we'll let the router worry about it. So our longest matching prefix rule allows us to encode this fairly simply and directly. You can see here what I'm getting at is the flexibility of the longest matching prefix rule. In particular, we can use longest matching prefixes in a couple of different ways. We can add less specific entries to a forwarding table to provide a kind of default behavior. You saw that with hosts, send it to the router. But we might also use it for routers within a network. For instance, you might have an enterprise network and routers in it might know which way to go for all sorts of your different networks. But for other IP addresses which are outside of your network, you might have a default rule saying send it to your ISP router. And your router could simply use the default rule to get packets out of the network. Similarly, instead of providing defaults, we can also provide special case behavior. You might take a particular addresses and request by using a more specific prefix that they get special handling at a router and they be sent a different way than they would normally. This might be for reasons of performance. Maybe this is a voice over IP call and you want to route it over a low latency path. Or it might be for reasons of security. This might be suspicious looking traffic and you want to send it along a path to a special box to inspect all of the packets more carefully and see if there's a security problem. This could be for any number of network management reasons you might like to come up with. The point is that we get a certain degree of flexibility from this longest matching prefix rule and we can use it to our advantage when managing networks. Well, the flip side of this is to talk about the performance of the algorithm. How well does longest matching prefix perform? Well, in terms of table size, it performs very well. We use hierarchy to get a nice compact table. And by using prefixes of different sizes, we can actually get quite a compact table. Note that this depends on people using addresses which have a reasonable prefix length, or actually rather small prefixes, which contain a large number of addresses, so less specific prefixes. Good grief, that's all I'm trying to say here. Actually, if everyone uses very specific, more specific addresses, we won't get as much compaction as otherwise. And another aspect of performance is just how fast the lookup operation runs at routers. It turns out that the longest matching prefix rule is computationally more complex than a simple table lookup. Actually, it can be quite so in some cases with strange overlapping entries. This was a concern when we were trying to build routers in the early days and make them fast. Today it's not really a performance concern. You can just get silicon which will do this and you don't need to worry about it. So I wouldn't worry about it too much if I were you. And finally, I've really just talked about addresses for forwarding. I do want to point out that it's not all about addresses. Here's our picture of an IP header again, and you can see the addresses were in here, but I've shaded in pink everything else in the header, and there are a lot of other fields. What do all of those other fields have to do with forwarding? Well, there are many other small aspects of forwarding. We've touched on some. Well, actually, I'll tell you about others in the future. And let me just briefly mention a few. You might have noticed there's a TTL field here, a time to live field. This value is decremented as you go through routers so that if it hits 0, you can throw away the packet. The reason for this is to protect against routing loops. What if there's a mistake and packets are going round and round in a circle? They can do this very fast and clog up the network. There were also other fields there, such as a checksum. A header checksum is used to just check that the header values are all okay to provide a little bit of added reliability. There are fields in there for fragmenting large packets. If the packet is too large to send out to the next link, we're going to break it into pieces. We'll cover some of this in a segment that's coming up. There are other fields in there to be able to deal with congestion. The network may be congested, and these other fields help us to send congestion signals to hosts. And there's other functionality to be able to generate error messages that goes hand in hand with IP. This is ICMP that will help us manage the network. We'll get to that later. And there are even other various optional fields which I'm not going to cover in any of these videos. If you're interested in all of this, you can look in your text for more information, a little more about IP. But we will get to some of the more important aspects quite soon. G'day viewers. In this segment we'll talk about ARP and DHCP, two key helper protocols that work with IP. Okay, so the astute viewers among you might have realized that there are a few gaps in my explanation of IP forwarding. In fact, we need a little bit of extra functionality to make things work, and in particular to answer a couple of questions. First of all, nodes need to be able to get an IP address from someplace to use as a source or a destination. And we'll look at how the DHCP protocol does this. Next, even to be able to send a packet across a link, we need to be able to fill in both IP addresses and link layer addresses. And that raises a problem of mapping between the two, going from a destination IP address to what the link layer address is. There's a protocol called ARP, which takes care of this that we'll look at. Both DHCP and ARP are actually pretty good examples of just the real-world kind of glue you would need to make designs work. They're very necessary for IP to work in practice. DHCP provides a little bit of IT support, if you will, whereas ARP provides a bit of glue between all of the layers to join the network layer to the link layer. Okay, so let's look at those questions. The first question here is getting an IP address. So imagine that you're a node, you've just been powered on, you wake up for the first time. You don't know very much. In particular, you'd like to know what your IP address is, what the IP address of the nearby router is, what network you're on, and so forth. One thing you do know that I'll point out now is that you know your Ethernet address. The reason you know this is that the Ethernet address is set on the hardware NIC, on the network interface card itself. So when a node wakes up, if it's attached to Ethernet, it usually knows its Ethernet address, but it doesn't know its IP address. So let's look at how we solve that problem. Well, it could be solved in a couple of different ways. Now, in the good old days, you would simply set up an IP address on a computer by manually configuring it. So someone would fill out a configuration file. Actually, this was really not that long ago, in the 90s. You would do some of this. So you just add the information by hand. This, you might wonder why this is necessary. For Ethernet, we simply have the address on the NIC so that no one has to encode it later on. For IP, however, the address you have depends on where you are in the network. And that's because, remember, to be able to forward efficiently, we required that all nodes that are sitting on the same network belong to the same prefix. So where you place the computer is going to affect its IP address, so it can't be set at the factory. The second alternative, and the one which of course we're going to follow and use today, it's very popular, is to come up with a protocol for automatically configuring the IP addresses of new nodes as they wake up. This protocol is called DHCP, Dynamic Host Configuration Protocol. And effectively what it's doing is shifting the burden from the user of a system, you and me, to some of the IT folks who help manage the network. If you like, in the manual configuration days, everyone was their own IT for all of their different computers. So let's learn a little about DHCP. I've already told you DHCP, it stands for Dynamic Host Configuration Protocol. It's been around since about 1993. It's now very widely used. Its main function that we're going to look at here is to provide a computer with its IP address. Actually, it doesn't give it to you permanently, it leases you this IP address. So when you wake up, the DHCP server will give you an address and say, you can use this for the next day. The addresses really belong to the network, so the DHCP server can give them out to other nodes over time. Now, DHCP also provides a lot of other parameters too. It's a general configuration parameter for hosts. It's quite useful, not only an IP address, but other things we would need to know to use the network. For instance, you might want to know the IP address of your local router, the network prefix you're on, so you can decide whether you're trying to send to another host on the local network or a remote host, as well as sundry other information that we haven't got to yet, but you could imagine would be very useful, such as a time server to be able to set your clock, And a DNS server, that's to be able to translate host names like www.cs.washington.edu into the IP address. Here's the protocol stack for DHCP. DHCP actually runs as a client-server application between the client that's on your machine when it's woken up and it's trying to talk to the network, and the server, which is running somewhere on the network. It runs on top of UDP, you can see here on the stack, and it uses UDP ports 67 and 68 to identify itself. Actually, if you remember all the way back to the beginning of the course, according to this diagram, DHCP is an application. It's really one of the first applications we're going to look at. It's a little funny because from the network's point of view, it is an application. You could write DHCP using the socket interface and all of that sort of API we looked at, although the one for datagrams, not streams. However, from most people's point of view, DHCP is a protocol hidden in the system. They wouldn't necessarily think of it as something that's an application. So let's see a little more about how DHCP works. There's in fact one crucial issue that it has to solve, and this is the bit in some ways that's most interesting for networks. That's the bootstrap issue. So if your node is trying to contact someone to find its own address because it's just woken up, how does it know the IP address of who it should contact to ask its address? I mean, it's just woken up and it's not configured. If we could configure that, we could probably work out how to configure the IP address. So there is this bootstrap issue of just waking up and getting things done. Now, the answer is, when your computer wakes up, it doesn't know the IP address of the DHCP server that it's trying to talk to on its network. Instead, it uses broadcast communication. It sends a packet on the network that is a broadcast packet. The network will then deliver it to every host on the network. One of those will be the DHCP server. That host will realize that the packet's intended for it, and it will further process it and begin answering DHCP messages. The way you send a broadcast is it uses a special destination address. By convention, the broadcast address is made up here of all ones. So for IPv4, which uses 32-bit addresses, when you write down the all ones and express that in the dotted quad notation here, you see that's going to come out to 255.255.255.255. When we write the all ones in a different format, the format of an Ethernet address that's 48 bits, it looks something like this. The reason is that an Ethernet address is usually written as 6 chunks of 8 bits, and each 8-bit quantity is expressed as 2 hexadecimal digits, where a hexadecimal digit goes from from 0 through F. So F is the highest, it has all of the ones on. When you turn all of the ones on, the broadcast address on an Ethernet is FF, 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 FF. So there you have it. So broadcast is a key component of DHCP. Now that we know it uses broadcast, let's talk about what the exchange is. This is a timeline diagram, so time's going to go down the page as usual here. And we have a line here to represent the client, that's you, a computer that's just woken up, and the other to represent a DHCP server. Now these need to be within one IP hop of one another, so they're on the same network. I say here the same link, the same set of connected links. You could actually have switches in between them, and that would be just fine. So we're really like one IP hop of connectivity that's going across a series of links which are joined by switches, which is logically still one link. How does DHCP work? This is what the exchange looks like. First of all, the client sends a message called a discover. That's basically saying, hello, is there a DHCP server out there? I'd like to contact the DHCP server so I can work out what my IP address is. The DHCP server will then reply with an offer. That offer packet is essentially saying, hello, yes, I'm here, and you could use this address if you would like. If you want to use it, your host will then send a request saying, yes, I would like to take this particular address. And if that's okay, assuming it will be if you're picking the one that's just been offered to you, then the final step is that the DHCP server will send an ACK, an acknowledgement to say, okay, you've got it, now we're both clear on that. The acronym for remembering this is DORA, D-O-R-A. And let me see, yes, okay, I've probably got it right. Here's a cleaned up version of that. And I've noted that the first packet here, at least, often more packets in the exchange. The request packet, for instance, so the request packet 2 is broadcast. So it is sent to the IP address and the Ethernet address that's all ones, and so it will be received by this DHCP server, and it will also be received by all other hosts on the network. And they'll simply throw it away because they won't have a DHCP server running on port 68. Okay, so that's the exchange to get an IP address the first time. Once you've got an IP address, the more lightweight operation is simply to renew it. Remember, we said this is a lease, so a DHCP server might give you an address for a day, for 4 hours, for anything like that. Once that time period is up, you're going to want to get another IP address. What you usually want to do is not change your IP address, but keep the same address and say, yes, I'd just like to renew my lease. If that's the case, you can use an abbreviated sequence, just the last 2 packets in this exchange, the request followed by the ACK. The protocol is actually much more interesting if you'd like to look at it in detail. It supports, for instance, replicated DHCP servers, so that an organization can set up several DHCP servers, all of which run in parallel. And using broadcast communication helps us here. That's why the packets are often broadcast, because that way all of the DHCP servers can see what messages the clients are sending and coordinate themselves. But this is a little advanced for where we're at. We're just going to skip over that. I point that out in case you're interested. Okay. We'll move on then to the second problem. The second problem essentially was, how do you send an IP packet? To do that, you need to be able to craft the header, and the header has all sorts of addresses on it. Source and destination IP addresses and source and destination link layer addresses. Now, the question here really, if we're trying to send a packet to a certain IP address, we already have the addresses, is where do we get the link layer addresses to go with the frame to be able to send it over the local link? If we might have an IP address here, and a client might know that it's trying to send a message to a router with a certain IP address, but it still needs to make the packet with all of the addresses, including the link layer, and it might not be sure what link layer address to use. So let me just try and clarify that a little bit by drawing a diagram. So we now have a client trying to send, well, a node trying to send to another node on the same network. To do that, it needs to craft a packet. So here's a picture of the packet. You can see there's the payload at the end, but in front of it we have the IP header, and in front of that we have the link layer header. Those headers have addresses in, and I've just shown the addresses. You have a destination IP address. That's the target. We'll assume that's known because you've got to know somehow, if you want to send a packet to someone, you need to know their address. There's a source IP address. That's your address. Where do you get that? From DHCP. We just answered that question. Now we need to be able to make the link layer addresses on a frame to send something into the network. How do we do that? Well, the source Ethernet address, we can get that. That's on our NIC. Remember, we said these were configured at the factory. So you just sort of ask your NIC what its address is. But we also need this one here, the destination IP address, which is the right destination, the destination Ethernet address, the right address which corresponds to the destination IP address. Where do we get that address? The answer is that we get that address by using the ARP protocol. So let's talk a little bit about ARP. Here's the protocol stack for ARP. ARP stands for, if I didn't say this already, Address Resolution Protocol. So it sits directly on top of a link layer such as Ethernet. There are no servers involved here, so it's actually different than DHCP. Instead, since ARP by definition is going to help us send a frame to a node on the local network, we're going to essentially interrogate everyone on the local network and ask the person who has the right address, who we're trying to talk to just chime up and tell us what their Ethernet address is. So ARP is just going to ask the node with the target IP address to identify itself. Like DHCP, it's going to use broadcast to reach all of the nodes so that its message will go to the target node as well as everyone else. Here's how the exchange works. It's simpler than DHCP. We're still operating on the one logical link here, even if it's a series of physical links connected by a switch. So we can't go across routers with this protocol. In this protocol, we simply send a request, and then the request is broadcast across the network. Everyone will get it. The request is going to be looking for the Ethernet address that corresponds to a certain IP address. Whoever has that IP address will get the packet, say, oh, someone wants to know my Ethernet address, look up what their Ethernet address is, and send it back to them in a reply. So here's that cleaned up. And I've also shown you the sort of conventions for what these messages contain. The request usually is viewed as a who is message. It's essentially asking the question, who is or who has IP address 1234? That will go everywhere, including to the node with IP address 1234. That node address will send a reply saying, I do. I'm the one who has that IP address at my particular link address, and it's this thing here. So the node who's asking can then have the mapping between them, and it now knows the destination Ethernet address to use. So it can fill in the frame, send it, and we're happy. We're done with ARP. I'll just make a few comments. Both ARP and DHCP contain elements of discovery protocols. So these are protocols that help nodes find one another. They're very useful actually, and there are more of them. Some of you might have heard of ZeroConf, or if not Bonjour. The Bonjour protocol is Apple's implementation essentially of ZeroConf. These nodes help other nodes find one another for many reasons. Often it's to do with configuration, and so typically in these protocols they use the broadcast trick that we just saw, where a message on a link one logical link will be delivered to everyone on that network. So this is a good way to search for someone. It will get to the party you're intending. And you do this since, with this discovery protocol, you're trying to find a node. If you already knew it, you'd be able to send a message to it directly. But if you're just searching if it's there, nearby printers, for instance, this is how when you open your Mac, it might be able to show you nearby computers to connect to. They're all discovering one another with these protocols. So this is a very handy kind of glue, which is used very much in practice. Okay. G'day viewers. In this segment, we'll talk about the issue of packet fragmentation. So our topic here is really an issue that arises because of the heterogeneity of different networks. When we connect networks together, they might have different maximum packet sizes that can go through the network. If that's the case, you could send a large packet in one network and it wouldn't fit through in another portion of the network. We need some way to handle this issue. And in this video, we'll look at, a couple of different approaches. One is simply having routers inside the network split the packet up into pieces, each of which will fit through a link because it's not too big. And an alternative to that is having hosts discover what size packet will fit through the network. So let's just recap some of the problem here before we dive into the details of the solution. The problem, in a nutshell, is that different networks have different maximum packet sizes. You'll often see this referred to as an MTU, or maximum transmission unit. That's just a fancy way of saying the largest packet which will fit through this network. It'd be wonderful if we could just kind of mandate one single maximum packet size. Then everything would be simple. A lot of this issue would go away. Well, maybe, in theory. But this is not the case. This is never going to happen. All sorts of different kinds of network technologies have different maximum transmission unit sizes. We're stuck with this problem for many reasons. Just as a quick example, the Ethernets we've talked about, the very popular wired technology, permit packets up to about 1.5 kilobytes. On the other hand, Wi-Fi, and this is garden variety for both of these technologies, permits packets up to about 2.3 kilobytes. And different versions of Ethernet and Wi-Fi actually have different maximum packet sizes that they will allow through. So we're really stuck with this issue. Now the problem arises because not only do different networks carry different packet sizes, but we would like to send packets that are as large as will fit through the network. The reason for this is because of efficiency. If we send large packets, we'll spend fewer bits sending those headers, and routers will also have to process fewer packets to get the same amount of information through. So we want a large size. But what large size? What size is too large and what size is okay? This is difficult to work out because a host on the network knows how big packets it can send through the link to which it's attached, but it doesn't know what size packets will fit through somewhere way on the other side of the network if it's sending packets to a particular destination out there. There are two different kinds of solutions that we'll look at to this problem. One is fragmentation, which is simply the word for splitting a large packet up into smaller pieces that will fit through the network. This is the classic method that's used in IP. It's somewhat dated now and is depreciated in favor of another method. The other method that we'll look at is a discovery method. This is a method that hosts can use to find ahead of time the largest packet which will fit through the network. Once they know this, they can simply use this size and they'll avoid unnecessary fragmentation. Okay, so let's look at how fragmentation works. This picture shows an overall setup. I have a source here on the left and a destination here on the right. And I simply want to send a packet across. Now, the way fragmentation works, fragmentation will happen at routers inside the network. Our source here sends a big packet, the biggest packet which would fit on its link, its first link, and it looks like that's fairly big. When we get to some router, any router in the network, if that packet is too large to fit on the outgoing links, then the router will fragment it. And you can see that's exactly what happens at this first router. We've now divided the packet into two different fragments. A long one, which was probably the longest size that fit over that link, and then a leftover chunk. Well, those fragments then proceed through the network. They're routed independently. The other routers treat them all as individual packets, as it were. And these pieces will then go through the network and arrive at the destination. When they're at the destination will do the hard work of reassembling these pieces, putting them back together, completing the jigsaw puzzle to produce the original packet. And that original packet will then be handed up to the transport layer. So the transport layer won't know whether or not there was fragmentation. You'll note here that there's a little bit of asymmetry. Fragmentation happens at routers where it needs to happen because the packet simply couldn't go onwards, it was too big. But reassembly happens at the ultimate receiving host. And the reason for this is to reduce the load on routers. We don't want them to have to reassemble the pieces, buffer things, and complete a jigsaw puzzle to put them back together. That's a lot of work, potentially, and we would like to push all of this work to the end host where we can to reduce the amount of work routers have to do so they can forward packets at a very high rates. So going into more detail for fragmentation, fragmentation information is conveyed using header fields on the IP packet. I'm showing you here a picture of the format of the IPv4 header. This is the same picture we've seen before, and I've shaded in pink some of the fields which are used for fragmentation. We'll see how in just a minute. So those fields are identification. This sort of provides a number on a packet. So we'll have a stamp that's unique for a packet that we can use to put pieces of it together if it's broken. There is a total length field. That's highlighted because the length field will change if we break the packet into pieces. We'll update it to reflect the length of the pieces, not the complete packet. There's a fragment offset field. This field is used to indicate where in the overall packet the fragment belongs, what its offset or position is. And then there are a couple of control bits. MF here stands for more fragments. That's used to indicate whether there are any more pieces. So in this way, a receiving host can know whether it has all of the pieces of a fragment, or all of the fragments of a packet. There's also DF, which we'll see later, which is don't fragment. It's used to turn fragmentation off. Okay, so with these fields, now let's go through the procedure that's used to perform fragmentation. So when routers receive a packet which is too large, they'll begin fragmentation. To do that, they need to divide the packet into pieces. Typically, they'll break it into large pieces. The largest piece, which will fit across the next link, and whatever's left over after that. And you could break it into more than 2 pieces too. We're just using 2 in our examples here. You then copy the IP header to all of the different pieces, because each different piece needs to be routable through the network, and routers need to have an IP header on packets so they can work out what to do. Then you adjust the length on the pieces so that the length reflects the fragment, not the overall packet. You set an offset in the fragment offset field to indicate the position of this fragment in the overall packet, so we'll know how to put them together. And finally, you use the MF, the more fragments flag, as a single bit to indicate whether there are any more fragments. This is fairly clever because when we turn this bit on, as soon as a host at the end receives any packet with the more fragments bit on, it knows the packet has been fragmented and it should put all of the pieces together. And it will look for all of the pieces until eventually it will find a last piece that has this flag cleared and it knows that it's got to the end. The receiving host reassembles these pieces when they've all made it through the network. The identification field is the field that's used to link all of the different fragments together. They all bear the same identification value. And I've already talked about the importance of the MF flag, the more fragments flag here. Let's go through an example. That will probably make fragmentation clearer. So here I have a packet. It's a large packet, comes into a router. Let's say the MTU of the link beforehand was 2300 bytes. So a large packet came in. Now, when I talk about length here, I am just going to talk about the length of the data. Actually, the total length field on the IP packet includes the length of the header, so we would need to adjust things. But to keep this example simple, I'm just going to talk about length as though it refers to the data in a packet. So here, imagine I have a packet comes in. It has some identifier value, random one. Oh look, it's OX12EF. The length, the data length of this packet is 2300 bytes. It has an offset of 0 because it's not fragmented. It begins at position 0 at the beginning. And the more fragments bit is cleared since there's been no fragmentation. Now, for the outgoing link, let's say the MTU is 1500 bytes. It won't fit. What do? You guessed it, we fragment. We're going to have to break it into 2 pieces. The first piece we'll break it into is the largest size that will fit. Let's call that 1500. So I'm going to fill in we have a fragment here. Here's the fragment. This is the first piece. Let's fill in these fields. For the identification number, we just copy that, 12EF. The data length, I told you we'll try and send 1500 bytes. That's what we'll send in the first fragment. The offset is going to be 0 for the first piece. The more fragments flag will be set to 1 to indicate there is something coming. The second piece will be whatever's left over. Now, if the first piece is 1500 bytes, we've got another 800 bytes left to make up the packet. For the identifier, I copy it again. The offset we need to change. The offset should now be 1500 to indicate that this 800 bytes of data starts at position 1500. And the more fragments flag will be set to 0 to indicate that this is the last of the fragments. Okay, so if I clean that up a bit, you can see that example. And I've just highlighted there the fields which differ to show you that fragmentation has occurred and how they changed as the pieces were divided. That's fragmentation. You've seen an example of the procedure. Basically, it works. This design, by the way, has some clever properties. You might have wondered what will happen if we encounter another router where the MTU is even smaller. Well, this design allows fragments to be fragmented using exactly the same procedure and without having to group any packets together or do anything that would be hard work. However, and here's the issue really, it turns out that fragmentation is undesirable for many reasons. Experience with networks has shown us this. Fragmentation is more work for the routers and hosts compared to not doing it. For the routers, they're trying to process packets, millions of packets per second maybe. So it can be a lot of work to do. For hosts, they don't maybe have to process at such a long rate, but they have to buffer. They might have to hold on to pieces of packets for a long time to see if they can put them together and solve a jigsaw puzzle. Now, if you lose a fragment, you also lose the entire packet. There's no provision for retransmitting individual fragments. So this tends to magnify the loss rate and complicate things for the host, because if you lose any fragment, it might be holding a lot of the other fragments for a long time before it decides to give up. Fragmentation even causes security problems too. Fragmentation makes it easier to kind of hide the contents of what's in a packet. So it's more difficult for security boxes to check that the traffic isn't malicious. So let's move on and look at the alternate method that's used instead these days. And that is path MTU discovery. Really here we're trying to discover the largest MTU which will fit through the network. If we can do this, we avoid fragmentation. And this is the method that's in use today. Now the procedure we'll follow is here. The host is essentially going to try and send the data, and as a side effect it's going to test the network. It will send a large packet with the data it wants to get through. Hopefully that will get through. But if it doesn't, because it's too large, then routers will send feedback to the host telling it what size packet would have fit through the network. That way the host can discover how large packets it can send through the network. Here's an example. So let's just imagine we have a source on the left sending to a destination on the right. They're going through a couple of routers. The MTU of the first link is 1400 bytes. So on try number 1, the host might send 1400 bytes. It knows this is the MTU because it's attached to this link. So it just hopes this will fit through the network all the way to the destination. But as we go through the network, guess what? The first router, the MTU goes down. It's only 1200 bytes. This packet won't fit. Now, if this were fragmentation, we divide it into pieces and send them onwards, but this is not. This is path MTU discovery. So instead, the router sends back a message to the host saying, try 1200, and then it drops the packet. Host gets this message, and then it will try again. It will send another packet. This time it will resend packets with an MTU, a packet with an MTU of 1200 bytes. That will make it through the first router and to the second router. And when it gets to the second router, unfortunately it's too big because the MTU of the next link is 900 bytes, which is even smaller. Well, in this case, we'll send another feedback message. Now we'll say try 900 bytes. Okay, the host will get that message and these other two packets have been discarded. And the host will now try sending 900 bytes and it will go through the network all the way up. And eventually it will be received by the destination. The destination will then send a normal reply and we won't get any error message from the network saying that we should try something smaller to fit our packet through. Here's a version that's cleaned up, and that's essentially path MTU discovery. Now this process might seem a little bit involved. There was a whole dance we do here with messages and negotiation to find the MTU along the network path. But actually it usually works fairly quickly to find the right size because there are some common number of sizes and there usually aren't that many discontinuities we run into. You can also usually remember this information. You're doing it once maybe to talk to a destination and it's usually fairly stable. So it works reasonably well in practice. It is, and this is interesting too, it's really, because the path MTU depends on the path and the path can change, the search is really an ongoing procedure. We're really performing the search in parallel with sending data. It may be the case that we stabilize at a path MTU and use it for a while and then suddenly it changes, it gets smaller or possibly larger. We would like to discover that. So we might send a larger probe packet occasionally, and occasionally during the connection we may get error messages saying to use a smaller packet. You might wonder how all of this is implemented. This is implemented with a protocol called ICMP. That's the protocol that sends the error messages. We're going to talk about that next. And in addition to ICMP, one bit that's used that's key is this DF, don't fragment bit. To use path MTU discovery, hosts send packets with the don't fragment bit set. This tells routers not to fragment the pieces, and instead, if the packet is too large, this error message will be triggered. And that's our feedback. We'll see that soon. G'day viewers. In this segment we'll talk about how IP handles connectivity errors with a protocol called ICMP. Now, many different things can happen while a packet is being forwarded. They can go wrong because maybe the fields in the packet were not quite what was expected. The topic that we're looking at in this video is what do we do when there's an error during packet forwarding? What we would like is some kind of error reporting facility so that information about problems could be returned to the host or whoever's sending so they could actually do something about it. Not surprisingly, this is the kind of facility that turns out to be very important in real networks to help them operate smoothly. So let's look at how IP does it. Well, IP handles the various kinds of error reporting and connectivity problems with a protocol called ICMP. That stands for Internet Control Message Protocol. It's what's called a companion protocol to IP, is how it's often described. Essentially, IP and ICMP is always implemented together. You'll really hear about IP all of the time, but ICMP is implemented right beside it. ICMP messages are actually carried inside IP packets. So if you like, ICMP as a protocol sits on top of IP. And you can tell this if you look at an IP packet and the protocol number is set to 1, then that IP packet is carrying an ICMP message. ICMP provides a variety of functionality that's useful for understanding connectivity problems. From our point of view, most of this functionality is error reporting. When there's an error, when there's a problem forwarding a packet at a router, that's what I'm calling an error, and that is often then reported to whoever sent the packet so they could do something about it. IP also provides a little bit of other functionality, for instance, for testing the network without having to have any error occur. But we won't worry about this too much. We'll concentrate on errors. Here's the overall picture for how ICMP is involved in errors during forwarding. What happens is that, step number 1, someone sends a packet. This source on the left, send a packet into the network. It looks like a strange packet. Maybe it makes it through the network somehow. And then at some router has a problem forwarding this packet because of bad information in it perhaps. This is step number 2. What does the router do then? Well, it sends a report. That's this ICMP report, and then it discards the packet because it can't handle it. So this ICMP report, this is step number 3. This will make its way back across the network to the source that sent this bad packet. And hopefully, step number 4, the source will receive this ICMP message, understand what it's doing wrong, and take some step to fix the problem. Let's learn a little bit more about ICMP by looking at the format of ICMP messages. So every ICMP message has an ICMP header that carries information about the type and code of the message, as well as a checksum. Most ICMP messages also carry a portion of the offending packet, the trigger packet, whatever you want to call it, the packet that encountered an error and caused this message to be generated. By carrying the start of that packet, as much of it as will fit in the ICMP message, we're sort of returning that packet to whoever sent it so they can look at it and see what it was they did wrong. And this whole message is carried in an IP packet. So instead of letting me just talk, let me just try and draw some of this. So we'll start sort of in the middle. Here's the ICMP header. I said it has a type, a code, and then a checksum. So they maybe be different portions of it. It's then going to carry some data. So here's the ICMP data. What's carried in there? Well, essentially the beginnings of an IP packet. I'll just call it bad packet. That's the packet which caused this problem in the first place. And this ICMP message is sent over the network in its own IP packet. So at the front of it, there'll be an IP header. Just a standard IP header. Here I've cleaned up that drawing, and I've also added a little bit more information about the addressing. We need to be able to put different addresses in this packet to make sure the message gets to the right place. So let's think about how it is that the router knows to send an ICMP message back to the host which was causing the problem. The packet which we have inside the ICMP data here, since it's the beginning of a bad packet, it will have its own IP header. That header will have a source and a destination. It tells us where this bad packet came from and where it's going to. So to send the ICMP report, we can look at the source of the packet, who sent it, that's A, and we can use that as the destination when we make an IP header to slap on the ICMP message. For the source of the message, we don't use anything that's in the packet. Rather, the source of this ICMP message is the router which is generating it, which had the problem. So you can see here that the router will put its own IP address on the source packet as the source address and send it through the network. I've shown the protocol here 1 to indicate that inside the packet, the IP packet, there is ICMP information. That will have a different type and code depending on the message and some other information. The format of ICMP messages depends on their type and code values, so it can be different after some initial type and code values. Here are some examples of ICMP messages which you might see on networks. There is a destination unreachable network. If you ever sort of get a message about hosts not being reachable or networks not being reachable, usually it's because your computer has received a destination unreachable ICMP message when you tried to send a destination and the network couldn't work out which way to send it. It will be type 3 and it'll have different codes depending on what it's trying to say is unreachable. Another kind of unreachable message is destination unreachable because of fragmentation. The network needed to fragment the packet, but the don't fragment bit was set, so it couldn't. Returns this error message. That's actually what's used to provide for PathMTU discovery, the mechanism we looked at in a previous segment. Now, another interesting message is one called a time exceeded in transit message. This essentially means that the packet has been in the network too long and has not yet reached its destination. This is functionality which is cleverly used by Traceroute. We'll look at that on just the next slide. And then finally, there's another bit of functionality you might see from time to time. And that's an echo request or echo reply packet. This is used for the program ping. You might have used ping to ping a host and see if it's alive and reachable on the network. This last category, ping, is a little different than the former ones because this is not an error that occurs that's generated by a router during forwarding. Instead, an echo request is something that a host sends from one host to another host, and the destination host, the IP layer inside the destination host, knows that it is an echo request and it responds with an echo reply. So it's a way of seeing if a host is alive rather than error reporting. So to wrap up information on ICMP, let's look at how Traceroute uses ICMP. Recall, here's another picture, same picture, of the IP header. And now I'm highlighting that the IP header includes this time to live field. The time to live field is a value which is put on the packet when it's sent into the network, and then it's decremented every time the packet goes through a router. So it's really actually a hop limit field, not a time to live field. That's an old name. And if this counter ever reaches 0, then the router throws away the packet and sends an ICMP message, error message, back to the source. The purpose of this time to live field is to protect against forwarding loops. Imagine that the network forwarding tables were somehow messed up and they had a loop in them. Well, if you sent packets, they could get caught in this loop and go round and round and round amazingly fast and clog up the network. So the time to live field is important for robustness. It throws away packets if they're caught in a routing loop. Traceroute very cleverly repurposes this time to live functionality as well as the ICMP error message functionality. This, you might recall, is a slide from something I showed you right back in a much earlier unit at the start of the course. It's how Traceroute works. You recall that Traceroute sends a probe into the network 1 hop and then it gets a message back, so it knows what the first hop is, then 2 hops, gets a message back, 3 hops, and so on, so it finds the path through the network. You might have been wondering exactly how that works. Well, it works with ICMP errors and the time to live field. The way Traceroute works is it sends a message with a TTL of 1 to do the first hop. That will expire at the first router and cause this ICMP message to be sent back. Next, it will send a message with the TTL of 2 to go 2 hops, and we'll get another ICMP message back. Then a TTL of 3, that will produce an ICMP error, the third router out, and so forth. And you can see that this is essentially how traceroute performs its magic. By repurposing this functionality that was there for other mechanisms, by reusing it in a very clever way, we have one of the most important error debugging facilities in the internet. G'day viewers. In this segment I'll talk about IP version 6, the future of the Internet Protocol. So most of us use IPv4 when we access the Internet today, IP version 4 that is. But there's a new version of the Internet Protocol, IP version 6, which has been standardized and has been deployed into the Internet to solve some problems. I should say maybe that it's still being deployed, because it's been in the process of being deployed for more than a decade now. So in this segment I'm going to talk about why we need IPv6, what it is, and what the state of it is, how it's been rolled out. Okay, so here's the background. This is a slide, actually you saw this slide earlier on in I think the first week of the course. This slide simply shows you the graph, gives you the internet growth, and you can see how rapidly the internet is growing. Excuse me. It's really exponential growth here as we trend up the line. And over the past couple of decades, we've gone from a small number of million hosts to 1 billion. This is a huge number of hosts on the internet and still growing rapidly as every device goes online. And to top it all off, we're using 32-bit addresses. With 32-bit addresses, we have a maximum of 2 to the 32 addresses. That's basically about 4 billion. Actually, there are fewer addresses because there are all sorts of reserved things and format difficulties and so forth. So there are many fewer than 4 billion addresses. Not only that, but you can't use them all because we allocate these addresses in blocks. So we've used up a good fraction of the internet's usable addresses already. Actually, the situation is more dire than I'm letting on. We are very close to the end of the availability of new IPv4 addresses. This somewhat complicated diagram on the left shows how IP addresses are allocated. IP addresses start with a body called IANA, the Internet Assigned Number Authority, I think. And IANA owns all of the IP space. What IANA does is it hands it out, big chunk at a time, to these other bodies which are shown here. These are the arrows going here. These other bodies, ARIN, APNIC, RIPE, LACNIC, and AFRINIC, you might have heard of or you might not. These are regional bodies that hand out, that administer IP addresses in different parts of the world. ARIN is for the US, Canada, and various other bits of the world. I think Antarctica, for instance. RIPE covers most of Europe, and you can see all of the other bodies for Latin America, Africa, and the Asia Pacific region. APNIC covers Australia, of course. So IANA hands off IP addresses to all of these bodies, and these bodies in turn hand out IP addresses to ISPs and other companies when they ask for them. Now, IANA has handed out all of its IP addresses. It exhausted the addresses in February of 2011. So that's a little while ago. That's almost a couple of years ago now. You might think this is no big deal, but IANA has been going for, I think, more than 40 years handing out IP addresses, and just in recent history, it's run out. So this means the routing registries really have only their leftover blocks to use. Already, some of the routing registries have run out. RIPE, that's the other way around. APNIC was the first to go. In April of 2011, it ran out. Much more recently, RIPE ran out of addresses in September of last year. So everyone is sort of on a countdown. Now that the addresses are almost gone, much tighter allocation policies are being used. You need to satisfy many greater hurdles if you're to obtain new IP addresses. And secondary markets are springing up where companies are selling the IP addresses they already have to other companies and so forth. So it's all getting more difficult. Maybe this is actually somehow tied to the end of the world, the Mayan calendar. At the end of 2012, the world's going to end because we run out of IP addresses. What can we do? Well, don't worry, don't panic. This will be, one of those softs falling off the cliff kind of things. And there's a solution in the wings. It's IP version 6 is going to come to our rescue. Actually, it's been coming to our rescue for a very long time already now. IP version 6 was an effort started almost 20 years ago by the ATF in 1994, following on some research. The main feature of it really is motivated by this addressing crisis. The exhaustion of addresses is much larger addresses. These addresses are 128 bits long, and 2 to the 128th power is an enormous number. It's not simply 4 times as big as 2 to the 32, it's 2 to the 96 times as big. So there are more addresses than essentially every device on the planet in the foreseeable future in this number, many more. It's an astronomical number. The reason for starting on IP version 6 with these big addresses, even almost 20 years ago, was that the growth of the internet was obvious then, and it was clear that we would shoot through these addresses. And really, different techniques people have been using have only been delaying the end of these addresses. IP version 6 also includes many sundry small improvements. Basically, you really don't get to change the internet protocol, the bedrock of the internet, very often at all. It's a very rare event, so everyone would like to take advantage of it to clean up a few things in many ways. IP version 6, by the way, is the version that comes after IP version 4. 5 was allocated to a protocol that never really made it big time, so it's disappeared. At any rate, IP version 6 became a standard in 1998. That's more than a decade ago. So what's happened? Since it became a standard, after that, it was expected that people would begin to deploy it. Well, really very little's happened in the past decade. Maybe that's not quite fair. There's been various improvements. Windows notably began to ship it around 2000. Other major operating systems had begun to ship it and had it enabled by about 2008. So all sorts of people got a little ready in the meantime. But I think the big point is here. Deployment has really been hampered, greatly hampered by the difficulty of deploying it. We'll talk about that in a while, because it's really such a big change to the internet. And also a lack of adoption incentives. I mean, if you're a new ISP or company, why should you bother installing IPv6 if you can still get IPv4 addresses? It gives you a lot of headache and not really a lot of new features. So deployment has been very slow. Of course, now, in recent history, over the past couple of years, there's a big push to deploy IPv6, and it's beginning to take off because the exhaustion of IP addresses is really very close, and so the price of IP addresses will shoot up, and the costs and the difficulties, and we'll gradually switch over to IPv6. This slide shows you a little bit about IPv6 deployment. The medal here is a campaign to launch into the future with IPv6. It's World IPv6 Launch Day. And that was about the middle of 2012. It follows about a year after a World IPv6 Day in which ISPs and many large networks turned on IPv6 for a day just to try and do a bit of a test and debug it, since it is such a big change to the internet. They wanted to see if everything's compatible. That went well enough that in World IPv6 Launch Day, many big content providers and ISPs turned on IPv6 and left it on so that you can now begin to use it. This graph comes from Google. It shows you just some of their data that you can look up of how many of their different users are coming to them and making queries using IPv6 rather than IPv4. You can see a while ago it started at basically nothing, and it's been going up, and I think we're getting ready for some growth, at least I hope. Here, in case you can't read it easily, this is about 1% of the traffic, so IPv6 is still very much in the noise, but hopefully it's growing very rapidly now. So I still haven't really told you what IPv6 is. What we're going to do now is just look at the header of IPv6 so we can see the messages and just see what's a little bit different compared to all of the IPv4 messages. So here's another one of those header diagrams. It looks maybe the same sort of thing as IPv4, but it is different in some respects. The biggest difference by far is this shaded region. These are the addresses, the source and destination addresses. They now take up the bulk of the header because they're huge. They're 4 times bigger than the IP addresses used to be before them. So because of that, we have a new convention for how to write them. IPv6 addresses are written as 8 groups of 4 hexadecimal digits. Each of these 4 hexadecimal digits really corresponds to 16 bits. That's why there are 8 of them to make 128 bits. So here's an example in longhand notation of an IPv6 address. You see this address here, 2001 colon 0 db8 colon 0000, another zeros, ff00, 0042, 8329, and so on. Wow, that's a very long address. Most of the notation we use is about how to shorten those addresses so that we don't have to write it in such a longhand way. There are 2 rules for shortening essentially. You're allowed to, within a group of 4, omit the leading zeros, and you're also allowed to omit entirely groups of zeros. We'll know the range of ones which have been omitted by, usually there's just one run of them, by seeing that there are 2 colons in a row. So let me just write out, and you can help me, what this address would be in the new notation. So I'm going to shorten each group as I go across. So 2001 colon, I'm going to get rid of this 0, db8 colon. Oh, look, I can get rid of this block, and this block. Now I'm left with another colon there. Then I've got ff00. I can't get rid of the 0 zeros because they mean something at the end. It would be a different number otherwise. Colon, get rid of this. 42 colon 8329. Well, that's still pretty long, but it's a lot shorter than what we started with. So those are the addresses. What else is in the header? Well, there are lots of other smaller changes. I've shaded the other header fields. One feature of IPv6 is a more streamlined header processing. If you want to, you can compare it to IPv4 and you can read more about it in your text just to understand some of these details in more detail than I'm going to give you. You might notice, for instance, that the header length field has disappeared. The header has a fixed length here, and the next header points towards anything that's optional as well as the higher layer headers. You can also see that the header checksum has disappeared. That was something that maybe added a little bit of reliability, but it wasn't felt to be worth it and the complications in practice. So things have gotten simpler here. There's also a feature called a flow label that's likely to be important in the future. Recall that datagrams are all sent individually through routers, but often if we're doing something, all of these datagrams might belong to a higher level construct, like a video conference. What you can do is use this flow label to put labels on packets and identify the ones which are in the same group together. This is almost a little like a virtual circuit, just without any of the setup. If we do this, then we almost have a basis for the network to treat all packets with the same flow label in the same way. It might route them the same way through the network, forward them the same way through the network, Or it might try and do different things in terms of congestion or priority with them in the same way. This is mostly in the future, and this is to do with quality of service. We'll probably get to that later. And finally, IPv6 has a better fit with some of these advanced features. Now, I'm not going to go into all of the details here. The point I would just make is that over time, lots of experience has been gained in the internet with how to implement mobility, different kinds of multicasting. That's sort of like a cross between unicast and broadcast, so a packet is sent to a group, and a little bit extra security. Those learnings have been incorporated into IP just to sort of make the fit between these features and IP a little smoother. So this is basically what IPv6 looks like. Now let's talk about the big issue for IPv6, and that's the transition. If IPv6 is such a big thing and we really need it, great, let's get on with it. But how do we go about using it? How do we transition to it? The internet is far too big for us to have any kind of flag day where we say, everyone stop using IPv4 and start using IPv6. Instead, both of the protocols will need to coexist, probably for decades together. So we need some deployment strategy which will let us deploy IPv6 and begin to allow people on IPv6 networks to talk amongst themselves and with people on IPv4 networks. This is very difficult. It's really an internetworking problem, like before, but it's difficult because there are fundamental incompatibilities. They have very different addresses, for instance. How on earth are we ever going to get them to talk directly to one another? Well, this is the problem, and there's no magic answer here. In fact, dozens of different approaches have been proposed. I can't go into them all. That would be more detailed than we want. but I can just sketch some of the different alternatives, and I'll go into one in detail because it's useful. So some people have proposed running what's called a dual stack. If you have a host, you might have it speak both IPv4 and IPv6. That way it could use the old IPv4 protocol to communicate to old hosts which are on an IPv4 network, and it could use the new IPv6 protocol to communicate with IPv6 hosts on a new IPv6 network. Another approach is to add translators into the network and try and convert packets from one to the other. That will allow us to talk across IPv6 and IPv4 hosts. It'd be wonderful if we could do it. It's just kind of hard, and there are various constraints because, for instance, we have to work out how to fit IPv4 and IPv6 addresses in each other's packets using some kind of convention. And the third approach is something called tunnels. We might have islands of IPv6 where new networks which are using IPv6 are set up, but they might not all be connected. Some of them might be connected via the IPv4 network. We can tunnel across the IPv4 network to allow the IPv6 hosts to talk with one another. And this is the one that I'm going to explain in a slide or so, just so you can get the sense of how tunnels work. Here really to help with IPv6, but tunnels are a useful mechanism in general. They're not specific to IPv6. So here is the tunneling scenario. We have on the left, we have an IPv6 network. On the right, we have another IPv6 network. So we'd like to send a packet from the source on to the destination. Source on the left, destination on the right. They're both on IPv6 networks. Sounds wonderful, except of course in the middle, we have an IPv4 network. Now, because these are very different protocols, what we probably can't do, for instance, is have a host in this IPv6 network talk directly to a host in this IPv4 network. They speak different protocols. So we're not even going to try. We really just want to get our source to communicate with our destination, even though the path goes across an IPv4 network. What can we do? Well, here's what we can do. We can send our IPv6 packet, because that's what will be produced by the source, across the network, the IPv6 network. Then it will get to the border router, which is at the edge of an IPv4 network. At that time, what we can do is simply wrap the IPv6 packet in an IPv4 packet. We'll take it as a payload and not even look at the IPv6 packet. We'll simply encapsulate it with our own IPv4 packet and send it to another border router on the other side of the network so that it can get back onto an IPv6 network. This is a tunnel in the middle here. And it's called a tunnel because when the packet goes into it with this wrapper, this IPv4 wrapper, it's going to come out the other side. It can't get out halfway through the tunnel and go to, say, this host up here. It has to go through the network. So it can only go through this tunnel and out the other side. Now, in fact, if we look at the source and destination of this IPv4, we'll have the source will be here, this ingress router, and the destination will be here. It's identifying the tunnel endpoints, and the wrapper is just to carry the IPv6 packet through there. Once it gets to the other side, it can be unwrapped, and then it will go across the IPv6 network and arrive at the destination. So effectively, this IPv4 network in the middle is acting as a single logical link. That's how we're folding it into our network. Let's try and draw some of the layered protocol stacks for that, just to make sure we understand it. So on the sender side, let's say we have IPv6 on top of some link protocol, such as Ethernet. So we're going to have the same thing on the receiver side, IPv6 link. In the middle, what's going to happen? Well, at this ingress, we need to have the same thing, so this is meant to go here, IPv6 and link, because we need to terminate these protocols. But now we need to enter the tunnel. So we're actually going to do something tricky on this side. We'll have IPv6. We need to have this because we are maintaining IPv6 connectivity across this entire path. But underneath IPv6, we'll put IPv4. That means we will take an IPv6 packet and encapsulate it in an IPv4 packet. And then the link layer. And so we've got to do the reverse on the other side. So I'll have to have 3 in here. And this then will be our tunnel over IPv4. Whereas this is really a native IPv6 network, and so is this. So that's what the protocol layers will look like corresponding to those packet formats. You can see this is a bit of a strange device. We're putting a network layer on top of a network layer just to provide a fancy path. But it's quite effective. And tunneling, we'll see it again in some other context when we get to security and look at VPNs, for instance. Here's the diagram. Again, just cleaned up so you can see, yep, and check that I got it right and check your understanding. But that's basically it. Now you know about tunneling, you know about IPv6, and at least one option for how it can be rolled out. G'day viewers. In this segment we'll talk about network address translation, a networking technology that's widely used in the internet today. So many of you probably have a NAT or network address translation box that you use. This is because NAT boxes are commonly used to connect home networks to the internet, say as part of a wireless router or AP or any other kind of router device that connects your home network to the internet. We're going to cover them today and talk about what a NAT box actually is and how it does its job. And we'll do this for a couple of reasons. You might be interested just to find out how it works, since it's pretty much an everyday networking technology. That's one reason. And the other reason is it'll give you a chance just to think about how some of the NAT mechanisms fit with some of the principles of networking we've learned. Or rather, maybe you'll see how they don't fit and some of the tensions. Okay, so I'd like to start with just a little bit of a review of layering. You remember this layering model? This is the kind of slide we saw early on in the course. We have some applications using TCP at a source on the left, and there's a destination on the right. And that application is able to send information down the network. It goes across the network through routers and arrives on the other side. This is our standard layered model. The way layering worked with encapsulation, what it meant was that TCP passed information down to IP. It was encapsulated to be wrapped in a packet. That packet went through the network. I'll draw it at the router. So there was an IP packet on the outside, and on the inside was the TCP data, header and data. And because of our layering, this meant that IP devices didn't look at what was inside. They didn't inspect or modify the TCP packet in any way. This is a nice, clean layering abstraction. That's great in theory. That's actually the way a lot of networking devices work, but it's not the whole story. It turns out that there's a whole class of devices called middle boxes, of which NAT is going to be one example, of course. Now, middle boxes are these very odd kind of beasts which don't fit with our architecture at all. Middle boxes sit inside the network, so logically they're in the middle of the network, or physically they're in the middle of the network in some way, I should say. But they perform functionality that goes further than simply IP. So in some way they're doing processing on packets which would logically belong at the host on the edge of the network. And I've tried to draw it just on this device here in a router. I don't know how to draw a middle box in our diagram because it doesn't really fit. You can see here I've drawn that it's interfering with this data flow somehow between the sending TCP and the receiving TCP. It's mucking it up. The reason for middle boxes is that people use them to add new kinds of functionality. So a NAT box is one example, and we'll see exactly what a NAT box does just in a short while. There are other middle boxes you might have come across too. A firewall is an example of one, and an intrusion detection system. So to understand more about why we have these middle box devices, let's talk about their advantages and disadvantages. They have some very strong advantages and very strong disadvantages, so they're quite controversial. The advantages really have to do with the deployment of new functionality. Often it's possible to deploy new functionality just by upgrading one box in the network and turning it into a middle box. This is a wonderful alternative compared with, for example, upgrading all of the routers in the network or upgrading all of the hosts, both of which might be well nigh impossible or take a very long time. So if you can deploy something with a middle box, there's a very strong incentive to. If you're in the IT business too, a middle box can also be quite helpful in that if you can deploy it at a good position in the network, it can see traffic from many hosts, and so it provides almost a scalable point of control. It's easier, again, then deploying functionality on many different hosts in the network. You can sort of almost do that by deploying a middle box. On the other hand, it comes with some pretty strong disadvantages. This middle box breaks our layering model. It very much runs counter to it. Now, you could say, well, so what? It was only an abstraction, we'll just break it. Fine. What that does is it interferes with connectivity. This means that connectivity is no longer just a simple matter of sending and receiving IP packets, and often strange things will happen. We will have strange side effects depending on exactly what that does, some of which can complicate the future deployment of things. So and we'll see more about this when we get to NAT boxes. This is the primary downside, that they really make the network more complicated. It also turns out that a middle box is a pretty poor vantage point for implementing some functionality. We simply see packets going through the network. If you wanted to do a lot of functionality like intrusion detection, for instance, you might want to see the web pages or complete documents. But it's difficult to see that at the packet level. You would maybe need to reassemble all of the packets into complete documents to inspect them. That can be a lot of work, and it's not always possible if, for example, end-to-end encryption is used so that inside the network you can't see the contents. So let's move on now. That's middle boxes. You've heard about this class of devices. Now we'll talk about a NAT box, or a network address translation box. This is a specific kind of middle box whose job is to translate addresses. And it translates addresses to connect an internal network, which has many hosts, to an external network using a very small number of addresses, or a relatively small number of addresses in that network. It's very much motivated by address scarcity. So NAT boxes have been around since IPv6 was proposed and explored. They've sort of really developed concurrently, and they were first proposed as a solution to the address scarcity problem, really as an alternative or a short-term measure before IPv6 would hit. They're really very controversial at first because of the way they break the layering model and the damage they cause. But over time, they've come to be accepted as part of the internet architecture. Or maybe that's too strong. Maybe I should say they're accepted as a widely deployed networking technology that we just have to live with today. So I still really haven't told you very much about what a NAT box is or how it works. Let's zoom in on a NAT box. And I'll do that just by sketching the common scenario that we're going to talk about. I do want to point out that there are many variations on NAT technology. So if you look it up on the web, you'll potentially see all sorts of different ways that NAT works. The variety I'm going to talk about fits our common home usage scenario. It's actually a network address and port translation. So the scenario is this. You're at home. This is your home here on the left-hand side. You have many computers at home, maybe. I don't know, 5 computers, 10 computers, 2 computers, I don't know. You're connected to the internet via your ISP. Of course, your ISP gives you a single public IP address to connect. It doesn't actually want to give you many more IP addresses, particularly since we're running out. But you want to have as many computers as you like. You set up your computers in your home network, and actually you can give every computer what's called a private IP address. There are reserved prefixes for private addresses. For example, one of them is 192.168.0.0/16 is one. 10.0.0.0/8 is another one. You might see these numbers around quite a lot. They're private addresses, so this means they can be used on anyone's private network. You just can't really attach them to the public network because they don't have any unique meaning. Nonetheless, we can set up our home network and give every computer its own IP address and be perfectly happy. What the NAT box will do is it will translate between these many private addresses at home and the one unique public IP address in the ISP. To the computers at home, it will make it look as though everyone has their own address and they can use this to talk to hosts out on the internet. To the ISP or other hosts out on the internet, it will make it look like there's a single machine at home. I see I've drawn this pink line around all of the boxes. They're sort of looking from the outside as though they're one big happy machine that sits at the public IP address that the ISP has given you, which the NAT box is reusing. So that's the functionality that a NAT box is going to achieve. And just to point out, the NAT box, often a NAT box will be integrated into a wireless router that's part of your access point, and it's often part of a firewall, since it's providing some firewall-like technology in any case. So you might not be buying a NAT box, but you might find that NAT is in many of the boxes you use to connect your home network to the internet. So let's dive in a little bit and talk about how NAT works. We've talked about the goals, how it's trying to translate the addresses. How does it do it? It does it by keeping this big table that has a mapping between the internal address for the home side and the external address for the internet side. Now, in the table that I've shown here, the mapping is between an IP address and a port to another IP address and a port. This is sort of typical of the way NAT technology is used inside homes. This is actually technically called address and port translation, as opposed to only address translation. The reason you do this is that if you have many computers at home and they're using the internet all at once, well, we can't map them all to the one IP address without getting confused. We would really like an entry in this table to map uniquely from the left side to the right side and vice versa, so we could go back. To do that, we can use port numbers and map a combination of IP address and port number on the left to IP address and port number on the right in a unique way, so that there's a one-to-one mapping, and we won't get confused about what belongs on one side to what on the other side. This is an example table of a mapping that I just made up. So let me point out a few things about this table. Here we have the IP addresses inside the house. These are private IP addresses. Now they map to another IP address, on the external side, that's this one. This is just one public address. So while there were many internal addresses, there's just one public address. So all of the different IPs map to that same one public address. The way we're disambiguating this is using ports. When you made a connection, you also have if it's a TCP connection, a TCP port. So we're going to assume the traffic here is TCP for the moment. The port numbers are shown here. Different hosts might have different port numbers. It turns out that two of these different hosts actually by chance use the same port number. Well, when we map to port numbers on the external side, since we've got the one IP address, well, all the port numbers better be different, so we could know which internal thing it maps to. So you can see here that the different combinations are mapped to 3 different port numbers. None of these port numbers can be the same. And none of these port numbers needs to be any of the original port numbers. It can all get redone. I've shown them here as sequential, 1500, 1501, 1502, that's chosen on the output side. But really, it's more likely a NAT box would choose them randomly because it's slightly better for security. Okay, so if that's still a little puzzling, let's just try and work through an example to see what happens. The NAT box has this table. To use this translation table, as packets come and they're going from the internal side to the external side, the NAT box is going to use this table and rewrite the IP header of the packet according to the table. And for packets coming in from the internet to the private side to the internal region, the home network is also going to rewrite the headers of the IP packets according to this table. So let's see exactly how that would happen. Imagine that you just have this table, that your NAT box is somehow configured with this table. I've just shown one entry in this table. There would normally be many, but this is the only one we need for this example. It maps this internal pair of IP address and port to an external pair. So if we have a packet that's going from this internal source to an external destination, say a big popular web server, I've just used X for the IP address and Y for the port. Let's write down on the internal side what the source address would be of this packet. Well, it's going to be the internal source, and we know here from the table this one is 192.168.1.12. And the port, which I'm showing after a colon, is 5523. I recall that a port number is just a 16-bit number. It's used in TCP. We mentioned that very briefly at the beginning of the course, and we'll see that in more detail when we get on to TCP. What about the destination? Well, where do we want this packet to go to? We want it to go to IP address X and port Y. So the packet will then proceed through the NAT box. As it goes through the NAT box, for an outgoing packet, what we want to do is look up and rewrite the source IP and port. That's right, this box is going to change the IP header, so it's going to rewrite our traffic, which can be very confusing. So the source is going to get changed according to our table. We map this incoming source and port to this particular external IP address and port. So now the source will be 44.25.80.3:1500. Oops, a little squish there. The destination is going to be unchanged because we want it to go to x:y. And it will reach that web server, which will hopefully do some things and send a reply. Moving on, now it's sending the reply. So our packet is coming from the external side to the internal side. Let's look at that packet. On the external side, what do we have? Well, the source here, since it comes from this web server or whatever the external source is, it's going to have IP address X and port Y. The destination, where's it going to go to? It will reply to whatever the source is on the packet it received. And I can remember the source, we made this external IP address and port. So the destination of this packet will be the previous source, which is 44.25.80.3:1500. That packet arrives at the NAT box because the destination IP address takes it there. And then as it goes through the NAT box will look up and rewrite the destination address. It's now going to map that from the external name to the internal name. Okay, so let's go through. On the internal side, the source, well, that's going to be the same. We didn't change that. Will be x:y, meaning it really came from this external web server. The destination will get mapped, according to our table, to 192.168.1.12:5543. And that will be routed to this internal host. And so we translated between these addresses. There's one other bit we need. You might wonder how this table is formed in the first place. Now, you could maybe have your network administrator fill it in by hand, but that would be cruel and unusual punishment. For any reasonable networking technology, we want to automatically create this mapping table. And we can do this by populating the table whenever a host on the internal side first makes a connection to something on the external side. Suppose you're surfing the web and you contact a particular web server. Then you're going to send this packet from the internal source to the external destination. Now, if the NAT box can recognize this at the beginning of connection packet, the first packet, the very first TCP packet, which it can, we'll see how later when we get to TCP, but it will look to see if something is a TCP start of connection or SYN packet. If it is, the NAT box will make another entry in the table. It will copy the source, which was here, 192.168.1.12:5523. It will actually take this and copy this into this table. I actually had already written that in this table. It'll make a new entry. The destination was still x:y. And on the other side, since this is a new entry in the table, it doesn't have an external IP and port yet. It will fill in the external IP because that's the one it has from the ISP. Goodness, I can't remember what it was I had. Let's just say 180. I'm sure, well, whatever it is. And let's say the port that it's going to is, or maybe it's going to port 80. Oh, sorry, that's not where it's going to. This is what we're going to put to the source. So I'm just going to map that. I had 1500 before. The point is this 1500 port, that's chosen at random. This is really going to be the key in this table, the one thing that's unique, since the external IP address will all be the same. So on the outgoing side, we've then moved it to our 44.25.1.80:1500. The destination is still x:y. Don't worry if I've used a slightly different external IP address. It's just meant to be whatever the NetBox is configured with. This one is configuration. But once we've done that, we have populated an entry in the table, then when a reply comes from that external host, we're set. We'll know how to map it to the internal one, and we can continue using this. Eventually, we'll reclaim the space from this when the connection's closed down or hasn't been used for a long time. So that's how a NatBox works. And just to wrap up, I'd like to talk about some of the pros and cons of NatBoxes. There are definitely some downsides here, and that's why NATs were really very controversial. The connectivity has been broken. We said that breaking the layering abstraction would interfere with the connectivity and cause strange side effects. Well, it has, and hopefully you can realize exactly what one of the side effects is here. That if you want an internal host to communicate with an external one, you can only do it by having the internal host send the incoming packets to the internal host has to make a connection to the external host. You can only send incoming packets, that is from the external host to the incoming one, after this outgoing connection has been set up. Well, that actually fit quite well with web usage in the early days, because your client at home is usually making a connection to a web server. That's exactly what we want, and then the web server can reply. Of course, it doesn't work very well if you want to run a server at home and have people contact you, or if you use peer-to-peer technologies, or apps, including things like Skype. These do not work very well with NAT boxes. Or at least NAT boxes pose a big complication for them. So this is a good example of how NAT boxes have strange side effects, which can make it very complicated for apps to work. There's a lot more to this. I'm not going to go into too much detail, but you need to do a lot to get a NAT box to work well. You might have noticed I'm talking about TCP, so actually NAT doesn't work so well with connectionless kind of transports like UDP. It also breaks apps which somehow expose their IP addresses. The NAT box is translating between internal and IP addresses. If the IP address is in the header, if you use any other mechanism to convey it, like you found out your IP address and put it in a packet and told someone, well, it's not going to be the right IP address by the time it gets to the other side, because the NAT box won't have translated it. And in general, to get something like a TCP connection to work, there's a lot of other traffic that goes with it. As well as a TCP connection, for instance, you might have ICMP traffic that goes with it. You might have DNS traffic on top of UDP. Later we'll see that this is the traffic to map between host names like www.uw.edu and the IP address of their servers. So all of that traffic has to get to and fro through the NAT box properly for the overall application to work. Otherwise it will only half work and will have these strange effects. So these are the downsides. What are the upsides? If there weren't upsides, we wouldn't be using these devices. NAT boxes really have been quite effective at relieving much of the IP address pressure. Many homes use NAT boxes to connect multiple hosts behind NATs to the public internet. So they have really greatly helped with the use of the address space, and they really pushed off the exhaustion of IPv4 addresses by a long shot. They're also very easy to deploy. You can deploy it rapidly on your own at home and gain some value from it. This is really, I think, why NAT has rolled out. These incentives are very much in favor of its deployment, since you really have very few alternatives, even though there are downsides. And NATs also provide useful functionality. For instance, as well as all of this helping with addresses, they're also providing some kind of firewalling technology. Maybe a weak one, but one nonetheless, because external hosts can't connect to any of your internal hosts so easily. There will be no state in the NAT box, so it will simply drop a packet because it can't map it properly. It also helps somewhat with privacy, since in the internet, maybe your 7 machines look like one machine. So you can't really be sure who behind a NAT box in a department was necessarily doing what. And I think over time, NAT boxes are part of the internet now. At least they're widely deployed. They're something we need to live with. So many of the kinks will get further worked out as NAT boxes get cleaned up a little bit over time. Technologies such as NAT traversal, you might have heard of, for instance, will streamline how applications from the public internet can get through NAT boxes to devices on the other side. Applications like Skype use NAT traversal to operate more smoothly behind NATs. And a lot of this functionality has been sorted out. So there you have it. Now you know about NAT boxes and how they work. G'day viewers. In this segment I'll give you an overview of the routing topics that we're going to cover. Well, here's a reminder of where we are in the course. We've gone through some of the lower layers, the physical layer, the link layer. We're partway through the network layer. Don't worry, there's more fun to come. We previously talked about packet forwarding. Now we're going to get on to the business of routing. That's our topic for this unit. Before we dive into it, let me go over the distinction between routing and forwarding to make sure that you recall it from previous lectures. So forwarding is this process of when you get a packet, actually sending it on its way. So it's very much a local node process. You can see here a node gets a packet and forwards it, sends it in the right direction. And we've looked at that already and seen how IP forwards. Routing is the process of deciding which direction to send traffic when you get it. So that's an agreement process amongst all of the nodes to understand which way they should send traffic through the network. So if you like, if I was to draw the equivalent circle, routing is a process that involves all of the nodes in the network. So they're quite different in character, and we're going to look at routing now. Well, actually, the truth is we've already seen a very simple kind of routing called a spanning tree. We looked at a spanning tree when we looked at LAN switches, and the spanning tree provided basic connectivity in the network. So you can see here in the network of switches I have on the left, I've drawn a spanning tree. So some of the links are kind of turned on there, not all of them. So there are a couple of links in the network there that are unused, but this spanning tree is enough to connect all of the nodes, and in fact it provides some path between every pair of nodes. For instance, between B and C, traffic is sent along this route. Well, that's great for being able to get something through it all, but it's not really a very good route in terms of using the network, because you can see here that there is a link that's unused. So with routing, we would like to make good use of all of the links in the network, because bandwidth is the key resource of the network, so we want to be able to use it well. What does that mean? Well, that's actually a little bit of a tricky subject that we'll look at in the next segment. But I'll tell you right now that we would expect good paths to be able to use all of the links in the network. For example, here we've shown links between B and E and C, I'm drawing over them, and B and C. These are all links in the network, and so we would like to be able to use all of them if we wanted to send traffic between those individual nodes. We couldn't do that with a spanning tree because the spanning tree can't have all of these links at the same time, or it would have a cycle and it would no longer be a spanning tree. So these kind of routes were precluded under our spanning tree. We're going to see how we can do better. And at the risk of going a little bit meta on you, I'd also like to provide some perspective on where routing fits in to the set of techniques we have in networking. Routing is really, you could think of it as one technique for allocating network bandwidth. The key resource of the network is the bandwidth it has to provide connectivity between the different points. We want to use it well, and the way we're going to use it is going to adapt along different timescales. The routing we're going to look at will find paths through the network which will adapt to equipment failures. So the routes will be recomputed if a link fails or if a node fails. Well, there are also other timescales on which we might allocate bandwidth. Starting at the longest timescale down here, there's provisioning. Provisioning is all about building your network to fit your customers and what they actually want to do with traffic. So it takes place at a long timescale, months, even years. An example might be if you had a lot of customers sending traffic between Seattle and San Francisco. It would be pretty sensible to build a network that had a direct path between Seattle and San Francisco in that case. If all traffic had to go via the east coast of the United States, that would be not so good. So provisioning will take care of that problem. And really, routing can only do what it can do on top of the network. It can't change where the links physically are. At a slightly slower scale than routing is traffic engineering. This is adapting the routing itself on a time scale of hours or so, minutes to hours to even days, depending on the overall load of the network. For instance, just talking about our United States network again, the load might be different at different times of day, and because of the time differences, you might have a lot going on the East Coast and the West Coast at different times of day. So you might want to specialize your routes for the busy hour on the West Coast and the busy hour on the East Coast slightly differently. Traffic engineering would let you do that, to adapt to the network load slowly over the day and the week. Routing, as I've said before, is about adapting to equipment failures, finding good paths around or using only the working equipment. So the routes are going to change on the order of minutes at most, we would hope, less often, unless we've got a lot of failures. There's also a much more dynamic form of bandwidth allocation that I'll call here load-sensitive routing. This is adaptation on the timescale of seconds around hotspots in the traffic. For instance, if there's a lot of traffic going between Seattle and that San Francisco, for some reason there might be a big pileup and a lot of congestion in Oregon. If that's the case, it might make sense to route some traffic via Chicago. That's going to be a longer path, but if there's really a problem in Oregon, like a traffic jam, it might be advantageous to take the longer route to get around it. So these are all important in the overall management of the network as different mechanisms to allocate our bandwidth, our key resource. The one we're going to focus on right now, and for all of this unit, is routing. So let's adapt to some of those failures. Okay, so for routing, it turns out routing is actually quite a large field in that there's a lot of literature on many different variants of routing. We're only going to focus on one kind of routing in our unit here. And I've shown here 4 different delivery models in terms of how the network can deliver traffic. We are going to spend all of our time looking at a unicast routing model. That's the one on the left here. Unicast is the kind of routing that takes traffic from a given source to a given destination. So you can see I've got a path through the network to send traffic between one source to one destination. Great, that's what you'd expect. So this is going to be our focus. I do want to point out to you that there are other kinds of delivery models, and they're important and useful in the internet. We don't have time to cover them in this introductory course, but if you're interested in some of these other models, I provided pointers to the sections. I'll just very briefly tell you what those models are. So in a broadcast model, you're trying to deliver traffic from a node to all other nodes of the network. So you can see here from the source here, if I follow the arrows, I'm drawing over it, it's maybe not the clearest to see, but hopefully you get the idea. If I follow these blue arrows, then I will end up delivering a copy of the packet to every other node on the network. That's broadcast. Multicast is like a subset of broadcast. In a multicast model, we deliver a packet from one node to a group of nodes, but not everyone else on the network. So you can see this tree here is a multicast tree that I'm drawing over right now, and it is delivering packets to these 2 pink nodes here. I'll just circle them, and not all of the other nodes in the network. So there's another 3 nodes there that aren't circled as end destinations that don't directly receive these packets. And a final other model is really a pretty interesting one if you would like to look something up. That's something called Anycast. The model here is that when you send to an Anycast address, the network will deliver it to the nearest member of a group. So you can see here, if we send from somewhere over here in the network, we might send a packet to this particular pink node here. That would be the nearest member of the group to these 2 sending nodes. On the other hand, if we send from a different destination to the same Anycast address, then we might be delivered to a different destination. It actually has the same address, and that is the closest instance of that group to where the sender was. This may seem like a very strange model, but it's actually quite useful in the network if you want to deliver packets, for instance, to the nearest root DNS server, or the nearest of one of a copy of many servers in a content distribution network. But as I say here, we're all going to focus on unicast delivery. Okay, now I just have a little bit more to tell you before we go ahead and look at some of these algorithms. I thought that I would give you some of the goals of the routing algorithms. This is really food for thought for you to keep in the back of your mind. We'll see different algorithms. How do you know which ones are any good? Well, these are the goals. This is what we want of our routing algorithms. First of all, we want them to be correct in finding paths that actually work to get from a source to a destination. That might seem obvious, but it'll turn out that it's a little harder than simply looking at a map and finding out which way to go for some of these routing algorithms, because they need to work in a distributed setting where everyone can't see the whole picture. We still want them to be correct in this setting. We want routing algorithms to find efficient paths that use the network bandwidth well. I haven't defined what well is yet. We'll get into that later. We also want these paths to be fair. Well, life's not entirely fair, so by fair I really mean that they shouldn't starve any of the nodes. For instance, it wouldn't be reasonable in our network to come up with good paths that work for most nodes, but we could only do it by making sure that some other node really didn't get to send traffic at all. That wouldn't be reasonable. Every node on the network should have the ability to send traffic through the network reasonably. And then here are another couple of important properties at the bottom. We would like fast or rapid convergence. So if we're adapting to failures, after there's a failure, we would like the routes to recover quickly because they need to do that before we can really use the network again. And a last goal is one of scalability. We know that many of the networks we build grow large very quickly. They become success disasters if you do it right. We would like routing schemes that can work well even as the network grows large. These are called scalable algorithms. Okay, and here is the setting for some of these routing algorithms. This is really what makes a routing algorithm interesting. Routing is really not like looking at a map and trying to work out which way to go, because the routing algorithm must operate in a decentralized and distributed setting. This is actually what makes routing both difficult and somewhat interesting intellectually. Now in this setting, just imagine there are all of these nodes in the network. They're all alike and they're all working on this problem of routing. No one's in charge, there's no controller. So somehow they're all going to have to work out how to agree on what to do. What's more, they can't all talk to one another directly. They can only talk to other nodes by exchanging messages with the neighbors that they're directly connected to. They don't yet have any other way to reach further away than their neighbor. They don't even know what the rest of the network looks like. They're all doing this concurrently, so they're all operating in parallel, which makes coordination even a little bit more difficult. And we also want them to be able to work and find correct paths even when some of the links and nodes may fail. Whichever links and nodes remain working, we would like all of that equipment to sort it out and simply find good routes. So you can see that it's really a pretty interesting problem. Well, we'll see some of the solutions to these problems as we go through the different topics. Last time we went through forwarding essentially. That was our IPv4 and IPv6 model, as well as other things like NATs. Now it's all about routing. So I'm going to tell you just about some different frameworks for routing, like what shortest paths are, as well as different algorithms for computing routes on some of these networks to find their way through. And we'll start by looking at enterprise networks or even individual ISP networks. And by the end of this unit, we will have grown in scope to consider routing across the internet where all of the ISPs and networks are combined together. You can look at this topic list if you like. That will just be your roadmap for where we're going to go through, but I won't go into it in detail now. Let's just jump ahead and see some of those units. G'day viewers. In this segment I'm going to talk about shortest path routing for selecting good paths through the network. So in previous segments I've talked a fair bit about what a good path through the network, or that routing is going to find the best path through the network, but we haven't really said what that means. In this segment we're going to delve into that topic and provide an answer. And the answer we're going to provide is going to assign costs to links and use the notion of shortest paths as a way of defining what a good path is. Let me go into that in a little more detail. So we would like routing to find best paths or good paths. Well, what are they? It really depends on what you, the network operator, want. And there are many different possibilities here. You might want a good path to have low latency because this would avoid a circuitous route. There's no need to sort of go from the west coast to the east coast and back if you could avoid it. On the other hand, if you had a different kind of network, we might want paths which had high bandwidth. You might want to avoid any kind of slow or low bandwidth links because this way you would fit more traffic through your network. Depending on exactly how you paid for your network too, you might want to avoid expensive links. Maybe you'd want to avoid cellular links of some kind, for instance, just because you had some budget on them and you were going to have to pay a lot of money if you used them too much. Or you might want to minimize the number of hops that packets went through the network, because in some way that would reduce the volume of switching that goes on, and if you're lucky, maybe some of your equipment. These are all different possibilities. Now, there's actually, while it might seem like I've admitted pretty much everything here, there's a class of best that we've actually ruled out here that I haven't mentioned, and that is to do with hotspots. Now, it might be the case that just in this network there's a bit of a hotspot at B, and if we've sent traffic from A to E along that blue path there that's shown in the network here, like this path, then maybe we would say, hey, there's already a lot of traffic at B, so we don't want to send traffic from G, say, to C. We would like other traffic to go round instead of through B. Well, we're not going to focus on those kind of policies today because that kind of routing involves the traffic. And best, as we're going to define it now, we'll only consider static features of the topology, such as what nodes are connected where. You might also see that I'm going to represent networks as these kind of graphs. So in this diagram here, a line here, this is a link, and the circle here, this is a node. Previously I had a little icon or a picture for some of these things, but often for routing it'll suffice just to call it a dot and give it a label like a name, like A through G. Okay, so best could be all of these things. This is a little bit too complicated. What can we do? With shortest paths, we come up with an approximation which can represent many of these factors roughly. And what we will do is make a cost function so that we'll be able to compute the cost of different paths, and we'll choose the path which has the lowest total cost to be the best path. By assigning the costs in different ways, we'll be able to capture some of these different factors. Now, often we'll call the lowest cost path the shortest path. This is what you would get if you assigned the cost function to be the distance. And since this is a common choice in large ISP networks, what I will tend to do is I'll be a little sloppy, and I'll use cost or distance interchangeably, and we'll also use lowest or shortest interchangeably, so don't be too confused about that. The way shortest paths will work is we'll go through these 3 steps. First of all, we will assign to every link a cost or a distance, and we'll do that to capture the factors we care about. It's literally distance if we wanted to minimize the latency through the network. If you made it all 1, you would minimize the hops through the network if every link was 1. If you cared about bandwidth, you might assign fast links low costs and slow links higher costs, because that way if we take the lowest cost, we'll tend to prefer the faster links. At any rate, you assign a cost to a link, and the operator does this. This is policy. And then we simply define the best path through the network between every pair of nodes as the path through the network that has lowest total cost or is shortest. And if we turn up any ties in that process and a couple of different paths have an equal cost, then we're just going to randomly break those ties and pick a path. Whatever we pick out of those ones, since it will have lowest cost, it'll be good. It will be best according to our definition. Well, let's see some examples to see how shortest paths work. Here I have a picture on the right of a fairly complicated looking network topology. It's that graph from before where the lines represent links and the nodes represent different equipment kinds of icons. And what you can see I've added here is I've added a number on every link. This is the cost of using the link which I've assigned. In this diagram, all of the links are bidirectional and they have the same cost in either direction. It's possible to extend all of these models to networks that have links which are not bidirectional and which have unequal costs in either direction, even when they are bidirectional. But we're going to ignore all of this, and in the networks we'll look at, we'll have bidirectional links with equal costs. Okay, so the task here is to find the shortest path from node A to node E through this network. What's it going to be? In this segment, we're going to solve problems like this simply by inspection, and later we'll see algorithms which will work this out. Now, just looking at this network, I see different possibilities here. I mean, there's a node directly here from A to E. That could be good. That has cost 10. Well, actually, I can see I can do a little better than that if I go through here. If I go A, B, E, that has cost 8. That's lower, so it's a shorter path. It's best. Is this the shortest possible path? Well, you should have a look at for a moment and see if you can come up with anything better. There is actually a better path through this network. Hopefully you've worked it out. Now I'm going to draw it in for you. It's this path, A to B, B to C, and C to E. that has cost 4 plus 2 plus 1 is 7, and that's the shortest path on this graph. I've cleaned up this diagram a little bit and retraced it over, and you can see it there. And I've also listed just the costs or the distance function for some other paths that you might think of. Here was our AE, that was 10. We also discarded ABE as 8. We did slightly better than that. You might also come up with some other paths just looking around, but they'll turn out not to be better. For instance, ABFE, this path, has cost 9. No, not quite so good. Or you could imagine doing something going a little further around looking for something better. ABCDE costs 10. Nope, and everything else is getting longer. So the other one is definitely the shortest path. So now we know what a shortest path is. The interesting thing about these shortest paths, which we're going to use as part of our routing algorithms to compute these things, is that the paths have what's called an optimality property. And the optimality property is that if you have a shortest path, any subpath of it is also a shortest path. That's kind of handy, actually. So in one shortest path, there are actually many different shortest path segments we found. So for instance, our path ABCE is the shortest path. Okay, well that means I actually found a lot of other shortest paths. AC is the shortest path, sorry, ABC, that first segment. CE is the shortest path. BCE is also a shortest path, and so on. Now, you can actually reason fairly easily to see why these must be shortest paths. The reason, for instance, that BCE is the shortest path, if ABCE is the shortest path, is imagine for the moment that I could find a better path than BCE. Well, if that was the case, I would simply use a different route to reach E by taking that path and stapling the A to B bit on front of it. And then I would have a better path from A to E. But we know that the path from A to E we have is the shortest, so it's not possible to do this. It's a contradiction. So that means that the path from B, C, and E must itself be a shortest path. There's also another nice property we get with some of these shortest paths. And this should give you a nice warm feeling. You should be beginning to see why, in fact, we work with shortest paths, because they can approximate some of these different cost factors, and they have a lot of attractive properties. So the other interesting property is that if I take the union of all of the different shortest paths from all nodes to a particular destination, then I will get what's called the sync tree. It will actually be a tree, because once you go further in, then the path, when two paths meet, they will both follow the same route from there on to the destination because of this optimality property. So let's see if we can find the sync tree for E. So that's all destinations going towards E. You can also similarly, in our formulation, find source trees, which would be all of the paths from one node, say E again, out to all other nodes. In fact, given that we're looking at bidirectional links with equal cost, the sync tree and the source tree will basically be the same. They'll just be pointing in different directions to go towards the root or away from the root. And I'll use them a little interchangeably too, depending on what is most convenient. So let's find the sync tree for E. Well, C goes towards E, so we had this link here. Now I can see the shortest way to get from D to E is just to go along this link, so that will be part of the sync tree. From F to E, the shortest way is along this link. There's no other shorter way around. It's not always the case that the direct link is shortest, by the way. From B to E, we actually saw that, we want to go to C, and then from C up to E, a dogleg way, rather than going along that direct link BE. Well, what's left? Can all of the nodes get to E yet? Not quite. I need to extend it. We need to work out how H gets to E. Well, it's going to have to go along here to C, and then from C, it's going to go straight up to E. And G also is going to have to decide which way to go. I can see cost 3, 6 here, or I can also see cost 6 up here. That's a tie, and we could choose either of these, and I'm somewhat arbitrarily going to go like this. So this is a sync tree for E, and since we broke a tie, there could be more than one. Let's just clear that up. So there are some very nice implications of sync trees. Because of this shortest path property. Given that we have these shortest paths, All we need to follow them towards a destination is the destination. The source that they came from is irrelevant. So you can see here once I get to node C, I'm going to then go onwards to E. It doesn't matter whether the packet came from H, or whether it came from B, or whether it actually came from A. Once it gets to C, it simply follows the same remainder route to E, and so all we need to do is look at the destination. That's fairly simple. What's more, each node only needs to work out the next hop to send it to. In this graph, we can sort of see how we might send the whole path, but really all A needs to know, for instance, is that it needs to send it to B rather than directly to E, and then someone else like B will carry it further onwards. This leads to a notion of a forwarding table for a node. We assumed that there were forwarding tables to do IP forwarding. At a node, the forwarding table is going to list the next hop for every single destination. So that's going to allow us to forward a packet because we'll know the direction to send it in by simply looking at the destination. You can see this will fit well with shortest path routes. It may be that if we compute shortest path routes, we will actually know a lot more about the routes through the network than simply the next hop. As I was saying, in this diagram, we know the whole path that you're going to take from a node to the destination. But we're not going to need that for forwarding, and so we might distill a forwarding table out of the routing table and ignore information we have. So far, we've just been using inspection to look at these graphs and find out which way to go with the sync trees. In the next segments, we'll look at how you can compute these paths yourself, or rather the nodes can compute it themselves by using well-defined algorithms. G'day viewers. In this segment we'll talk about Dijkstra's algorithm for computing shortest paths. This will let computers do the calculations instead of us, which is generally a good thing. So the figure down below here shows an example of a network topology. What we'd like to be able to compute in this network topology is the source tree from a particular node, like for instance E, out to all of the other destination nodes in the network, all of the other nodes as destinations. This will allow us to work out the forwarding table for E, or which way to go to reach all the different destinations. If we can do that, we've solved the forwarding problem. Dijkstra's algorithm provides one way of computing these source trees, and it's widely used as part of a common routing protocol, which is why we're covering it. Dijkstra's algorithm is named after E.W. Dijkstra, a famous computer scientist. He is well known for his contributions to programming languages. You might have heard of a paper called Goto Considered Harmful. That was him. He's also made many contributions to distributed algorithms, such as the algorithm we'll study for computing shortest paths, as well as program verification. So Dijkstra's algorithm that we'll look at, it dates from 1969, so it's been around for a while. It's a single source shortest paths algorithm, which means that it takes a given source, and from that source it computes shortest paths to all of the other nodes in the network. To do this, it needs to know the network topology, and there's also a caveat, a little restriction here. All of the link costs that are on the various links in the network need to be non-negative. This is usually perfectly fine for using network graphs, because if the quantities, the costs, correspond to anything physical or meaningful, chances are that they're non-negative anyhow. Okay, so here's an outline of the algorithm. I'll go through this outline and then we'll work through an example so you can see it in action. So first of all is an initialization step. Dijkstra's algorithm is going to visit all of the nodes. So we begin by marking all of the nodes as tentative, and we set up distances for them. All of the nodes are keyed by their distance. The distance of the source from which we want to compute the shortest paths from there out to everywhere else is set at 0. And the distance of all of the other nodes, we'll initialize it to be some constant that means infinity. We don't know how to reach them yet. And then we proceed in this main loop. This main loop says, while there are any nodes which are tentative, meaning the algorithm hasn't found them yet, how they fit in to the source tree, then what we will do is we'll extract the node with the lowest distance that we know. We'll then add that node to the source tree by drawing a link from wherever it was used to get its current distance to the node. And then we will we will use the information from that node to relax other costs, to lower other costs. We do that by taking the cost of the node, looking at the node's neighbors, and seeing if there is a lower distance way to reach any of the node's neighbors. That might sound a little mysterious, but let me go through an example and you'll see that this relaxation step is quite straightforward. Okay, here's an example that I'm going to walk through. It's the same topology from before, and I've shown it with an initialization phase where you can see that next to all of the nodes I've written in red their costs. For many nodes it's infinity. For the source node where we're going to start from, it's 0. Now I'll proceed through that while loop. First step of the while loop, we're going to take the node with the lowest distance, that's A, where we want to start from, and do a relaxation around A. So if A now has cost 0, you can see I've changed the cost to blue. It's locked in. It's once we visited the node then and taken it, then we found the path to that node. Of course, this is just the source. Now I'm going to color nodes that we visit black. And then the relaxation from here, it looks at the cost of this node at 0, visits all of its neighbors, and sees if it can lower the cost. What are its neighbors of A? One is B. You can see here I've circled B. B's cost used to be infinity, but B is one link of cost 4 away from A, which has cost 0. Therefore, B's cost could be reached via A at cost 4. That's less than infinity, so we're going to lower the cost of B from infinity to 4. That's one relaxation. We'll do the same thing for E. E's cost used to be infinity when we didn't know how to get there. But now we have an option. We can go from A to E directly over this link of cost 10, so E's cost will be 10. Both of these nodes have been relaxed. That's a step in the right direction. Next iteration, what do? We pick the next lowest node. That's going to be B with cost 4, just circled B. So we add B to the shortest path tree from the source tree from A. Now B with cost 4 was reached from A directly over this link, so we add this link to the shortest path tree. Now let's perform a relaxation. We'll go around all of the nodes connected to B and see if we can use the links from B to lower the cost. Let's look at C first. C's cost used to be infinity, but C is a link of cost 2 away from B at cost 4, so C can go down to cost 6. It got lowered. E, well, E is a link of cost 4 away from B, so that can be reached at 8. E's cost before used to be 10, so actually E has now been lowered to be cost 8. So interestingly, E's distance has fallen not just from infinity down, but it used to be some finite number 10, now it's gone down to 8. So we're finding better paths over time as we go out further and further away from A. Similarly, we'll do the relaxation for the relaxation from B when we look at its neighbor F. Its cost goes down to 7, and G goes down to 7 too. This is great. Okay, next step. What do? The next lowest cost, well, the lowest cost of the remaining nodes that haven't been visited is C with cost 6. So we take it. I've changed its cost to blue to say that it's done. We add this link. C with cost 6 could be reached at that cost from B. So we add that to the tree. That's a new link. I've colored C black too to indicate that node's visited. Now we do our relaxation around C. What's going to happen? Well, H's cost is going to fall. We have the cost of D can be reached now at 8 here. So I think D's cost has fallen too. I'm not sure. We'll see that, I guess. Well, you have to look at the previous slide. Relaxing from C, we get that the cost of E has now gone down to 7 because it can be reached over a link of cost 1 from C is 6. 1 plus 6 is 7. So it's gone down again. Wow, our route to E is just getting better and better. Yes, D, I guess D went down from, well, I don't know. You can look at the previous slide. It's hard work going through these graphs. I hope I haven't made too many mistakes that you're going to find. Okay, so continuing, well, it looks like actually we've done all of the relaxations for C. So let's continue on. Now we've got to pick the next lowest node. There are actually 3 nodes that have cost 7. So any of those will do as the minimum cost to extract. We're going to arbitrarily pick G just to work our way around the graph. G could be reached at cost 7 from B, so we've now added this link here to the shortest path tree out from A. And I've changed the cost of G in 7 to blue and marked the node G in black. Let's do the relaxation from G. G has one other neighbor. So that other neighbor we can reach at a link at cost 4. So the cost to reach F by G would be 11. 11 is not bigger than 7. So actually that means that routing to F by G would be a bad move. And we don't lower the cost. And remember that as a new route. So that hasn't changed anything. Next, moving on, we'll do a relaxation around F. So first of all, we are taking F as the next lowest node. We're going to add the link at which F was reached at cost 7 to the shortest path tree. That is a link from B. It was reached from B at cost 7. So we've added this node to the shortest path tree. We do the relaxation. And we find actually that it doesn't lower anyone else's cost. Everyone else has reached a better way than going through F, I guess, is what that means. Continuing, now we get to E. So we want to do a relaxation around E. So we take E, make its cost in 7 is now in blue. We've colored the node black. We've added the link. E at cost 7 was reached via C. So we add this line from C. To our shortest path tree. Now as we do that relaxation, I think nothing much changes because by the way, all of these nodes that have already been visited and are in blue, they're not going to change. We found the lowest cost way to reach them. The only node that could potentially change is this one in red, but 7 plus 2 is 9, that's bigger than 8, doesn't change. Okay, going on, what's left? D. D, now we'll take that as the next lowest. And we will take this link to D. We added that, relaxation doesn't change anything. And finally, there's one node left, that's H at cost 9, so we add this one, and we're done. We've now found the source tree from A to all nodes. If you just look at all of these blue lines, you can see that they start at A, they go out, and they provide a set of paths to reach all other nodes on the graph. And these are the least cost paths to reach any of these other nodes. So we've done it. We have a nice methodical procedure for finding this source tree from a given node for a particular topology. And that's Dijkstra's algorithm. Let me make just a couple of comments before we wrap up. So you might have noticed that Dijkstra's algorithm finds the shortest paths in order of increasing distance from the source. What it's really doing is leveraging this optimality property, that for long shortest paths, the smaller shortest paths, subpaths, are also shortest paths. So we can build up from small paths to large paths, and they all overlap. That's why it works to go out at increasing distance, and that ensures that once we've gone out to a certain distance, we'll never change our mind later and change any of the paths we've already selected. This algorithm can take a little while to run on a graph topology. Actually, the efficiency of running it depends on how you implement this extract minimum cost node function, depending on what data structure you use. You can use different ones depending on if your network is dense in edges or sparse in edges. But in any case, the running time is superlinear in the size of the network. That means as the network grows larger, the run time of this algorithm is going to go even more quickly, and eventually, for very large networks, the run time will get very large. It's not surprising really, there are so many different little paths that you can easily imagine some of the complexity here. And finally, I'll note that it gives us the complete source tree or sink tree, depending on which way you run it. This is actually more than we need for forwarding. Each node just needs to know the next hop for all particular destinations. So we have more than we need for forwarding. We can use it, that's great. To get this, of course, we needed to know the complete topology. So that's going to be an issue we'll have to address in routing. Okay, now that we know Dijkstra's algorithm, I think we can keep moving on and look at other routing algorithms. G'day viewers. In this segment I'm going to tell you about distance vector routing, one of the two main methods which you use to find routes. So we've talked about the notions of shortest paths and how you can use Dijkstra's algorithm to compute shortest paths if you have the topology all in front of you. What we're going to see now is how to compute these same shortest paths but in a distributed network setting, as we need to in the internet. And we're going to look at what's called the distance vector approach to do so. Well, distance vector is a fairly simple approach to computing routes. It was used fairly on in the internet, actually when it was called the ARPANET, and also in a protocol that you might have heard of called RIP. Distance vector is one of the two main approaches towards routing, the construction of routes, that is. If you want to impress someone, I guess you can tell them that, technically this is a distributed version of the Bellman-Ford algorithm. Maybe that won't impress them, who knows. The algorithm itself works fairly well, it's correct, but it does suffer from very slow convergence behavior after some kinds of link failures. And for that reason, the kind of algorithms which we use to compute routes in most real networks today are often link state algorithms, which we'll see in a little while. These algorithms are a little more involved in terms of the work they do, but result in better overall behavior. Okay, now here's one thing that I would like to stress, because I think it's very interesting for our routing protocols. We had looked at a centralized scheme where you run Dijkstra if you know the whole topology. That's not how networks work at all. Okay, now we need to compute routes in a distributed setting. What is a distributed setting? Well, I'm glad you asked. It's really very different than this centralized setting where we have the whole network in front of us. In fact, if you're a node in this setting, all you know is your neighbors and maybe the cost to reach your neighbors. So you just have local knowledge. You don't know the overall topology at all. In terms of finding out things and deciding things, you can only talk to your neighbors using messages. You can't send messages magically to faraway places. You can only gossip and exchange messages with your immediate neighbors. It's also the case that all nodes run the same algorithm concurrently. There's no special leader or boss or centralized place that's in control of it. Every node is equal, and yet amongst themselves somehow they all need to decide on compatible routes. And just to make things a little more challenging, nodes and links can fail and messages can be lost. Actually, so it's not just the links that can fail and messages that can be lost, but nodes themselves can go down and fail. And that's going to be a little tricky because you might have been talking to a node a while ago and now it's gone away, and yet we still want to be able to find correct routes. How do we do this? Well, distance vector is one approach, and here's how it works just in one slide, and then we'll go through an example. Now, in the distance vector algorithm, each node maintains a vector of distances, let me just underline that, as well as next hops, to all destinations. This is the distance vector, and that's the heart of the algorithm. What you're going to do is compute the best distance vector and keep that best distance vector over time. So you start by initializing your distance vector with 0 for yourself as a destination, because you're already there, congratulations, and infinity to everywhere else. You don't know anything else. And then with this algorithm, all you do, and this is a simple repeated step, is you exchange every node sends its distance vector, the one it currently has, to all of its other neighbors. You keep doing this. And then as you receive from your other neighbors their new distance vectors periodically, you update your own distance vector. And you update your own distance vector to choose the best path, and that's going to be since we're after shortest paths, the lowest distance to each destination that you've heard. When you correct, of course, by adding the cost of the link towards your neighbor that you've just gone across. That's the one extra link from the distance vector information they gave you. And you're going to pick the best route and then you'll use it for forwarding. Okay, that's the distance vector algorithm. It's a little bit of a mouthful if you're not used to these kinds of algorithms. So let's see an example of how it works in practice. So here's a simple network. I'm just going to look at this basic network with 4 nodes, A, B, C, and D. And just a few links here. You can see I put the costs on all of the different links. And every node in this network is going to run its own instance of the distance vector algorithm and keep its own distance vector and exchange messages with hosts. Here, with its neighbors, excuse me. Here is the view of just the distance vector that A has at the beginning of time. So A says, well, I can reach A with cost 0. Great, I'm already here. B, C, and D, they're the other nodes in the network. infinity, don't yet know how to get to them best. And you'll note here that A can only talk to nodes B and D directly, can't reach C directly. So what happens? Well, what's going to happen is that A is going to send its distance vector to the other nodes B and D. Now B and D and all other nodes are of course going to be sending their distance vectors to all of the other links. So A is going to be receiving two distance vectors, one from B and one from D. And I put them here in this table. The distance vector tells us information to all of the different destinations, A, B, C, and D. And we can see what B says. B can just reach B and everything else is infinity, and D can just reach D and everything else is infinity. Now A needs to choose the best entries after correcting for the local link costs. So for B, we really want to look at B plus 3 because 3 is the cost to go over the link from B to A. So here's B plus 3 in this column here. You can see that I've added 3. And for D, we really want to look at D plus 7 because that's the cost of going over the link. And we want to choose the lowest number here as we go across. So what do we have? Well, A actually, to A, that's the special case. We already had 0. For everyone else, so to B, what did we find? Here was the lowest. It's just cost 3 going directly via B. To C, we don't have any lowest cost. It's still at infinity. And to D, we have 7. So that's going to go over here. And then we can see here is the distance vector that A has learned after the first iteration. And it will have, in fact, found the best one-hop routes which are possible in this network. And all you can do with one hop is just reach B and D directly. So this is what A is going to do. A is really here learning the minimum of B plus 3 and D plus 7, as well as for a special case of reaching itself at cost 0, because it knows its own identity. Of course, this same process is going on not simply at node A, but everywhere else. So wow, this looks a little more complicated, but let's just imagine for a moment what's going on elsewhere. Now here, this table here shows us all of the distance vectors that B, C, and D exchange with their neighbors. We worked out what happened today. I've just copied it over here. B is going to learn the minimum of A plus 3 as it comes in here, C plus 6 as we come in on the link on the right, and D plus 3 as we come in those things. And I've written that there. I could also tell you that C is going to be equal to the minimum of, let's see, C is connected to B over a link with cost 6 and to D over a link with cost 2. So that would be what you would want to use to compute the routes for C. So if we follow the same process, and you can check this, hopefully I've got all of the numbers right, then you can compute the one-hop best routes that B, C, and D learn. Well, this process doesn't end. Actually, it's quite complicated thinking, just trying to keep in your head what's going on in all of these nodes. So I've tried to write it down. In the second exchange, here are the distance vectors that are going to be advertised. These are simply the best ones which were learned at the end of the first exchange. So they're going to be sent out. And we will then, every node will go through exactly the same process. And here you'll end up finding the best 2-hop routes after the second exchange. Well, what's A going to learn? Remember we said that A is equal to the minimum of what? E plus 3 and D plus 7. Well, let's look here. So we really want these ones plus 3 and these ones plus 7. What's going to be the minimum here? Well, to A, of course, is this special case of 0. To B, let's see. Well, 0 plus 3 is 3. That's lower than 10. So we're going to learn a route to, well, I guess we already had that. We're still at that. I've colored in pink here the ones that change. So what's actually changed? Down here, we've got C is, to C via B is cost 6 plus 3 is 9. To D, to C via D is cost 2 plus 7 is the cost of that link is also 9. So A now actually knows 2 routes to reach C at cost 9. So it will choose simply one of them. Let's say it's arbitrarily here chosen D, via D to reach C. Similarly, if we look down here, we have 3 and 3 is 6, and 7 and 0 is 7. So we find that A can actually reach D at cost 6 via B. It's learned a better 2-hop route. That is this route to get to D. We've now learned that that is shorter, cost 6, instead of this route that A was using after the first exchange. Well, this process continues. I'm going to leave you to check some of it at home. What we will find out is that we're now finding the best 3-hop routes, and there is actually some 3-hop routes that are better. A here is reaching C via B at cost 8. So that's actually going to be like this, is the shortest route. And it looks like we're actually using this in 2 directions. C is seen to A via D, so it's going to go like this too. So we found that as the best 3-hop route. Well, after that, if you go through and check all of this table, you should find that there are no shorter 4-hop routes because the diameter of this network is 3 hops. There are no longer paths. So we've converged now. And all subsequent exchanges should send the same information until there's a failure, that is, and then the routes may change. So in distance vector, you should imagine that in the dynamics here, in terms of adding routes, news about new possible routes is being added in 1 hop per exchange. Every exchange we were finding information about routes which were 1 hop longer. We haven't yet got to when you remove routes, but I'll tell you when you remove routes, what happens is that a node fails. So actually it doesn't send a message saying, oh, you can no longer use any of my routes. What happens instead is that other nodes need to forget and time out the information over time if it's not reiterated. There are problems though with distance vector. Remember we said some convergence issues can arise, particularly with something that's called partitions. A partition is when you divide a network into 2 different portions so that you can't get from one side to the other side. If this happens because, say, a key link breaks, this is why you actually want more than 1 key link in network, so there's a little bit of reliability, you get a convergence problem. You get what's called the count to infinity scenario. Here's that scenario. So I've shown on the left the desired behavior. This is a simple chain and we're looking at how information from the destination A propagates. You can see here good news, reaching A, news travels quickly. After 1 hop, B knows you can reach A at node 1, that's down here. After 2 hops, C knows you can reach A at cost 2, and similarly as we're going down and down and down this table. What about when there's a failure here on the right-hand side and A can no longer tell people how it can be reached? Well, initially we'd found out all of these good routes and now there's a failure. What's going to happen? Something strange can happen actually. If you look at B, B will now get an announcement not from A because A can no longer reach it, but from C. C will say, well, I can reach A at cost 2 because that's what it could. So B will now say, okay, well, I can reach A at cost 3 because that is the C's distance plus 1 to go over that link. Well, you can imagine what might happen here. In the next iteration, C is learning how to get to A from B. C is going to raise its cost to 4. That will cause B to raise its cost to 5 and D to raise its cost to 5 in the next round. And subsequently, C is going to have to raise its cost to 6, all because they depend on one another. And you can see that something really screwy is going on here. This is called a count to infinity scenario because the network is really exploring ever longer routes in a vain attempt to try and reach a destination which is not reachable. And this is undesirable convergence behavior because it means that for a long time the routes in the network can be in flux. Now, you might think that my example was a little contrived because C shouldn't be fooled so easily. C knew that it was getting to, B shouldn't be fooled so easily because B knew that it was normally getting to A directly and it was in fact telling C the best route to use. So B shouldn't really decide to go via C and then just add 1 to the cost. It seems a little silly. However, these same effects arise in larger cycles, in longer paths in other networks, even when you're not talking to one another directly. Cycles of 3 nodes and so forth. So they're very involved in these networks and they're quite hard to get rid of. There are various heuristics. They have colourful names here like split horizon and poison reverse. Just means, B, don't suddenly start using information from C if you told C how to actually get to A. But these heuristics turn out not to be very effective in practice. They get complicated and they don't really solve the problem in nearly all of the cases. For that reason, link state algorithms are more favoured in practice. And we'll look at link state protocols in the next segment. One exception is that distance vector is really very lightweight. All you're doing is keeping this distance vector and propagating it. No complicated graph algorithm. So you can use distance vector when you're very resource constrained, might be one exception. Okay, so distance vector is the technique. Distance vector is the technique which is used in a protocol called RIP. You might have heard of it. It's one of the more famous distance vector protocols. So it uses hop count as a metric. So we're simply counting the number of hops routers we go through. And we use infinity as 16 hops. Just to, this limits the network size, but also stops us exploring ever longer routes in case of some of these weird things. It also includes these heuristics for split horizon and poison reverse. RIP is actually quite an old protocol now. You're unlikely to use it in practice. So you might look at it just to understand how some of these protocols worked. There's an old RFC you could look at. It's it's quite dated now, but it's a nice small RFC. You can read the whole thing and understand the protocol. You'll get all of the details like the 30-second timers for sending these distance vectors. It's run on top of UDP. Information times out if a node goes away after 180 seconds as a way of detecting failure. So there can be a failure. Once there's a failure, it can be a long time before the network responds and fixes routes. This is not so good these days. And this is why we run faster and better routing protocols these days. But nonetheless, it's an interesting protocol to look at. Okay, you know about distance vector. G'day viewers. In this segment we'll talk about flooding, a useful primitive for routing. So flooding is a mechanism to broadcast a copy of a message from one node to all other nodes in the network. It's called flooding because it really works by making sure that the message appears everywhere. It's flood throughout the entire network, just like water going everywhere. This makes sure it'll be received by everyone. It's a simple mechanism, but somewhat inefficient, such that you wouldn't want to use it regularly a lot of the time. So here is the rule for flooding. Now, I'll remind you that this is a distributed setting, so all nodes are executing this rule in parallel, concurrently, right? And none of them know the overall topology of the network. The rule for flooding is very simple. That's its virtue. Every node, when you receive an incoming message which is meant to be flood to the network, you simply send it out on all of your other links so it will reach all of your other neighbors except where it came from. Great. And there's one condition here just to make sure that we don't keep sending messages round and round in circles. You need to remember the message that you flood in some way so that if you see it again because it arrived at another path, you won't reflood it and keep it going around the network. Flooding is inefficient because one node can receive multiple copies of the message along different network paths. And really, it only needed one copy of the message to see it. The copies that come along the other network paths are wasted in some sense. So let's go through an example just to see how flooding works. Same topology as before for our examples. We're going to flood from A. So I've shown the node that is busy doing the forwarding of messages. It starts at A. I've labeled A in red. A is going to flood the message by sending it to its neighbors. So it will send to B via AB and E via AE. And I've shown both of those floods in blue. So you can see that the message is propagated to the other nodes and has used some of the links. What happens next? So our message reached both B and E. So let me just circle the nodes which were reached. Both of these nodes should now flood. Let's look at B. B received the message from A, so flooding means it should send it on all of the other links. So it's going to send it to C, it's going to send it to E in this way, it's going to send it up to F, and it's going to send it to G. Similarly, E is going to flood by sending it to all of its neighbors. So it will send it down here to D, it will send it down to C, it will send it back to B, and it will send it to F. So you can see this message is really getting copied around the network. So F here has received two copies of it, one from B and one from E. It only wanted one, but it's got two. And B and E actually happen to do their flooding at the same time, so both of them have sent each other the same message. So it's crossed the link between them in both directions. This is what flooding can do. It'll really make sure the message gets everywhere. What next? Well, we've gone through A, B, and E. The other nodes which received the message most recently and haven't yet flooded it were C, D, F, and G. They all need to do their flood. Let's have C do the flood. C received 2 copies of the message, one from B and one from E. So we're going to send it to the other nodes. That's H and D here. D received the message from E, so it can send it to its other neighbor, that's C, down here. So you can see the message has crossed this link between C and D 2 times. Now F is going to flood. F's actually received a copy of the message on 2 links from B and E, so all F has to do is send down to G. And G similarly received it from B, it can send up to F. So F, in fact, you'll see here, is very fortunate or popular. It's got yet another copy of the message. So F has received a copy of this message along all of its links, and it's sent it out once. And finally, we've reached H. H has no one left to flood because it's at a dead end. And we're done with the flooding algorithm. You can see here that the algorithm was fairly simple, and it caused the message to be carried on each link at least once. Each link in at least one direction is maybe a better way to say that. So for a given link, it could have gone in both directions or only one. These pink arrows show you what happened. This is inefficient because really to reach nodes like F, we didn't need to send it along all of these links. We could have omitted many of these messages and we would have still broadcast the message effectively. So there are a couple more details I could tell you about flooding just to complete the algorithm. I said one of the keys here is to remember the message so that you can stop the flood eventually. Well, we only considered one message. This would be harder if many different nodes were using flooding. What is typically done is instead of literally memorizing the whole message, you will, for each source, associate a sequence number and put sequence numbers in the message. That way we might remember that A last flood a message with sequence number 7. If you ever see a message from A whose sequence number is 7 or lower, you know that you've already flooded and not to worry about it. If you see a message from A with a higher sequence number, you assume it's new, flooded, and then update your sequence number. And the flooding we saw was also unreliable. If you want to make flooding reliable, you can simply use the ARQ mechanism we saw. So when we flood and one node sends it to a neighbor, the neighbor can acknowledge that flood. And if the node doesn't receive the acknowledgement, then it can resend the flood message at a later time by using a timeout. This will make sure that we reliably send the information and reliably broadcast it to all of the nodes in the network. So now you know about flooding. Flooding is fairly simple, it's a little inefficient, but it's a good building block or foundation on which to build other more efficient protocols. G'day viewers. In this segment we'll talk about the linked state approach to routing. So our topic is really computing the shortest path that we've talked about previously in a distributed setting that corresponds to a network. We've looked at distance vector routing. Now we'll look at linked state, a very different approach. One in which there are a couple of phases. First everyone floods the information and then we compute the routes. So it's interesting to compare linked state routing with the distance vector approach that we've seen, because they operate quite differently. The distance vector approach spread the work of computing the routes out across all of the nodes of the network. In linked state, we give everyone a copy of the topology and let everyone compute their own routes. So we're really replicating a lot of work in some ways, as opposed to having everyone work cooperatively as in distance vector. So linked state is actually a little closer to that old view of giving everyone a map of the network and then letting them work out their own routes. Now, linked state routing is widely used in practice. It's been around for a long time, almost as long as distance vector. It's been used in the ARPANET since about, what's it say here, 1979 onwards. And many modern networks today use protocols that are based on the linked state approach. Here I mentioned OSPF and ISIS, which we'll just mention very briefly at the end. But these are protocols that would be used in ISP networks, large enterprise networks like on campus or in a big company. They all use this link state approach. Before I dive into the details of the link state approach, let me just remind you of the setting we're working in. This is the same as the setting for distance vector. It's really our distributed setting, which makes routing more complicated than simply looking at a picture and being able to centrally compute things. I'll remind you briefly. So, in this setting, the nodes only know about who they're connected to, their neighbors and their cost to the neighbors. They don't a priori, when they're turned on, know the whole topology. They can only talk to their neighbors using messages to find out what's going on for the network at large. So they have no other way to gain information about the network. All of the nodes are running the same algorithm concurrently. None of the nodes are special, so there's no centralized controller. They're just going to have to agree amongst themselves on what's going on. And they operate in parallel, so they'll have to coordinate their actions. And finally, since this is routing, we would like to be able to deal with failed components. So some of the nodes and links may fail, and we would like the remaining portion of the network that's working to correctly find routes. Messages may also be lost. So that's the setting. What about the link state algorithm? Here's how it works. There are two phases. In the first phase, each node floods information about its local portion of the topology to everyone else using what's called link state packets. In this way, every node will get a picture of the full topology. So we do this whenever the topology changes or when we start. And then, when everyone has the full topology, we'll move from step 1 to step 2. Each node is simply going to compute its own routes and forwarding table. So as you can see, the first step here uses flooding, which we've looked at previously, and the second step uses Dijkstra's algorithm, which we've also looked at previously. Link state really just combines these two steps, and that's how it works. I'll go into just a little more detail. So the first phase, this flooding to disseminate the topology. Each node is going to flood what is called a link state packet that describes their portion of the topology. So I've shown the link state packet for node E here. And you can see from node E, if I just look at node E, its portion of the topology includes a link to D. Actually, let me go through it in order. It includes a link to A, which I'm drawing over here, with cost 10. Then a link to B with cost 4. And you can see in the link state packet, it lists all of the connectivity from node E, so we can see there's a link here to A at cost 10, B at cost 4, and similarly there's C here, D, trace over, and then E, well, there's no connection to E because that's where we are, and there is a connection to F. All of those are listed in this vector with the appropriate cost. That is the link state packet, that's what node E will flood out, and every other node will do similarly for its portion of the topology. Well, once that phase 1 is completed, every node will have received every other node's link state packet. By putting them together, they'll have a picture of the complete topology. Phase 2 is to compute the routes. All we do is have every node run Dijkstra's algorithm. So there's some replicated computation here. The nodes are looking for the source trees from themselves out, and so that can be different in different parts of the topology, although there's definitely some overlap here. Once we find the source tree at a node, we'll be able to compile the forwarding table from it directly. It sort of tells us all we need to know, and that's it. Let's look in just a little more detail to get comfortable with that. Here at node E, again, I've shown the source tree that is the result of running Dijkstra's algorithm. So node E will gain this picture and gain this source tree by itself by going through these steps. And it will then know which way to go to reach all of the nodes. What I've done now from this source tree, all of the different lines here have arrows which show the path to take. For instance, to get from E to A, I follow this path through the network, through here and over here, through ECBA. What I can do now is simply compile it into a forwarding table. The forwarding table lists for every destination the next step. So for instance, to get to A, the next step is simply to forward to C. And that's all E needs to know. C will then take care of the packet from then on. And similarly for all of the other destinations. That's our forwarding table. And if that's all that's going on in the network, we're done. But of course, the whole purpose of routing protocols is to be able to adapt to changes. So when there's any change in the topology because a component has failed, or maybe because a new router or link has been added, we want to redo some of this process, go through the phases again. So you'll flood any updated versions of the link state packets and recompute the routes. Let's look at an example here of just what would happen. What is going to happen when there's a failure is that the nodes that are adjacent to the failed link or node will notice that something's changed. They'll be able to send updated information, and everyone who receives it will be able to recompute. So you can see here, I failed node G. It's gone. Just, I don't know, it blew up. What will happen? Eventually its neighbors B and F should realize that it's gone. They'll need to be exchanging some sort of regular hello message to make sure that it's alive, but eventually when there's no answer, they'll notice that it's gone. At this stage, they can issue updated link state packets. In their link state packets, I've listed the same neighbors as before, but you can see I've changed the cost from both those nodes to reach G to be infinity, meaning this link does not work. The cost is infinite, so don't take it. When that information is spread around, the other nodes will recompute and they'll work out paths which do not go through G. Now, if you think about it, you might notice that there's a subtle difference between a link failure and a node failure. When there is a link failure, then both of the nodes that are adjacent that connect to the link will notice that the link no longer carries packets, so they'll both send updated link state packets saying the cost of that link is infinity. And therefore the link will be removed from the topology effectively when nodes calculate their links. Now imagine though that there's a node failure. This is kind of interesting. Well, all of the neighbors of that node will notice that they can no longer talk to it over the link, so that there's something wrong with the link to the node. Actually, these neighbors don't know whether it's their link to the node that's failed or the node that's failed. Both of these cases look the same. In any case, all of the neighbors of the failed node will notice that something's gone wrong, and they'll be able to issue updated link state packets that say they can't reach that node anymore. The node that's failed, however, won't issue a new link state packet. I mean, it's failed. It can hardly send a message saying, hi, I'm sorry I failed, because it's no longer there. And it's very unlikely we could count on it to issue something saying, I'm going to fail. That's just not the way failures work. However, it's okay here. Because since all of the neighbors send messages saying they can no longer get to that node, the shortest path computation will effectively remove paths which go through the node, even though that node didn't send an update itself saying that its links had changed to cost infinity. It's interesting if you think about it. And just for the sake of completeness, let me mention that there are other changes. For instance, you might add new links or nodes to the topology. In this case, the nodes that have the new links or the new nodes will send updated link state packets. Everyone will learn of extra bits of the topology, and they'll use some of those new links and nodes as they recompute the shortest paths. Really here, additions are the easy case. It's failures where someone fails and can no longer tell everyone they failed, which are the tricky case. But we want routing to be able to adapt to either one, of course. Now, to be fair, I also want to tell you that there are complications in link state protocols. I'm making it sound kind of easy, and I'm describing the normal operation, the normal cases. They work as I've described them. But when you design a protocol, you want it to be correct and work pretty much no matter what happens. And there are some bizarre cases that we could come up with. And I've made up some here. Now, as part of flooding, you have a sequence number on the flood so that we can stop the flood and only flood new information. What's going to happen when this sequence number reaches its maximum? We could make that maximum very high, but then what's going to happen if the sequence number somehow gets corrupted to a very high number and gets close to the maximum? This seems very unlikely, but the point is we don't want the network to be jammed up permanently if this happens. Another case would be that a node might crash And when it comes back up, it's forgotten what sequence number it was using before. It can't just start at 0 again because other nodes might know higher sequence numbers for its messages that are flood, and so they won't listen to the low-numbered sequence messages. Or, other bizarre cases, the network could partition itself. It could divide into two components due to failures. Both of these components could evolve independently, and then when the network connects itself again, each side could think the other portion of the network is in a different state, and we would need to fix that. Wow, this is a little messy. Really, a lot of the complexity of real protocols has to do with handling these corner cases, so that things work well in the common case, but they are correct even in these weird cases. I'm not going to go into these complications in any detail at all. I just want to point out to you that it's important that real protocols handle them. You can read a little bit more about them in your text. I'll tell you one strategy that's used, and that is aging. It's very useful. So one strategy that's used is that we include a timestamp on all of the link state packets and most information that goes around networks. If this information is not refreshed over time because whatever created it has gone away, then we forget the old information. This tends to remove old information which is no longer relevant from our network and lets the network get on and adapt to the real situation that we're now faced with. So this is used in link state protocols, but it's also a generally useful strategy. Okay, what else about link state? One thing we've reached now that we've gone over it, is we can compare it briefly with distance vector. This is useful just to see some of the differences between the two. Here's a table that lists our goals for routing protocols from long ago, and we'll see how the two stack up. Now, for correctness, we wanted to be able to calculate correct paths even in this distributed environment. The two approaches use different algorithms. Link state's based on Dijkstra with some replication. Distance vector is based on a version of the Bellman-Ford algorithm, which has been distributed. Okay, different approaches, but they both work. In terms of efficient and fair paths, we're using our shortest path framework where we assign costs to links for both. It's the same in both. Well, where they differ a little bit is in these last two entries. Convergence, we would like rapid convergence to the new routes after any kind of change to the topology, like a failure. We've seen that distance vector can be slow in some cases. It can have this count to infinity and require many exchanges. Whereas link state generally tends to provide fast convergence. All you have to do is flood the new topology and everyone recomputes, so it wins here. In terms of scalability, however, the trade-off is the other way around. Distance vector really has excellent scalability in terms of storage and computation at a node because it does the minimum. We just have, the list of nodes. The computation is really adding numbers and comparing them. You can't beat it. Link state, on the other hand, has more computation. The amount of computing we need to do and storage to store the whole graph grows superlinearly with the network, so it increases more rapidly than the size of the network. So distance vector actually wins in terms of scalability here. It's an interesting trade-off. Okay, and finally, I'll just mention a couple of real protocols which use the link state approach. And they are ISIS, Intermediate System to Intermediate System, and OSPF, Open Shortest Path First. OSPF is really the IETF or Internet version of the ISIS protocol, which had its roots more on the OSI side of the house. These are modern link state protocols. They're very widely used in ISPs and large enterprises. They have supplanted distance vector protocols because they have different, better convergence behavior. Even though they require a little more computation, well, computation's gotten cheaper over time. The basic operation is as I've described it, so you know the heart of how they work with the link state protocol. I'll also tell you they have many more features that are added. There are notions, for instance, of different kind of regions so that will help to scale the protocol to larger networks, or stub areas, so that it's easy to compute routes for stub areas. You just need to, if you're in it, go out. You don't need to worry about doing a lot of shortest path computation. Don't worry too much about these features. There are many of them in any real protocol. And I'm just mentioning them so you have some sense. But you know how these protocols work, and now you have a sense of the link state approach to routing. G'day viewers. In this segment we'll talk about equal cost multipath routing. That's a mouthful, but it's really an extension to the shortest path routes we've seen before. What we would like to do now is to allow the use of multiple routes between a given node and a destination. In everything we've seen so far with the shortest path formulation, we picked a single path from a node to a destination. But what if you want to allow multiple paths? For instance, in this network, to get from A to E, you could see I could take this path here, or there's another path through the topology, which actually turned out to be our shortest path before. I could allow both of these to be used at the same time. That's what we're going to look at. The general name for this procedure is multipath routing, the use of multiple paths. Now, these multiple paths usually exist in the topology already. And the reason for that is you want to provide enough links in your network topology for redundancy. In case one link fails, you want to be able to have a different link to reach a destination. So there probably were multiple paths somehow. We would just like to be able to use them both at the same time during forwarding. And the reason for this is simply to improve performance. Maybe we can fit more traffic through the network if we can use these multiple paths. What we're going to look at now is really a simple extension to our framework so far to incorporate multiple paths. It's fairly straightforward. There are really two questions we need to answer. How do we find these multiple paths as opposed to finding a single path we did before? And when we have them, how do we use them for forwarding? So the first question is about routing, the second question is about forwarding. Given that we have multiple paths, how do we use them at the same time to send traffic? So let's go through these questions, and we'll do it in the context of equal cost multipath routing. This is really one form of multipath routing, which is an extension of our shortest path model. All we do here, the extension really is to keep a set of next hops and routes if there are ties. Previously, we just chose one randomly when the costs happened to be the same. There was one that was not a unique minimum cost. So here's our picture of a network again, just to illustrate that. And I've changed a few of the costs here in red. And I've changed it so that, now we're going to have some paths, multiple paths, which have the same minimum cost. So you can see them in this graph. I've sketched them, but we can just compute them to make sure that they're okay. The path ABE is one way to get from A to E. That has cost 8, okay? Well, there's also another path, and that is the path A, B, C, E. That has cost 4 plus 2 is 8 again. And there's even another path which goes A, B, C, D, E. That is more hops, but it happens that the cost of these hops is lower, and so when you add it up, guess what you get again? 8. All of these paths are the minimum path, and in our equal cost multipath formulation, we'd like to use them all. Now, equal cost multipath, since it generalizes shortest path routing, it actually changes our notion of a source tree and a sink tree. With ECMP, these source and sink trees are actually not trees anymore. They become a slightly more general structure called a DAG, which stands for a directed acyclic graph. Now, in a normal tree, we have a structure like this on the left, and you can see just a classic hierarchical tree there. To get to a particular destination, there's just one next hop. In a DAG, however, you can see I've added some of these cross links. Every node can have a set of next hops that it can use to reach a destination. So for instance, there are two paths through here from the source to the one destination. So that means from the root, I could go either of two different ways and I would still be able to arrive at this same particular node down at the bottom. It's a DAG, it's acyclic, so there are no cycles or loops in this topology. As you follow paths through here, you'll definitely get to a destination without going round and round in loops. So we haven't admitted loops. There's also still a compact representation for routing. Each node now has not a single next hop, but a set of next hops to reach a destination. But we don't need to have nodes store the entire path or anything like that. Let's just see a little bit of an example. Here's our graph again. Now we'd like to find the source tree, or really DAG, for E. The procedure that we go through is simply Dijkstra, but keep all of the ties instead of randomly picking one. And then once we've got this tree, we'll be able to compile it into a forwarding table. I'm not going to show you here, but you'll find that as well as Dijkstra, there's also a straightforward extension for distance vector, where instead of choosing one minimum cost route, you can keep multiple of the minimum cost routes, the set of neighbors if you like. Okay, let's see that source tree for E. Well, let's see, I'm going to start going out with minimum cost. From E we can reach D here. Now at distance 2 we can get to F, we can get to C. Now interestingly, this is where things have been added. I can get to C in two different ways. The direct loop route here and via D. It still costs 2. And we can then go on adding other paths through the network. So for instance, to get to H, well, let me do B first. To get to B, you can get to B here over this loop, but you can also get to B along this path. They both have cost 4. And similarly, we're going to get to A along here, H along here, and F along here. None of this has changed. And this is the shortest path, the source tree, which is really a directed acyclic graph. If I just flip ahead, you'll see, now hopefully they were actually the same as what I drew, that there are 2 new lines here that really got added with the ECMP case. Just tracing over them. We can now compile, so this is just a source tree as before, but a slight generalization of it. You can verify that for yourself. We can now compile this into a forwarding table. It's the same procedure as before, just mapping from a tree down to all we need to do is remember the next hops. But you'll notice here that to get to certain destinations, I have a choice of next hops. One of the biggest ones is to get from E to A. I can go many different ways. We had seen I could go this way. These are the examples I sketched before. I could go this way, or I could go this way. 3 different paths, all of minimum cost 8. That means from E, I could choose any of B, C, or D as the next hop, and you can see that in the table. Now instead of one entry, we have multiple entries. And you can go through the rest of the table, and you can see that I've colored in pink there some of the entries that now differ. They have sets instead of the single next hop. Well, that's it for the routing. What about the forwarding? We like to forward with these equal cost multipaths. One way you could do this is when you have a packet, since you only want to send the packet down to one neighbor, otherwise we'll be making copies of it. You could simply choose at random for every packet which of the next hops to use. That's this option here. That's actually very effective in terms of balancing traffic across all of the different paths. However, it adds jitter. Now what I mean by this is that the different nodes going from a given source to a given destination might experience quite different delays through the network. For instance, maybe if you send packets 1, 2, 3, 4 at a particular node, 1 and 3 and 4 will all take a certain choice, which is a shorter path physically. And in terms of seconds, the cost is going to be the same. Whereas path 2 might randomly be chosen to take a different next hop, which will be a more circuitous route, which will take longer. So we might send packets 1, 2, 3, 4, but they might be received at the destination 1, 3, 4, because they took the short path, and a long time later, packet 2 will arrive. You can imagine this can get a little complicated for the receiver to work out things. So we would like to avoid these kind of effects. So instead, what we'll try to do is send packets from a given source-destination pair on the same path. This is, imagine if you've got a video conference. It's between it's a set of traffic or a flow, this is sometimes called, traffic between a particular source-destination pair, often for a particular purpose, is called a flow. We would like to send the traffic from a given flow along the same path through the network. This way, the ordering of packets within it should be preserved. We shouldn't get any of this wild jitter. So all we do to handle this is we make the choice not at random per packet, but we map a flow to a single next hop. How do we do this? Well, here's an example. I've shown the paths here, just a segment of the paths that range from F to H. And you can see we have different paths through the network. We might go this way, or we might go this way. This also includes, by the way, the paths from E to H. We can take those different choices, and the paths from F to C, and the paths from E to C as well as E to H. Well, I said one twice there, but you can see that there are 4 different source-destination pairs. I've listed them here as flows, traffic from F to H and F to C, as well as E to H and E to C. Now, for all of these different flows, as they go through E, they could be sent either to C or D. Instead of choosing at random, we'll simply make this set of choices. For the packets that come from F, we'll send them to D. And for the packets that come from E, when they're going to H or C, we'll send them to C as a next hop. In this way, we have some consistency for the flows. But if we think about traffic that's heading towards C, we're actually using both of the next hops. We're using D and C. So traffic towards those destinations is utilizing multiple different paths through the network in parallel. And that's how we forward with ECMP. Now you know this slight generalization of the shortest paths we've seen before. G'day viewers. In this short segment we'll talk about how hosts and routers are combined in the internet for the purpose of routing. Now this topic is really just to provide a little bit of a bridge, because we've talked about routing and nodes, but we've also talked about forwarding and said that there is a distinction between hosts and routers. Routers route and hosts don't, and we would like to glue them together into a network. Just to recap that slightly and remind you what's going on, here's what I've told you before. In the internet, hosts on the same network have IP addresses that come from the same prefix. We do this in order to be able to scale routing and assign addresses. And the way hosts handle the issue of routing is that they send any traffic that is not for a local host that has to go off the network. They just send it to the nearest router. They don't need to know what the router does with it. Their rule is simply, if you don't know, if it's not on the local network, send it to the router. Routers, on the other hand, have to talk to one another and discover the routes to use to get packets to every address in the internet. And the way they do this and implement this is that they use a longest prefix matching algorithm on their forwarding table to decide what next hop to send a packet to based on their address. Okay, so let's try and put these pieces together. Here is how hosts and routers would be combined in a network. Now the networks I've drawn have pictures here like a router. Here's a router A, and that router has links that connect it to the rest of the network. That's fine. That's mostly what we've seen with our pictures of graphs. The dots represent all of the different routers which are doing the routing. But we also have hosts in these networks, so where do they fit? Well, the hosts are attached to the routers. Now often there is like a switch, a LAN switch here, so that we can attach multiple different hosts to the same LAN. As far as the router is concerned, all of these hosts are reachable over that one wire or wireless link. And even though there are multiple hosts here, it's really a single network, a single prefix that they're all representing. Whether it's one host or many, they're all on the same prefix. So if I just draw that as the topology, this is the situation I have. All of these other nodes before, A and B and E, really are what we saw in the other diagrams. Here's maybe a portion of it. E and B go off to the rest of the network. But what we do to add the hosts is we add them by adding a link from a router towards one prefix, which represents all of the different hosts. And that way we've connected the host to our network. Now what do we do? Well, now all we do is proceed with the routing algorithms exactly as I've described, and they all just work. The routers, what they're going to do, now that they're connected to this prefix to represent the host, is they will advertise the IP prefixes for the hosts. It will just go out, instead of a single node address, it's a prefix. This fits, by the way, with the way they advertise their own addresses. a router address, an individual address, is really like a /32 prefix. It's most specific. It's a block of addresses with one address in it. When they do this, all of the routers will be able to find a path to all of the different prefixes that have been sent around, and this will allow them to find a path to all of the different hosts. Great. The hosts are also able to fit into this equation because they have this simple routing rule that says essentially they don't route. If it's not for someone on the local network where they can reach directly, then they simply send to the router, and the router knows the route to all of the other hosts in the network. And we're done. This is really just a little bit of glue so that you can be clear on how we plug our routing algorithms together with the host forwarding behaviors we've seen in IP. G'day viewers. In this short segment we'll talk about how hosts and routers are combined in the internet for the purpose of routing. Now this topic is really just to provide a little bit of a bridge, because we've talked about routing and nodes, but we've also talked about forwarding and said that there is a distinction between hosts and routers. Routers route and hosts don't, and we would like to glue them together into a network. Just to recap that slightly and remind you what's going on, here's what I've told you before. In the internet, hosts on the same network have IP addresses that come from the same prefix. We do this in order to be able to scale routing and assign addresses. And the way hosts handle the issue of routing is that they send any traffic that is not for a local host that has to go off the network. They just send it to the nearest router. They don't need to know what the router does with it. Their rule is simply, if you don't know, if it's not on the local network, send it to the router. Routers, on the other hand, have to talk to one another and discover the routes to use to get packets to every address in the internet. And the way they do this and implement this is that they use a longest prefix matching algorithm on their forwarding table to decide what next hop to send a packet to based on their address. Okay, so let's try and put these pieces together. Here is how hosts and routers would be combined in a network. Now the networks I've drawn have pictures here like a router. Here's a router A, and that router has links that connect it to the rest of the network. That's fine. That's mostly what we've seen with our pictures of graphs. The dots represent all of the different routers which are doing the routing. But we also have hosts in these networks, so where do they fit? Well, the hosts are attached to the routers. Now often there is like a LAN switch here so that we can attach multiple different hosts to the same LAN. As far as the router is concerned, all of these hosts are reachable over that one wire or wireless link. And even though there are multiple hosts here, it's really a single network, a single prefix that they're all representing. Whether it's one host or many, they're all on the same prefix. So if I just draw that as the topology, this is the situation I have. All of these other nodes before, A and B and E, really are what we saw in the other diagrams. Here's maybe a portion of it. E and B go off to the rest of the network. But what we do to add the hosts is we add them by adding a link from a router towards one prefix which represents all of the different hosts. And that way we've connected the host to our network. Now what do we do? Well, now all we do is proceed with the routing algorithms exactly as I've described, and they all just work. The routers, what they're going to do, now that they're connected to this prefix to represent the host, is they will advertise the IP prefixes for the hosts. It will just go out, instead of a single node address, it's a prefix. This fits, by the way, with the way they advertise their own addresses. A router address, an individual address, is really like a /32 prefix. It's most specific. It's a block of addresses with one address in it. When they do this, all of the routers will be able to find a path to all of the different prefixes that have been sent around, and this will allow them to find a path to all of the different hosts. Great. The hosts are also able to fit into this equation because they have this simple routing rule that says essentially they don't route. If it's not for someone on the local network where they can reach directly, then they simply send to the router, and the router knows the route to all of the other hosts in the network. And we're done. This is really just a little bit of glue so that you can be clear on how we plug our routing algorithms together with the host forwarding behaviors we've seen in IP. G'day viewers. In this segment we'll talk about hierarchical routing. So our topic here is really how to scale routing to very large networks, and the technique we're going to use is hierarchy, where we route not to an individual node but to a large region of the network. So before we get into that, I'd like to give you a little bit of motivation. Here's a slide you've seen before about internet growth. We're growing very rapidly. There are now more than 1 billion internet hosts and growing. And of course, the previous slide was just the number of internet hosts. This slide shows the growth of the internet routing tables, which are the tables which are maintained in routers to be able to forward packets to all directions. This table is also growing very rapidly. You can see pretty much exponential growth. And just looking at the axis, right now, as of about 2013, the number of IP prefixes in a router in the middle of the internet that's got to be able to reach everywhere is around 450,000. That's a lot. The impact of all of this routing growth is bad in pretty much every dimension you look at. You might look at the size of the forwarding tables that need to be kept in memory. That's growing. That's the one that's reached 450,000. That means both larger tables, so more memory in routers, and it could potentially mean an increase in lookup time depending how it's done. As well as the size of the forwarding table itself, another concern is the number of routing messages which need to be sent around. As there are more places and addresses to reach, the number of routing messages continues to grow. And it can actually grow very quickly because not only are there more locations, but we need to be able to inform every node about what's going on in terms of paths to reach every other node. So there's a lot of growth there. And finally, the routing computation itself grows. If every node gets to learn enough about a topology to be able to compute routes, the computation over this graph grows faster than the size of the network. It's superlinear in terms of the amount of work that needs to be done. So this is all bad. Routing growth is going to stress the network. We would like to come up with techniques to scale routing so that it can more gracefully handle a large network. What are those techniques? Well, I'm glad you asked because I've written them down here. In fact, we've seen some of them. The first technique here is the use of IP prefixes, where we don't have an entry in the table for every individual host. Rather, we have an entry for a block of hosts called an IP prefix. We've seen how IP prefixes work. In this segment, we're going to talk about network hierarchy, which is the routing to the different regions of the network. And then, in a future segment, we'll talk about IP prefix aggregation, which essentially are more games you can play to join or split prefixes that use hierarchy in different ways. We'll see that later. So let's look at hierarchical routing, that's our focus here, in a little more detail and find out what it actually is. So the overall goal here is to introduce some kind of larger routing unit and be able to structure tables so that they send packets towards that unit. We've already seen that we now have IP prefixes, which are groups of hosts. That's a larger routing unit from an individual host. That's great. We want to build on that. And we'll build on that by introducing the notion of a region of the network. This might be a complete ISP network, for instance, but I'll just call it a region for now. And we would like to change our routing procedure so that we route first to the region, and then when we've arrived at the region, we route to the particular node within the region. This is really no different than, to pick a real-world example, navigating by driving to the city you're trying to reach, and only when you get to the city, trying to find a particular address and worrying about how to get around the city. What we're doing here, really, the gain that we'll get for routing is that we'll hide the details that are internal to the region from everyone outside of that region. Well, I'm sure you get the sort of theory of how we could use hierarchy in regions, but let's go through an example to make some of this concrete and make sure we understand it. So I have a network here on the left, and you can see that there are 5 different regions, and within each region there are a few nodes connected together, and the regions are connected together too. Now every node in this network is going to have its own forwarding table so that it can send packets in different directions. The forwarding table here is shown for node 1A. That's this big long table. You can see it lists all of the other nodes and which output line, which next hop to get there, and how many hops away. So this is shortest path where the distance is simply the number of hops. So this is the kind of table you would get, this large table, if you use the techniques we have so far. On the right, I have the hierarchical table for 1A. Now you notice in this table, it lists in detail, it has the same entries for entries within region 1, because it's 1A, that's 1A, 1B and 1C. Well, 1A, not hard to get to since you're already there. However, the other entries have been collapsed. If you look at the full table, it had 4 entries for network for region 2. That's collapsed into a single entry. We don't care about differences here. We just want to know which way to go to get to region 2. Similarly, region 3 has been collapsed into a single entry, and region 4 and region 5. Oops, my arrows are a little off there, but you get the idea. Okay, so we now have a much smaller table. We can also use it to route. Let's just see, here we have a packet that's trying to go from 1A to 5C, and I've colored in those nodes just so you can see them on the graph. At 1A, we can look up the decision for 5C. Now, since this is a hierarchical table, there's no entry for 5C in particular. There's just a blanket entry for 5. It's this last one. It says to get to region 5, go via 1C, and it's going to be 4 hops. So we'll go here. We don't have the table for 1C written down, but the reason we went here, of course, is to go this way. And you can imagine that the path we will take to get to 5C, that's this path. Let me just clean up this figure. Okay, so you can see the path we took to get from 1A to 5C. And we could perform the same exercise for different paths through this network. But I chose this path for a reason. And that's to illustrate the penalty that we can pay sometimes when we use hierarchical routing. For most of the paths we're using hierarchical routing, their distance that we take in hops when we follow them is the same, even if we didn't use hierarchical routing, and we've just got a smaller table. But for some paths, we can actually end up taking slightly longer paths than the shortest possible path. That's the example here. Now you can see in the full entry, the full table, from 1A, if I want to go to 5C, it's this entry here, it says I can get there in 5 hops going via 1B. And you can see I've put in blue on the diagram the path we would have taken to get there. And you can count it and you can see that it's 5 hops. However, in the hierarchical routing version, the best route to get to region 5 is simply given here as 1C, and that took us along the other path. That's because we've forgotten about all of the detail inside region 5, and we simply wanted to get into region 5 as quickly as possible. So that's the penalty we might pay sometimes. And just to close on this, I'll make a couple of observations about hierarchical routing, just to reinforce the concept. So the main concept here is that outside a region, every node has a route to all hosts within that region. We're hiding what's inside that region. We don't worry about it when we're far away. This is what gives us the savings in table size. They can be substantial. It's also a savings in terms of messages and computation. We also get benefits there, even though we didn't look at them in detail. One thing I want to point out, though, because it's sometimes a source of confusion, is this doesn't mean that all nodes inside a region need to take the same path towards another region. They typically don't. Every node has a path to a region for all destinations in that region, but every node could take a different path to reach the same region. And the reason for this is that routing decisions are still being made individually by nodes. It's just we're looking at the routing decision to reach an entire region. There's no notion of taking a single decision that everyone within a region has to follow to get somewhere else. Okay, now you know about hierarchical routing. G'day viewers. In this segment we'll talk about things you can do with IP prefixes, aggregating, joining them together, and subdividing them to split them up. Our topic here really is how to help scale the routing of the internet, as well as improve its management, and we can do that by adjusting the size of IP prefixes. And in particular we'll look at two ways to adjust the size. We might split up a large prefix into smaller subnets, or we might join together several prefixes and aggregate them into a larger prefix. So just a little bit of background. So recall that IP addresses, as we've gone through, they're allocated in blocks called IP prefixes, such as this prefix, 18.31.00.16. And a key observation is the hosts on one network share the same prefix. Now, just as a quick reminder, because they share the same prefix, we can route towards the prefix. That's where we're getting scalability in routing, as we've gone over. Just as a reminder, let's work through an example here. A /n prefix has the first n bits fixed, and so it contains the other 32 minus n bits are free, so it contains 2 to the 32 minus n addresses. So for instance, the /24 will have 8 bits free, so it will contain actually 2 to the power of 8 addresses. Oh, that's not very clear. 2 to the 8 is 256 addresses. And a /16 will have 2 to the 16 addresses in it, and that is, what's that, 64k addresses, 64,000 different addresses, or 65,000 actually if you compute all of the numbers out. Okay, now, the key flexibility that we get from using prefixes is that actually it's routers that keep track of the length of different prefixes. They use it for the longest prefix matching algorithm to decide which way to forward traffic. Now, because it's routers that keep track of the length of prefixes, not hosts, the key flexibility we gain with prefixes is that routers can change the lengths of prefixes without affecting the hosts for the most part. In particular, we can change an IP prefix to make it more specific by lengthening the prefix, turning it into a block which has fewer addresses, so dividing a big block into blocks with fewer addresses. Or we can change the prefix to make it less specific, and we can take several blocks and then join them together into a bigger block, which is the less specific prefix. Well, let's just go over a little bit how that would work. Here is just an example of the sort of thing we're going to do. In this figure down here, we have 3/18 prefixes, IP1, IP2, and IP3. And what we'll do when we use aggregation is we would join those together, for instance, into one larger /16, if all of the addresses were of the right form such that we could aggregate them. That /16 would then represent the whole region here, and we'd be able to route towards that, for instance. So, in fact, there are two different use cases which are really just converses that allow us to adjust the size of IP prefixes. Both of them are taking advantage of hierarchy in slightly different ways, and they'll help us both manage the network and to reduce the size of the routing table. We're really after scalability by doing this. So what are the two use cases? One is that you can do what's called subnetting. You can divide a large prefix which has many addresses into more specifics, multiple more specifics, each of which represents a smaller network. These are then, or a smaller portion of the network. These more specifics, prefixes, are then called the subnets. And in this way, you can acquire a big block of addresses or a block of addresses from your ISP, and you can divide it up into different chunks to help you use it most effectively within your organization. The converse side of this is aggregation. Externally, we might have IP prefixes for several networks, and we might be able to join them together into a more specific, into one large prefix, which is a less specific prefix. We take all of those more specifics and we join it into less specific prefixes, which will represent a larger number of addresses. We can do this if all of the addresses are about right, if they're in the same portion of the address space, so that they could be aggregated. Let's see an example of how this would work. So here, externally, maybe this is a company here. You can see the line is dividing it. The company is to this side, and here's the rest of the internet. So from the ISP, the company has acquired this IP prefix here for all of its computers, 128.208.00/16. So it's a /16, so it has 64K different addresses. Well, internally, it might want to divide that into different structure because often there is structure inside an organization. Here it's a university and we have the E, CS and art departments. So what are they going to do? Well, internally, they could divide a /16 up into a /17, a /18 and a /19. There's actually a little bit left over. Now, I'll let you go ahead and afterwards work out all of the different addresses here, just to see that in fact this block of addresses, if you draw the address space, has been divided up properly. It looks like the /18 here starts at the very bottom of the address range. The /17, it looks like it starts about halfway through the address range and then goes up. And there's also a /19 somewhere in there above the /18. And there's actually a little bit of space left over. It can be a little confusing unless you look at the values of the binary in binary and draw a bit of a map of how the address space has been divided. And here's an example of the flip side. I might have three different universities here, Cambridge, Oxford and Edinburgh, have a /21, a /20 and a /22. Now, it just so happens that these prefixes are also chosen from address space, which is quite close. It's all related. In fact, it all forms a larger block. I can aggregate those prefixes so into a single /19 is large enough to contain all of the IP addresses in here. And you can see here's the address of the /19, the lowest address in the /19. And again, to really understand how these prefixes have been joined, you need to be able to write down the top and bottom address for all of these things and see how they relate and for the size of the prefixes and the size of the overall block. But there's an example of subnets and aggregation and adjusting IP prefixes to suit our needs. G'day viewers. In this segment we'll talk about routing when there are multiple parties in the network. So this formulation for routing is very much like the internet in which we work. The network is comprised of multiple parties altogether, and in the internet here they're the ISPs. You can see 3 ISPs here. And the complication is that each of these parties might have its own goals, its own idea about what would be a good route. Yet somehow they all need to work together to be able to get traffic, from a source to a particular destination across the network. Okay, so first of all, let's just drill down on the overall formulation a little bit by looking at the structure of the internet to give us a better idea of what we're talking about. So here's a picture of the internet architecture, and you can see that there are a series of different networks here that are shown. There are 1, 2, 3, 4, 5, 6 different networks that are connected here. The networks act as they source and sync traffic. They have different prefixes here. We talked about prefixes being blocks of IP addresses. They're everywhere here. These are all the sources and destinations on the networks. Now there are different kinds of networks. ISP networks host customers here. CDN networks provide content which is often delivered to the customers at ISPs. There are maybe other kinds of networks, enterprise networks and so forth. All of these different networks are richly interconnected with one another in all sorts of different ways. They might be connected directly, but it's a common strategy that many different networks will actually connect together. They will connect to what's called an IXP. IXP stands for Internet Exchange Point. And an IXP is really a meeting place where many different networks can come together and exchange traffic. Now, our routing problem is that somehow, even though these are all different networks run by different people, and hence they have different ideas of what routes they would like to choose, we want to be able to find routes from a source, let's say the CDN here is sending traffic, somehow to reach a particular destination, such as a customer here within this ISP. Well, we'll get to how exactly we do that in a moment. What I want to talk about first of all are just the issues which are introduced by this internet-wide view of routing across multiple parties. Because really, these multiple parties bring in two different problems that go beyond what we've seen in routing in individual networks. The first one is just of scale. We now have a very large network because we're gluing all of the different networks we could think of together to form the internet. So we're going to need to use techniques to improve the scaling of the network. We've already seen things like IP prefixes and how they provide hierarchy, and we'll see other kinds of the scaling techniques that will be used, such as prefix aggregation. I guess we talked about that, but we'll also see the use of how we can use these parties also for a bit of scaling that's going to help. The other thing that I want to talk about in more detail, because this is really what's unique to the multiple parties, is that we need to incorporate what are called policy decisions. Each different party, I've said before this abstract statement, they might have their own idea about what constitutes a good route. So they might want to choose routes, or at least portions of routes, to suit their own needs. The way they choose it is described according to a policy. So I said yikes here because, what's going to happen to the overall route when different people are trying to choose different portions of it? Will it even work? That's exactly the issue. In fact, having different parties in the network with different preferences can lead to some strange effects. So let's look at the kinds of things that can and do happen in the internet today. So here's a simple model network. We have two ISPs, ISP A on the left and ISP B on the right. Now, the policy for each of these ISPs is that they want to choose the shortest path within their own network. Why? Well, if they carry the traffic the shorter distance, it'll probably be cheaper, and that way it'll be more cost effective to run the network. Okay, that seems like a pretty reasonable policy. And actually, you might think that if everyone chooses short routes, everything would all be fine. But let's see and that we would get short routes overall. That's not quite what's going to happen. Let's look at what happens. Let's consider, amongst all of the different prefixes we have here, just the path that gets chosen between traffic going from A2 to B1. So here is A2. We start inside ISP A. ISP A gets to control how traffic goes through its network. So from here, we want to send it along the shortest path to reach B2. Well, we could go via any of these different points, these links which connect to ISP B to reach prefix B1. This is where we're trying to reach, not B2. So which of these am I going to choose? Well, I'm going to choose the one that's closest to wherever I am because that will be the shortest path in the network. Now, I've drawn this figure so I can tell you that this one is the shortest path. So then we'll go over this segment here, out the network, we'll land in ISP B here, and we'll take the most direct path to B1 here. Okay, it's a little bit of a roundabout path, as you can see. Well, what about the path from B1 to A2? Okay, well, I start in B1, I'm going to go back, but I similarly want to go to ISP A to reach prefix A2. I could use any of these three exit points, which I'm drawing. The closest one is this top one here. So I will go there, and then across the link. Then within ISP A, I'll go directly to prefix A2. So you can see here the result of the best paths that would be found according to these two policies, if we could somehow come up with a mechanism to find them. And I've just cleaned up this diagram to draw them, and I'd like to make a few points about these paths, because they're not quite what you might expect. If we had done one overall routing formulation and called this one big happy network, we would have found the shortest path between these 2 points. Actually, both of the shortest paths both of the paths which are selected according to these policies, from A2 to B1 and back, neither of them are the shortest path. The shortest path here is the one that's shown in the pink. I'm tracing over it. And we took a different path in one direction that was longer and a different path in the other direction, which was also longer than the shortest path. Not only that, but the two paths are different in different directions, so they're asymmetric. So you can see that policy routing, in fact these effects are common in the internet, policy routing often leads to asymmetric paths where it's different going from A to B than B to A, and often paths which are not quite shortest. And these effects are really consequences of the independent goals and decisions which have been made by the parties, rather than simply the effect of hierarchy hiding a bit of information causing us to take longer paths. We've seen that effect too. Well, so this is what we're up against. What I'm going to do now is talk just a little bit about policies, and then we'll have fulfilled our goal of just understanding the formulation for routing with multiple parties and what policies are. And later in the next segment, we'll move on to BGP, the protocol which finds policy routes in the internet today. So policies, the idea with policies is that they'll capture the goals of the different parties. Now, policy is this general word, and that's because it's abstract, because policies could actually be anything. Here's an example of a real policy. The Internet 2 is a research and education network in the United States that's used to connect universities. One of its policies is that it will only carry non-commercial traffic. So it will carry traffic between educational institutions, so UW to MIT and back, but it won't carry traffic from those educational institutions to commercial networks, so that we could all surf Google, for instance. Why? Well, that's just its acceptable use policy, because that's what the network is for, and that's a condition of funding the network. So the routes will be computed to comply with this. That's one policy. In fact, we don't know for all of the commercial networks exactly what their policies are, because these are proprietary. They can depend on the two different parties that are connecting, can have all sorts of different policy. What we're going to do instead is talk about two common policies. I'm going to talk about the policy of transit. ISPs give transit service to their customers. That's one kind of common example of a policy that's often held up. And we'll talk about a different kind of policy called a peering service, where an ISP provides a peering kind of service. Two ISPs often provide a peering service to one another under some situation. So let's look at those two policies. Well, here's this transit service. So the idea of transit service is that one party in this deal, that's the customer who's going to pay for this, is going to get what's called transit service from another party, the ISP. So transit service is what you get when you connect to your ISP. You're paying it for transit service. And the idea of transit service, the policy, is that the ISP party, I'm going to refer to them as just the ISP and the customer, will accept traffic from the customer and make sure that traffic can be delivered to anywhere else in the network. So you're a customer here, you can hand packets to your ISP and destined for wherever, and your ISP will somehow send them to the rest of the internet, and where they will reach customers who are outside that ISP. Similarly, your ISP will accept traffic from the rest of the internet and deliver it to you. So some traffic could come from here, and the ISP will accept this traffic because it's for you and make sure that it gets to you. And you, the customer, generally pay for this privilege. When we connect to the internet, pricing often depends on the amount of bandwidth we have, the size of our DSL link, how rapidly it can send information. But often what we're really paying for, as well as the size, is connectivity to the rest of the internet, the ability to send traffic and receive traffic from all of the other destinations that are out there. And the transit policy is providing us that. But there are other kinds of policies too. And here's our peering policy. In this policy, we have two parties. I have ISP A on the left and ISP B on the right. These parties are both going to give one another, they're going to use a policy which gives peer service to each other. Now, in peer service, each ISP accepts traffic from the other ISP only when it's for the customers, to and from their customers. So I have the two customers down here, and you can see we can send from one customer to the other across this link and back. And similarly for the customers up here, we could do the same. Okay, that's great. You might wonder what I precluded by that. Well, actually, why is this not transit service? Well, here's what ISPs don't do. ISPs do not carry traffic to the rest of the internet for each other. So, in fact, customer A1 can't send via this link to reach some other place on the internet. Not allowed. I'm going to cross that off. Not allowed. We don't do that. Why? Because that's not part of the peer policy. So it will allow, the ISPs will allow these routes just between their customers, but not further out. And as a consequence of this, both ISPs are sort of doing one another a favor, because by doing this, they then don't have to send traffic via a transit provider and pay for it. And usually, as part of peer service, we say that the ISPs don't pay one another because they're both providing value for each other. So these are the two policies that we've seen. And in the next segment, we'll look at a mechanism called BGP, a protocol, which finds these kinds of routes in the internet today. G'day viewers. In this segment, we'll talk about the Border Gateway Protocol, which is used to find routes across the internet. So we talked before about the fact that the internet is comprised of multiple independently run parties, such as ISPs, and we need to find routes across those parties that respect the policy constraints of the different parties. What we haven't told you so far is how those routes are actually found. Well, in the internet, it's with a protocol called BGP. In this segment, I'm going to give you a brief introduction to some of the issues that we find in BGP, rather than extensive coverage, because BGP is kind of complicated, and you might go over more details in an advanced networking course. Okay, so just as context, recall that we're viewing the internet as made up of all of these different independently run networks. We have here content distribution networks, ISPs, and just generic networks here. And we might be trying to find paths through this network from a source here, say, prefix C1, acting as a source address. That's going to send along some path through the internet to get to a destination here, such as A1. Now, which path will be chosen through this graph? Well, I've just picked an arbitrary path there, but the routing protocol needs to decide which one will actually be used. And that's exactly what BGP does. So here's just an overview of some of the aspects of BGP, and then we'll move into some examples. So BGP computes interdomain routes, as they're called. These are routes across different entities, such as across ISPs in the internet, as distinct from intra-domain routes. Intra-domain routes are routes within one single network, such as within an ISP. Now, we've already talked about distance vector and link state protocol methods for computing routes. BGP, it turns out, is what's called a path vector protocol. It's closely related to a distance vector protocol, but a little more general. In a path vector protocol, what happens is that route announcements, which carry the path from the point in the network back towards a destination, are propagated throughout the internet. So you can see here the blue line is meant to represent a route announcement, which is propagating out in the network. It's propagating out from prefix F1, so it's going to tell people how to get to F1. And if we look at it inside ISPA, we might receive a route announcement that says something like, well, to get to prefix F1, that's the destination here, here is a path you can use. It goes ISPB netf. Well, they are the networks through which you go along this path once you leave your ISPA to get to the destination. And the way you access this path, the next hop is to go via the IXP. That's here. So you just send across the link to the IXP and you'll be on your way along this path. That's an example of a path vector announcement. Okay, a little more terminology about BGP before we see examples. First of all, we're used to talking about ISPs here as the different parties in the internet, but in BGP terminology, these are ASs. That stands for autonomous system. All sorts of networks might be autonomous systems. You don't have to be an ISP. It could be a content distribution network, a campus network, and so forth. So ISP and AS are not one-to-one. We're also interested here in what are called the border routers. These are, not surprisingly, the routers which are on the border of the ISP, and they send routing announcements to border routers that are on the edge of another ISP or another AS to which this AS is connected. So we're really interested in the announcements that flow between the ISPs here. There are also announcements that can flow within a network such as an ISP, but I'm not looking at them here. We're really going to focus on these route announcements as they move around. And I'll tell you that a route announcement, just like we saw in that picture before, contains several things. It contains an IP prefix, that's the destination that you're trying to reach. So that was F1 in our example on the previous slide. A path vector that you go through to reach this destination. I forget what that was. That was maybe ISPB and netf on the other side. And a next hop that you use to get onto this path, and that was via the IXP or Internet Exchange Point in our example. Now, the reason that you actually carry the list of ASs, the whole path, rather than the distance, actually if you think and just compare to a distance vector protocol, in a distance vector protocol, you'd be sending a prefix or a destination, a next hop, which way to go maybe, and a distance metric to decide which way is best. In BGP, we don't send this distance metric, we just send the whole path as a list of ASs. One reason this is done is that the designers were very worried about loops between multiple ISPs. Just imagine that packet zapping around across multiple ISPs. That would be pretty nasty. And so the idea is that if you list the whole path, you'll be able to recognize directly if there's a loop, if you've already gone through a particular ISP, and you'll be able to not use that route. And you're going to see two kinds of flows in network diagrams. I'm primarily going to be talking about the route announcements, how they go out from a destination to other places in the network to tell you how to reach that destination. But if you think about actual traffic that is forwarded along the internet, realize that this traffic will go in the opposite direction to the root announcement. So it will go from wherever you are in the internet towards that destination. Well, here's a little example just to look at to see how some simple announcements would propagate. In this diagram here we have three ASs. You could think of them as ISPs if you like. AS1, AS2 and AS3. I'm just going to look at the announcements that propagate out from prefix C. So that's the destination. Well, along these dotted paths you can see that announcements, BGP announcements carrying path vectors propagate out in the network. And I've shown them here above. Now, this announcement here, to reach prefix C, you go via AS3, and the next hop is here, R3A, is the announcement you would see if you would look over this wire, connecting this border router in AS3, R3A, to a corresponding border router in AS2, R2C. As that announcement propagates further along, if we look at it over this link here, between AS1 and AS2, you can see that now the path has changed. So the path you go through now is AS2 and AS3 to get to C, and also the next hop has changed. Now to access it you go via here. And this last announcement just looks at what you would see actually in the middle here of AS1, since it can't really propagate any further out to A. Similarly, you'll note that routes towards prefix C are also propagated along this other path along the bottom of the diagram. So it's not the case that each AS is making a single decision for routes towards each prefix. In different places in the AS, different routes are propagating using different next hops and so forth. So we can see as we go down here, I'll just circle the corresponding places where these announcements are, that here we go out, the paths actually look the same in terms of the path vectors, the ASs that you go through, but the next hops are all different. Here, actually let's do this one here. You can see that AS1, which here's this announcement, goes via R2B, not R2A, to get to C. So anyone down in the lower portion here of AS1 is probably going to go via a path here to reach C, whereas anyone up here is probably going to end up going by a different path to reach C, even though they'll go through the same sequence of ASs. I've also drawn darker arrows on this diagram, and those dark lines represent the flow of traffic, which is the opposite of the flow of the routing announcements. So for instance, over the top of the diagram, a dark line goes from C all the way through the top of the diagram to A, going in the reverse direction that the route announcements propagate. Right, well, so you've now seen a lot of the mechanics of BGP. I haven't explicitly talked about policy though, and that's really what we wanted to get out of this. So far I've just shown you a path vector. How do we get this policy of our ISPs being able to make decisions which suit their need, choose routes which suit their need? Well, in two ways. When a border router, the first way is that when a border router announces paths to the border routers of other ASs, it only announces paths that it's willing to have those ASs use. It doesn't need to announce other paths that might exist, but it doesn't want someone else to use. It can just withhold them and filter them out. That is applying policy. A second way is that when a border router in an AS hears multiple routes towards a particular destination prefix, it can choose whichever one of those routes it would like to use. If this was a distance vector protocol, we choose the one which has the shortest distance. In BGP, we don't have to choose the one that has the shortest path. We can choose whichever one we want for our own reasons, which may have to do with strange contractual requirements between the companies, for instance, which you wouldn't normally think would be part of a protocol. But BGP can accommodate them by letting you choose the particular route you want, regardless of the length of the path vector. So BGP is looking a little tricky. Let's see an example, and then we'll call it quits, and you'll have a rough idea of how BGP works. Here's another diagram. In this diagram, I have 4 ASs. And I'm going to focus on this one here. This is AS2. We'll look at the route announcements it makes and receives and how it chooses its own paths to get elsewhere in the network. I will also tell you that in terms of commercial relationships between these ISPs, 2 things are going on. AS1 is buying AS2, the one we're looking at, is buying transit service from AS1. AS1 up the top here is this big ISP that's kind of providing transit service to everyone. It will connect everyone to one another if you pay it money. AS2 is also getting a peer service with AS3, and it looks like they're doing that to exchange traffic between A and B. just for their traffic between A and B. That's what you would do with a peer service. So we want to see how paths are found which are consistent with these policies. What happens? Well, several kinds of route announcements flow around. First of all, we're going to look at what are called customer route announcements. The customer side is really the flip side of transit. For an AS like AS1 to provide transit service to let everyone reach a certain prefix and to allow traffic from that prefix to go everywhere else, the prefix needs to get to the transit provider. That destination needs to tell the transit provider who they are, that they want service. This is a customer announcement. You see it's going up here. It's labeled CU in this diagram. So AS2 is going to tell AS1, okay, here's an announcement to prefix A, that's the destination. The path is going to be AS2, just via me, and it's going to send that to AS1. That's the only customer announcement. This is pretty straightforward, really. This is really just saying to AS1, hey, prefix A exists down in me, AS2. Well, let's look at the flip side. AS2, the one we're looking at, that's this one here, is also going to receive transit routing announcements from AS1, which will tell it how to reach other prefixes in the internet. What transit announcements will it receive? Well, AS3 has B as a prefix destination and AS4 has C as a prefix destination. Both of those are going to advertise B and C to AS1. And since AS1 is providing transit, it will tell AS2 about the possibility of reaching these destinations. So AS1 will tell AS2 a couple of routes. For B as a destination, AS1 will say, hey, there's this prefix B. You can reach it via the route AS1, AS3. You can see our path has now gotten longer. So we're now going through two ASs to reach that destination. I'm ignoring the next tab here. And similarly, we will hear, AS2 will hear from AS1 that it can reach prefix C via the path AS1, AS4. Okay, that's a transit announcement. But wait, there's more. AS2 here is also going to receive a peer routing announcement across here. And it's also going to send a peer routing announcement. So what are they for? Well, this is really, AS2 wants to tell AS3 that it is allowed to send to A over this link, and AS3 is also going to tell AS2 that it can send to B over the same link. So AS2 is going to say, well, AS3, you can send to A via the path AS2 over this link, and AS3 will say, hey, AS2, you can send to B, and the path is AS3 over this link. So now we have all of these different announcements that have been received by AS2. So what route will AS2 actually choose to use in the internet? Well, let's do an easy one first. AS2 will actually only hear one route to C. So the way from AS2 that you're going to reach C is actually, this is the way the traffic will flow. It's the dark line. And the routing announcement that we're selecting to follow that is the one that propagated in the opposite direction. That's the only one we heard, so that's what you're going to use to reach C. What about to reach B? Well, we actually heard two announcements. We heard one which came up here, the transit one, and we heard one which came here from AS3 directly to AS2. Since AS2 has now heard two announcements, it can use its policy to decide which of them is better. And the answer is that the peering service is better because peering service is typically free, whereas you're paying for transit service by the volume. So AS2 is going to send over this link to reach B. And similarly, you can work through on your own what's going to happen for the route that AS3 and AS4 will choose to be able to send from B to other destinations on the internet. Well, that's our simple example of BGP, so you've now seen a little bit about how it works, and hopefully that gives you a feel for it. There's actually a lot more here to BGP than the basics, and all sorts of strange effects. We're going to leave that, though, for a more advanced networking course. I hope that one thing I would like you to take away from this is an appreciation that the policies which ISPs use, is a substantial factor in the routes which are used in practice. AS2 could have chosen any of two paths, and they're really quite different, and different things would have happened, and it totally depended on what AS2 wanted. In fact, there are various issues like, can you even be sure if everyone chooses paths independently that the overall routes will actually work? This is an interesting problem, something that researchers look at, how we guarantee that will be the case. And there are other key factors that you might care about for BGP. We're not going to look at them now, but I'll just mention some of them so you know what are interesting areas to find out more about if you would like to. One is convergence, just how fast these protocols converge when anything changes to find a new route. Another is scalability. BGP needs to scale to the size of the whole internet. So we sort of want to know how many routing messages are going around and how much work routers have to do. And also you'll note that I skipped the integration between the BGP we looked at, where messages are sent across ISPs, with the routing that goes on inside ISPs. Really, those two parts of routing need to be integrated together well for overall internet routes to work well. So that's it for BGP. I hope you've learned a little bit, and we're done. G'day viewers. In this segment I'll provide you with an introduction to the transport layer. But first, congratulations are in order. This diagram shows where we are in the course, and you can see that we've gone through the physical, link and network layers, and now we're starting on the transport layer. The transport layer builds on the services of the network, and it delivers data across the network to applications with different kinds of reliability or quality depending on the transport service model. So here are a couple of slides just to recall where we are with protocols in general. This diagram shows two hosts communicating across a network with a single router, and you can ignore all of the details of the protocols. They happen to be TCP/IP and so forth. The point I want to make is that TCP, the transport layer, is communicating information from host to host across the network. And this is the first time we've reached a layer where all of the information that's sent by it is not examined by devices inside the network, or at least it shouldn't be. That wasn't the case with the network, link and physical layer, where intermediate systems, switches and routers, handled all of the information there. The transport layer is really using the network simply to get information between hosts. And we can also provide just a brief review in terms of data units. The name for a message at the transport level is a segment. And you can see here that segments, here's a segment. They have transport control information like a TCP header as well as a payload. The payload is application data that's carried across the network. The segment itself is carried within a packet at the network layer and within a frame at the link layer. Okay, so I'm going to spend most of this segment talking about the different kinds of transport services that a transport layer might offer to its user, an application. Now, there are many different transport services you could imagine. The axes I'm going to use to classify them here are the ones that we use in the internet. A transport service could provide either reliable or unreliable transport. By reliable, we mean if you send it, it will be delivered to the other side. Unreliable, packets can be lost in the network, and this will be exposed to the transport user. Packets can still be lost in the network with a reliable service model. It's just the transport layer takes care of fixing this, so the transport layer doesn't see any of the loss. So that was this top axis. And you can also see a distinction in the unit of data that's transferred. We might transfer individual messages, sort of like a post office model, or an infinite stream of bytes. That's the byte stream model. Now, in the internet, we really provide two kinds of service for applications to use, two transport services. The common one you probably heard of is TCP. TCP is actually the protocol that implements one of the services. The service itself is a stream service. It's a reliable byte stream, a bidirectional reliable byte stream between applications. The other service that the internet provides is a datagram model where you send messages. That service is implemented by UDP. Okay, let's just compare some of the features of these two different transport services to get a little bit of a feeling for how they differ, what different kinds of services you could get depending on what the transport layer does for you. So on the left here we have TCP in this table, and you can see that TCP, well, it sends information reliably, and so there are many features that are related to reliability. Connections have to be set up. The bytes then are delivered reliably, meaning essentially that they're delivered once and in the same order that they were sent. Actually, ordering and reliability are somewhat separate, but we get both of them here. There is also, since it's a byte stream, It's an arbitrary content length model. You can send as many bytes as you like. They will have to be divided into packets or segments inside the network, but that's the transport layer's business. At the other side, you'll receive messages as if they came in on an infinite byte stream. The transport layer with TCP also provides flow control to match sender to the receiver capabilities. We haven't seen any of this yet. We're going to in the future. So I don't expect you to know what flow control is yet, nor congestion control. That's going to be a mechanism that matches the sender to the network's capabilities in terms of its bandwidth. So you can see here, TCP is really quite a full-featured protocol. It does a lot on top of the network layer to provide a service for applications. On the other hand, UDP on the left side, on the right side of this table, is really just a glorified packet transport. It does very little over IP. You send datagrams, well, they're really like packets. The messages, just like the post office, they can be lost and reordered. Somewhat like the postal service, they can be duplicated in a network, so you could send one copy and two could come out. That's a little odd, but that could happen. There's a limited message size because these are like packets, these datagrams, and you can send them at any time. Now this might sound good, but essentially here I'm saying that the transport service provides you no guidance on when it's a good time to send in terms of the receiver being able to handle those messages or the network being able to deliver them. TCP helps us with those tasks. So this right-hand column, you can also see that if I wrote down the capabilities for packets, they would be very much like this. So here we see a bit of a dichotomy between TCP and UDP. You either get basically nothing but IP or the whole kitchen sink in terms of features. Okay, let me go on and talk more about the interface between the transport layer and the application layer, which is using it as a service. We've actually seen this interface before. It's our good old Sockets API. Now, Sockets provided this simple abstraction called a socket to use the network. Before we talked about the network API, they're really allowing applications to use the network. But now that we're zoomed in, you can see they're really providing an interface to a transport layer service. Sockets are used to write all of the different internet applications you see out there. The Socket API supports both of these kinds of internet transport services, both the streams and the datagrams that we just saw. When we looked at sockets before, we only looked at the stream model. And you might have also seen this, we call this the connection-oriented, or a connection-oriented transport, and datagrams are connection-less. Just different names for some of those kinds of services. A little bit more about the sockets. If you recall, one of the key addressing attributes in the socket model is ports. Ports are where applications attach to the transport layer, and sockets, these different ports are what lets multiple different applications use the same transport layer instance on a given machine. So we can multiplex the network between different applications. You can see here two applications, 1 and 2, using different sockets and ports, that's the addressing, to attach to the transport layer. Here was the API, again, for sockets. Again, we went through this a long time ago when we did an introduction to the course. So I'm not going to provide you an example of using this yet. I'll just point out here is the table. Now you know that it's the same kind of API that's used for both sockets and datagrams. It turns out, however, that these three calls here, listen, accept, and connect, you only need them for streams because this is all about setting up the connection. Datagrams are connectionless, so you don't need to establish any connection before you use them. Similarly, for send and receive, with the streams, we simply use send and receive to send information across the network and receive it at the other side. With datagrams, slightly different forms are used, send to and receive from. This is because if you have no connection and you want to send information, a missing parameter you need to specify is who to send it to. And with a datagram model, you can actually send datagrams to many different receivers without having to set up any different connection between them over the same socket. Similarly, receive, uses a form called receive from. Now that provides information about who sent the datagram to you, since many different senders could have sent that datagram that could be received on your port in a datagram model. Let's talk a little bit more about ports, and that will round out the service API that the transport layer provides in the internet to applications. So we've said that there are ports. These are the 16-bit identifiers which provide addressing for applications to use. Actually, it turns out that an application process which is running on machine is identified by the tuple of the IP address, so that sort of tells you the machine, the protocol, since this could be TCP and UDP, and they share the same port space, and the port number itself. Now, you could simply think of a port, even though it's a 16-bit number, as representing a numbered mailbox. Applications can lease those mailboxes to use the services of the transport layer, just like you might get a mailbox at a post office to use the postal system. In this case, not only would you get things delivered to it, but that's where you put things in when you want them sent across the network. Clients and servers use ports slightly differently. Servers often bind to what are called well-known ports. These are ports below 1024. The naming is not quite accurate. Really, these ports are ports which require administrative privileges to use. The idea here is that since you need to know the port to contact someone, servers are going to sit on well-known ports. They'll bind to well-known ports, so you'll know how to find a server. On the other hand, clients can use any old port. As long as they tell the server who they contact what port they're sitting on the other machine, the server will be able to reply back to them. So clients are assigned what are called ephemeral ports, and you can ask the OS just for a new port and it will pick one for you that's convenient for you to use temporarily. This table shows some of the well-known ports. You're probably familiar with some of them. So these are ports that servers would use so that a transport peer across the network would be able to open a connection to the server. The most common one here that you'll be familiar with, I bet, is port 80. That's used for the HTTP protocol for web traffic. Some of you might also have heard of port 443. That's used when we use HTTPS, a secure version of HTTP. And there are many other ports in the table. I won't go through them, but they provide different kinds of ways to access your mail, printers, remote systems, move files around, and so forth. All of the different ways we use the internet. Well, that's all I want to say about the transport service that's provided to higher layer applications. In the coming segments, we'll talk more about the implementation of that service inside the transport layer. So we've covered these service models here. That's all done. And when we look inside the transport layer, we'll now see all sorts of machinery. Most of it's going to be related to how TCP works. Its sliding window and how timeouts are used to provide reliability, how connections are set up, this mechanism called flow control, and so forth. There is one big part of TCP, however, that as a transport layer service that I'm going to defer until later, and that is congestion control, shown here in gray. Congestion control is about matching the transport rate at the edges of the network to the capabilities within the network, depending on the traffic. That's a major subject in itself, and we'll get to that later. First, we'll go through all of this other material on the transport layer. So let's go for it.